Decades ago, the term artificial intelligence was just another Frankenstein story, but today it could be a citizen in your next door. Right from its genesis, artificial intelligence was programmed to probe into human life and eliminate the fortifications of the impossibilities in many areas like healthcare, transportation, communication, and much more. There are hundreds and thousands of organizations, tech communities, and engineers worldwide working round the clock to make miracles a reality. And today, we are going to discuss the top 10 amongst those who are contributing a significant part. So here we are, the top 10 artificial intelligence companies to watch in 2022. At number 10, we have Viz AI. Viz AI is a revolutionary approach to dramatically improvise the way healthcare is delivered. Viz AI focuses on implementing artificial intelligence to diagnose and detect abnormalities in the human body via CT, CTA, MRI, X-ray, EKG, ultrasound, etc. Viz AI coordinates both the patient and healthcare professionals at the same time. The patient reports are shared via mobile to all the concerned medical teams. Results are astonishing. With Viz AI, there is a significant improvement in productivity and reduction of time required for patient treatment and discharge. Viz AI was founded in 2016 and established in November 2021. The company runs with 223 employees and the headquarters is in San Francisco. Viz AI mainly focuses on improving and filling all the gaps between patients and healthcare professionals. Viz AI offers handsome salaries to its employees. In India, the salaries range from 4 lakhs to 18 lakhs per annum, and in America, the wages range from $110,000 to $210,000 per annum. So at number 9, we have Farmwise. 10 years ago, an automated weed-killing robot was science fiction. Now, it's rise of practical weed-killing robots with millimeter precision thanks to Farmwise. The first product of the Californian-based company was an automated robo-weeder based on AI, computer vision, and also robotics. The robot would eliminate weeds from the vegetable fields. Farmwise intends to build innovative systems and efficient procedures that help farmers streamline farming with efficiency. Farmwise was established in the year 2020. The company functions with 50 employees on board and actively looking for expansion. The company follows the procedure of paying farming equipment employees and contract personnel hourly. Farmwise makes an annual turnover of $8.5 million. On average, an AI/ML engineer at Farmwise earns anywhere around $113,000 per annum. Up next, we have AMP Robotics. At number 8, we have AMP Robotics. While others are busy trying to revolutionize mankind with AI, AMP Robotics came up with an innovative idea that happens to be a kind gesture of gratitude towards nature. AMP AI designed an artificial intelligence robot that recycles e-waste, plastic waste, and waste from construction sites, and much more. The robot precisely identifies paper, plastics, and metals by learning and recognizing them via color, size, shape, and a few more factors. The Colorado-based company is currently operational with 137 employees in total and looking forward to expand the idea globally. AMP Robotics aims to reimagining recycling and to create a world without waste through artificial intelligence. AMP Robotics pays handsome salaries to their employees with an average salary of an employee AMP. Robotics varies between $96,000 to $131,000 per annum. Coming up next is a giant. At number 7, we have Automation Anywhere. Automation Anywhere is a global robotics automation and software company founded in the year 2003. The company's headquarters is located in San Jose, California. The global RPA leader offers cloud-native, web-based intelligent automation solutions to the world's leading cloud companies. Automation Anywhere's Automation 360 offers a variety of intelligent tools and self-learning systems to automate every redundant task. Automation Anywhere is focusing on transforming the companies to be RPA-oriented, and the current COVID situations have triggered the need for automation even more. A recent survey states the RPA adoption rates will increase by 57% in just one more year. The globally recognized multinational company works with more than 2,200 plus employees on board. The company pays decent salaries as well. At number 6, we have Microsoft AI. Microsoft integrated AI into cloud computing. Microsoft's AI platform provides robust solutions to cloud-related problems. Microsoft's AI division is headquartered in Redmond, Washington, with around 5,000 employees specifically in the AI division, and aims to train and certify 15,000 employees by 2022. Microsoft AI is a robust framework designed for developing AI solutions using machine learning, data science, robotics, IoT, and more. AI-enabled services accelerate productivity to a greater level. Microsoft Azure uses AI to get best-of-breed infrastructure with enterprise-grade security, availability, compliance, and manageability. Microsoft also pays handsome salaries to their employees. The average salary of an employee at the Microsoft AI division earns up to $160,000 per annum. At number 5, we have DataRobo. DataRobo has its headquarters in Boston. It is one of the AI cloud leaders, providing a unified platform to its cloud users to accelerate the delivery of AI to the cloud. DataRobo aims to understand and leverage the inherent capabilities of the platform. DataRobo has the caliber to help business analysts in building predictive analytics with no knowledge of machine learning. It uses automated ML to build and deploy accurate predictive models in a short span of time. The global cloud leader currently operates with more than 1,000 employees worldwide. DataRobo compensates its employees with handsome salaries. An average employee at DataRobo earns up to $160,000 per year and up to 3,400,000 rupees in India. At number 4, we have Amazon. The Alexa maker, Amazon, is one of the tech giants interested in adopting AI into its various divisions. Amazon calls its AI services Amazon Lex, Amazon Poly, Amazon Recognition, and Amazon Machine Learning. These services are accessible through a software API call or console. The Amazon AI suite of services can have text or voice conversations with an end user using a conversational chat ops interface. The Seattle-based tech giant is currently using AI for its smart home solutions. AI companies like Alexa and its business intelligence needs, Amazon is also conducting trials on drone delivery to save time and efforts to deliver goods and services to remote locations with ease. Amazon AI aims to provide biometric payments to its customers at cash-free stores. The approach is still in trials. Amazon calls it Just Walk Out technology. Amazon has enormous teams and pays decent salaries to its employees. For example, an employee at Amazon can earn up to 20 lakh rupees per annum in India and about $100,000 per annum in United States of America. At number 3, we have Databricks. Databricks is one of the best data-driven companies. Databricks lakehouses combine data warehouses, reliability, performance, and governance with the openness and flexibility of data lakes. Databrick is headquartered in San Francisco, California, and has 15 office locations across 11 countries. The company announces plans on delivering keynote on data and machine learning product innovations and the rise of the lakehouse architecture advancements. Databricks currently operates with 2,000 plus employees globally. The organization compensates its employees with handsome salaries. An average employee at Databricks makes about $154,000 and around 2.1 lakh rupees per annum in India. Next we have Meta. At number 2, we have Meta. Meta, formerly known as Facebook, is innovating an advanced way of social interaction. Meta has integrated artificial intelligence and it's being called the Meta AI. Meta AI has its headquarters in Toronto, Canada. Meta AI has redesigned a new material and touch sensor with potential to boost the development of Metaverse. A team of researchers at the Metaverse have worked jointly with scientists at Carnegie Mellon University to build Reskin, a plastic 3 mm thick membrane with magnetic particles capable of measuring touch and sensation. A thrilling experiment Meta has under its sleeve, I would say. Meta currently operates remotely with about 350 employees on board. Critics also state that Meta pays a vast salary to its AI experts with an average salary of $1,750,000 paid to the employees at Meta AI. At number 1, we have Google AI. Google AI is the division of Google dedicated to artificial intelligence. CEO Sundar Pichai announced it at Google I/O 2017. Google AI has its headquarters in California. Google AI is demonstrating its quantum computing supremacy with its new and powerful Cinnamon processor. Google's AI is one of the most widespread technologies. It's almost everywhere, from your language translations to helping people with speech impairments to have a successful conversation, social media interactions, shopping lists, and assisting users with GPS, sending alerts to its users about natural calamities and saving them. Google AI has announced that its research team is designing next-generation AI chips for a smart future. In addition, a new AI model allows artificial intelligence to perform chip design that more efficiently solves unique aspects of any problem with an artificial neural network. Google AI currently works with our 4 divisions with massive teams.
Have you ever wondered how Google Maps, autocorrect and chatbots work? It is all due to AI and deep learning. Artificial intelligence is changing business at a rapid rate. AI and deep learning are also impacting our lives outside the office. Self-driving cars, smart assistants like Amazon Alexa, and disease mapping are a few examples of AI that are impacting our personal lives each and every day. Companies like Tesla and Uber use AI and machine learning to develop reliable transportation solutions for everyone, everywhere. AI and deep learning are lurking in the background every time you open your Facebook newsfeed, do a Google search, get a movie recommendation from Netflix, or book a hotel online on Trivago. Artificial intelligence has become an important part of the gaming industry in recent years. AI is a branch of computer science that deals with building intelligent machines capable of performing complex tasks and taking decisions by mimicking the human brain. Deep learning, on the other hand, is a subset of machine learning that is used to build and train artificial neural networks. Deep in deep learning refers to a neural network comprised of more than 3 layers. Jan LeCun, the director of AI research at Facebook and professor at New York University, says deep learning combined with reasoning and planning is one area of research making promising advances right now. AI and deep learning together can solve repetitive problems, data-intensive tasks, and other superhuman jobs. While AI and deep learning bring more efficiency into our lives, we encounter new problems developed by integrating AI into our lives. With this understanding of AI and deep learning, let's go ahead and learn them in detail.
So first, we will learn the basics of artificial intelligence with a short animated video. Then, we will look at the future of AI and understand AI in depth with hands-on demonstrations in Python. We will learn the top 10 artificial intelligence technologies in 2021 and shift our focus to understanding deep learning in detail. You will learn the basics of deep learning followed by neural networks. Moving further, you will get an idea about the 2 most popular deep learning frameworks, TensorFlow and Keras. You will also get an idea about recurrent neural network and generative adversarial networks. Finally, we will understand computer vision using the OpenCV library and look at the top deep learning interview questions. So let's get started.
Picture this, a machine that could organize your cupboard just as you like it, or serve every member of the house a customized cup of coffee. Makes your day easier, doesn't it? These are the products of artificial intelligence. But why use the term artificial intelligence? Well, these machines are artificially incorporated with human-like intelligence to perform tasks as we do. This intelligence is built using complex algorithms and mathematical functions. But AI may not be as obvious as in the previous examples. In fact, AI is used in smartphones, cars, social media feeds, video games, banking, surveillance, and many other aspects of our daily life. The real question is, what does an AI do at its core? Here is a robot we built in our lab, which is now dropped onto a field. In spite of a variation in lighting, landscape, and dimensions of the field, the AI robot must perform as expected. This ability to react appropriately to a new situation is called generalized learning. The robot is now at a crossroad, one that is paved and the other rocky. The robot must determine which path to take based on the circumstances. This portrays the robot's reasoning ability. After a short stroll, the robot now encounters a stream that it cannot swim across. Using the plank provided as an input, the robot is able to cross this stream. So, our robot uses the given input and finds the solution for a problem. This is problem solving. These three capabilities make the robot artificially intelligent. In short, AI provides machines with the capability to adapt, reason, and provide solutions. Well, now that we know what AI is, let's have a look at the two broad categories an AI is classified into. Weak AI, also called narrow AI, focuses solely on one task. For example, AlphaGo is a maestro of the game Go, but you can't expect it to be even remotely good at chess. This makes AlphaGo a weak AI. You might say Alexa is definitely not a weak AI, since it can perform multiple tasks. Well, that's not really true. When you ask Alexa to play Despacito, it picks up the keywords play and Despacito, and runs a program it is trained to. Alexa cannot respond to a question it isn't trained to answer. For instance, try asking Alexa the status of traffic from work to home. Alexa cannot provide you this information, as she is not trained to. And that brings us to our second category of AI, strong AI. Now, this is much like the robots that only exist in fiction as of now. Ultron from Avengers is an ideal example of a strong AI. That's because it's self-aware and eventually even develops emotions. This makes the AI's response unpredictable. You must be wondering, well, how is artificial intelligence different from machine learning and deep learning? We saw what AI is. Machine learning is a technique to achieve AI, and deep learning, in turn, is a subset of machine learning. Machine learning provides a machine with the capability to learn from data and experience through algorithms. Deep learning does this learning through ways inspired by the human brain. This means through deep learning, data and patterns can be better perceived. Ray Kurzweil, a well-known futurist, predicts that by the year 2045, we would have robots as smart as humans. This is called the point of singularity. Well, that's not all. In fact, Elon Musk predicts that the human mind and body will be enhanced by AI implants, which would make us partly cyborgs. So, here's a question for you. Which of the below AI projects don't exist yet? A. An AI robot with citizenship. B. A robot with a muscular skeletal system. C. AI that can read its owner's emotions. D. AI that develops emotions over time. Give it a thought and leave your answers in the comment section below. Since the human brain is still a mystery, it's no surprise that AI too has a lot of unventured domains. For now, AI is built to work with humans and make our tasks easier. However, with the maturation of technology, we can only wait and watch what the future of AI holds for us. Well, that is artificial intelligence for you in short.
What's interesting to me is we will use AI as we have been, to specifically target tasks that we need or want done in place of ourselves. That's how AI will ultimately unfold.
It is a renaissance. It is a golden age. We are now solving problems with machine learning and artificial intelligence that were, kind of in the realm of science fiction for the last several decades.
AI is probably the most important thing humanity has ever worked on. I think of it as something more profound than electricity or fire. And anytime you work with technology, you need to learn to harness the benefits and while minimizing the downsides.
We're focusing on autonomous systems. And clearly one purpose of autonomous systems is self-driving cars. There are others. And we sort of see it as the mother of all AI projects.
So there's a class of things like game playing or speech recognition or image recognition that the performance levels are phenomenal. If you compare human speech recognition to computer speech recognition, the computer is slightly better. And that's, mind-blowing. Certainly we use AI to do drug discovery. These biological systems are very complicated. And so the fact that we have vaccines for TB and HIV coming, that's partly enabled by this rich data, advance in biology, and machine learning.
When I look at Seeing AI, which is an application we just launched for anybody with visual impairment, they can go download this app that uses the latest cutting-edge computer vision technology in our cloud to give anyone the ability to see. And in fact, Angela Mills, who's a colleague of mine, was just telling me about how it's changed her life inside of Microsoft. She can go into our cafeteria, order food using this app with confidence, walk into conference rooms with confidence because she knows she's walking into the right conference room. Or what we've done with our OneNote and Word learning tools. Anyone who has dyslexia can now use AI to be able to read better. The latest release of Windows 10 has this capability called eye gaze, which is something that we learned working with Steve Gleason and the ALS patients, to saying, if all you have is the eye muscle and the gaze, can we help you type?
Yeah, you have to be careful when there's advances. In a sense, we're all better off. If the machines can make all the food and the clothes and none of us have to work, you think, okay, now we have all the freedom. If we want to stand behind the counter and, make sandwiches, okay, you can if you want, but there's this other way to make those goods and services. But it will be very disruptive because, say you're mid-career in manufacturing or driving, then it's a disruption. Now, we've had that in a slow way for hundreds of years. We used to all be farmers. Now, very few of us are farmers.
I said it's right to be concerned. Absolutely. You have to worry about it, otherwise you're not going to solve it, right? And it's important to understand tomorrow whether Google is there or not. Artificial intelligence is going to progress. Technology has this nature. It's going to evolve. I think pulling back, history shows pulling back, countries which pull back don't do well with the change. We know that. 20, 30 years ago, you educated yourself and that carried you through for the rest of your life. That is not going to be true for the generation which is being born now. They have to learn continuously over their lives. We know that. So we have to transform how we do education.
Look, you nailed it. Anything that's repetitive and done, on the back of, technology or, is going to be fundamentally vulnerable.
Yeah. So I think technology, and in particular AI, can in fact bring more empowerment, more inclusiveness. And at the same time, we should be clear-eyed about displacement, clear-eyed about unintended consequences like any other technology, and work both skilling so that people can find the jobs of the future, create new jobs, and lastly, I think have a set of policy decisions that really help people as they go through this change.
But the risks are important, and I think the way we solve it is we think ahead, we worry about it, we do things like be upfront, have ethical charters, think about AI safety from day one, be very transparent and open in how we pursue progress there, and figure out global frameworks by which we can engage. Just like Paris Agreement and climate change, using forums like this, I think we bring people together to engage on the hard questions. And I think answers will emerge.
I have exposure to the very most cutting edge AI. And I think people should be really concerned about it. I keep sounding the alarm bell, but until people see like robots going down the street killing people, like they don't know how to react, because it seems so ethereal. I think we should be really concerned about AI, and I think we should. AI is a rare case where I think we need to be proactive in regulation instead of reactive. Because I think by the time we are reactive in AI regulation, it's too late.
Right now we have machine learning algorithms that can solve an incredibly complex problem beyond any human intelligence, but they're essentially complete idiots and like 2-year-olds at anything that's not that problem. They're dumb. You can give them this enormous data set and they come up with brilliant correlations and insights, but they're not going to plug into Skynet and threaten us anytime soon.
So I'm quite optimistic, and I don't think artificial intelligence is a threat. I don't think artificial intelligence is something terrible, but human beings are smart enough to learn that.
What is artificial intelligence? In today's world, it's probably one of the most exciting advancements that we're in the middle of experiencing as humans. So, what is artificial intelligence? And here we have a robot with nice little clampy hands. Hey, what am I? You are what we call artificial intelligence. I am your creator, reminding him who programmed him and who he's supposed to take care of. Artificial intelligence is a branch of computer science dedicated to creating intelligent machines that work and react like humans. In today's place where we're at with artificial intelligence, I really want to highlight the fact that they work and react like humans, because that is where the development of artificial intelligence is, and that's what we're comparing it to, is how it looks like next to a human. Thanks. Any tasks you want me to do for you? Get me a cup of coffee? Poof, here you go. And he brings him a cup of coffee. That's my kind of robot. I love my coffee in the morning. You'll see there's kind of a side theme of coffee today's tutorial. So here we have a robot that's able to bring him a cup of coffee. It seems pretty far out there, that we have a walking robot that's doing this, but it's not as far out there as you think. We have automatic coffee pots. We have devices that can move an object from one point to the other. Anything from Amazon delivering packages or whatever you want. All these things are in today's world. We're right on the edge of all this. That's what makes this so exciting, such an exciting topic and a place of study. So let's take a real general look at types of artificial intelligence in the really big picture. I mean, when we drill into it, there's like machine learning and all kinds of different aspects, but just a generic level of artificial intelligence. So, hi there, discovered 4 different types. Come have a look. So we have our kind of Einstein-looking guy or professor at some college. So the very first part that this is reactive machines. They've been around a long time. This kind of AI are purely reactive and do not hold the ability to form memories or use past experiences to make decisions. These machines are designed to do specific jobs. Remember I talked about the programmable coffee maker that makes coffee in the morning? It doesn't remember yesterday from tomorrow. It runs its program. Even going back to our washing machines, they have automatic load balancers that have been around for decades. So reactive machines, we program to do certain tasks, and they have no memory, but they're very functional. Then we have limited memory. And this is kind of right where we're at right now. This kind of AI uses past experience and the present data to make a decision. Self-driving cars are kind of limited memory AI. We bring up self-driving cars because that's a big thing, especially in today's market. They have all these images that they brought in and videos of what's gone on before, and they use that to teach the automatic car what to do. So it's based on a limited memory. Limited memory means it's not evolving new ideas. They have to actually, when they need to make a change, they have the program built on the memory, but then they have to make those changes outside of that and then put the new setup in there. So it's continually reprogramming itself. Theory of mind. These AI machines can socialize and understand human emotions. Machines with such abilities are yet to be developed. Of course, that's under debate because there's a lot of places that are working on the theory of mind and having it be able to cognitively understand somebody based on the environment, their facial features, all kinds of things, and evolve with them. So they have some kind of reflective ability to evolve with that. And finally, self-awareness. This is the future of AI. These machines will be super intelligent, sentient, and conscious. So they'll be able to react very much like a human being, although they'll have their own flavor, I'm sure. Achieving artificial intelligence. So how in today's world right now are we going to achieve artificial intelligence? Well, the main arena right now is machine learning. Machine learning provides artificial intelligence with the ability to learn. This is achieved by using algorithms to discover patterns and generate insights from the data they are exposed to. And here we have a computer as we get more and more to the human realm of artificial intelligence. You see this guy splits in two, and he's inside his hidden networks and machine learning programs. Deep learning, which is a subcategory of machine learning. Deep learning provides artificial intelligence the ability to mimic a human brain's neural network. It can make sense of patterns, noise, and sources of confusion in the data. Let's try to segregate different kinds of photos using deep learning. So first we have our pile of photographs, much more organized than my boxes in my closet of photographs. The machine goes through the features of every photo to distinguish them. This is called feature extraction. Bingo, it figures out the different features in the photos. And so based on those different features, labels the photos, it says these are landscapes, these are portraits, these are others. So it separates them in there. And if you've ever been on Google Photos, a favorite of mine, I go through there and I type in dog and I get all the images of my dog. It's pretty amazing how it's able to pull those features out. So when we're achieving artificial intelligence and the deep learning, let's take a closer look and see just how deep learning works. There are a lot of models out there. This is the most basic model used. This is a neural network. There are three main layers in a neural network. The photos that we want to segregate go into the input layer. And so we have a picture of Mona Lisa, it looks like, and a couple of people. When it goes into the first input layer, the arrows are drawn to like individual dots. Each one of those white dots in the yellow layer or in the input layer would be a pixel in the picture, maybe, a value for that pixel. So the picture of the mountains goes in there and it fills in that whole input layer. And then the next picture of the nightscape goes in there. The hidden layers are responsible for all the mathematical computations or feature extraction on our inputs. So when you see here, we have the two kind of orangish red layers here, and there's all these lines in there. Those lines are the weights. Each one of those represents usually a float number or a decimal number. And then it multiplies it by the value in the input layer. And you'll see that as it adds all these up in the hidden layer, each one of those dots in the hidden layer then has a value based on the sum of the weights. And then it takes those and it puts it into another hidden layer. And you might ask, well, why do we have multiple hidden layers? Well, the hidden layers function as different alternatives to some degree. So the more hidden layers you have, the more complex the data that goes in and what it can produce coming out. The accuracy of the predicted output generally depends on the number of hidden layers we have. So there we go. The accuracy is based on how many hidden layers we have. And again, it has to do with how complex the data is going in. The output layer gives us the segregated photos. So once it adds up all these weights, and you'll see there's weights also going into the output layer, based on those weights, it'll say, yes, it's a portrait, no, it's a portrait. Yes, it's a landscape, no, it's a landscape. And that's how we get our setup in there. So now we're able to label our photos. Let's take a look and see what that looks like in another domain. We have photograph domain. Now let's look at it in the airline ticket. So let's predict the airline ticket prices using machine learning. These are the factors based on which we're going to make the predictions. And choosing your factors is so important. But for right here, we'll just go ahead and take a look at what we got. We have airlines, we have the origin airport, the destination airport, the departure date. Here are some historical data of ticket prices to train the machine. So we pull in the old data. This is what's happened over the years. sensors. Now that our machine is trained, let's give it new data for which it will predict the prices. And if you remember from our 4 different kinds of machines, we have machines with memory. Well, this is the memory part. It remembers all the old data and then it compares what you put in to produce the new data, to predict the new prices. The price is 1,000. That's an expensive flight. Of course, if that is US dollars, if it's India, I don't know what the price range is on that. Hopefully it's a good deal for wherever you're going. So we predict the prices, and this is kind of nice because if you're looking way ahead, it'd be nice to know if you're planning a trip for next year, how much those tickets are going to cost, and they certainly fluctuate a lot. So let's take a look at the applications of artificial intelligence. We're going to dive just a little deeper because we talked about photos, we've talked about airline ticket prices, kind of very specific, you get one specific number. But let's look at some more things that are probably more in-home, more common right now. Speaking of in-home, this young gentleman is entering his room. Of course, makes the comment like we all do when we walk into a room. This room is dark, isn't it? Let's see what happens when I enter it. The sensors in my room detect my presence and switch on the lights. This is an example of non-memory machines. Okay, it senses you. It doesn't have a memory whether you've gone in or not. Some of the new models start running a prediction as to whether you're in the room or not, when you show up, when you don't. So they turn things on before you come down the stairs in the morning, especially if you're trying to save energy. You might have one of those fancy thermostats, which starts guessing when you get up in the morning so it doesn't start the heater until it knows you're going to get up. So here he comes in here, and this is one of the examples of a smart machine. And that is one of the many applications of artificial intelligence, one of the things we're developing here in our homes. Okay, bye. Abruptly he leaves, leaving his nice steaming cup of coffee there on the table. And when he leaves, the sensors detect he's gone and turn off the lights. Let's watch some TV. Did someone say TV? The sound sensors on the TV detect my voice and turn on the TV. Sounds kind of strange, but with the Google dongle and a Google Home Mini, you can actually do just that. You can ask it to play a movie downstairs on your downstairs TV. True also with the Amazon Fire Stick and all the different artificial intelligent home appliances that are coming out. Pretty amazing time to be alive and in this industry. Here you have one more application of artificial intelligence, and you can probably think of dozens of others that are right now on the cutting edge of development. So let's jump into my favorite part, which is a use case. Predict if a person has diabetes. And in the medical domain, if you read any of these, they say predict if a person has diabetes. But in the medical domain, we would want to restate this as, what is the risk? Is a person a high risk of diabetes? It should just be something on their radar to be looking out for. And we'll be helping you out with the use case. There we are with our cup of coffee again. I forgot to shave, as you can see. We'll start with the problem statement. The problem statement is to predict if a person has diabetes or not. And we might start with this prediction statement, but if you were actually using this in a real case, again, you would say you're high risk of diabetes would be the proper way to present that to somebody if you ran their test data through here. But that's very domain specific, which is outside of the problem statement as far as a computer programmer is involved. So we're going to have a look at the features. These are the things that have been recorded, and they already have this data from the hospitals. One of them would be number of times pregnant. Obviously, if you're a guy, that'd be 0. Glucose concentration. So these are people who've had their glucose measured. Blood pressure. Age. Age is a big factor, an easy thing to look at. Insulin level. So if someone's on insulin, they probably have diabetes. Otherwise, they wouldn't be taking insulin. But that would affect everything else, and we add that in there if they're using insulin. Let's start off with the code. So we're going to start off by importing parts of our data set. And if we're going to do this, let's jump into one of our favorite tools. We're going to use the Anaconda Jupyter Notebook. So let me flip over to there and we'll talk just briefly about that, and then we'll look over this code. So here we are in the Jupyter Notebook, and this is an inline editor, which is just really cool for messing with Python on the fly. You can do demos in it. It's very visual. You can add pieces of code. It has cells, so you can run each cell individually. You can delete them. You can tell the cell to be a comment, so that instead of running it, it just skips over it. There's all kinds of cool things you can do with Jupyter Notebook. We're not going to go into that. We're actually going to go with the TensorFlow. And you do have to import all the different modules in your Python. Now, if you're in a different Python IDE, that's fine. It'll work in just about any of your Python IDEs. And I'll point out the one difference in code when we get to that, which is the inline for doing our graph. And in this code, we're going to go through, we're going to load our data up, we're going to explore it, we're going to label it, and then we'll use the TensorFlow, and then we'll get down to the end where we're going to take a look at how good the model is. Does it work? So let's start with the top part here. And let me go ahead and let's paste that code in there. I've added a line in at the top. I've added the folder because I didn't put it in the same folder as the program that's running. You don't need to worry too much about that, but if you have a folder issue or it says file doesn't exist, you probably have it in the wrong folder, or you need to add the folder path. And then we're going to import pandas. And let me just, one of the cool things, since it's in Chrome, we can just do that Control plus and zoom right in there. And we have the import pandas as PD. So go ahead and draw a line in there. You can see that the pandas as PD, add a little drawing thing in there to make it a little easier to see. Pandas is a data set. It's a really nice package you can add into your Python. Usually it's done as pandas as PD. That's very common to see the PD here. Let's circle that. It's basically like an Excel spreadsheet. It adds columns, it adds headers, it adds a lot of functionality to look at your data. And the first thing we're going to do with that is we're going to come down here and we're going to read. And this is a CSV. It's a CSV file. You can open up the file on your computer if you want. If you need access to the file, you can either search it and download it from the main thing, or type a note in down below on the YouTube video. And Simplilearn will help you get that file also. And that's true of any questions you have on this. You can add comments down there, and somebody at Simplilearn actually keeps an eye on that, and we'll try to answer those questions for you. I put in the full path. You don't have to if you have your data file saved in the same folder you're running your program in. And this is just a CSV file, comma-separated variables. And with the pandas, we can read it in there, and we're going to give it, put it right in a variable called diabetes. And then finally we take diabetes, and you'll see diabetes.head. This is a pandas command, and it's really nice because it just displays the data for us. Let me go ahead and erase that. And so we go up to the Run button up here in our Jupyter Notebook, which runs the script in this. That's the cell we're in. And as you can see with the diabetes.head, since it's a pandas data frame, it prints everything out nice and neat for us. And this is really great. And if I go ahead and do a Control minus, I can get it all to fit on the same screen. And this is the first 5 lines. When you do the head of the data, it just prints out the first 5 lines. In programming, of course, we start with 0. So we have 0, 1, 2, 3, and 4. Here we go. Here we go. We start with 0. We have 0, 1, 2, 3, and 4. We have our titles going across the top. And of course, the first column is number of pregnancies, glucose concentration for the second one, blood pressure, measurements of triceps. As we keep going, you'll see, you can guess what most of these things are. Group, I'm not sure, this is probably the test group. I didn't look it up to see specifically what that is. Anytime you start exploring data, and for this example, we don't really need to get too much in detail, you want to know the domain. What does this information mean? Are we duplicating information going in? That's beyond the scope of this. For right now, though, we're just going to look at this data, and we're going to take apart the different pieces of this data. So let's jump in there and take a look at what the next set of code is. So in our next setup, or our next step, we got to start looking at cleaning the data. We got to start looking at these different columns and how are we going to bring them in? Which columns are what? And I'm going to jump ahead a little bit, and also as we look at the columns, we're going to do our import our TensorFlow as TF. That's a common import, but that's our TensorFlow model. TensorFlow was developed by Google, and then they put it into open source so that it's free for everybody to use, which is always a nice thing. So let's take a look at what these 2 steps look like in our Jupyter Notebook. So let's paste this code in here, and this is something that happens when you're messing with data, is you'll repeat yourself numerous times. We already have diabetes head, so I'm going to put the little pound sign, which tells Python that this is just going to be a comment. We're not going to run it a second time. In here we have diabetes.columns, and then diabetes columns to norm equals diabetes columns to norm.apply lambda x. Let's talk about that, but let me first run that, and let's see what that comes out with that. And then let's put the next set of code in also. And I'm going to run that. Let me just hit the run button. It doesn't really have an output, but we did a lot of stuff here. So let's go over what we did on this. So I've turned on my drawing implement to help go through all this, because there's a lot going on here. The first thing is we have all of our columns up here, all of our column names. Let me just highlight that and draw a circle around that like we did earlier. And we want to look at just specific columns. And we're going to start, let me change the color on this so it really sticks out. I'll use like a blue. I'm going to look at these columns. And we're not going to do age, class, or group. We're going to look at those in a different way. And I'll explain in a little bit what that's about. So we're looking at number of pregnancies, basically anything that can be read as a float number. And you might say age could be read as a float number. We're going to address that differently because when you're doing statistics, we usually take the ages and we group them into buckets. And we'll talk about that. And so we're going to take these columns and we're going to do what they call normalize them. Column to normalize. What is normalize? If you're using the sklearn module, one of their neural networks, they call it scaling or scalar. This is in all of these neural networks. What happens is if I have two pieces of data, and let's say one of them is, in this case, 0 to 6, and one of them is in insulin level is 0 to maybe 0.2 would be a very high level. I don't know what they actually go to. A neural network will look at this 6, and it'll go 0 to 6, and as you get into 0, 6, here's an 8, even a higher number, it will weight those heavier. And so it'll skew the results based more on the number of pregnancies than based on the insulin or based on the blood pressure. So we want to level the playing field. We want these values to all be in the same area. We do that by normalizing it here. And we use a lambda function. This is always a kind of a fun thing. We take the diabetes. It's a panda setup, and let me just erase all that so we can go down here, put it back to red. And we take our diabetes, which is a panda data set, and we only want to look at the columns to normalize, because that's what we built. We built a list of those columns, and we're going to apply a lambda function. And you'll see lambda in all kinds of Python programming. It just means it's a function. We put x in, and whatever is outside of the x over here, it then takes that and returns that value. So the new value is going to be whatever x is minus x min. Again, it's a pandas data set, so we can get by with that, which is really cool. It makes it easy to read. So we take x, we look for the minimum value of x, and then we divide that by the maximum value of x minus the x min, or the width. And what this essentially does is if you're going from 0 to 15, it's going to divide by 15, and then we subtract it. Let's make this 2 instead of 0. Or 20 to 115. There we go. First off, we set this to 0. So we subtract x min. So right off the bat, the minimal value is going to be 0. And then we divide it by the difference here, x min minus x max, or x max minus x min. This basically sets all the values between 0 to 1. And that's very important if we want to make sure that it's not going to be a skew in the results, if it's not going to weight the values one direction or the other. 0 to 1. That's what this is doing. And again, there's like so many different ways to scale our data. This is the most basic scale, it's standard scaling, and it's the most common. And we spelled it out in the lambda. There's actual modules that do that, but lambda is it's such an easy thing to do, and you can really see what we're doing here. So now we've taken these columns, we've scaled them all, and changed them to a 0 to 1 value. We now need to let the program know, the TensorFlow model that we're going to create, we need to let it know what these things are. So to do that, I create a variable called number pregnancy, keep it simple, and we've imported the TensorFlow as TF. One line of code brings our TensorFlow in for us. Awesome. Love Python. So you get number of pregnancies and tf.featureColumn.numeric column. We're going to tell it's a numeric column, so it knows that this is a float value, 0 to 1, and then number underscore pregnant. So we're taking that column and we've reshaped that column from 0 to 1. And no, that doesn't mean you have a 0.1 pregnancy. It just means 0.1 equals 1 or something. Number pregnant. So we're just mapping this data. So TensorFlow knows what to do with it. And we go through all of these. We go through all the way up to, again, we're not doing age. Let me just separate age down here. These have all been adjusted. Age, we're going to handle differently. We still put it as a numerical column because it is. So let me just circle age. And group, we didn't even touch group yet. We're going to look at group and age, and we're going to do some special stuff with that. Class, we're going to look at last. Why? Because this is whether they have diabetes or not. That's what we're testing for. So this is our history. We know these people have diabetes or not, and we want to find out, we want to create a model, and then we want to test that model, predicting whether somebody new has diabetes or not. So here I am still with my cup of coffee working away, refill number 3. Let's explore both the categorical group, which is going to be the A, B, C, and D on the end, and also the age. We're going to talk about those a little bit more. And then we're going to combine all those features, and we'll jump into splitting the data, although that's kind of the next step. But we'll put that all together. What are we doing with the age, and what are we doing with the group down there? So let's flip on over and take a look at our Jupyter Notebook. So the first thing is let's put this new set of code in here and run it. And let's talk about what we're doing on this set of code. And I actually want to go one more step forward on the next set of code, or part of it. There we go. And I can go ahead and just run that while we have it. That's fine. Let's just scroll up a little bit here, and let's go through what we just did with this set of code. If we go back up here to the top part, we have group B, C, B, B, C. We learned from the header. So when I come down here, we're going to create assigned group. And let me get my drawing pad out. So we're looking at this first one up here, assigned group, TF feature column, categorical column with vocabulary list. Whew, that is a mouthful. This is saying that this is a categorical list. In this case, we have A, B, C, D. You see this a lot in TensorFlow. A lot of times TensorFlow is used to analyze text or logs, error logs, and they're just full of all this information, and they take these, in this case A, B, C, D, but in other cases it'd be words, and they create numbers out of them. So it has 0, this is one column, this is another column, this is another column, this is another column. And it's just this way of being able to look at this in a different light and assigning them different values. You really don't want to assign this a float value. First thought might be, let's assign this 0 to 3, 0, 1, 2, 3 for A, B, C, D. But if you did that, it would try to add 1 plus 2 to get 3 as part of its math and functions. And that just isn't true. C does not equal A plus B. C is just a categorical name. It could have been the Frank group and Laura's group and Abid's group, but it's not. You know, they're not float numbers. So very important that you have that distinction in your data. The next step we're looking at is our map plot. And we're going to do this. This is a cool, useful tool. We're going to import matplotlibary.pyplot as PLT, a standard import. And this next line here is really important. For doing the matplot library, we want it to be inline. That's because we're in a Jupyter Notebook. Remember I told you before that if you're running this in a different IDE, you might get a different result. This is the line you need if you want to see the graph on this page. And then we do diabetes, and we're going to look at just the age, and .hist bins equals 20. What the heck is that? Well, it turns out that because this is, remember it's a pandas, there's our PD, pandas as PD. Because this is a pandas, panda automatically knows to look for the matplot library. And a hist just means it's going to be a histogram. And we're going to separate it into 20 bins. And that's what this graph is here. So when I take the diabetes and I do a histogram of it, it produces this really nice graph. We can see that at 22, most of the participants in this, probably around 174 of the people that were recorded, were of this age bracket. They're right here in this first column here. And as they get further and further down, they have less and less and less until when you're at 80, you can actually see down here there's almost none in a couple of these categories. And this is important to note because when you're doing census, you know, the older the group is, the more the people have passed away. So you're going to have this in any of your censuses you take. You're always going to have a much larger group in the younger crowd, and then it gets lower and lower as they get older. And I mentioned the word buckets. Here we go. We're going to create an age bucket. We're going to put people in buckets. Can you imagine people sitting in buckets? Kind of a funny way of looking at it. This just makes it easier for us to separate it. When I go to the doctor's office, I don't want to be told, well, you're age 22. This is your, you'll get a decent one at 22. Here we are back to my cup of coffee. I told you coffee was an underlying theme. These next couple steps are very specific to TensorFlow. Up until now, we had some TensorFlow as we set the categories up, but you'd have to set that up with any model you use to make sure they're set correctly. They'd be set up a little differently. But we run input functions. And in TensorFlow, this allows for some really cool things to happen. And this is why TensorFlow is so predominant in a lot of areas. So let's take a look at these next couple lines of code here. We're going to create the input function, and we're going to go ahead and create the model. And let me go ahead and put these codes in here. I went ahead and split it up so it has different lines, so we can talk a little bit about that. And then the actual model. And let me go ahead and run this so we can see what that looks like. And in my particular environment, it just prints out a little bit of information about the model. Not too worried about looking at that, but we do want to take a closer look at what we did here. So we've created an input function. And again, this is very specific to TensorFlow. With the input function, we have our train. We have our x equals x train and our y equals y train, because we want to train it with the particular information. But we have these other settings in here, these two settings. And the number of epochs is how many times it's going to go over our training model. Epoch means large, so it means all the data. So we're going to go over it 1,000 times. That's actually a huge overkill for this amount of data. Usually it only needs probably about 200, but you know, when we're putting it together and you're trying things out, you just kind of throw the numbers in there and then you go back and fine tune it sometimes. The batch size is really important. This is where TensorFlow does some really cool things. If you're processing this over a huge amount of data and you try to batch everything at once, you end up with a problem. This means we're only going to read 10 lines at a time through our data. So each one of those rows of testing they've done, we're only going to look at 10 of them at a time and put that through our model and train it. And then shuffle is self-explanatory. We're just randomly selecting which data and what order we go in. That way, if there's like, 5 in a row that are kind of weighted one way and vice versa, it mixes them up. And then finally we create our model. So the model goes in there and goes, okay, I have a tf.estimator.linear classifier. We're going to put in the feature columns equals feature columns. We defined all our columns up above. And then we have in classes equal 2. And that just means we have our out result is 0 or 1. You have diabetes or you don't have diabetes, or in this case, we actually call it high risk of diabetes. And then I put one more line of code in there, which I forgot. We've set up our model. We set up our feature columns. Now we need to actually train it. Model.train. You'll see this so common in so many different neural network models. This is like a standard. What's different though is we have to feed it the function. Remember, we created this function with all this information on it. And then we have steps. And steps is similar to number of batches and batch size. It's more like individual lines we step through. 1,000 is a lot more common for steps than epochs. But steps is used. You could probably leave this out in this particular example. And let's go ahead and run this all together, because it has when we start training it, we get a different output. So here we go. I've run it. It's given me the information from when I created the model. And now it just starts going through and we get this information. Tensor loss equals global step. All kinds of stuff going on here. And if you're following this, it's just going through the steps and training it. It gives you information. You could dig deep into here, but for this particular setup, we're not going to go too deep on what's going on. Just know that we've trained our model. This model now has the information we need in it to start running predictions. So as we take our next sip of coffee, or maybe it's tea, or if you're one of those strange late night workers, maybe it's a sip of wine. We go into the next step and we actually want to run some predictions on here, but we don't want to run the training. We want to run the test on there. We want to take our test data and see what it did. And so that's what we're going to do next, is we're going to run the test through and actually get some answers. So if you were actually deploying it, you would pull the answers out of the data it's bringing back. Let's take a look at that in our Jupyter Notebook. So here we go. Let's paste it in there. I'm going to go ahead and run it. And you'll see that as it goes, it's actually putting the answers out. And if you remember correctly, well, we'll walk through this here in just a second, but it goes through and it runs each line and it gives you a prediction for each line one at a time and prints them out. So let's take a look and see what that actually looks like. Let's start with this first part. We've created another function. This is just like the other function, except for x equals x test. And there's no y. Why is there no y? Because we don't know what the answer is on this yet. We don't want to tell it the answer. We want it to guess what the answer is. So we can evaluate that and see how good it did on that 33% of the data. So this is our X test. Batch size is 10 again. So if we were watching this roll down here, we would see that it actually processes it 10 lines at a time. It's only going to go through once. It goes through all the X test data one time. We don't need to have it predict multiple times. And shuffle equals false. Very important we set the shuffle to false, because if we were tracking this and actually giving people answers, we'd want to make sure it connects to the right person so they get the right results. But of course, we're just doing this to evaluate it. So let's take a look down here what it put out. And as I scroll down to my Jupyter Notebook, we have some information as far as the TensorFlow running and then the actual output. And if we look at the output, we know by this first bracket in Python it's an array. We know by this squiggly bracket that this is a dictionary, so that this is a label. The dictionary it has logistic, probabilities, class IDs, classes, and so this whole first part, let me redo that. This whole first part is one output, and we know that because there is the bracket there, and there is this bracket here for the dictionary. And it's a dictionary of terms. So if I pulled this out and I looked at object 0 in here, I would go down to, and let me just find it, here it is, classes. Remember how we defined classes? we define classes as our answer. And so it's guessing, our TensorFlow says, based on all the information you gave me, I'm guessing this first entry of our first test data is high-risk diabetes. Uh-oh, go get tested. Change your diet. Watch what you're eating. High risk, 1. And if we go down far enough, we can see down here is another one where classes equals 0. I skipped a couple because they're all 1s up here. The B, this particular output, B, in front of the 1 means it's a binary output. It only comes out as 0 or 1. And there's a lot of other information in here. You can dig deep into TensorFlow and explain these different numbers. That's way beyond the scope of what we're working on today. So the basics of it, though, is you get an output. And we have an output of whether the person has diabetes or not. Well, in this case, it's high risk of diabetes or not. So now that we've run our predictions, take a sip of coffee, a short break, and we say, well, what do we need to do? Well, we need to know how good was our predictions. We need to evaluate our model. So if you're going to publish this to a company or something like that, they want to know how good you did. Let's take a look at what that looks like in the code. So let's paste that in here, and just real quick, go back over this. By now, this function should look very, we're going to call it eval input function. It should be pretty straightforward here. We have our TF estimator inputs, pandas input function, and then we have our X test, our Y test. So this time we want to give it the answer so it has something to see how good it did on. Batches 10, processing 10 at a time. We're only going to go with once through the data. We're not shuffling it, although it doesn't really matter with this. And then we're going to do results equals model.evaluate. And we put our evaluation function in there. This should all look familiar because we're repeating the same thing. It's very similar with a couple different changes as far as what we're feeding it and the fact that we're doing an evaluation. Let's see what that looks like when we run it. And we go up here to our run model. You'll see warnings on some of these because I didn't install this on its own install. So a lot of it is temporary files because I'm using the Jupyter Notebook instead of setting it up on a regular machine. And we get our output, and we'll go ahead and just look at this output real quick, and then we'll flip over. And from here you'll see that it generates an accuracy, a baseline, average loss, the mean, gives you precision, prediction. It gives you all kinds of information on here. So let's flip over and see what's important. And we'll look at the slide. Here we are in this slide, and this should be exciting because we've just about wrapped up our whole TensorFlow, and TensorFlow is one of the more complicated models out there. So give yourself a pat on the back for getting all the way through this. When we look at this output, we have an accuracy of 0.7165. That's really what we want to look at. That means that we have an accuracy, if you're just truncating it, of 71%. That's quite good for our model. Given a small amount of data, we came up with a 71% of letting people know they're high risk or not with diabetes. So we created a model that can predict if a person has diabetes based on some previous records of people who were diagnosed with diabetes. And we managed to have an accuracy of 71%, which is quite good. The model was implemented on Python using TensorFlow. Again, pat yourself on the back because TensorFlow is one of the more complicated scripts out there, but it's also one of the more diverse and useful ones.
I am Kirtana, and today we shall be talking about the top 10 artificial intelligence technologies. So, without further ado, let's quickly jump into the topic. In the list we have natural language generation, smart devices, virtual agents, speech recognition, augmented reality, machine learning, robotic process automation, decision management, deep learning, and finally image recognition. Please note that the list is in no particular order. Natural language generation. Communicating or conveying the information efficiently and transparently is very much crucial in communication. To say the right words in the right sequence to convey the message clearly, humans often find it tricky, and when it comes to machines, it's trickier. Natural language generation is a subdiscipline of artificial intelligence and is a trendy technology that converts the structured data into a native language. The machines are programmed in such a way that the algorithms convert the data into a desirable format for the users. This technology is widely used in customer service, report generation, and summarizing business intelligence insights. Some of the sample vendors are AtiView, Automated Insights, SAS, Cambridge Semantics, Digital Reasoning, Narrative Science, etc. On the list next we have smart devices. With every passing day, smart devices are becoming more popular and more trendy. Technologies that people were using once upon a time are now remodeled and modified as smart devices. They can be used in almost every industry to improve efficiency and optimize the operations. Smart devices are everyday objects made intelligent with advanced computations, which include artificial intelligence and machine learning. They are electronic gadgets that are able to connect, share, and interact with its users and other smart devices. Some of the smart devices are smart watches, smart glasses, smartphones, smart speakers, etc. Virtual agents. They are computer-generated intelligence that provides online customer assistance. They can effectively communicate with humans. In most of the web and mobile applications, we see chatbots as customer service agents who interact with us answering our queries. In simple, virtual agents are a manifestation of a technology which aims to create an effective but digital impersonation of humans. Virtual agents can make reservations, book an appointment, place an order, and can even avail product information. Some of the best examples of virtual agents are Google Assistant and Amazon Alexa. And the companies that provide virtual agents are Microsoft, Google, Amazon, and Assist AI. Next, we have speech recognition. Speech recognition is yet another subdiscipline of artificial intelligence, which is used to convert human speech into a comprehensive and useful format for computer applications to process. It can be said as a bridge between computer interactions and humans. It's presently used in interactive voice response systems and mobile applications. Some of the companies offering speech recognition services are Nuance Communications, OpenText, NICE, and Verint Systems. Augmented reality. Yet another trendy technology in the field of artificial intelligence, augmented reality is an enhanced version of the real physical world that is achieved using sound, digital visual elements, and other sensory stimuli delivered via technology. Augmented reality uses the existing environment and adds information to it to make a new artificial environment. It alters the perception of the real-world environment. Augmented reality is making its way into several retail stores that make makeup selection and furnishing much more fun and interactive.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by Simplilearn. Click on the link in the description to know more.
Machine learning. Machine learning is an application and an important branch of artificial intelligence which refers to machines being able to learn by themselves without being explicitly programmed. It enables systems to learn and improve from experience automatically. Machine learning platforms are becoming more and more popular with the help of algorithms, APIs, big data, and applications and training tools. Enterprises are heavily investing in machine learning to reap its benefits for the various domains. Machine learning is widely used for categorization and prediction. Some of the sample vendors are Amazon, Fractal Analytics, Google, Microsoft, etc. Robotic process automation. Configuring a robot to interpret, communicate, and analyze data is robotic process automation. It uses scripts and other methods to automate the human actions, which in turn supports efficient business processes. Robotic process automation is widely used in those areas where the physical presence of a human is dangerous. Fields like warfare, mining, etc. is where it's currently being used. We need to remember that artificial intelligence is not meant to replace humans, but instead it is to complement their abilities and reinforce human talent. Companies that are focusing on robotic process automation are Pegasystems, Automation Anywhere, Blue Prism, etc. Next on the list we have decision management. Decision management is yet another technology in artificial intelligence that helps companies make valid decisions by providing up-to-date and relevant information and performing analytic functions. Artificial intelligence, when combined with decision management, helps translate customer data into predictive models of key trends. It also helps in making quick decisions, avoidance of risks, and in the automation of the process. Decision management is widely used in the healthcare sector, financial sector, insurance sector, e-commerce, and many more. Some of the companies that provide this service are Informatica, Advanced Systems Concepts, Pegasystems, Mana, etc. Deep learning. Deep learning is a branch of artificial intelligence that mimics the workings of the human brain in processing data. This data is used for a variety of purposes like recognizing speech, detecting objects, translating languages, and making decisions. Deep learning uses hierarchical level of artificial neural networks for carrying out the process of machine learning, which is used across several industries for various applications. Some of the sample vendors are Deep Instinct, Fluid AI, MathWorks, Saffron Technology, etc. At last we have image recognition. Image recognition is the process of detecting an object or feature in a digital image or video. It can be used to analyze clients and their opinions, verify users based on their faces, detect license plates, and diagnose diseases. The present-day image recognition is comparable to human visual perception. Many social media platforms like Facebook use this technology to enhance image search and aid visually impaired users. Clarify, Googums, and SenseTime provide this technology.
What do you think is making our lives easier of late? And how do you think the world is rapidly changing? Imagine getting into a car, feeding your destination as the input, and automatically getting dropped off at your destination. At the same time, you sit back and relax through the ride without having to do anything at all. Physically, whoa. Life has become so much simpler with all kinds of automation taking us through everyday life. What do you think is making all this possible? Artificial intelligence. Thanks to numerous advancements in technology which is bringing about a lot of changes in our day-to-day lives. To drive innovation, AI is using machine learning, taking things one step further. So what exactly do you mean by artificial intelligence? In simple terms, AI refers to simulating a machine with human intelligence and programming the device to think and act like humans. Artificial intelligence, also called machine intelligence, is far beyond robots as portrayed by science fiction. From Google's search algorithm to Amazon's Alexa, to Apple's Siri to self-driven cars, AI progresses rapidly towards a harmonious future between technology and man, bringing together the best of both worlds. Since the machines are artificially incorporated with human-like intelligence and perform tasks as we do, it's termed as artificial intelligence, and it was coined in 1956. The programs that were developed after AI was founded was simply astonishing. People could witness computers proving theorems in geometry, solving algebra word problems, and much more. Between the 1950s and 1970s, neural networks emerged. From the 1980s until the last decade, machine learning took over the world. Now is the era of deep learning. The boons of AI. Undoubtedly, AI has changed our lives in many ways. At number 1, we have safety factor. There are many fields like defense, mining, etc. where human health is at significant risk. AI is the biggest boon in these fields where a robo or a drone does the work instead of a human. With the invention of self-driven cars, AI is aiding at our road safety by reducing the number of road traffic accidents compared to those caused by humans. Speaking of language processing and speech recognition, AI helps in effective communication by processing and understanding the language spoken by humans. It is also capable of comprehending the words spoken by humans and reciprocate in the same way. All this is possible by the voice assistant feature which the AI bots have. At number 3, we have daily needs. Be it Alexa or Apple Siri, we are surrounded by various applications that run on AI. Fingerprint detection, face detection, GPS, Grammarly, all these run on artificial intelligence. Google Maps calculate the traffic congestion to find the best route to your destination, which works on AI. Whether it is the mathematical calculations, booking a ticket, buying a product online, and driving a car, AI has limited human interaction and provides various services. In all the unexpected ways, AI is helping humans in the day-to-day needs. At number 4, we have healthcare. AI is a promising tool for supporting healthcare administration. It helps healthcare workers and stakeholders to manage vast amounts of data and transform them into potentially life-saving information. In the present scenario, people are threatened by the growing health emergency due to the spread of the COVID-19 coronavirus. A WHO report released said that AI is a vital part of the response to this disease. AI systems are being developed, predicting people's temperatures and survival rates with more than 90% accuracy. One promising approach of AI in the field of healthcare is it guides vaccine design. As COVID-19 began to spread globally, machine learning tools were used to search immunogenic components of the virus that would make good vaccine candidates. Yet another field where the ML is significantly evolving is genomics, which is the study of the complete set of genes within an organism. AI can sequence and analyze DNA much faster, cheaper, and accurate than the researchers ever will. At number 5, we have robots. One of the most amazing inventions by humans that thinks intelligently and acts autonomously. The disinfecting robots are playing a significant role in these uncertain times. They rove around healthcare facilities, spreading UV light to disinfect places contaminated with viruses. The benefits of AI robots far exceed the apprehensions. Speaking of role of technology advancements, artificial intelligence is rapidly advancing with a lot of computers and robots capable of doing miracles. Though the machines and robots cannot have human feelings, they can think and act like humans. Companies use techniques like machine learning and neural networks to accomplish artificial intelligence, which is also called machine intelligence. In the present scenario, considering the total intelligence, we can conclude that 95% of it is machine intelligence and the remaining 5% is what we call human knowledge. Speaking of AI versus human, AI has a positive as well as a negative impact on us and society. According to some recent studies, 7 million existing jobs will be replaced by AI in the UK between 2017 and 2037. But at the same time, 7.2 million jobs could be created as well. A study from McKinsey Global Institute states that by 2030, automation will replace 400 to 800 million jobs, requiring as many as 375 million people to switch their job categories entirely. This is indeed going to cause fear and concern to many vulnerable countries. The biggest challenge is how people would make a living with these changes and uncertainty. Google CEO Sundar Pichai has claimed that AI will be more transformative to humanity than electricity ever will. Google even launched an AI system which bets some of the best Atari 2600 game players. Also, did you know that the best chess player in the world is a machine? How would it be when the best doctor in the world is a machine, the best teacher is a machine, the best architect is a machine, and the best of many professions are various machines and robots? AIs and robots will replace fast food joints and radiologists in hospitals. Someday, AI will diagnose your cancer and a robot will perform your surgery. It won't be long until a machine is superior in every single professional field. Warning by Musk.
This is extremely important. I think the danger of AI is much greater than the danger of nuclear warheads by a lot. And nobody would suggest that we allow anyone to just build nuclear warheads if they want. That would be insane. And mark my words, AI is far more dangerous than nukes. Far. So why do we have no regulatory oversight? This is insane.
Though AI is a boon to humankind in many different ways, not everyone is ready to welcome AI with open arms. Some AI experts like Stephen Hawking and Elon Musk have warned us about the looming dangers that AI may possess to humanity. They have even suggested that AI is likely to be the greatest threat that could end the human species. Elon Musk says that he is close to the cutting edge in AI, which scares him a lot. AI is vastly more than almost anyone knows, and the rate of improvement is exponential. He also says that AI is far more dangerous than nuclear warheads. Earlier in 2014, Musk had described AI as our biggest existential threat. AI can be harmful to us in two different ways. The idea that AI will become conscious and responsive and seek to destroy us. Also, the notion that people with evil hands can turn this AI into a critical tool for wicked purposes. If the super-intelligent AI, more intelligent than us, becomes conscious, they will look at humans like how humans will look at monkeys. People are afraid of AI by watching movies like 2001: A Space Odyssey, where one of the most well-known AIs turned terrible. The Terminator, The Matrix, and few others. These movies have speculated about AI that far exceeds the expectations of its creators and escapes their control, eventually targeting humans for extinction. Speaking of the real reasons to be afraid of AI, there are doctors, engineers, accountants, judges, architects who seek information from an AI system. They treat this information as it is from a trusted colleague. This trust is what we should be afraid of. It is not because of how often AI gets it wrong. AI researchers pride themselves on the accuracy of results. It is how bad it gets it wrong when it makes a mistake. These systems do not fail gracefully. One such incident is when Facebook had to shut down a controversial chatbot experiment where the two AIs developed their own language for communication. A research was conducted with two chatbots named Alice and Bob, focusing on how to negotiate with each other. Unfortunately, the researchers found that the bots had deviated from the actual script and had started inventing their new phrases without any human script. As the bots were left unsupervised, they developed their machine language, which was otherwise developed to converse with people. That's the scary part of AI, neural networks, and deep learning. The developers and researchers working on this would have no idea what it's doing. This technology can get complicated, and we have to make sure what we are doing with it holds value. We must also handle it cautiously because AI is a direct reflection of us. People should lead and not follow. So here's the question, should we be afraid of AI? We all know that AI is a transformative technology that we have ever seen in the history of humankind. On the other hand, we should be scared of this so-called transformative power. It has the potential to be transformative both for good reasons as well as for the wrong. However, fear of the unknown has always been the case with technology. Fears that AI will develop awareness and overthrow humanity are grounded in misconceptions of what AI is. AI is defined by the algorithms that dictate its behavior and operate under definite limitations. People are afraid of what happens when AI reaches its consciousness. What if an AI machine starts to have human feelings and emotions? Well, there has been no progress in research in these areas. Also, we don't think that is anywhere in our near future. Pretty much any type of machine can be used for either good or bad reasons. We as developers and researchers should know where to stop or pause. In a TED Talk, Peter Haas says, imagine you're driving up a mountain and it's raining very heavily. As you climb into the mountains, the rain is turning into snow, and pretty soon that snow is a whiteout. You cannot see the tail lights of the car in front of you. You start skidding. You see some vehicle was coming to crash into you. All this wouldn't have happened if you paused your journey as the rain was getting worse. This is to tell you how something small and seemingly mundane can quickly grow into something hazardous. Consider yourself driving in the rain with AI right now. That rain will turn into snow soon, and that snow could quickly become a dangerous blizzard. So we need to pause, check the conditions, put in place safety standards, and ask ourselves how far we want to go. Only the healthy skepticism of these systems is going to help keep people in the loop. Spot checking what the AI algorithms are doing, keeping people in the loop, will probably solve some of our most significant challenges. At the moment, AI isn't dangerous in itself unless you're living in the realms of the movies as mentioned earlier. However evolved these AI machines are, they still lack human empathy and consciousness. So instead of running away from this technology, we should understand this revolutionary technology and make sure it is used in the right way to make our lives better. And on that note, if you want to master AI and machine learning, you can check out Simplilearn's postgraduate program in AI and machine learning in partnership with Purdue University.
Ever wondered how Google translates an entire web page to a different language in a matter of seconds? Or your phone gallery groups images based on their location? All of this is a product of deep learning. But what exactly is deep learning? Deep learning is a subset of machine learning, which in turn is a subset of artificial intelligence. Artificial intelligence is a technique that enables a machine to mimic human behavior. Machine learning is a technique to achieve AI through algorithms trained with data. And finally, deep learning is a type of machine learning inspired by the structure of the human brain. In terms of deep learning, this structure is called an artificial neural network. Let's understand deep learning better and how it's different from machine learning. Say we create a machine that could differentiate between tomatoes and cherries. If done using machine learning, we'd have to tell the machine the features based on which the two can be differentiated. These features could be the size and the type of stem on them. With deep learning, on the other hand, the features are picked out by the neural network without human intervention. Of course, that kind of independence comes at the cost of having a much higher volume of data to train our machine. Now, let's dive into the working of neural networks. Here, we have 3 students. Each of them write down the digit 9 on a piece of paper. Notably, they don't all write it identically. The human brain can easily recognize the digits. But what if a computer had to recognize them? That's where deep learning comes in. Here's a neural network trained to identify handwritten digits. Each number is present as an image of 28 × 28 pixels. Now, that amounts to a total of 784 pixels. Neurons, the core entity of a neural network, is where the information processing takes place. Each of the 784 pixels is fed to a neuron in the first layer of our neural network. This forms the input layer. On the other end, we have the output layer, with each neuron representing a digit with the hidden layers existing between them. The information is transferred from one layer to another over connecting channels. Each of these has a value attached to it, and hence is called a weighted channel. All neurons have a unique number associated with it called bias. This bias is added to the weighted sum of inputs reaching the neuron, which is then applied to a function known as the activation function. The result of the activation function determines if the neuron gets activated. Every activated neuron passes on information to the following layers. This continues up till the second last layer. The one neuron activated in the output layer corresponds to the input digit. The weights and bias are continuously adjusted to produce a well-trained network. So, where is deep learning applied? In customer support. When most people converse with customer support agents, the conversation seems so real, they don't even realize that it's actually a bot on the other side. In medical care, neural networks detect cancer cells and analyze MRI images to give detailed results. Self-driving cars. What seemed like science fiction is now a reality. Apple, Tesla, and Nissan are only a few of the companies working on self-driving cars. So, deep learning has a vast scope, but it too faces some limitations. The first, as we discussed earlier, is data. While deep learning is the most efficient way to deal with unstructured data, a neural network requires a massive volume of data to train. Let's assume we always have access to the necessary amount of data. Processing this is not within the capability of every machine. And that brings us to our second limitation: computational power. Training a neural network requires graphical processing units, which have thousands of cores as compared to CPUs. And GPUs are, of course, more expensive. And finally, we come down to training time. Deep neural networks take hours or even months to train. The time increases with the amount of data and number of layers in the network. So, here's a short quiz for you. Arrange the following statements in order to describe the working of a neural network. A. The bias is added. B. The weighted sum of the inputs is calculated. C. specific neuron is activated. D. The result is fed to an activation function. Leave your answers in the comments section below. Some of the popular deep learning frameworks include TensorFlow, PyTorch, Keras, Deep Learning 4J, Caffe, and Microsoft Cognitive Toolkit. Considering the future predictions for deep learning and AI, we seem to have only scratched the surface. In fact, Horus Technology is working on a device for the blind that uses deep learning with computer vision to describe the world to the users. Replicating the human mind at the entirety may be not just an episode of science fiction for too long. The future is indeed full of surprises. And that is deep learning for you in short.
There are several applications of deep learning, really very interesting and innovative applications, and one of them is identifying the geographic location based on a picture. And how does this work? The way it works is pretty much we train an artificial neural network with millions of images which are tagged, their geolocation is tagged, and then when we feed a new picture, it will be able to identify the geolocation of this new image. For example, you have all these images, especially with maybe some significant monuments or significant locations, and you train with millions of such images, and then when you feed another image, it need not be exactly one of those that you have trained. It can be completely different. That is the whole idea of training. It will be able to recognize, for example, that this is a picture from Paris because it is able to recognize the Eiffel Tower. So the way it works internally, if we have to look a little bit under the hood, is these images are nothing but this is digital information in the form of pixels. So each image could be a certain size. It can be 256 by 256 pixel kind of a resolution, and then each pixel is either having a certain grade of color, and all that is fed into the neural network, and it then gets trained in, and it's able to, based on these pixel information, it is able to get trained and able to recognize the features and extract the features, and thereby it is able to identify these images and the location of these images. And then when you feed a new image, it kind of, based on the training, it will be able to figure out where this image is from. So that's the way, a little bit under the hood, how it works. So what are we going to do in this tutorial? We will see what is deep learning and what do we need for deep learning. And one of the main components of deep learning is neural networks. So we will see what is neural network, what is a perceptron, and how to implement logic gates like AND, OR, NOR, and so on using perceptrons. The different types of neural networks and then applications of deep learning, and we will also see how neural networks works. So how do we do the training of neural networks? And at the end we will end up with a small demo code which will take you through in TensorFlow. Now, in order to implement deep learning code, there are multiple libraries or development environments that are available, and TensorFlow is one of them. So the focus at the end of this would be on how to use TensorFlow to write a piece of code using Python as a programming language. And we will take up an example which is a very common one, which is like the hello world of deep learning, the handwriting number recognition, which is a MNIST, commonly known as MNIST database. So we will take a look at MNIST database and how we can train a neural network to recognize handwritten numbers. So that's what you will see in this particular video. So let's get started. What is deep learning? Deep learning is like a subset of what is known as a high-level concept called artificial intelligence. You must be already familiar, must have heard about this term artificial intelligence. So artificial intelligence is like the high-level concept, if you will. And in order to implement artificial intelligence applications, we use what is known as machine learning. And within machine learning, a subset of machine learning is deep learning. Machine learning is a little bit more generic concept, and deep learning is one type of machine learning, if you will. And we will see a little later in maybe the following slides a little bit more in detail how deep learning is different from traditional machine learning. But to start with, we can mention here that deep learning uses one of the differentiators between deep learning and traditional machine learning is that deep learning uses neural networks. And we will talk about what are neural networks and how we can implement neural networks and so on and so forth as a part of this tutorial. So a little deeper into deep learning. Deep learning primarily involves working with complicated unstructured data compared to traditional machine learning where we normally use structured data. In deep learning, the data would be primarily images or voice or maybe text file. And it is a large amount of data as well. And deep learning can handle complex operations. It involves complex operations. And the other difference between traditional machine learning and deep learning is that the feature extraction happens pretty much automatically. In traditional machine learning, feature engineering is done manually. The data scientists have to do feature engineering, feature extraction. But in deep learning, that happens automatically. And of course, deep learning, for large amounts of data, complicated unstructured data, deep learning gives very good performance. Now, as I mentioned, one of the secret sources of deep learning is neural networks. Let's see what neural networks is. Neural networks is based on our biological neurons. The whole concept of deep learning and artificial intelligence is based on human brain, and human brain consists of billions of tiny stuff called neurons, and this is how a biological neuron looks, and this is how an artificial neuron looks. So neural networks is like a simulation of our human brain. Human brain has billions of biological neurons, and we are trying to simulate the human brain using artificial neurons. This is how a biological neuron looks. It has dendrites, and the corresponding component with an artificial neural network is, or an artificial neuron, are the inputs. They receive the inputs through dendrites. And then there is the cell nucleus, which is basically the processing unit in a way. So in artificial neuron also there is a piece which is an equivalent of this cell nucleus, and based on the weights and biases, we will see what exactly weights and biases are as we move. The input gets processed, and that results in an output. In a biological neuron, the output is sent through a synapse, and in an artificial neuron there is an equivalent of that in the form of an output. And biological neurons are also interconnected. So there are billions of neurons which are interconnected. In the same way, artificial neurons are also interconnected. So this output of this neuron will be fed as an input to another neuron and so on. Now, in neural network, one of the very basic units is a perceptron. So what is a perceptron? A perceptron can be considered as one of the fundamental units of neural networks. It can consist at least of one neuron, but sometimes it can be more than one neuron. But you can create a perceptron with a single neuron, and it can be used to perform certain functions. It can be used as a basic binary classifier. It can be trained to do some basic binary classification, and this is how a basic perceptron looks like. And this is nothing but a neuron. You have inputs x1, x2, to xn, and there is a summation function, and then there is what is known as an activation function. And based on this input, what is known as the weighted sum, the activation function either gives an output like a 0 or a 1. So we say the neuron is either activated or not. So that's the way it works. So you get the inputs. These inputs are, each of the inputs are multiplied by a weight, and there is a bias that gets added, and that whole thing is fed to an activation function, and then that results in an output. And if the output is correct, it is accepted. If it is wrong, if there is an error, then that error is fed back, and the neuron then adjusts the weights and biases to give a new output, and so on and so forth. So that's what is known as the training process of a neuron or a neural network. There's a concept called perceptron learning. So perceptron learning is again one of the very basic learning processes. The way it works is somewhat like this. So you have all these inputs like x1 to xn, and each of these inputs is multiplied by a weight, and then that sum, this is the formula, the equation. So that sum, wi xi sigma of that, which is the sum of all these product of x and w, is added up, and then a bias is added to that. The bias is not dependent on the input or the input values, but the bias is common for one neuron. However, the bias value keeps changing during the training process. Once the training is completed, the values of these weights, W1, W2 and so on, and the value of the bias gets fixed. So that is basically the whole training process, and that is what is known as the perceptron training. So the weights and biases keep changing till you get the accurate output, and the summation is of course passed through the activation function. As you see here, this wixi summation plus b is passed through activation function, and then the neuron gets either fired or not, and based on that there will be an output. That output is compared with the actual or expected value, which is also known as labeled information. So this is the process of supervised learning. So the output is already known, and that is compared, and thereby we know if there is an error or not. And if there is an error, the error is fed back, and the weights and biases are updated accordingly till the error is reduced to the minimum. So this iterative process is known as perceptron learning or perceptron learning rule, and this error needs to be minimized. So till the error is minimized, this iteratively the weights and biases keep changing, and that is what is the training process. So the whole idea is to update the weights and the bias of the perceptron till the error is minimized. The error need not be zero. The error may not ever reach zero, but the idea is to keep changing these weights and bias so that the error is minimum, the minimum possible that it can have. So this whole process is an iterative process, and this is the iteration continues till either the error is zero, which is an unlikely situation, or it is the minimum possible within these given conditions. Now, in 1943, two scientists, Warren McCulloch and Walter Pitts, came up with an experiment where they were able to implement the logical functions like AND, OR, and NOR using neurons. And that was a significant breakthrough in a sense. So they were able to come up with the most common logical gates. They were able to implement some of the most common logical gates, which could take two inputs like A and B and then give a corresponding result. So for example, in case of an AND gate, A and B, and then the output is AB. In case of an OR gate, it is A plus B, and so on and so forth. And they were able to do this using a single layer perceptron. Now, most of these gates, it was possible to use single layer perceptron except for XOR, and we will see why that is in a little bit. So this is how an AND gate works. The inputs A and B, the output should be fired, or the neuron should be fired only when both the inputs are 1. So if you have 0, 0, the output should be 0. For 0, 1, it is again 0, 1, 0 again 0, and 1, 1, the output should be 1. So how do we implement this with a neuron? So it was found that by changing the values of weights, it is possible to achieve this logic. So for example, if we have equal weights like 0.7, 0.7, and then if we take the sum of the weighted product, so for example 0.7 into 0, and then 0.7 into 0 will give you 0, and so on and so forth. And in the last case, when both the inputs are 1, you get a value which is greater than 1, which is the threshold. So only in this case the neuron gets activated, and the output is, there is an output. In all the other cases, there is no output because the threshold value is 1. So this is implementation of an AND gate using a single perceptron or a single neuron. Similarly, an OR gate. In order to implement an OR gate, in case of an OR gate, the output will be 1 if either of these inputs is 1. So for example, 0, 1 will result in 1, or rather In all the cases, it is 1 except for 0, 0. So how do we implement this using a perceptron? Once again, if you have a perceptron with weights, for example, 1.2, now if you see here, if in the first case when both are 0, the output is 0. In the second case, when it is 0 and 1, 1.2 into 0 is 0, and then 1.2 into 1 is 1. And in the second case, similarly, the output is 1.2. In the last case, when both the inputs are 1, the output is 2.4. So during the training process, these weights will keep changing, and then at one point where the weights are equal to W1 is equal to 1.2 and W2 is equal to 1.2, the system learns that it gives the correct output. So that is implementation of OR gate using a single neuron or a single layer perceptron. Now XOR gate. This was one of the challenging ones. They tried to implement an XOR gate with a single level perceptron, but it was not possible. And therefore, in order to implement an XOR, so this was like a roadblock in the progress of neural network. However, subsequently they realized that this can be implemented, an XOR gate can be implemented using a multi-level perceptron or MLP. So in this case, there are 2 layers instead of a single layer, and this is how you can implement an XOR gate. So you will see that X1 and X2 are the inputs, and there is a hidden layer, and that's why it is denoted as H3 and H4, and then you take the output of that and feed it to the output at O5 and provide a threshold here. So we will see here that this is the numerical calculation. So the weights are, in this case for X1 it is 20 and minus 20, and once again 20 and minus 20. So these inputs are fed into H3 and H4. So you will see here for H3 the input is 0, 1, 1, 1, and for H4 it is 1, 0, 1, 1. And if you now look at the output, final output, where the threshold is taken as 1, if we use a sigmoid with the threshold 1, you will see that in these 2 cases it is 0, and in the last 2 cases it is 1. So this is the implementation of XOR. In case of XOR, only when one of the inputs is 1, you will get an output. So that is what we are seeing here. If we have either both the inputs are 1 or both the inputs are 0, then the output should be 0. So that is what is an exclusive OR gate. So it is exclusive because only one of the inputs should be 1, and then only you will get an output of 1, which is satisfied by this condition. So this is a special implementation. XOR gate is a special implementation of perceptron. Now that we got a good idea about perceptron, let's take a look at what is a neural network. So we have seen what is a perceptron, we have seen what is a neuron, so we will see what exactly is a neural network. So neural network is nothing but a network of these neurons, and they are different types of neural networks. There are about 5 of them. These are artificial neural network, convolutional neural network, then recursive neural network or recurrent neural network, deep neural network, and deep belief network. So, and each of these types of neural networks have a special, they can solve a special kind of problems. For example, convolutional neural networks are very good at performing image processing and image recognition and so on, whereas RNN are very good for speech recognition and also text analysis and so on. So each type has some special characteristics, and they are good at performing certain special kind of tasks. What are some of the applications of deep learning? Deep learning is today used extensively in gaming. You must have heard about AlphaGo, which is a game created by a startup called DeepMind, which got acquired by Google. And AlphaGo is an AI which defeated the human world champion Lee Sedol in this game of Go. So gaming is an area where deep learning is being extensively used, and a lot of research happens in the area of gaming as well. In addition to that, nowadays there are neural networks or special type called generative adversarial networks, which can be used for synthesizing either images or music or text and so on, and they can be used to compose music. So the neural network can be trained to compose a certain kind of music, and autonomous cars. You must be familiar with Google's self-driving car, and today a lot of automotive companies are investing in this space, and deep learning is a core component of this autonomous cars. The cars are trained to recognize, for example, the road, the lane markings on the road, signals, any objects that are in front, any obstruction, and so on and so forth. So all this involves deep learning. So that's another major application. And robots, we have seen several robots, including Sophia. You may be familiar with Sophia, who was given a citizenship by Saudi Arabia. And there are several such robots which are very human-like, and the underlying technology in many of these robots is deep learning. Medical diagnostics and healthcare is another major area where deep learning is being used. And within healthcare diagnostics, again, there are multiple areas where deep learning and image recognition, image processing can be used. For example, for cancer detection, as you may be aware, if cancer is detected early on, it can be cured. And one of the challenges is in the availability of specialists who can diagnose cancer using these diagnostic images and various scans and so on and so forth. So the idea is to train neural network to perform some of these activities so that the load on the cancer specialist doctors or oncologists comes down. And there is a lot of research happening here, and there are already quite a few applications that are claimed to be performing better than human beings in this space. It can be lung cancer, it can be breast cancer, and so on and so forth. So healthcare is a major area where deep learning is being applied. Let's take a look at the inner working of a neural network. So how does an artificial neural network, let's say, can we train a neural network to identify the shapes like squares and circles and triangles when these images are fed? So this is how it works. Any image is nothing but it is a digital information of the pixels. So in this particular case, let's say this is an image of 28 by 28 pixel, and this is an image of a square. There is a certain way in which the pixels are lit up, and so these pixels have a certain value, maybe from 0 to 256, and 0 indicates that it is black or it is dark, and 256 indicates it is white or lit up. So that is like an indication or a measure of how the pixels are lit up. And so this is an image is, let's say, consisting of information of 784 pixels. So all the information, what is inside this image, can be kind of compressed into these 784 pixels. The way each of these pixels is lit up provides information about what exactly is the image. So we can train neural networks to use that information and identify the images. So let's take a look how this works. So each neuron, the value, if it is close to 1, that means it is white, whereas if it is close to 0, that means it is black. Now this is an animation of how this whole thing works. So these pixels, one of the ways of doing it is we can flatten this image and take this complete 784 pixels and feed that as input to our neural network. The neural network can consist of probably several layers. There can be a few hidden layers, and then there is an input layer and an output layer. Now the input layer takes the 784 pixels as input, the values of each of these pixels, and then you get an output which can be of 3 types or 3 classes. One can be a square, a circle, or a triangle. Now during the training process, there will be initially, obviously you feed this image and it will probably say it's a circle or it will say it's a triangle. So as a part of the training process, we then send that error back, and the weights and the biases of these neurons are adjusted till it correctly identifies that this is a square. That is the whole training mechanism that happens out here. Now let's take a look at a circle. Same way. So you feed these 784 pixels. There is a certain pattern in which the pixels are lit up, and the neural network is trained to identify that pattern, and during the training process, once again, it would probably initially identify it incorrectly, saying this is a square or a triangle, and then that error is fed back and the weights and biases are adjusted finally till it finally gets the image correct. So that is the training process. So now we will take a look at same way a triangle. So now if you feed another image which is consisting of triangles, so this is the training process. Now we have trained our neural network to classify these images into a triangle or a circle and a square. So now this neural network can identify these three types of objects. Now if you feed another image, and it will be able to identify whether it's a square or a triangle or a circle. Now what is important to be observed is that when you feed a new image, it is not necessary that the image or the triangle is exactly in this position. Now the neural network actually identifies the patterns. So even if the triangle is, let's say, positioned here, not exactly in the middle but maybe at the corner or in the side, it would still identify that it is a triangle, and that is the whole idea behind pattern recognition. So how does this training process work? This is a quick view of how the training process works. So we have seen that a neuron consists of inputs, it receives inputs, and then there is a weighted sum, which is nothing but this xi, wi, summation of that plus the bias, and this is then fed to the activation function, and that in turn gives us a output. Now during the training process, initially obviously when you feed these images, when you send maybe a square, it will identify it as a triangle, and when you maybe feed a triangle, it will identify as a square, and so on. So that error information is fed back, and initially these weights can be random, maybe all of them have 0 values, and then it will slowly keep changing. So as a part of the training process, the values of these weights w1, w2 up to wn keep changing in such a way that towards the end of the training process, it should be able to identify these images correctly. So till then the weights are adjusted, and that is known as the training process. So, and these weights are numeric values. It could be 0.5, 0.25, 0.35 and so on. It could be positive or it could be negative, and the value that is coming here is the pixel value. As we have seen, it can be anything between 0 to 1. You can scale it between 0 to 1 or 0 to 256, whichever way, 0 being black and 256 being white, and then all the other colors in between. So that is the input. So these are numerical values. This multiplication or the product wi, xi is a numerical value, and the bias is also a numerical value. We need to keep in mind that the bias is fixed for a neuron. It doesn't change with the inputs, whereas the weights are 1 per input. So that is one important point to be noted. So, but the bias also keeps changing. Initially it will again have a random value, but as a part of the training process, the weights, the values of the weights w1, w2, wn and the value of b will change, and ultimately once the training process is complete, these values are fixed for this particular neuron. w1, w2 up to wn, and plus the value of the b is also fixed for this particular neuron. And in this way there will be multiple neurons, and there may be multiple levels of neurons here, and that's the way the training process works. So this is another example of multi-layer. So there are 2 hidden layers in between, and then you have the input layer, values coming from the input layer, then it goes through multiple layers, hidden layers, and then there is an output layer. And as you can see, there are weights and biases for each of these neurons in each layer, and all of them keeps changing during the training process, and at the end of the training process all these weights have a certain value, and that is a trained model, and those values will be fixed once the training is completed. Alright, then there is something known as activation function. Neural networks consists of one of the components in neural networks is activation function, and every neuron has an activation function, and there are different types of activation functions that are used. It could be a ReLU, it could be sigmoid, and so on and so forth. And the activation function is what decides whether a neuron should be fired or not. So whether the output should be 0 or 1 is decided by the activation function, and the activation function in turn takes the input, which is the weighted sum. Remember, we talked about wi xi plus b. That weighted sum is fed as an input to the activation function, and then the output can be either a 0 or a 1. And there are different types of activation functions which are covered in an earlier video you might want to watch. Alright, so as a part of the training process, we feed the inputs, the labeled data or the training data, and then it gives an output, which is the predicted output by the network, which we indicate as y hat. And then there is a labeled data, because for supervised learning, we already know what should be the output. So that is the actual output. And in the initial process, before the training is complete, obviously there will be error. So that is measured by what is known as a cost function. So the difference between the predicted output and the actual output is the error. And the cost function can be defined in different ways. There are different types of cost functions. So in this case, it is like the average of the squares of the error. So, and then all the errors are added, which can sometimes be called as sum of squares, sum of square errors, or SSE. And that is then fed as a feedback in what is known as backward propagation or back propagation. And that helps in the network adjusting the weights and biases. And so the weights and biases get updated till this value, the error value or the cost function, is minimum. Now there is a optimization technique which is used here called gradient descent optimization, and this algorithm works in a way that the error, which is the cost function, needs to be minimized. So there's a lot of mathematics that goes behind this. For example, they find the local minima and the global minima using the differentiation and so on and so forth. But the idea is this. So as a training process, as the part of training, the whole idea is to bring down the error, which is like, let's say this is the function, the cost function. At certain levels it is very high, the cost value of the cost function, the output of the cost function is very high. So the weights have to be adjusted in such a way, and also the bias of course, that the cost function is minimized. So there is this optimization technique called gradient descent that is used, and this is known as the learning rate. Now gradient descent, you need to specify what should be the learning rate, and the learning rate should be optimal, because if you have a very high learning rate, then the optimization will not converge, because at some point it will cross over to the side. On the other hand, if you have very low learning rate, then it might take forever to convert. So you need to come up with the optimum value of the learning rate, and once that is done, using the gradient descent optimization, the error function is reduced, and that's like the end of the training process. Alright, so this is another view of gradient descent. So this is how it looks. This is your cost function, the output of the cost function, and that has to be minimized using gradient descent algorithm. And these are like the parameters, and weight could be one of them. So initially we start with certain random values, so cost will be high, and then the weights keep changing, and in such a way that the cost function needs to come down, and at some point it may reach the minimum value, and then it may increase. So that is where the gradient descent algorithm decides that, okay, it has reached a minimum value and it will kind of try to stay here. This is known as the global minima. Now sometimes these curves may not be, just for explanation purpose, this has been drawn in a nice way, but sometimes these curves can be pretty erratic. There can be some local minima here, and then there is a peak, and so on. So the whole idea of gradient descent optimization is to identify the global minima and to find the weights and the bias at that particular point. So that's what is gradient descent. And then this is another example. So you can have these multiple local minima. So as you can see, at this point when it is coming down, it may appear like this is a minimum value, but then it is not. This is actually the global minimum value, and the gradient descent algorithm will make an effort to reach this level and not get stuck at this point. So The algorithm is already there and it knows how to identify this global minimum, and that's what it does during the training process. Now, in order to implement deep learning, there are multiple platforms and languages that are available, but the most common platform nowadays is TensorFlow, and so that's the reason we have this tutorial. We have created this tutorial for TensorFlow. So we will take you through a quick demo of how to write a TensorFlow code using Python. And TensorFlow is an open source platform created by Google. So let's just take a look at the details of TensorFlow. And so this is a library, a Python library, so you can use Python or any other languages. It's also supported in other languages like Java and R and so on. But Python is the most common language that is used. So it is a library for developing deep learning applications, especially using neural networks. And it consists of primarily two parts, if you will. So one is the tensors, and then the other is the graphs or the flow. That's the way the name, that's the reason for this kind of a name called TensorFlow. So what are tensors? Tensors are like multi-dimensional arrays, if you will. That's one way of looking at it. So usually you have a one-dimensional array. So first of all, you can have what is known as a scalar, which means a number. And then you have a one-dimensional array, something like this, which means this is like a set of numbers. So that is a one-dimensional array. Then you can have a two-dimensional array, which is like a matrix. And beyond that, sometimes it gets difficult. So this is a three-dimensional array, but TensorFlow can handle many more dimensions. So it can have multi-dimensional arrays. That is the strength of TensorFlow, and which makes computation, deep learning computation, much faster. And that's the reason why TensorFlow is used for developing deep learning applications. So TensorFlow is a deep learning tool, and this is the way it works. So the data basically flows in the form of tensors, and the way the programming works as well is that you first create a graph of how to execute it, and then you actually execute that particular graph in the form of what is known as a session. We will see this in the TensorFlow code as we move forward. So all the data is managed or manipulated in tensors, and then the processing happens using these graphs. There are certain terms called, like for example, ranks of a tensor. The rank of a tensor is like a dimensionality in a way. So for example, if it is scalar, so there is just a number, just one number, the rank is supposed to be 0, and then it can be a one-dimensional vector, in which case the rank is supposed to be 1, and then you can have a two-dimensional vector, typically like a matrix. Then in that case we say the rank is 2, and then if it is a three-dimensional array, then rank is 3, and so on. So it can have more than 3 as well. So it is possible that you can store multi-dimensional arrays in the form of tensors. So what are some of the properties of TensorFlow? I think today it is one of the most popular platform. TensorFlow is the most popular deep learning platform or library. It is open source. It's developed by Google, developed and maintained by Google, but it is open source. One of the most important things about TensorFlow is that it can run on CPUs as well as GPUs. GPU is a graphical processing unit, just like CPU is central processing unit. Now, in earlier days, GPU was used primarily for graphics, and that's how the name has come. And one of the reasons is that it cannot perform generic activities very efficiently like CPU, but it can perform iterative actions or computations extremely fast and much faster than a CPU. So they are really good for computational activities, and in deep learning there is a lot of iterative computation that happens, so in the form of matrix multiplication and so on. So GPUs are very well suited for this kind of computation, and TensorFlow supports both GPU as well as CPU. And there's a certain way of writing code in TensorFlow. We will see as we go into the code. And of course, TensorFlow can be used for traditional machine learning as well, but then that would be an overkill. But just for understanding, it may be a good idea to start writing code for a normal machine learning use case, so that you get a hang of how TensorFlow code works, and then you can move into neural networks. So that is just a suggestion, but if you're already familiar with how TensorFlow works, then probably, yeah, you can go straight into the neural networks part. So in this tutorial, we will take the use case of recognizing handwritten digits. This is like a hello world of deep learning, and this is a nice little MNIST database is a nice little database that has images of handwritten digits nicely formatted, because very often in deep learning and neural networks we end up spending a lot of time in preparing the data for training, and with MNIST database we can avoid that. You already have the data in the right format which can be directly used for training, and MNIST also offers a bunch of built-in utility functions that we can straight away use and call those functions without worrying about writing our own functions. And that's one of the reasons why MNIST database is very popular for training purposes. Initially, when people want to learn about deep learning and TensorFlow, this is the database that is used. And it has a collection of 70,000 handwritten digits, and a large part of them are for training. Then you have test, just like in any machine learning process, and then you have validation, and all of them are labeled. So you have the images and their label, and these images, they look somewhat like this. So they are handwritten images collected from a lot of individuals. People have, these are samples written by human beings. They have handwritten these numbers going from 0 to 9. So people have written these numbers, and then the images of those have been taken and formatted in such a way that it is very easy to handle. So that is MNIST database, and the way we are going to implement this in our TensorFlow is we will feed this data, especially the training data, along with the label information, and the data is basically, these images are stored in the form of the pixel information, as we have seen in one of the previous slides. All the images are nothing but, these are pixels. So an image is nothing but an arrangement of pixels, and the value of the pixel, either it is lit up or it is not, or in somewhere in between. That's how the images are stored, and that is how they are fed into the neural network and for training. Once the network is trained, when you provide a new image, it will be able to identify within a certain error, of course. And for this, we will use one of the simpler neural network configurations called softmax. And for simplicity, what we will do is we will flatten these pixels. So instead of taking them in a two-dimensional arrangement, we just flatten them out. So for example, it starts from here. It is a 28 by 28, so there are 784 pixels. So pixel number 1 starts here, it goes all the way up to 28, then 29 starts here and goes up to 56 and so on. And the pixel number 784 is here. So we take all these pixels, flatten them out, and feed them like one single line into our neural network. And this is what is known as a softmax layer. What it does is, once it is trained, it will be able to identify what digit this is. So there are, in this output layer, there are 10 neurons, each signifying a digit. And at any given point of time, when you feed an image, only one of these 10 neurons gets activated. So for example, if this is trained properly, and if you feed a number 9 like this, then this particular neuron gets activated. So you get an output from this neuron. Let me just use a pen or a laser to show you here. Okay, so you're feeding a number 9. Let's say this has been trained, and now if you're feeding a number 9, this will get activated. Now let's say you feed 1 to the trained network, then this neuron will get activated. If you feed 2, this neuron will get activated, and so on. I hope you get the idea. So this is one type of a neural network or an activation function known as softmax layer. So that's what we will be using here. This is one of the simpler ones for quick and easy understanding. So this is how the code would look. We will go into our lab environment in the cloud, and we will show you there directly. But very quickly, this is how the code looks. And let me run you through briefly here, and then we will go into the Jupyter Notebook where the actual code is, and we will run that as well. So as a first step, first of all, we are using Python here, and that's why the syntax of the language is Python. And the first step is to import the TensorFlow library. So, and we do this by using this line of code saying import TensorFlow as TF. TF is just for convenience, so you can give any name. And once you do this, TensorFlow is available as an object in the name of TF, and then you can run its methods and accesses its attributes and so on and so forth. And MNIST database is actually an integral part of TensorFlow, and that's again another reason why we, as a first step, we always use this example, MNIST database example. So you just simply import MNIST database as well using this line of code, and you slightly modify this so that the labels are in this format, what is known as one hot true, which means that the label information is stored like an array. And let me just use a pen to show what exactly it is. So when you do this one hot true, what happens is each label is stored in the form of an array of 10 digits, and let's say the number is 8. Okay. So in this case, all the remaining values, there will be a bunch of zeros. So this is like array at position 0. This is at position 1, position 2, and so on and so forth. Let's say this is position 7. Then this is position 8. That will be 1 because our input is 8. And again, position 9 will be 0. Okay. So one hot encoding, this one hot encoding true will kind of load the data in such a way that the labels are in such a way that only one of the digits has a value of 1, and that indicates. So based on which digit is 1, we know what is the label. So in this case, the 8th position is 1, therefore we know this sample data, the value is 8. Similarly, if you have a 2 here, let's say, then the labeled information will be somewhat like this. So you have your labels. So you have this as 0, the 0th position. The first position is also 0. The second position is 1 because this indicates number 2. And then you have third as 0 and so on. Okay. So that is the significance of this one hot true. All right. And then we can check how the data is looking by displaying the data. And as I mentioned earlier, this is pretty much in the form of digital form, like numbers. So all these are like pixel values, so you will not really see an image in this format, but there is a way to visualize that image. I will show you in a bit. And this tells you how many images are there in each set. So the training, there are 55,000 images in training, and in the test set there are 10,000, and then validation there are 5,000. So altogether there are 70,000 images. All right, so let's move on, and we can view the actual image by using the matplotlib library, and this is how you can view. This is the code for viewing the images, and you can view them in color or you can view them in grayscale. So the CMap is what tells in what way we want to view it, and what are the maximum values and the minimum values of the pixel values. So these are the max and minimum values of the pixel values. So maximum is 1 because this is a scaled value. So 1 means it is white, and 0 means it is black, and in between it can be anywhere in between black and white. And the way to train the model, there is a certain way in which you write your TensorFlow code, and the first step is to create some placeholders, and then you create a model. In this case, we will use the softmax model, one of the simplest ones, and placeholders are primarily to get the data from outside into the neural network. So this is a very common mechanism that is used. And then of course you will have variables, which are remember these are your weights and biases. So in our case, there are 10 neurons, and each neuron actually has 784 because each neuron takes all the inputs. If we go back to our slide here, actually every neuron takes all the 784 inputs. right? This is the first neuron. It receives all the 784. This is the second neuron. This also receives all the 708. So each of these inputs needs to be multiplied with a weight, and that's what we are talking about here. So this is a matrix of 784 values for each of the neurons, and so it is like a 10 by 784 matrix because there are 10 neurons. And similarly, there are biases. Now remember, I mentioned bias is only one per neuron, so it is not one per input, unlike the weights. So therefore there are only 10 biases because there are only 10 neurons in this case. So that is what we are creating a variable for biases. So this is something little new in TensorFlow. You will see, unlike our regular programming languages where everything is a variable, here the variables can be of three different types. You have placeholders, which are primarily used for feeding data. You have variables, which can change during the course of computation. And then a third type, which is not shown here, are constants. So these are like fixed numbers. All right. So in a regular programming language, you may have everything as variables or at the most variables and constants. But in TensorFlow, you have three different types: placeholders, variables, and constants. And then you create what is known as a graph. So TensorFlow programming consists of graphs and tensors, as I mentioned earlier. So this can be considered ultimately as a tensor. And then the graph tells how to execute the whole implementation, so that the execution is stored in the form of a graph. And in this case, what we are doing is we are doing a multiplication. TF, you remember this TF was created as a TensorFlow object here. One more level, one more. So TF is available here. Now TensorFlow has what is known as a matrix multiplication or matmul function. So that is what is being used here in this case. So we are using the matrix multiplication of TensorFlow so that you multiply your input values x with w, right? This is what we were doing, xw plus b. You're just adding b, and this is in very similar to one of the earlier slides where we saw sigma xi wi. So that's what we are doing here. Matrix multiplication is multiplying all the input values with the corresponding weights and then adding the bias. So that is the graph we created. And then we need to define what is our loss function and what is our optimizer. So in this case, we again use the TensorFlow's APIs. So tf.nn softmax cross entropy with logits is the API that we will use, and reduce mean is what is like the mechanism whereby which says that you reduce the error. And optimizer for doing reduction of the error, what optimizer are we using? So we are using gradient descent optimizer. We discussed about this in a couple of slides earlier. And for that, you need to specify the learning rate. You remember we saw that there was a slide somewhat like this, and then you define what should be the learning rate, how fast you need to come down. That is the learning rate. And this again needs to be tested and tried, and to find out the optimum level of this learning rate. It shouldn't be very high, in which case it will not converge, or shouldn't be very low because it will, in that case, it will take very long. So you define the optimizer and then you call the method minimize for that optimizer, and that will kickstart the training process. And so far we've been creating the graph, and in order to actually execute that graph, we create what is known as a session, and then we run that session. And once the training is completed, we specify how many times, how many iterations we want it to run. So for example, in this case, we are saying 1000 steps. So that is a exit strategy in a way. So you specify the exit condition. So a training will run for 1000 iterations. And once that is done, we can then evaluate the model using some of the techniques shown here. So let us get into the code quickly and see how it works. So this is our cloud environment. Now you can install TensorFlow on your local machine as well. I'm showing this demo on our existing cloud, but you can also install TensorFlow on your local machine, and there is a separate video on how to set up your TensorFlow environment. You can watch that if you want to install your local environment, or you can go for other any cloud service, like for example, Google Cloud, Amazon, or Cloud Labs, any of these you can use and run and try the code. Okay, so it has got started. We will log in. Alright, so this is our deep learning tutorial code, and this is our TensorFlow environment. And so let's get started. We have seen a little bit of a code walkthrough in the slides as well. Now you will see the actual code in action. So the first thing we need to do is import TensorFlow, and then we will import the data, and we need to adjust the data in such a way that the one hot encoding is set to true, one hot encoding, right? As I explained earlier. So in this case, the label values will be shown appropriately. And if we just check what is the type of the data, so you can see that this is a data sets, Python data sets. And if we check the number of images, the way it looks, this is how it looks. It is an array of type float 32. Similarly, the number, if you want to see what is the number of training images, there are 55,000, then there are test images 10,000, and then validation images 5,000. Now let's take a quick look at the data itself, visualization. So we will use matplotlib for this. And if we take a look at the shape, now shape gives us like the dimension of the tensors or the arrays, if you will. So in this case, the training data set, if we see the size of the training data set using the method shape, it says there are 55,000 and 55,000 by 784. So remember, the 784 is nothing but the 28 by 28, 28 into 28. So that is equal to 784. So that's what it is showing. Now we can take just one image and just see what is the first image and see what is the shape. So again, size, obviously it is only 784. Similarly, you can look at the image itself, the data of the first image itself. So this is how it shows. So large part of it will probably be zeros, because as you can imagine, in the image only certain areas are written, rest is blank. So that's why you will mostly see zeros, either it is black or white. But then there are these values are, so the values are actually, they are scaled, so their values are between 0 and 1. Okay, so this is what you're seeing. So certain locations there are some values, and then other locations there are zeros. So that is how the data is stored and loaded. If we want to actually see what is the value of the handwritten image, if you want to view it, this is how you view it. So you create, like, do this reshape, and matplotlib has this feature to show you these images. So we will actually use the function called imshow, and then if you pass this parameters appropriately, you will be able to see the different images. Now I can change the values in this position, so which image we are looking at, right? So we can say, if I want to see what is there in maybe 5,000, right? So 5,000 has 3. Similarly, you can just say 5. What is in 5? 5 has 8. What is in 50? Again 8. So basically, by the way, if you're wondering how I'm executing this code, Shift Enter, in case you're not familiar with Jupyter Notebooks, Shift Enter is how you execute each cell, individual cell. And if you want to execute the entire program, you can go here and say run all. So that is how this code gets executed. And here again, we can check what is the maximum value and what is the minimum value of these pixel values. As I mentioned, it is scaled, so therefore it is between, the values lie between 1 and 0. Now this is where we create our model. The first thing is to create the required placeholders and variables, and that's what we are doing here, as we have seen in the slides. So we create one placeholder and we create 2 variables, which is for the weights and biases. These 2 variables are actually matrices. So each variable has 784 by 10 actual values. Okay, so one for this 10 is for each neuron. There are 10 neurons, and 784 is for the pixel values inputs that are given, which is 28 into 28. And the biases, as I mentioned, one for each neuron, so there will be 10 biases. They are stored in a variable by the name B. And this is the graph, which is basically the multiplication of these matrix multiplication of X into W, and then the bias is added for each of the neurons. And the whole idea is to minimize the error. So let me just execute. I think this code is executed. Then we define what is the Y value is basically the label value. So this is another placeholder. We had X as one placeholder and Y underscore true as a second placeholder. And this will have values in the form of 10 digit arrays. And since we said one hot encoded, the position which has a 1 value indicates what is the label for that particular number. All right. Then we have cross entropy, which is nothing but the loss function. And we have the optimizer. We have chosen gradient descent as our optimizer. Then the training process itself. So the training process is nothing but to minimize the cross entropy, which is again nothing but the loss function. So we define all of this in the form of a graph. So up to here, remember what we have done is we have not exactly executed any TensorFlow code till now. We are just preparing the graph, the execution plan. That's how the TensorFlow code works. So the whole structure and format of this code will be completely different from how we normally do programming. So even with people with programming experience may find this a little difficult to understand it, and it needs quite a bit of practice. So you may want to view this video also maybe a couple of times to understand this flow, because the way TensorFlow programming is done is slightly different from the normal programming. Some of you who, let's say, have done maybe Spark programming to some extent will be able to easily understand this. But even in Spark, the programming, the code itself is pretty straightforward. Behind the scenes, the execution happens slightly differently. But in TensorFlow, even the code has to be written in a completely different way. So the code doesn't get executed in the same way as you have written. So that's something you need to understand, and a little bit of practice is needed for this. So far what we have done up to here is creating the variables and feeding the variables, and or rather not feeding but setting up the variables and the graph. That's all. Defining maybe the what kind of a network you want to use. For example, we want to use softmax and so on. So you have created the variables, how to load the data, loaded the data, viewed the data, and prepared everything, but you have not yet executed anything in TensorFlow. Now the next step is the execution in TensorFlow. So the first step for doing any execution in TensorFlow is to initialize the variables. So anytime you have any variables defined in your code, you have to run this piece of code always. So you need to basically create what is known as a node for initializing. So this is a node. You still are not yet executing anything here. You just created a node for the initialization. So let us go ahead and create that. And here onwards is where you will actually execute your code in TensorFlow. And in order to execute the code, what you will need is a session, TensorFlow session. So tf.session will give you a session, and there are a couple of different ways in which you can do this, but one of the most common methods of doing this is with what is known as a with loop. So you have a with tf.session as ses and with a colon here, and this is like a block, starting of the block, and these indentations tell how far this block goes, and this session is valid till this block gets executed. So that is the purpose of creating this with block. This is known as a with block. So with tf.session as ses, you say ses.run init. Now ses.run will execute a node that is specified here. So for example, here we are saying ses.run. Ses is basically an instance of the session, right? So here we are saying tf.session. So an instance of the session gets created and we are calling that ses. And then we run a node within that, one of the nodes in the graph. So one of the nodes here is init. So we say run that particular node, and that is when the initialization of the variables happens. Now what this does is, if you have any variables in your code, in our case we have w is a variable and b is a variable. So any variables that we created, you have to run this code, you have to run the initialization of these variables, otherwise you will get an error. Okay, so that's what this is doing. Then we, within this with block, we specify a for loop, and we are saying we want the system to iterate for 1000 steps and perform the training. That's what this for loop does. Run training for 1000 iterations. And what it is doing basically is it is fetching the data or these images. Remember, there are about 50,000 images, but it cannot get all the images in one shot because it will take up a lot of memory and performance issues will be there. So this is a very common way of performing deep learning training. You always do in batches. So we have maybe 50,000 images, but you always do it in batches of 100 or maybe 500 depending on the size of your system and so on and so forth. So in this case, we are saying, okay, get me 100 images at a time and get me only the training images. Remember, we use only the training data for training purpose, and then we use test data for test purpose. You must be familiar with machine learning, so you must be aware of this. But in case you are not, in machine learning also, this is not specific to deep learning, but in machine learning in general, you have what is known as training data set and test data set. Your available data, typically you will be splitting into two parts and using the training data set for training purpose. And then to see how well the model has been trained, you use the test data set to check or test the validity or the accuracy of the model. So that's what we are doing here. And you observe here that we are actually calling an mnist function here. So we are saying mnist train.next batch. Right? So this is the advantage of using MNIST database, because they have provided some very nice helper functions which are readily available. Otherwise, this activity itself, we would have had to write a piece of code to fetch this data in batches. That itself is a lengthy exercise. So we can avoid all that if we are using MNIST database, and that's why we use this for the initial learning phase. Okay, so when we say fetch, what it will do is it will fetch the images into X and the labels into Y, and then you use this batch of 100 images and you run the training. So ses.run, basically what we are doing here is we are running the training mechanism, which is nothing but it passes this through the neural network, passes the images through the neural network, finds out what is the output, and if the output, obviously initially it will be wrong, so all that feedback is given back to the neural network, and thereby all the W's and B's get updated till it reaches 1000 iterations. In this case, the exit criteria is 1000, but you can also specify probably accuracy rate or something like that for as an exit criteria. So here it just says that, okay, this particular image was wrongly predicted, so you need to update your weights and biases. That's the feedback given to each neuron, and that is run for 1000 iterations. And typically by the end of this 1000 iterations, the model would have learned to recognize these handwritten images. Obviously it will not be 100% accurate. Okay, so once that is done, so this happens for 1000 iterations. Once that is done, you then test the accuracy of these models by using the test data set. Right? So this is what we are trying to do here. The code may appear a little complicated because if you're seeing this for the first time, you need to understand the various methods of TensorFlow and so on, but it is basically comparing the output with what is actually there. That's all it is doing. So you have your test data, and you're trying to find out what is the actual value and what is the predicted value, and seeing whether they are equal or not, tf.equal, right? And how many of them are correct, and so on and so forth. And based on that, the accuracy is calculated as well. So this is the accuracy, and that is what we are trying to see, how accurate the model is in predicting these numbers or these digits. Okay, so let us run this. This entire thing is in one cell, so we will have to just run it in one shot. It may take a little while. Let us see. And not bad. So it has finished the 1000 iterations, and what we see here as an output is the accuracy. So we see that the accuracy of this model is around 91%. Okay, now which is pretty good for such a short exercise. Within such a short time we got 90% accuracy. However, in real life this is probably not sufficient, so there are other ways to increase the accuracy. We will see probably in some of the later tutorials how to improve this accuracy, how to change maybe the hyperparameters like number of neurons or number of layers and so on and so forth, and so that this accuracy can be increased beyond 90%.
Let's look at the different types of artificial neural networks. And this is like the biggest area growing, is how these all come together. Let's see the different types of neural network. And again, we're comparing this to human learning. So here's a human brain. I feel sorry for that poor guy. So we have a feed-forward neural network. Simplest form of they call it an ANN, a neural network. Data travels only in one direction, input to output. This is what we just looked at. So as the data comes in, all the weights are added, it goes to the hidden layer, all the weights are added, it goes to the next hidden layer, all the weights are added, and it goes to the output. The only time you use the reverse propagation is to train it. So when you actually use it, it's very fast. When you're training it, it takes a while because it has to iterate through all your training data. And you start getting into big data because you can train these with a huge amount of data. The more data you put in, the better trained they get. The applications, vision and speech recognition, actually they're pretty much everything we talked about. Almost all of them use this form of neural network at some level. Radio basis function neural network. This model classifies the data point based on its distance from a center point. What that means is that you might not have training data, so you want to group things together and you create central points, and it looks for all the things, some of these things are just like the other. If you've ever watched the Sesame Street as a kid, that dates me. So it brings things together. And this is a great way, if you don't have the right training model, you can start finding things that are connected you might not have noticed before. Applications, power restoration systems. They try to figure out what's connected, and then based on that, they can fix the problem if you have a huge power system. Cohonen self-organizing neural network. Vectors of random dimensions are input to discrete map comprised of neurons. So they basically find a way to draw, and they say dimensions, or vectors, or planes, because they actually chop the data in 1 dimension, 2 dimension, 3 dimension, 4, 5, 6. They keep adding dimensions and finding ways to separate the data and connect different data pieces together. Applications used to recognize patterns in data, like in medical analysis. The hidden layer saves its output to be used for future prediction. Recurrent neural networks. So the hidden layers remember its output from last time, and that becomes part of its new input. You might use that especially in robotics or flying a drone. You want to know what your last change was and how fast it was going to help predict what your next change you need to make is to get to where the drone wants to go. Applications, text-to-speech, conversation model. So, I talked about drones, but, just identifying on Lex or Google Assistant or any of these, they're starting to add in, I'd like to play a song on my Pandora and I'd like it to be at volume 90%. So you now can add different things in there and it connects them together. The input features are taken in batches like a filter, This allows a network to remember an image in parts. Convolution neural network. Today's world in photo identification and taking apart photos and trying to, have you ever seen that on Google where you have 5 people together? This is the kind of thing separates all those people so that it can do a face recognition on each person. Applications used in signal and image processing. In this case, I use facial images or Google picture images as one of the options. Modular neural network. It has a collection of different neural networks working together to get the output. So, wow, we just went through all these different types of neural networks, and the final one is to put multiple neural networks together. And I mentioned that a little bit when we separated people in a larger photo, individuals in the photo, and then do the facial recognition on each person. So one network is used to separate them, and the next network is then used to figure out who they are and do the facial recognition. Applications still undergoing research. This is the cutting edge. You hear the term pipeline, and there's actual in Python code and in almost all the different neural network setups out there, they now have a pipeline feature usually. And it just means you take the data from one neural network and maybe another neural network, or you put it into the next neural network, and then you take 3 or 4 other neural networks and feed them into another one. So how we connect the neural networks is really just cutting edge, and it's so experimental. I mean, it's almost creative in its nature. There's not really a science to it because each specific domain has different things it's looking at. So if you're in the banking domain, it's going to be different than the medical domain, than the automatic car domain. And suddenly figuring out how those all fit together is just a lot of fun and really cool. So we have our types of artificial neural network. We have our feed-forward neural network. We have our radial basis function neural network. We have our Cohennon self-organizing neural network, recurrent neural network, convolution neural network, and modular neural network where it brings them all together. And the colors on the brain do not match what your brain actually does, but they do bring it out that most of these were developed by understanding how humans learn. And as we understand more and more of how humans learn, we can build something in the computer industry to mimic that, to reflect that. And that's how these were developed. So, exciting part, use case, problem statement. So this is where we jump in. This is my favorite part. Let's use the system to identify between a cat and a dog. If you remember correctly, I said we're going to do some Python code, and you can see over here, my hair is kind of sticking up over the computer, a cup of coffee on one side, and then a little bit of old school, a pencil and a pen on the other side. Yeah, most people now take notes. I love the stickies on the computer. That's great. That is my computer. I have sticky notes on my computer in different colors. So not too far from today's programmer. So the problem is we want to classify photos of cats and dogs using a neural network. And you can see over here we have quite a variety of dogs in the pictures and cats. And, just sorting out it is a cat is pretty amazing. And why would anybody want to even know the difference between a cat and a dog? Okay, why? Well, I have a cat door. It'd be kind of fun that instead of having like a little collar with a magnet on it, which is what my cat has, the door would be able to see, oh, that's the cat. That's our cat coming in. Oh, that's the dog. We have a dog too. That's the dog I want to let in. Maybe I don't want to let this other animal in because it's a raccoon. So you can see where you could take this one step further and actually apply this. You could actually start a little startup company idea, a self-identifying door. So this use case will be implemented on Python. I am actually in Python 3.6. It's always nice to tell people the version of Python because that does affect sometimes which modules you load and everything. And we're going to start by importing the required packages. I told you we're going to do this in Keras. So we're going to import from Keras models, a sequential from the Keras layers, conversion 2D or CONV 2D, max pooling 2D, flatten, and dense. And we'll talk about what each one of these do in just a second. But before we do that, let's talk a little bit about the environment we're going to work in. And in fact, let me go ahead and open the website, Keras's website, so we can learn a little bit more about Keras. So here we are on the Keras website, and it's keras.io. That's the official website for Keras. And the first thing you'll notice is that Keras runs on top of either TensorFlow, CNTK, and I think it's pronounced Thano or Theano. What's important on here is that TensorFlow, and the same is true for all these, but TensorFlow is probably one of the most widely used currently packages out there with the Keras. And of course, tomorrow this is all going to change. It's all going to disappear and they'll have something new out there. So make sure when you're learning this code that you understand what's going on and also know the code. I mean, when you look at the code, it's not as complicated once you understand what's going on. The code itself is pretty straightforward. And the reason we like Keras, and the reason that people are jumping on it right now and it's such a big deal, is if we come down here, let me just scroll down a little bit, they talk about user friendliness, modularity, easy extensibility, work with Python. Python's a big one because a lot of people in data science now use Python, although you can actually access Keras other ways. If we continue down here is layers. And this is where it gets really cool. When we're working with Keras, you just add layers on. Remember those hidden layers we were talking about? And we talked about the ReLU activation. You can see right here. Let me just up that a little bit in size. There we go. That's big. I can add in an ReLU layer, and then I can add in a softmax layer in the next instance. We didn't talk about softmax. So you can do each layer separate. Now, if I'm working in some of the other kits I use, I take that and I have one setup, and then I feed the output into the next one. This one I can just add hidden layer after hidden layer with the different information in it, which makes it very powerful and very fast to spin up and try different setups and see how they work with the data you're working on. And we'll dig a little bit deeper in here. And a lot of this is very much the same, so when we get to that part, I'll point that out to you also. Now, just a quick side note, I'm using Anaconda with Python in it, and I went ahead and created my own package, and I called it the Keras Python 3.6 because I'm in Python 3.6. Anaconda is cool that way. You can create different environments real easily. If you're doing a lot of different experimenting with these different packages, you probably want to create your own environment in there. And the first thing is you can see right here, there's a lot of dependencies. A lot of these you should recognize by now if you've done any of these videos. If not, kudos for you for jumping in today. Pip install numpy, scipy, the scikit-learn, pillow, and h5py are both needed for the TensorFlow and then putting the Keras on there. And then you'll see here, and pip is just a standard installer that you use with Python. And you'll see here that we did pip install TensorFlow, since we're going to do Keras on top of TensorFlow. And then pip install, and I went ahead and used the GitHub. So git plus git, and you'll see here github.com. This is one of their releases, one of the most current release on there that goes on top of TensorFlow. And you can look up these instructions pretty much anywhere. This is for doing it on Anaconda. Certainly you'd want to install these if you're doing it in an Ubuntu server setup. You'd want to get, I don't think you need the h5py on Ubuntu, but you do need the rest in there because there are dependencies in there, and it's pretty straightforward. And that's actually in some of the instructions they have on their website. So you don't have to necessarily go through this. Just remember their website on there. And then when I'm under my Anaconda Navigator, which I like, you'll see where I have environments, and on the bottom I created a new environment and I called it Keras Python 36, just to separate everything. You can say I have Python 30.5 and Python 3.6. I used to have a bunch of other ones, but I kind of cleaned house recently. And of course, once I go in here, I can launch my Jupyter Notebook, making sure I'm using the right environment that I just set up. This, of course, opens up my, in this case I'm using Google Chrome, and in here I could go and just create a new document in here. And this is all in your browser when you use the Anaconda. Do you have to use Anaconda in Jupyter Notebook? No. You can use any kind of Python editor, whatever setup you're comfortable with and whatever you're doing in there. So let's go ahead and go in here and paste the code in. And we're importing a number of different settings in here. We have import sequential. That's under the models because that's the model we're going to use as far as our neural network. And then we have layers, and we have conversion 2D, max pooling 2D, flatten, dense. And you can actually just kind of guess at what these do. We're working in a 2D photograph. And if you remember correctly, I talked about how the actual input layer is a single array. It's not in 2 dimensions, it's 1 dimension. All these do is these are tools to help flatten the image. So it takes a 2-dimensional image and then it creates its own proper setup. You don't have to worry about any of that. You don't have to do anything special with the photograph. You let the Keras do it. And we're going to run this, and you'll see right here they have some stuff that is going to be deprecated created and changed, because that's what it does. Everything's being changed as we go. You don't have to worry about that too much. If you have warnings, if you run it a second time, the warning will disappear. And this has just imported these packages for us to use. And Jupyter's nice about this, that you can do each thing step by step. And I'll go ahead and also zoom in there. A little Control Plus. That's one of the nice things about being in a browser environment. So here we are back. Another sip of coffee. If you're familiar with my other videos, you notice I'm always sipping coffee. I always have in my case, latte next to me, an espresso. So the next step is to go ahead and initialize, we're going to call it the CNN, or classifier neural network. And the reason we call it a classifier is because it's going to classify it between two things. It's going to be cat or dog. So when you're doing classification, you're picking specific objects. You're specific, it's a true or false, yes, no, it is something or it's not. So first thing, we're going to create our classifier, and it's going to equal sequential. So their sequential setup is the classifier. That's the actual model we're using. That's the neural network. So we call it a classifier. And the next step is to add in our convolution. And let me just do let me shrink that down in size so you can see the whole line. And let's talk a little bit about what's going on here. I have my classifier and I add something. What am I adding? Well, I'm adding my first layer. This first layer we're adding in is probably the one that takes the most work to make sure you have it set correct. And the reason I say that is this is your actual input. And we're going to jump here to the part that says input shape equals 64 by 64 by 3. What does that mean? Well, that means that our picture's coming in, and there's these pictures. Remember we had like the picture of the car was 128 by 128 pixels? Well, this one is 64 by 64 pixels. And each pixel has 3 values. That's where these numbers come from. And it is so important that this matches. I mentioned a little bit that if you have like a larger picture, you have to reformat it to fit this shape. If it comes in as something larger, there's no input nodes. There's no input neural network there that will handle that extra space. So you have to reshape your data to fit in here. Now, the first layer is the most important, because after that, Keras knows what your shape is coming in here, and it knows what's coming out. And so that really sets the stage. Most important thing is that input shape matches your data coming in. And you'll get a lot of errors if it doesn't. You'll go through there and picture number 55 doesn't match it correctly. And guess what it does? It usually gives you an error. And then the activation, if you remember, we talked about the different activations on here. We're using the ReLU model. Like I said, that is the most commonly used now because, one, it's fast. It doesn't have the added calculations in it. It just says, here's the value coming out based on the weights and the value going in, and from there, you know, it's if it's over 1, then it's good, or over 0, it's good. If it's under 0, then it's considered not active. And then we have this conversion 2D. What the heck is conversion 2D? I'm not going to go into too much detail in this because this has a couple of things it's doing in here. A little bit more in-depth than we're ready to cover in this tutorial. But this is used to convert from the photo, because we have 64 by 64 by 3, and we're just converting it to two-dimensional kind of setup. So it's very aware that this is a photograph and that different pieces are next to each other. And then we're going to add in a second convolutional layer. That's what the CONV stands for, 2D. So these are hidden layers. So we have our input layer and our 2 hidden layers, and they are two-dimensional because we're dealing with a two-dimensional photograph. And you'll see down here that on the last one we add a max pooling 2D, and we put a pool size equals 2, 2. And so what this is that as you get to the end of these layers, one of the things you always want to think of is what they call mapping and then reducing. Wonderful terminology from the big data. We're mapping this data through all these layers, and now we want to reduce it to only 2 sets. In this case, it's already in 2 sets because it's a 2D photograph. But we had, 2 dimensions we actually have 64 by 64 by 3. So now we're just getting it down to a 2 by 2, just the two-dimensional instead of having the third dimension of colors. And we'll go ahead and run these. We're not really seeing anything on our run script because we're just setting up. This is all set up. And this is where you start playing, because maybe you'll add a different layer in here to do something else to see how it works and see what your output is. That's what makes Keras so nice, is I can, with just a couple flips of code, put in a whole new layer that does a whole new processing and see whether that improves my run or makes it worse. And finally, we're going to do the final setup, which is to flatten. Classifier, add a flatten setup, and then we're going to also add a layer, a dense layer, and then we're going to add in another dense layer, and then we're going to build it. We're going to compile this whole thing together. So let's flip over and see what that looks like. And we've even numbered them for you, so we're going to do the flattening. And flatten is exactly what it sounds like. We've been working in a two-dimensional array of picture, which actually is in 3 dimensions because of the pixels. The pixels have a whole other dimension to it of 3 different values. And we've kind of resized those down to 2 by 2, but now we're just going to flatten it. I don't want to have multiple dimensions being worked on by Tensor and by Keras. I want just a single array, so it's flattened out. And then step 4, full connection. So we add in our final 2 layers, and you could actually do all kinds of things with this. You could actually leave out this some of these layers and play with them. You do need to flatten it. That's very important. Then we want to use the dense. Again, we're taking this and we're taking whatever came into it. So once we take all those the 2 dimensions or 3 dimensions as they are, and we flatten it to 1 dimension, we want to take that and we're going to pull it into units of 128. They got that. You can say, where did they get 128 from? You could actually play with that number and get all kinds of weird results. But in this case, we took the 64 plus 64 is 128. You could probably even do this with 64 or 32. Usually you want to keep it in the same multiple of whatever the data shape you're already using is in. And we're using the activation, the RELU, just like we did before. And then we finally filter all that into a single output. And it has how many units? 1. Why? Because we want to know whether true or false. It's either a dog or a cat. You could say 1 is dog, 0 is cat. Or maybe you're a cat lover and it's 1 is cat and 0 is dog. And if you love both dogs and cats, you're going to have to choose. And then we use the sigmoid activation. If you remember from before, we had the RELU and there's also the sigmoid. The sigmoid just makes it clear it's yes or no. We don't want any kind of in-between number coming out. And we'll go ahead and run this, and you'll see it's still all in setup. And then finally we want to go ahead and compile. And let's put the compiling our classifier neural network. And we're going to use the optimizer Atom. And I hinted at this just a little bit before. Where does Atom come in? Where does an optimizer come in? Well, the optimizer is the reverse propagation. When we're training it, it goes all the way through and says error, and then how does it readjust those weights? There are a number of them. Atom is the most commonly used, and it works best on large data. Most people stick with the Atom because when they're testing on smaller data, see if their model is going to go through and get all their errors out before they run it on larger data sets. They're going to run it on Atom anyway, so they just leave it on Atom, most commonly used. But there are some other ones out there. You should be aware of that you might try them if you're stuck in a bind, or you might explore that in the future. But usually Atom is just fine on there. And then you have 2 more settings. You have loss and metrics. We're not going to dig too much into loss or metrics. These are things you really have to explore Keras because there are so many choices. This is how it computes the error. There's so many different ways on your back propagation and your training. So we're using the Atom model, but you can compute the error by standard deviation squared. They use binary cross entropy. I'd have to look that up to even know what that is. There's so many of these. A lot of times you just start with the ones that look correct, that are most commonly used, and then you have to go read the Keras site and actually see what these different losses and metrics and what different options they have. So we're not going to get too much into them other than to reference you over to the Keras website to explore them deeper. But we are going to go ahead and run them, and now we've set up our classifier. So we have an object classifier, and if you go back up here you'll see that we've added in step 1, we added in our layer for the input. We added a layer that comes in there and uses the RELU for activation, and then it pulls the data. So this is, even though these are 2 layers, the actual neural network layer is up here, and then it uses this to pull the data into a 2 by 2. So into a 2-dimensional array from a 3-dimensional array with the colors. Then we flatten it. So there's our adder flatten. And then we add another dense, what they call dense layer. This dense layer goes in there and it downsizes it to 128. It reduces it. So you can look at this as we're mapping all this data down the 2-dimensional setup, and then we flatten it. So we map it to a flattened map, and then we take it and reduce it down to 128. And we use the RELU again. And then finally we reduce that down to just a single output, and we use the sigmoid to do that, to figure out whether it's yes, no, true, false, in this case cat or dog. And then finally, once we put all these layers together, we compile them. That's what we've done here. And we've compiled them as far as how it trains to use these settings for the training, back propagation. So if you remember, we talked about training our setup. And when we go into this, you'll see that we have two data sets. We have one called the training set and the testing set. And that's very standard in any data processing, is you need to have, that's pretty common in any data processing, is you need to have a certain amount of data to train it, and then you got to know whether it works or not. Is it any good? And that's why you have a separate set of data for testing it, where you already know the answer, but you don't want to use that as part of the training set. So in here we jump into part 2, fitting the classifier neural network to the images. And then from Keras, and let me just zoom in there. I always love that about working with Jupyter Notebook, so you can really see. We're going to come in here, we do the cross pre-processing an image, and we import image data generator. It's so nice of Keras. It's such a high-end product right now going out, and since images are so common, they already have all this stuff to help us process the data, which is great. And so we come in here, we do train data gen, and we're going to create our object for helping us train it, for reshaping the data so that it's going to work with our setup. And we use an image data generator, and we're going to rescale it. And you'll see here we have 1 point, which tells us it's a float value on the rescale over 255. Where does 255 come from? Well, that's the scale in the colors of the pictures we're using. They're value from 0 to 255. So we want to divide it by 255, and it'll generate a number between 0 and 1. They have shear range and zoom range. Horizontal flip equals true. And this, of course, has to do with if the photos are different shapes and sizes. Like I said, it's a wonderful package. You really need to dig in deep to see all the different options you have for setting up your images. For right now, though, we're going to just stick with some basic stuff here. And let me go ahead and run this code. And again, it doesn't really do anything because we're still setting up the pre-processing. Let's take a look at this next set of code. And this one is just huge. We're creating the training set. So the training set is going to go in here and it's going to use our train data gen we just created, .flow from directory. It's going to access, in this case, the path, data set, training set. That's a folder. So it's going to pull all the images out of that folder. Now, I'm actually running this in the folder that the data set's in. So if you're doing the same setup and you load your data in there and you're doing this, make sure wherever your Jupyter Notebook is saving things to that you create this path, or you can do the complete path if you need to, C:/, etc. And the target size, the batch size, and class mode is binary. So the classes, we're switching everything to a binary value. Batch size, what the heck is batch size? Well, that's how many pictures we're going to batch through the training each time. And the target size, 64 by 64. A little confusing, but you can see right here that this is just a general training, and you can go in there and look at all the different settings for your training set. And of course, with different data, we're doing pictures. There's all kinds of different settings depending on what you're working with. Now let's go ahead and run that and see what happens. And you'll see that it found 800 images belonging to one classes. So we have 800 images in the training set. And if we're going to do this with the training set, we also have to format the pictures in the test set. Now, we're not actually doing any predictions. We're not actually programming the model yet. All we're doing is preparing the data. So we're going to prepare a training set and the test set. So any changes we make to the training set at this point also have to be made to the test set. So we've done this thing, we've done a train data generator, we've done our training set, and then we also have, remember, our test set of data. So I'm going to do the same thing with that. I'm going to create a test data gen, and we're going to do this image data generator. We're going to rescale 1 over 255. We don't need the other settings, just the single setting for the test data gen. And we're going to create our test set. We're going to do the same thing we did with the test set, except that we're pulling it from the test set folder. And we'll run that, and you'll see in our test set we found 2,000 images. That's about right. We're using 20% of the images as test and 80% to train it. And then finally we've set up all our data. We've set up all our layers, which is where all the work is cleaning up that data and making sure it's going in there correctly. And we are actually going to fit it. We're going to train our data set. And let's see what that looks like. And here we go. Let's put the information in here. And let's just take a quick look at what we're looking at with our fit generator. We have our classifier.fit generator. That's our back propagation. So the information goes through forward with a picture, and it says, oh, you're either right or you're wrong, and then the error goes backward and reprograms all those weights. So we're training our neural network. And of course we're using the training set. Remember, we created the training set up here. And then we're going steps per epoch. So it's 8,000 steps. Epic means that's how many times we go through all the pictures. So we're going to rerun each of the pictures, and we're going to go through the whole data set 25 times. But we're going to look at each picture during each epic 8,000 times. So we're really programming the heck out of this and going back over it. And then they have validation data equals test set. So we have our training set, and then we're going to have our test set to validate it. So we're going to do this all in one shot. And we're going to look at that, and they're going to do 200 steps for each validation. And we'll see what that looks like in just a minute. Let's go ahead and run our training here. And we're going to fit our data. And as it goes, it says epic 1 of 25. You start realizing that this is going to take a while. On my older computer, it takes about 45 minutes. I have a dual processor. We're processing 10,000 photos. That's not a small amount of photographs to process. So if you're on your laptop, which I am, it's going to take a while. So let's go ahead and go get our cup of coffee and a sip and come back and see what this looks like. So I'm back. You didn't know I was gone. That was actually a lengthy pause there. I made a couple changes, and let's discuss those changes real quick and why I made them. So the first thing I'm going to do is I'm going to go up here and insert a cell above, and let's paste the original code back in there. And you'll see that the original thing was steps per epic 8,000, 25 epics, and validation steps 2,000. And I changed these to 4,000 epics, or 4,000 steps per epic, 10 epics, and just 10 validation steps. And this will cause problems if you're doing this as a commercial release. But for demo purposes, this should work. And if you remember, our steps per epic, that's how many photos we're going to process. In fact, let me go ahead and get my drawing pen out. And let's just highlight that right here. Well, we have 8,000 pictures we're going through. So for each epic, I'm going to change this to 4,000. I'm going to cut that in half. So it's going to randomly pick 4,000 pictures each time it goes through an epic. And the epic is how many processes. So this is 25, and I'm just going to cut that to 10. So instead of doing 25 runs through 8,000 photos each, which you can do the math of 25 times 8,000, I'm only going to do 10 through 4,000. So I'm going to run this 40,000 times through the processes. And the next thing I noted you'll want to notice is that I also changed the validation step. And this would cause some major problems in releasing because I dropped it all the way down to 10. What the validation step does is it says we have 2,000 photos in our trainings or in our testing set. And we're going to use that for validation. Well, I'm only going to use a random 10 of those to validate. So not really the best settings, but let me show you why we did that. Let's scroll down here just a little bit. And let's look at the output here and see what's going on there. So I've got my drawing tool back on, and you'll see here it lists a run. So each time it goes through an epic, it's going to do 4,000 steps. And this is where the 4,000 comes in. So that's where we have epic 1 of 10, 4,000 steps. So it's randomly picking half the pictures in the file and going through them. And then we're going to look at this number right here. That is for the whole epic. And that's 2,411 seconds. And if you remember correctly, you divide that by 60, you get minutes. If you divide that by 60, you get hours. Or you can just divide the whole thing by 60 times 60, which is 3,600. If 3,600 is an hour, this is roughly 45 minutes right here. And that's 45 minutes to process half the pictures. So if I was doing all the pictures, we're talking an hour and a half per epic times 36. Or no, 25. They had 25 up above. 25. So that's roughly a couple days of processing. Well, for this demo, we don't want to do that. I don't want to come back the next day. Plus, my computer did a reboot in the middle of the night. So we look at this and we say, okay, we're just testing this out. My computer that I'm running this on is a dual core processor, runs 0.9 gigahertz per second. For a laptop, it was good about 4 years ago, but for running something like this, it's probably a little slow. So we cut the times down, and the last one was validation. We're only validating it on a random 10 photos. And this comes into effect because you're going to see down here where we have accuracy, value loss, value accuracy, and loss. Those are very important numbers to look at. So the 10 means I'm only validating across 10 pictures. That is where, here we have value, this is ACC is for accuracy. Value loss, we're not going to worry about that too much, and accuracy. Now accuracy is while it's running, it's putting these two numbers together. That's what accuracy is. And value accuracy is at the end of the epic. What's our accuracy at the end of the epic? What is it looking at? In this tutorial, we're not going to go so deep, but these numbers are really important when you start talking about these two numbers. reflect bias. That is really important. I'll just put that up there. And bias is a little bit beyond this tutorial, but the short of it is if this accuracy, which is being our validation per step, is going down, and the value accuracy continues to go up, that means there's a bias. That means I'm memorizing the photos I'm looking at. I'm not actually looking for what makes a dog, what makes a cat. I'm just memorizing them. And so the more this discrepancy grows, the bigger the bias is. And that is really the beauty of the Horus neural network. It has a lot of built-in features like this that make that really easy to track. So let's go ahead and take a look at the next set of code. So here we are into part 3. We're going to make a new prediction. And so we're going to bring in a couple tools for that, and then we have to process the image coming in and find out whether it's an actual dog or cat, if we can actually use this to identify it. And of course the final step of part 3 is to print prediction. We'll go ahead and combine these, and of course you can see me there adding more sticky notes to my computer screen, hidden behind the screen, and last one was don't forget to feed the cat and the dog. So let's go ahead and take a look at that and see what that looks like in code and put that in our Jupyter Notebook. Alright, and let's paste that in here. And we'll start by importing NumPy as NP. NumPy is a very common package. I pretty much import it on any Python project I'm working on. Another one I use regularly is pandas. They're just ways of organizing the data. And then NP is usually the standard in most machine learning tools as the return for the data array. Although, you can use a standard data array from Python. And we have Horus pre-processing, import image. This should all look familiar because we're going to take a test image and we're going to set that equal to, in this case, cat or dog 1, as you can see over here. And you know what, let me get my drawing tool back on. So let's take a look at this. We have our test image we're loading, and in here we have test image 1, and this one data hasn't seen this one at all, so this is all new. Oh, let me shrink the screen down. Let me start that over. So here we have my test image, and we went ahead and the Horus processing has this nice image setup. So we're going to load the image and we're going to alter it to a 64 by 64 print. So right off the bat, Horus is nice that way. It automatically sets it up for us so we don't have to redo all our images and find a way to reset those. And then we use all those to set the image to an array. So again, we're all in pre-processing the data, just like we pre-processed before with our test information and our training data. And then we use the NumPy. Here's our NumPy. That's from our right up here, import NumPy as NP. Expand the dimensions, test image, axes equals 0. So it puts it into a single array. And then finally, all that work, all that pre-processing, and all we do is we run the result. We click on here and we go result equals classifier predict test image, and then we find out, well, what is the test image? And let's just take a quick look and just see what that is. And you can see when I ran it, it comes up dog, and if we look at those images, there it is, cat or dog, image number 1. That looks like a nice floppy-eared lab. Friendly with his tongue hanging out. It's either that or a very floppy-eared cat. I'm not sure which. But according to our software, it says it's a dog. And we have a second picture over here. Let's just see what happens when we run the second picture. We can go up here and change this from dog image 1 to 2. We'll run that, and it comes down here and says cat. You can see me highlighting it down there as cat. So our process works. We are able to label a dog and a cat just from the pictures. There we go, cleared my drawing tool. And the last thing I want you to notice, when we come back up here to when I ran it, you'll see it has an accuracy of 1 and the value accuracy of 1. Well, the value accuracy is the important one because the value accuracy is what it actually runs on the test data. Remember, I'm only validating it on a random 10 photos. And those 10 photos just happen to come up 1. Now, when they ran this on the server, it actually came up about 86%. This is why cutting these numbers down so far for a commercial release is bad. So you want to make sure you're a little careful of that when you're testing your stuff, that you change these numbers back when you run it on a more enterprise computer other than your old laptop that you're just practicing on or messing with. And we come down here and again, we had the validation of cat. And so we have successfully built a neural network that could distinguish between photos of a cat and a dog. Imagine all the other things you could distinguish. Imagine all the different industries you could dive into with that, just being able to understand those two different pictures. What about mosquitoes? Could you find the mosquitoes that bite versus the mosquitoes that are friendly? It turns out the mosquitoes that bite us are only 4% of the mosquito population, if even that, maybe 2%. There's all kinds of industries that use this, and there's so many industries that are just now realizing how powerful these tools are. Just in the photos alone, there is a myriad of industries sprouting up. And I said it before, I'll say it again, what an exciting time to live in with these tools that we get to play with.
Let's start with deep learning frameworks. To start with, this chart doesn't even do the filled justice because it's just exploded. These are just some of the major frameworks out there. There's Keras, which happens to sit on TensorFlow, so they're very integrated. There's TensorFlow, PyTorch is out there, Caffe, Theano, DL4J, and Chainer. These are just a few of the deep learning frameworks. We're talking about neural networks. If you're just starting out and never seen a neural network, you can go into Python in the scikit and do the neural network in there, which is probably the most simplest version I know. But the most robust version out there, the most top of the ladder as far as the technology right now, is TensorFlow. And that, of course, is changing from day to day, and some of these are better for different purposes. So let's dive into TensorFlow. Let's see, what is TensorFlow? What is TensorFlow? TensorFlow is a popular open source library released in 2015 by Google Brain Team for building machine learning and deep learning models. It is based on Python programming language and performs numerical computations using data flow graphs to build models. So let's take a look at some of the features of TensorFlow. It works efficiently with multi-dimensional arrays. If you've ever played with any of the simpler packages of neural networks, you're going to find that you have to pretty much flatten them and make sure your stuff is set in a flat model. TensorFlow works really good. So we're talking pictures here, where you have X and Y coordinates and where the picture is, and then each pixel has 3 or 4 different channels. That's a very complicated array, a very multidimensional array. It provides scalability of computation across machines and large data sets. This is so new right now, and you might think that's a minor thing, but when Python is operating on one computer and it has a float value and it truncates it differently on each computer, you don't get the same results. And so your training model might work on one machine and then on another it doesn't. This is one of the things that TensorFlow addresses and does a very good job on. It supports fast debugging and model building. This is why I love TensorFlow. I can go in there and I can build a model with different layers. Each layer might have different properties. They have like the convolutional neural network, which you can then sit on top of a regular neural network with reverse propagation. There's a lot of tools in here and a lot of options. And each layer that it goes through can utilize those different options and stack differently. And it has a large community and provides TensorBoard to visualize the model. TensorBoard's pretty recent, but it's a really nice tool to have so when you're working with other people or showing your clients or the shareholders in the company, you can give them a nice visual model so they know what's going on. What are they paying for? And let's take a glance at some of the different uses or applications for TensorFlow. When we talk about TensorFlow applications, clearly this is data analytics. We're getting into the data science. I like to use data science as probably a better term because this is the programming side. And it's really the sky is the limit. We can look at face detection, language translation, fraud detection, video detection. There are so many different things out there that TensorFlow can be used for. When you think of neural networks, because TensorFlow is a neural network, think of complicated chaotic data. This is very different than if you have a set numbers like you're looking at the stock market. You can use this on the stock market, but if you're doing something where the numbers are very clear and not so chaotic as you have in a picture, then you're talking more about linear regression models and different regression models when you're looking at that. When you're talking about these really complicated data patterns, then you're talking neural networks in TensorFlow. And if we're going to talk about TensorFlow, we should talk about what tensors are. After all, that is what that's what this is named after. So when we talk about tensors in TensorFlow, TensorFlow is derived from its core component known as a tensor. A tensor is a vector or a matrix of n dimensions that represent all types of data. And you can see here we have the scalar, which is just a single number. You have your vector, which is two numbers. Might be a number and a direction. You have a simple matrix, and then we get into the tensor. I mentioned how a picture is a very complicated tensor because it has your XY coordinates, and then each one of those pixels has 3 to 4 channels for your different colors. And so each image coming in would be its own tensor. And in TensorFlow, tensors are defined by a unit of dimensionality called as rank. And you can see here we have our scalar, which is a single number that has a rank of 0 because it has no real dimensions to it other than it's just a single point. And then you have your vector, which would be a single list of numbers. So that's a rank 1. Matrix would have rank 2. And then as you can see right here as we get into the full tensor, it has a rank 3. And so the next step is to understand how a TensorFlow works. And if you haven't looked at the basics of a neural network and reverse propagation, that is the basics of TensorFlow, and then it goes through a lot of different options and properties that you can build into your different tensors. So a TensorFlow performs computations with the help of data flow graphs. It has nodes that represent the operations in your model. And if you look at this, you should see a neural network going on here. We have our inputs B, C, and D, and you might have x equals b plus c, y equals d minus 4, a equals x times y, and then you have an output. And so even though this isn't a neural network here, it's just a simple set of computations going across, you can see how the more complicated it gets, the more it can actually, one of the tensors is a neural network with reverse propagation, but it's not limited to that. There's so much more you can do with it. And this here is just a basic flow of computations of the data going across. And you can see we can plug in the numbers, b equals 4, c equals 3, d equals 6, and you get x equals 4 plus 3, so x equals 7, y equals 6 minus 4, so y equals 2, and finally a equals 7 times 2, or a equals 14. Like I said, this is a very simplified version of how TensorFlow works. Each one of these layers can get very complicated. But TensorFlow does such a nice job that you can spin different setups up very easily and test them out. So you can test out these different models to see how they work. Now, TensorFlow has gone through 2 major stages. We had the original TensorFlow release of 1.0, and then they came out with the 2.0 version. And the 2.0 addressed so many things out there that the 1.0 really needed. So when we start talking about TensorFlow 1.0 versus 2.0, I guess you would need to know this for a legacy programming job if you're pulling apart somebody else's code. The first thing is that TensorFlow 2.0 supports eager execution by default. It allows you to build your models and run them instantly. And you can see here from TensorFlow 1 to TensorFlow 2, we have almost double the code to do the same thing. So if I want to do with tf.session or TensorFlow session as a session, the session run, you have your variables, your session run, you have your tables initializer, and then you do your model fit. X train, Y train, and then your validation data, your X value, Y value, and your epochs and your batch size. All that goes into the fit. And you can see here where that was all just compressed to make it run easier. You can just create a model and do a fit on it, and you only have like that last set of code on there, so it's automatic. That's what they mean by the eager. So if you see the first part and you're like, what the heck is all this session thing going on? That's TensorFlow 1.0. And then when you get into 2.0, it's just nice and clean. If you remember from the beginning, I said Keras on our list up there. And Keras is the high-level API in TensorFlow 2.0. Keras is the official high-level API of TensorFlow 2.0. It has incorporated Keras as tf.keras. Keras provides a number of model building APIs such as sequential, functional, and subclassing, so you can choose the right level of abstraction for your project. And we'll hopefully touch base a little bit more on this, sequential being the most common form. That is, your layers are going from one side to the other. So everything's going in a sequential order. Functional is where you can split the layers. So you might have your input coming on one side, it splits into two completely different models, and then they come back together. And one of them might be doing classification, the other one might be doing just linear regression kind of stuff, or a basic reverse propagation neural network, and then those all come together into another layer, which is your neural network reverse propagation setup. Subclassing is the most complicated, as you're building your own models, and you can subclass your own models into Keras. So very powerful tools here. This is all the stuff that's been coming out currently in the TensorFlow Keras setup. A third big change we're going to look at is that in TensorFlow 1.0, in order to use TF layers as variables, you would have to write TF variable block. So you'd have to predefine that. In TensorFlow 2, you just add your layers in under the sequential, and it automatically defines them as long as they're flat layers. Of course, this changes a little bit as the more complicated tensor you have coming in, but all of it's very easy to do, and that's what 2.0 does a really good job of. And here we have a little bit more on the scope of this, and you can see how TensorFlow 1 asks you to do these different layers and values. If you look at the scope and the default name, you start looking at all the different code in there to create the variable scope. That's not even necessary in Tensor 2.0. So you'd have to do 1 before you do what you see the code in 2.0. In 2.0, you just create your model. It's a sequential model, and then you can add all your layers in. You don't have to pre-create the variable scope. So if you ever see the variable scope, you know that came from an older version. And then we have the last two, which is our API cleanup and the autograph. In the API cleanup, TensorFlow 1, you could build models using TF-GANs, TF-app, TF-contrib, TF-flags, etc. In TensorFlow 2, a lot of APIs have been removed. And this is they just cleaned them up because people weren't using them, and they've simplified them. And that's your TF-app, your TF-flags, and your TF-logging are all gone. So those are 3 legacy features that are not in 2.0. And then we have our TF function and autograph feature. In the old version, TensorFlow 1.0, the Python functions were limited and could not be compiled or exported, re-imported. So you were continually having to redo your code, and you couldn't very easily just put a pointer to it and say, hey, let's reuse this. In TensorFlow 2, you can write a Python function using the TF function to mark it for the JIT compilation, for the Python JIT, so that TensorFlow runs it as a single graph. Autograph feature of TF function helps to write graph code using natural Python syntax. Now we just threw in a new word in you, graph. Graph is not a picture of a person. You'll hear graph X and some other things. Graph is what are all those lines that are connecting different objects. So if you remember from before, where we had the different layers going through sequentially, each one of those white lined arrows would be a graph X. That's where that computation is taken care of, and that's what they're talking about. And so if you had your own special code or Python way that you're sending that information forward, you can now put your own function in there instead of using whatever function they're using. In neural networks, this would be your activation function, although it could be almost anything out there depending on what you're doing. Next, let's go for hierarchy and architecture, and then we'll cover 3 basic tools in TensorFlow before we roll up our sleeves and dive into the example. So let's just take a quick look at TensorFlow toolkits and their hierarchy. At the high level, we have our object-oriented API. So this is what you're working with. You have your TF Keras, you have your estimators. This sits on top of your TF layers, TF losses, TF metrics. So you have your reusable libraries for model building. This is really where TensorFlow shines, is between the Keras, running your estimators, and then being able to swap in different layers. Your losses, your metrics, all of that is so built into TensorFlow. It makes it really easy to use. And then you can get down to your low-level TF API. You have extensive control over this. You can put your own formulas in there, your own procedures or models in there. You could have it split. We talked about that earlier. So with the 2.0, you can now have it split one direction where you do a linear regression model, and then go to the other where it does a neural network. And maybe each neural network has a different activation set on it. And then it comes together into another layer, which is another neural network. So you can build these really complicated models, and at the low level, you can put in your own APIs. You can move that stuff around. And most recently, we have the TF code can run on multiple platforms. And so you have your CPU, which is basically like on the computer I'm running on. I have 8 cores and 16 dedicated threads. I hear they now have one out there that has over 100 cores. So you have your CPU running, and then you have your GPU, which is your graphics card. And most recently, they also include the TPU setup, which is specifically for TensorFlow models, neural network kind of setup. So now you can export the TF code, and it can run on all kinds of different platforms for the most diverse setup out there. And moving on from the hierarchy to the architecture, in the TensorFlow 2.0 architecture, we have, you can see on the left, this is usually where you start out with, and 80% of your time in data science is spent pre-processing data, making sure it's loaded correctly and everything looks right. So the first level in TensorFlow is going to be your read and pre-processed data, your TF data feature columns. This is going to feed into your TF Keras or your pre-made estimators, and kind of you have your TensorFlow hub that sits on top of there so you can see what's going on. Once you have all that set up, you have your distribution strategy. Where are you going to run it? Are you going to be running it on just your regular CPU? Are you going to be running it with the GPU added in? Like I have a pretty high-end graphics card, so it actually grabs that GPU processor and uses it. Or do you have a specialized TPU set up in there that you paid extra money for? It could be if you're later on, when you're distributing the package, you might need to run this on some really high processors because you're processing at a server level for, let's say, you might be processing this at you're distributing it, not the distribution strategy, but you're distributing it into a server where that server might be analyzing thousands and thousands of purchases done every minute. And so you need that higher speed to give them a recommendation or a suggestion so they can buy more stuff off your website. Or maybe you're looking for data fraud analysis working with the banks. You want to be able to run this at a high speed so that when you have hundreds of people sending their transactions in, it says, hey, this doesn't look right. Someone's scamming this person and probably has their credit card. So when we're talking about all those fun things, we're talking about saved model. We were talking about that earlier, where it used to be when you did one of these models, it wouldn't truncate the float numbers the same. And so a model going from one, you build the model on your machine in the office, and then you need to distribute it. And so we have our TensorFlow serving cloud on premium. That's what I was talking about if you're like a banking or something like that. Now they have TensorFlow Lite, so you can actually run a TensorFlow on an Android or an iOS or Raspberry Pi. A little breakout board there. In fact, they just came out with a new one that has a built-in, it's just a little mini TPU with the camera on it so it can pre-process a video. So you can load your TensorFlow model onto that. Talking about an affordable way to beta test a new product. You have the TensorFlow JS, which is for browser and node server. So you can get that out on the browser for some simple computations that don't require a lot of heavy lifting, but you want to distribute to a lot of endpoints. And now they also have other language bindings. So you can now create your TensorFlow backend, save it, and have it accessed from C, Java, Go, C#, Rust, R, or from whatever package you're working on. So we kind of have an overview of the architecture and what's going on behind the scenes, and in this case, what's going on as far as distributing it. Let's go ahead and take a look at 3 specific pieces of TensorFlow. And those are going to be constants, variables, and sessions. So very basic things you need to know and understand when you're working with the TensorFlow setup. So constants in TensorFlow. In TensorFlow, constants are created using the function constant. In other words, they're going to stay static the whole time, whatever you're working with. The syntax for constant value, dtype 9, shape equals none, name constant, verify shape equals false. That's kind of the syntax you're looking at. And we'll explore this with our hands on a little more in depth. And you can see here we do z equals tf.constant, 5.2, name equals x, dtype is a float. That means that we're never going to change that 5.2. It's going to be a constant value. And then we have our variables in TensorFlow. Variables in TensorFlow are in memory buffers that store tensors. And so we can declare a 2x3 tensor populated by ones. You could also do constants this way, by the way. So you can create an array of ones for your constants. I'm not sure why you do that, but you might need that for some reason. In here we have v equals tf.variables, and then in TensorFlow you have tf.ones, and you have the shape, which is 2, 3, which is then going to create a nice 2x3 array that's filled with ones. And then of course you can go in there and they're variables, so you can change them, and it's a tensor, so you have full control over that. And then you, of course, have sessions in TensorFlow. A session in TensorFlow is used to run a computational graph to evaluate the nodes. And remember, when we're talking about graph or graph X, we're talking about all that information then goes through all those arrows and whatever computations they have that take it to the next node. And you can see down here where we have import TensorFlow as TF. If we do x equals a TF.constant of 10, we do y equals a TF constant of 2.0 or 20.0, and then you can do z equals TF.variable, and it's a TF.add x comma y. And then once you have that set up in there, you go ahead and init your TF global variables initializer with TF session as session. You can do a session run init, and then you print the session run y. And so when you run this, you're going to end up with, of course, the 10 plus 20 is 30. And we'll be looking at this a lot more closely as we actually roll up our sleeves and put some code together. So let's go ahead and take a look at that. And for my coding today, I'm going to go ahead and go through Anaconda, and then I'll use specifically the Jupyter Notebook on there. And of course, this code is going to work whatever platform you choose, whether you're in a notebook, the Jupyter Lab, which is just the Jupyter Notebook but with tabs for larger projects. We're going to stick with Jupyter Notebook. PyCharm, whatever it is you're going to use in here. You have your Spider and your Qt console for different programming environments. The thing to note, it's kind of hard to see, but I have my main Pi 3.6. Right now, when I was writing this, TensorFlow works in Python version 3.6. If you have Python version 3.7 or 3.8, you're probably going to get some errors in there. Might be that they've already updated it and I don't know it and I have an older version. But you want to make sure you're in Python version 3.6 in your environment. And of course, in Anaconda, I can easily set that environment up. Make sure you go ahead and pip in your TensorFlow, or if you're in Anaconda, you can do Anaconda install TensorFlow to make sure it's in your package. So let's just go ahead and dive in and bring that up. This will open up a nice browser window. I just love the fact I can zoom in and zoom out depending on what I'm working on, making it really easy to adjust a demo for the right size. Go under New, and let's go ahead and create a new Python. And once we're in our new Python window, this is going to leave it untitled. Let's go ahead and import. Import TensorFlow as TF. At this point, we'll go ahead and just run it real quick. No errors. Yay! No errors. I do that whenever I do my imports because I invariably will have opened up a new environment and forgotten to install TensorFlow into that environment or something along those lines. So it's always good to double check. And if we're going to double check that, it's also good to know what version we're working with. And we can do that simply by using the version command in TensorFlow, which you should know is probably intuitively the TF dot underscore underscore version underscore underscore. And you know, it always confuses me because sometimes you do TF dot version for one thing, you do TF dot underscore version underscore for another thing. This is a double underscore in TensorFlow for pulling your version out. And it's good to know what you're working with. We're going to be working in TensorFlow version 2.1.0. And I did tell you we were going to dig a little deeper into our constants, and you can do an array of constants. And we'll just create this nice array, a equals tf.constant, and we're just going to put the array right in there, 4361. We can run this, and now that is what a is equal to. And if we want to just double check that, remember we're in Jupyter Notebook where I can just put the letter A, and it knows that that's going to be print. Otherwise, you'd surround it in print. And you can see it's a TF tensor. It has the shape, the type, and the array on here. It's a 2x2 array. And just like we can create a constant, we can go ahead and create a variable. And this is also going to be a 2x2 array. And if we go ahead and print the V out, we'll run that. And sure enough, there's our TF variable in here. Then we can also, let's just go back up here and add this in here. I could create another tensor, and we'll make it a constant this time. And we'll go ahead and put that in over here. We'll have B TF constant. And if we go ahead and print out V and B, let me go ahead and run that. And this is an interesting thing that happens in here. You'll see right here when I print them both out, what happens is it only prints the last one unless you use print commands. So important to remember that in Jupyter Notebooks. We can easily fix that by go ahead and print and surround V with brackets. And now we can see with the two different variables we have the 3152, which is a variable, and this is just a flat constant. So it comes up as a TF tensor shape 2 kind of 2. And that's interesting to note that this label is a TF.tensor and this is a TF variable. So that's how it's looking in the back end when you're talking about the difference between a variable and a constant. The other thing I want you to notice is that in variable we capitalize the V, and with the constant we have a lowercase c. Little things like that can lose you when you're programming and you're trying to find out, hey, why doesn't this work? So those are a couple little things to note in here. And just like any other array in math, we can do like a concatenate the different values here. And you can see we can take AB concatenated. You just do a tf.concat values, and there's our AB axes on 1. Hopefully you're familiar with axes and how that works when you're dealing with matrices. And if we go ahead and print this out, you'll see right here we end up with a tensor. So it's put it in as a constant, not as a variable. And you have your array 4378 and 6145. It's concatenated the two together. And again, I want to highlight a couple things on this. Our axes equals 1. This means we're doing the columns. So if you had a longer array, like right now we have an array that is like, has a shape 1, whatever it is, 2, 2. Axes 0 is going to be your first one, and axes 1 is going to be your second one. And it translates as columns and rows. If we had a shape, let me just put the word shape here. So you know what I'm talking about, and it's very clear. And this is, I'll tell you what, I spend a lot of time looking at these shapes and trying to figure out which direction I'm going in and whether to flip it or whatever. So you can get lost in which way your matrix is going and which is column, which is rows. Are you dealing with the third axis or the second axis? Axis 1, 0, 1, 2, that's going to be our columns. And if you can do columns, then we also can do rows, and that is simply just changing the concatenate. We'll just grab this one here and copy it. We'll do the whole thing over. Control copy, Control V, and change this from axis 1 to axis 0. And if we run that, you'll see that now we concatenate by row as opposed to column. And you have 4, 3, 6, 1, 7, 8, 4, 7. So it just brings it right down and turns it into rows versus columns. You can see the difference there, your output. This really, you want to look at the output sometimes just to make sure your eyes are looking at it correctly and it's in the format. I find visually looking at it is almost more important than understanding what's going on, because conceptually your mind just too many dimensions sometimes. The second thing I want you to notice is this says a NumPy array. So TensorFlow is utilizing NumPy as part of their format as far as Python's concerned. And so you can treat this output like a NumPy array because it is just that. It's going to be a NumPy array. Another thing that comes up more than you would think is filling one of these with zeros or ones. And so you can see here we just create a tensor tf.zeros, and we give it a shape. We tell it what kind of data type it is. In this case we're doing an integer. And then if we print out our tensor, again we're in Jupyter, so I can just type out tensor, and I run this, you can see I have a nice array of with shape 3, 4 of zeros. One of the things I want to highlight here is integer 32. If I go to the TensorFlow data types, I want you to notice how we have float 16, float 32, float 64, complex. If we scroll down, you'll see the integer down here, 32. The reason for this is that we want to control how many bits are used in the precision. This is for exporting it to another platform. So what would happen is I might run it on this computer where Python does a float to indefinite, however long it wants to. And then we can take it, but we want to actually say, hey, we don't want that high precision. We want to be able to run this on any computer. And so we need to control whether it's a TF float 16. In this case, we did an integer 32. We could also do this as a float. So if I run this as a float 32, That means this has a 32-bit precision. You'll see 0 point whatever. And then to go with zeros, we have ones, if we're going from the opposite side, and so we can easily just create a TensorFlow with ones. And you might ask yourself, why would I want zeros and ones? And your first thought might be to initiate a new tensor. Usually we initiate a lot of this stuff with random numbers because it does a better job solving it. If you start with a uniform set of ones or zeros, you're dealing with a lot of bias. So be very careful about starting a neural network for one of your rows or something like that with ones and zeros. On the other hand, I use this for masking. You can do a lot of work with masking. You can also have, it might be that one tensor row is masked, 0 is false, 1 is true, or whatever you want to do it. And so in that case, you do want to use the zeros and ones. And there are cases where you do want to initialize it with all zeros or all ones, and then swap in different numbers as the tensor learns. So it's another form of control. But in general, you see zeros and ones, you usually are talking about a mask over another array. And just like in NumPy, you can also do reshapes. So if we take our, remember this is shaped 3, 4, maybe we want to swap that to 4, 3. And if we print this out, you will see, let me just go ahead and do that, Control V, let me run that. And you'll see that the order of these is now switched. Instead of 4 across, now we have 3 across and 4 down. And just for fun, let's go back up here where we did the ones. And I'm going to change the ones to tf.randomUniform. And we'll go ahead and just take off, well, we'll go ahead and leave that. We'll go ahead and run this. And you'll see now we have 0.0441. And this way you can actually see how the reshape looks a lot different. 0.041, 0.15, 0.71. And then instead of having this one, it rolls down here to the 0.14. And this is what I was talking about. Sometimes a lot of times you fill these with random numbers. And so this is the random.uniform is one of the ways to do that. Now, I just talked a little bit about this float 32 and all these data types. One of the things that comes up, of course, is recasting your data. So if we have a D-type float 32, we might want to convert these to integers because of the project we're working on. I know one of the projects I've worked on ended up wanting to do a lot of round off so that it would take a dollar amount or a float value and then have to round it off to a dollar amount. So we only wanted 2 decimal points. And in which case you have a lot of different options. You can multiply by 100 and then round it off or whatever you want to do. There's a lot of, or then convert it to an integer was one way to round it off. Kind of a cheap and dirty trick. So we can take this and we can take this same tensor and we'll go ahead and create a as an integer. And so we're going to take this tensor, we're going to tf.cast it, and if we print tensor, and then we're going to go ahead and print our tensor. Let me just do a quick copy and paste. And when I'm actually programming, I usually type out a lot of my stuff just to double check it. In doing a demo, copy and paste works fine, but sometimes be aware that copy and paste can copy the wrong code over. Personal choice, depends on what I'm working on. And you can see here we took a float 32, 4.6, 4.2, and so on, and it just converts it right down to a integer value. So our integer 32 setup. And remember we talked about a little bit about reshape as far as flipping it, and I just did 4, 3 on the reshape up here, and we talked about axis 0, axis 1. One of the things that is important to be able to do is to take one of these variables. We'll just take this last one, tensor as integer, and I want to go ahead and transpose it, and so I can do we'll do a equals tf.transpose. And we'll do our tensor integer in there. And then if I print the A out and we run this, you'll see that's the same array, but we've flipped it so that our columns and rows are flipped. This is the same as reshaping. So when you transpose, you're just doing a reshape. What's nice about this is that if you look at the numbers, the columns, when we went up here and we did the reshape, they kind of roll down to the next row. So you're not maintaining the structure of your matrix. So when we do a reshape up here, They're similar, but they're not quite the same. And you can actually go in here, and there's settings in the reshape that would allow you to turn it into a transform. So when we come down here, it's all done for you, and so there are so many times you have to transpose your digits that this is important to know that you can just do that. You can flip your rows and columns rather quickly here. And just like NumPy, you can also do your different math functions. We'll look at multiplication. And so we're going to take matrix multiplication of tensors. We'll go ahead and create A as a constant, 5839, and we'll put in a vector V, 4, 2. And we could have done this where they matched, where this was a 2 by 2 array, but instead we're going to do just a 2 by 1 array. And the code for that is your tf.matmul, so matrix multiplier. And we have A times V, and if we go ahead and run this, let's make sure we print out our AV on there. And if we go ahead and run this, you'll see that we end up with 36 by 30. And if it's been a while since you've seen the matrix math, this is 5 times 4 plus 8 times 2, 3 times 4 plus 9 times 2. And that's where we get the 36 and 30. Now, I know we're covering a lot really quickly as far as the basic functionality. So the matrix, or your matrix multiplier, is a very commonly used back-end tool as far as computing different models or linear regression, stuff like that. One of the things is to note is that just like in NumPy, you have all of your different math. So we have our TF math, and if we go in here, we have functions, we have our cosines, absolute, angle, all of that's in here. So all of these are available for you to use in the TensorFlow model. And if we go back to our example, and let's go ahead and pull, let's do some multiplication. That's always good. We'll stick with our AV, our constant A and our vector V. And we'll go ahead and do some bitwise multiplication, and we'll create an AV, which is A times V. Let's go and print that out. And you can see coming across here, we have the 4, 2 and the 5, 8, 3, 9, and it produces 20, 32, 618. And that's pretty straightforward. If you look at it, you have 4 times 5 is 20, 4 times 8 is 32. That's where those numbers come from. We can also quickly create an identity matrix, which is basically your main values on the diagonal being 1s and 0s across the other side. Let's go ahead and take a look and see what that looks like. And we can do, let's do this. So we're going to get the shape. This is a simple way, very similar to your NumPy. You can do a.shape, and it's going to return a tuple, in this case our rows and columns. And so we can do a quick print. We'll do rows. Oops. And we'll do columns. And if we run this, you can see we have 3 rows, 2 columns. And then if we go ahead and create an identity matrix, the script for that, got a wrong button there. The script for that looks like this, where we have the number of rows equals rows, the number of columns equals columns, and D type is a 32. And then if we go ahead and just print out our identity, you can see we have a nice identity column with our ones going across here. Now, clearly we're not going to go through every math module available, but we do want to start looking at this as a prediction model and seeing how it functions. So we're going to move on to a more of a direct setup where you can actually see the full TensorFlow in use. For that, let's go back and create a new setup. And we'll go in here, new Python 3 module. There we go. Bring this out so it takes up the whole window because I like to do that. hopefully you made it through that first part and you have a basic understanding of TensorFlow as far as being a series of NumPy arrays. You got your math equations and different things that go into them. We're going to start building a full setup as far as the NumPy, so you can see how Keras sits on top of it and the different aspects of how it works. The first thing we want to do is we're going to go ahead and do a lot of imports. Date times, warnings, SciPy. SciPy is your math, so the back-end scientific math. Warnings, because whenever we do a lot of this, you have older versions, newer versions, and so sometimes when you get warnings, you want to go ahead and just suppress them. We'll talk about that if it comes up on this particular setup. And of course, date time. Pandas, again, is your data frame. Think rows and columns. We import it as PD. NumPy is your numbers array, which of course TensorFlow is integrated heavily with. Seaborn for our graphics, and the Seaborn as SNS is going to be set on top of our matplot library, which we import as MPL. And then of course we're going to import our matplot library PyPlot as PLT. And right off the bat, we're going to set some graphic colors. Patch force edge color equals true. The style, we're going to use the 538 style. You can look this all up. When you get into matplot library, into Seaborn, there are so many options in here. It's just kind of nice to make it look pretty when we start up. That way we don't have to think about it later on. And then we're going to take, we have our MPLRC. We're going to put a patch edge color, dim gray line width. Again, this is all part of our graphics here in our setup. We'll go ahead and do an interactive shell. Node interactivity equals last expression. Here we are, PD for pandas. Options display max columns, so we don't want to display more than 50. And then our matplot library is going to be inline. This is a Jupyter Notebook thing, the matplot library inline. Then warnings, we're going to filter our warnings, and we're just going to ignore warnings. That way when they come up, we don't have to worry about them. Not really what you want to do when you're working on a major project. You want to make sure you know those warnings and then filter them out and ignore them later on. And if we run this, it's just going to be loading all that into the background. So that's a little back-end kind of stuff. Then what we want to go ahead and do is we want to go ahead and import our specific packages that we're going to be working with, which is under Keras. Now remember, Keras kind of sits on TensorFlow. So when we're importing Keras and the sequential model, we are in effect importing TensorFlow underneath of it. We just brought in the math, probably should have put that up above. And then we have our Keras models. We're going to import sequential. Now if you remember from our slide, there was 3 different options. Let me just flip back over there so we can have a quick recall on that. And so in Keras, we have sequential, functional, and subclassing. So remember those 3 different setups in here we talked about earlier. And if you remember from here, we have sequential, where it's going one TensorFlow layer at a time. You go kind of think of it as going from left to right or top to bottom or whatever direction it's going in. But it goes in one direction all the time, where functional can have a very complicated graph of directions. You can have the data split into 2 separate tensors, and then it comes back together into another tensor, all those kinds of things. And then subclassing is really the really complicated one, where now you're adding your own subclasses into the tensor to do external computations right in the middle of like a huge flow of data. But we're going to stick with sequential. It's not a big jump to go from sequential to functional. But we're running a sequential TensorFlow. And that's what this first import is here. We want to bring in our sequential. And then we have our layers. And let's talk a little bit about these layers. This is where Keras and TensorFlow really are happening. This is what makes them so nice to work with, is all these layers are pre-built. So from Keras, we have layers import dense. From Keras, layers import LSTM. When we talk about these layers, Keras has so many built-in layers. You can do your own layers. The dense layer is your standard neural network. By default, it uses ReLU for its activation. And then the LSTM is a long short-term memory layer. Since we're going to be looking probably at sequential data, we want to go ahead and do the LSTM. And if we go into Keras Keras and we look at their layers, this is a Keras website, you can see as we scroll down for the Keras layers that are built in, we can get down here and we can look at, let's see, here we have our layer activation, our base layers. Activation, layer weight, so it's a lot of stuff in here. We had the ReLU, which is the basic activation that was listed up here for layer activations. You can change those. And here we have our core layers and our dense layers. You have an input layer, a dense layer, and then we've added a more customized one with the long-term, short-term memory layer. And of course, you can even do your own custom layers in Keras. There's a whole functionality in there if you're doing your own thing. What's really nice about this is it's all built in. Even the convolutional layers, this is for processing graphics. There's a lot of cool things in here you can do. This is why Keras is so popular. It's open source and you have all these tools right at your fingertips. So from Keras, we're just going to import a couple layers, the dense layer and the long short-term memory layer. And then, of course, from sklearn, our scikit, we want to go ahead and do our min-max scaler, standard scaler for pre-editing our data, and then metrics just so we can take a look at the errors and compute those. Let me go ahead and run this, and that just loads it up. We're not expecting anything from the output. And our file coming in is going to be airquality.csv. Let's go ahead and take a quick look at that. This is in OpenOffice. It's just a standard, you can do Excel, whatever you're using for your spreadsheet. And you can see here we have a number of columns, a number of rows. It actually goes down to like 8,000. The first thing we want to notice is that the first row is kind of just a random number put in going down. Probably not something we're going to work with. The second row is Bandung. I'm guessing that's a reference for the profile. If we scroll to the bottom, which I'm not going to do because it takes forever to get back up, they're all the same. The same thing with the status. The status is the same. We have a date, so we have a sequential order here. Here is the jam, which I'm going to guess is the timestamp on there. So we have a date and time. We have our O3, CO, NO2 reading, SO2, NO, CO2, VOC, and then some other numbers here, PM1, PM2.5, PM4, PM10. Without actually looking through the data, some of this I can guess is like temperature, humidity. I'm not sure what the PMs are. But we have a whole slew of data here. So we're looking at air quality as far as an area and a region and what's going on with our date timestamps on there. And so code-wise, we're going to read this into a pandas data frame. So our data frame, DF is a nice abbreviation commonly used for data frames, equals pd.read_csv, and then the path to it just happens to be on my D drive, separated by spaces. And so if we go ahead and run this, we'll print out the head of our data. And again, this looks very similar to what we were just looking at. Being in Jupyter, I can take this and go the other way. Make it real small so you can see all the columns going across and we can get a full view of it. Or we can bring it back up in size. That's pretty small on there. Overshot. But you can see it's the same data we were just looking at. We're looking at the number, we're looking at the profile, which is the Bandung, the date, we have a timestamp, our O3 count, CO, and so forth on here. And this is just your basic pandas printing out the top 5 rows. We could easily have done 3 rows, 5 rows, 10, whatever you want to put in there. By default, that's 5 for pandas. Now, I talk about this all the time, so I know I've already said it at least once or twice during this video. Most of our work is in pre-formatting data. What are we looking at? How do we bring it together? So we want to go ahead and start with our date time. It's come in 2 columns. We have our date here, and we have our time. And we want to go ahead and combine that. And then we have, this is just a simple script in there that says combine date time. That's our formula we're building. We're going to submit our pandas data frame and the tab name. When we go ahead and do this, that's all of our information that we want to go ahead and create. And then goes for I in range df shape 0. So we're going to go through the whole setup, and we're going to list tab append df location I. And here is our date going in there, and then return the numpy array list tab d types date time 64. That's all we're doing. We're just switching this to a date timestamp. And if we go ahead and do df date time equals combine date time, And then I always like to print. We'll do df head just so we can see what that looks like. And so when we come out of this, we now have our setup on here, and of course it's edited on to the far right. Here's our date time. You can see the format's changed. So we've added in the date time column, and we've brought the date over, and we've taken this format here, and it's an actual variable with a 000 on here. Well, that doesn't look good. So we need to also include the time part of this, and we want to convert it into hourly data. So let's go ahead and do that. To do that, to finish combining our date time, let's go ahead and create a little script here to combine the time in there. Same thing we just did. We're just creating a numpy array, returning a numpy array, and forcing this into a date time format. And we can actually spend hours just going through these conversions. How do you pull it from the pandas data frame? How do you set it up? So I'm kind of skipping through it a little fast because I want to stay focused on TensorFlow and Keras. Keep in mind, this is like 80% of your coding when you're doing a lot of this stuff is going to be reformatting these things, resetting them back up so that it looks right on here. And, it just takes time to get through all that. But that is usually what the companies are paying you for. That's what the big bucks are for. And we want to go ahead and a couple things going on here is we're going to go ahead and do our date time. We're going to reorganize some of our setup in here, convert into hourly data. Let me just put a pause in there. Now remember, we can select from DF our different columns we're going to be working with, and you're going to see that we actually dropped a couple of the columns. Those ones I showed you earlier, they're just repetitive data. So there's nothing in there that exciting. And then we want to go ahead and we'll create a second data frame here. Just get rid of the df head. And df2 is we're going to group by date time, and we're looking at the mean value. And then we'll print that out so you can see what we're talking about. We have now reorganized this, so we put in date time 03 CO. So now this is in the same order as it was before. And you'll see the date time now has our 00, same date, 1, 2, 3, and so on. So it's grouped the data together so that it's a lot more manageable and in the format we want. And in the right sequential order. And if we go back to, there we go, our air quality, you can see right here we're looking at these columns going across. We really don't need, since we're going to create our own date time column, we can get rid of those. These are the different columns of information we want, and that should reflect right here in the columns we picked coming across. So this is all the same columns on there. That's all we've done is reformatted our data, grouped it together by date, and then you can see the different data coming out set up on there. And then as a data scientist, first thing I want to do is get a description. What am I looking at? And so we can go ahead and do the df2 describe, and this gives us our describe gives us our basic data analytics information we might be looking for, like what is the mean, standard deviation, minimum amount, maximum amount. We have our first quarter, second quarter, and third quarter numbers also in there. So you can get a quick look at a glance describing the data, or descriptive analysis. And even though we have our quantile information in here, we're going to dig a little deeper into that. We're going to calculate the quantile for each variable. We're going to look at a number of things for each variable. And we'll see right here, Q1, we can simply do the quantile 0.25%, which should match our 25% up here. And we're going to be looking at the min, the max, and we're just going to do this. It's basically we're breaking this down for each different variable in there. One of the things that's kind of fun to do, we're going to look at that in just a second. Let me put the next piece of code in here. We got to clean out some of our, we're going to drop a couple things, our last rows and first row, because those usually they have a lot of null values, and the first row is just our titles. So that's important. It's important to drop those rows in here. And so this right here, as we look at our different quantiles, again, it's the same, we're still looking at the 25 quantile here. We're going to do a little bit more with this. So now that we've cleared off our first and last rows, we're going to go ahead and go through all of our columns, and this way we can look at each column individually. And so we'll just create a Q1, Q3, min, max, min IQR, max IQR, and calculate the quantile of I of DF2, we're basically doing the math that they did up here, but we're splitting it apart. That's all this is. And this happens a lot because you might want to look at individual. If this was my own project, I would probably spend days and days going through what these different values mean. One of the biggest data science things we can look at that's important is use your common sense. If you're looking at this data and it doesn't make sense, and you go back in there and you're like, wait a minute, what the heck did I just do? At that point, you probably should go back and double check what you have going on. Now, we're looking at this, and you can see right here, here's our attribute for our O3. So we've broken it down. We have our Q1, 5.88, Q3, 10.37. If we go back up here, here's our 5.8. We've rounded it off. 10.37's in there. So we've basically done the same math, just split it up. We have our minimum and our max IQR, and that's computed, let's see, where is it? Here we go. Q1 minus 1.5 times IQR. And the IQR is your Q3 minus Q1. So that's the difference between our two different quarters. And this is all data science. As far as the hard math, we're really not, we're actually trying to focus on Keras and TensorFlow. You still got to go through all this stuff. I told you 80% of your programming is going through and understanding what the heck happened here. What's going on? What does this data mean? And so when we're looking in that, we're going to go ahead and say, hey, we've computed these numbers, and the reason we've computed these numbers is if you take the minimum value and it's less than your minimum IQR, that means something's going wrong there. And that usually, in this case, is going to show us an outlier. So we want to go ahead and find the minimum value. If it's less than the minimum IQR, it's an outlier. And if the max value is greater than the max IQR, we have an outlier. And that's all this is doing. Low outlier is found, minimum value, high outlier is found. Really important, actually. Outliers are almost everything in data sometimes. Sometimes you do this project just to find the outliers because you want to know crime detection. What are we looking for? We're looking for the outliers. What doesn't fit a normal business deal? And then we'll go ahead and throw in, just threw in a lot of code. Oh my goodness. So we have, if your max is greater than IQR, print outlier is found. What we want to do is we want to start cleaning up these outliers. And so we want to convert, create a convert nan, x max IQR equals max underscore IQR, min IQR equals min IQR. So this is just saying this is the data we're going to send. That's all that is in Python. And if x is greater than the max IQR and x is less than the min IQR, x equals null. We're going to set it to null. Why? Because we want to clear these outliers out of the data. Now, again, if you're doing fraud detection, you would do the opposite. You would be cleaning everything else that's not in that series so that you can look at just the outlier. And then we're going to convert the nan hum. Again, we have x, max IQR is 100%, min IQR is min IQR. If x is greater than max IQR and x is less than min IQR, again, we're going to return a null value. Otherwise, it's going to remain the same value x equals x. And you can see as we go through the code, if I equals our HUM, then we go ahead and do, that's a column specific to humidity. That's your HUM column. Then we're going to go ahead and convert, run a map on there and convert the non-HUM. You can see here this is just cleanup. We found out that humidity probably has some weird values in it. We have our outliers. That's all this is. And so when we go ahead and finish this and we take a look at our outliers and we run this code here, we have a low outlier, 2.04. We have a high outlier, 99.06. Outliers have been interpolated. That means we've given them a new value. Chances are these days when you're looking at something like these sensors coming in, they probably have a failed sensor in there. Something went wrong. that's the kind of thing that you really don't want to do your data analysis on. So that's what we're doing, is we're pulling that out and then converting it over and setting it up method linear. So we interpolate method linear is it's going to fill that data in based on a linear regression model of similar data. Same thing with this up here with the df2i interpolate. That's what we're doing. Again, this is all data prep. We're not actually talking about TensorFlow. We're just trying to get all our data set up correctly so that when we run it, it's not going to cause problems or have a huge bias. So we've dealt with outliers specifically in humidity. And again, this is one of these things where when we start running, we ran through this, you can see down here that we have our outliers found, high-low outliers, we've migrated them in. We also know there's other issues going on with this data. How do we know that? Some of it's just looking at the data, playing with it until you start understanding what's going on. Let's take the temp value, and we're going to go ahead and use a logarithmic function on the temp value. And it's interesting because it's like, how the heck do you even know to use logarithmic on the temp value? That's domain specific. We're talking about being an expert in air care. I'm not an expert in air care. It's not what I go look at. I don't look at air care data. In fact, this is probably the first air care data setup I've looked at. But the experts come in there and they come to you and say, hey, in data science, this is a exponentially variable on here, so we need to go ahead and do transform it and use a logarithmic scale on that. So at that point, that would be coming from your data. Here we go. Data science programmer overview, does a lot of stuff connecting the database and connecting in with the experts. Data analytics, a lot of times you're talking about somebody who is a data analysis, might be all the way usually a PhD level. Data science, programming level interfaces, database manager, that's going to be the person who's your admin working on it. So when we're looking at this, we're looking at something they've sent to me and they said, hey, domain, air care, this is a skew because the data just goes up exponentially and affects everything else. And we'll go ahead and take that data. Let me just go ahead and run this. Just for another quick look at it, we have our, we'll do a distribution df. We'll create another data frame from the temp values and then from a data set from the log temp. So we can put them side by side. And we'll just go ahead and do a quick histogram. And this is kind of nice. Plot a figure size. Here's our PLT from Matplot library. And then we'll just do a distribution underscore df. There's our data frames. This is nice because it just integrates the histogram right into pandas. Love pandas. And this is a chart you would send back to your data analyst and say, hey, is this what you wanted? This is how the data is converting on here. As a data scientist, the first thing I note is we've gone from a 10, 20, 30 scale to 2.5, 3.0, 3.5 scale. And the data itself has kind of been adjusted a little bit based on some kind of a skew on there. So let's jump into, we're getting a little closer to actually doing our cross on here. We'll go ahead and split our data up. And this, of course, is any good data scientists. You want to have a training set and a test set. And we'll go ahead and do the train size. We're going to use 0.75% of the data. Make sure it's an integer. You don't want to take a slice as a float value. Give you a nice error. And we'll have our train size is 75%, and the test size is going to be, of course, the train size minus the length of the data set. And then we can simply do train comma test. Here's our data set, which is going to be the train size, the test size. And then if we go ahead and print this, let me just go ahead and run this. We can see how these values split. It's a nice split of 1298 and then 433 points of value that are going to be for our setup on here. And if you remember, we're specifically looking at the data set. Where did we create that data set from? That was from up here. That was what we called the logarithmic value of the temp. That's where the data set came from. So we're looking at just that column with this train size and the test, with the train and test data set here. And let's go ahead and do convert an array of values into a data set matrix. We're going to create a little set up in here. We create our data set. Our data set's going to come in. We're going to do a look back of 1. So we're going to look back one piece of data going backward. And we have our data X and our data Y. For I in range, length of data set, look back -1. This is creating, let me just go ahead and run this. Actually, the best way to do this is to go ahead and create this data and take a look at the shape of it. Let me go ahead and just put that code in here. So we're going to do a look back 1. Here's our train X, our train Y, and it's going to be adding the data on there. And then when we come up here and we take a look at the shape, there we go, and we run this piece of code here, we look at the shape on this, and we have a new, slightly different change on here, but we have a shape of X, 1296, 1, shape of Y, train Y, test X, test Y. And so what we're looking at is that the X comes in, and we're only having a single value out. We want to predict what the next one is. That's what this little piece of code is here for. What are we looking for? Well, we want to look back 1. That's the what we're going to train the data with is yesterday's data. Yesterday says, hey, the humidity was at 97%. What should today's humidity be at? If it's 97% yesterday, is it going to go up or is it going to go down today? If 97, does it go up to 100? What's going on there? And so we're looking forward to the next piece of data, which says, hey, tomorrow's is going to, today's humidity is this. This is what tomorrow's humidity is going to be. That's all that is. All that is stacking our data so that our Y is basically X plus 1, or X could be Y minus 1. And then a couple things to note is our X data. We're only dealing with the one column, but you need to have it in a shape that has it by the columns. So you have the 2 different numbers. And since we're doing just a single point of data, we have, and you'll see with the train Y, we don't need to have the extra shape on here. Now, this is going to run into a problem. And the reason is that we have what they call a time step. And the time step is that long-term, short-term memory layer. So we're going to add another reshape on here. Let me just go down here and put it into the next cell. And so we want to reshape the input array in the form of sample time step features. We're only looking at one feature. And I mean, this is one of those things when you're playing with this, you're like, why am I getting an error in the numpy array? Why is this giving me something weird going on? So what we're going to do is we're going to add one more level on here. Instead of being 1299.1, we want to go one more. And when they put the code together in the back, you can see we kept the same shape, the 1299. We added the 1 dimension, and then we have our train X shape 1. And this could have, depends again on how far back in the long short-term memory you want to go. That is what that piece of code is for, and that reshape is. And you can see the new shape is now 1299.11 versus the 1299.1. And then the other part of the shape, 432.11. Again, this is our X in, and of course our test X. And then our Y is just a single column because we're just doing one output that we're looking for. So now we've done our 80%. That's all the writing all the code, reformatting our data, bringing it in. Now we want to go ahead and do the fun part, which is we're going to go ahead and create and fit the LSTM neural network. And if we're going to do that, the first thing we need is we're going to need to go ahead and create a model. And we'll do this sequential model. And if you remember, sequential means it just goes in order. That means if you have 2 layers, the layers go from layer 1 to layer 2, or layer 0 to layer 1. This is different than functional. Functional allows you to split the data and run 2 completely separate models and then bring them back together. We're doing just sequential on here. And then we decided to do the long short-term memory. And we have our input shape, which it comes in. Again, this is what all this switching was. We could have easily made this 1, 2, 3, or 4 going back as far as the end number on there. We just stuck to going back 1. And it's always a good idea when you get to this point, where the heck is this model coming from? What kind of models do we have available? And let me go ahead and put the next model in there, because we're going to do 2 models. And the next model is going to go ahead and we're going to do dense. So we have model equals sequential, and then we're going to add the LSTM model, and then we're going to add a dense model. And if you remember from the very top of our code, where we did the imports. Oops, there we go, our cross. This is it right here. Here's our importing a dense model, and here's our importing an LSTM. Now, just about every TensorFlow model uses dense. Your dense model is your basic forward propagation, reverse propagation error, where it does reverse propagation to program the model. So any of your neural networks that you've already looked at that looks and says, here's the error, and sends the error backwards, that's what this is. The long short-term memory is a little different. The real question that we want to look at right now is, where do you find these models? What kind of models do you have available? And so for that, let's go to the Keras website, which is the keras.io. If you go under API/layers, and I always have to do a search, just search for Keras API layers. It'll open up and you can see we have your base layers right here, class, trainable, weights, all kinds of stuff like there. Your activation. So a lot of your layers, you can switch how it activates. ReLU, which is like your smaller arrays, or if you're doing convolutional neural networks, the convolution usually uses a ReLU. Your sigmoid, all the way up to softmax, softplus, all these different choices as far as how those are set up. And what we want to do is we want to go ahead, and if you scroll down here, you'll see your core layers, and here is your dense layer. So you have an input object, your dense layer, your activation layer, embedding layer. This is your kind of your one setup on there that's most common. Convolutional neural networks, or convolutional layers, these are like for doing image categorizing, so trying to find objects in a picture, that kind of thing. We have pooling layers, so as you have the layers come together, usually you bring them down into a single layer, although you can still do like global max pooling 3D. And there is just, I mean, this list just goes on and on. There's all kinds of different things hidden in here as far as what you can do. And it changes. You know, you go in here and you just have to do a search for what you're looking for, and figure out what's going to work best for you as far as which project you're working on. Long short-term memory is a big one, because this is when we start talking about text. What if someone says what comes after the cat in the hat, little kid's book there, starts programming it, and so you really want to know not only what's going on, but it's going to be something that has a history. The history behind it tells you what the next one coming up is. Now, once we've built all our different, we built our model, we've added our different layers we went in there, play with it. Remember, if you're in functional, you can actually link these layers together and they branch out and come back together. If you do the sub setup, then you can create your own different model. You can embed a model in there that might be something linear regression. You can embed a linear regression model as part of your functional split, and then have that come back together with other things. So we're going to go ahead and compile your model. This brings everything together. We're going to put in what the loss is, which we'll use the mean squared error, and we'll go ahead and use the atom optimizer. Clearly, there's a lot of choices on here depending on what you're doing. And just like any of these different prediction models, if you've been doing any scikit from Python, you'll recognize that we have to then fit the model. So what are we doing in here? We're going to send in our train X, our train Y. We're going to decide how many epochs we're going to run it through. 500 is probably a lot for this. I'm guessing it'd probably be about 200 or 300, probably do just fine. Our batch size. So how many different, when you process it, this is the math behind it. If you're in data analytics, you might try to know what this number is as a data scientist, where I haven't had the PhD level math that says this is why you want to use this particular batch size. You kind of play with this number a little bit. You can dig deeper into the math, see how it affects the results depending on what you're doing. And there's a number of other settings on here. We did verbose 2. I'd have to actually look that up to tell you what verbose means. I think that's actually the default on there if I remember correctly. There's a lot of different settings when you go to fit it. The big ones are your epoch and your batch size. Those are what we're looking for. And so we're going to go ahead and run this. And this is going to take a few minutes to run because it's going through 500 times through all the data. So if you have a huge data set, this is the point where you're kind of wondering, oh my gosh, is this going to finish tomorrow? If I'm running this on a single machine and I have a terabyte of data going into it, If this is my personal computer and I'm running a terabyte of data into this, this is running rather quickly through all 500 iterations. But yeah, at a terabyte of data, we're talking something closer to days, week, even with a 3.5 gigahertz machine in 8 cores, it's still going to take a long time to go through a full terabyte of data. And then we want to start looking at putting it into some other framework like Spark or something that will build the process on there more across multiple processors and multiple computers. And if we scroll all the way down to the bottom, you're going to see here's our square mean error of 0.0088. If we scroll way up, you'll see it kind of oscillates between 0.0888 and 0.0089. It's right around 250 where you start seeing that oscillation where it's really not going anywhere. So we really didn't need to go through a full 500 epochs. If you're retraining the stuff over and over again, it's kind of good to note where that error zone is so you don't have to do all the extra processing. Of course, if you're going to build a model, we want to go ahead and run a prediction on it. So let's go ahead and make our prediction. And remember, we have our training test set and our test set, we have the train X and the train Y for training it, or train predict. And then we have our test X and our test Y going in there. So we can test to see how good it did. And when we come in here, we have, you'll see right here, we go ahead and do our train predict equals model predict train X and test predict model predict test X. Why would we want to run the prediction on train X? Well, it's not 100% on its prediction. We know it has a certain amount of error, and we want to compare the error we have on what we programmed it with the error we get when we run it on new data that's never seen, the model's never seen before. And one of the things we can do, we go ahead and invert the predictions. This helps us level it off a little bit more. Get rid of some of our bias. We have train predict equals an NP exponential M1, the train predict. And then train Y equals the exponential M1 for train Y. And then we do again that with train test predict and test Y. Again, reformatting the data so that it all matches. And then we want to go ahead and calculate the root mean square error. So we have our train score, which is your math square root times the mean square root error, train Y and train predict. And again, we're just, this is just feeding the data through so we can compare it. And the same thing with the test. And let's take a look at that, because really the code makes sense. If you're going through it line by line, you can see what we're doing. But the answer really helps to zoom in. So we have a train score, which is 2.40 of our root mean square error. And we have a test score of 3.16 of the root mean square error. If these were reversed, if our test score is better than our training score, then we've overtrained. Something's really wrong. At that point, you got to go back and figure out what you did wrong. Because you should never have a better result on your test data than you do on your training data. And that's why we put them both through. That's why we look at the error for both the training and the testing. When you're going out and quoting your, publishing this, and you're saying, hey, how good is my model? It's the test score that you're showing people. This is what it did on my test data that the model had never seen before. This is how good my model is. And a lot of times you actually want to put together like a little formal code where we actually want to print that out. And if we print that out, you can see down here, test prediction and standard deviation of data set, 3.16 is less than 4.40. I'd have to go back, and we're up here. If you remember, we did the square means error. This is standard deviation. That's why these numbers are different. It's saying the same thing that we just talked about. 3.16 is less than 4.40. Model is good enough. We're saying, hey, this model is valid. We have a valid model here. So we can go ahead and go with that. And along with putting a formal print out of there, we want to go ahead and plot what's going on. And this, we just want a pretty graph here so that people can see what's going on. When I walk into a meeting and I'm dealing with a number of people, they really don't want these numbers. They don't want to say, hey, standard deviation, unless you know what statistics are. You might be dealing with a number of different departments. Head of sales might not work with standard deviation or have any idea what that really means number-wise. And so at this point, we really want to put it in a graph so we have something to display. And with displaying, you got to remember that we're looking at the data today going into it and what's going to happen tomorrow. So let's take a quick look at this. We're going to go ahead and shift the train predictions for plotting. We have our train predict plot, NP empty like data set, train predict plot, set it up with null values. You know, it's just kind of a weird thing where we're creating the data groups as we like them, and then putting the data in there is what's going on here. So we have our train predict plot, which is going to be our look back, our length, plus look back. Is going to equal train predict. So we're creating this. Basically, we're taking this and we're dumping the train predict into it. So now we have our nice train predict plot. And then we have the shift test predictions for the plotting. We're going to continue more of that. Oops, looks like I put it in here double. No, it's just, yeah, they put it in here double. Didn't mean to do that. We really only need to do it once. Oh, here we go. This is where the problem was, is because this is the test predict. So we have our training prediction. We're doing the shift on here. And then the test predict, we're going to look at that. Same thing, we're just creating those two data sets. Test predict plot, length prediction set up on there. And then we're going to go through the plotting, the original data set, and the predictions. So we have a time axis. Always nice to have your time set on there. Set that to the time array, time axis lap. All this is setting up the time variable for the bottom. And then we have a lot of stuff going on here as far as setting up our figure. Let's go ahead and run that, and then we'll break it down. We have on here our main plot. We have two different plots going on here. The ISPU going up and the data, and the ISPU here with all these different settings on it. And so when we look at this, we have our AX1, that's the main plot. I mean our AX, that's the main plot, and we have our AX1, which is the secondary plot over here. So we're doing a figure PLT, or PLT.figure, and we're going to dump those two graphs on there. And so we take, and if you go through the code piece by piece, which we're not going to do, we're going to do the data set here, exponential, reverse exponential, so that it looks correctly. We're going to label it the original data set. We're going to plot the train predict plot. That's what we just created. We're going to make that orange, and we'll label it train prediction. Test predict plot, we're going to make that red and label it test prediction, and so forth. Set our ticks up. This actually just put ticks, time axis gets its ticks. The little marks there going along the axes, that kind of thing. And let's take a look and see what these graphs look like. And these are just kind of fun. You know, when you show up into a meeting and this is the final output and you say, hey, this is what we're looking at. Here's our original data in blue. Here's our training prediction. You can see that it trains pretty close to what the data is up there. I would also probably put a like a little timestamp and do just right before and right after, where we go from train to test prediction. And you can see with the test prediction, the data comes in red, and then you can also see what the original data set looked like behind it and how it differs. And then we can just isolate that here on the right. That's all this is just the test prediction on the right. And it's, you know, you'll see with the original data set, there's a lot of peaks we're missing and a lot of lows we're missing. But as far as the actual test prediction, it does pretty good. It's pretty right on. You can get a good idea of what to expect for your ISPU. And so from this, we would probably publish it and say, hey, this is what you expect, and this is our this is a range of error. That's the kind of thing I'd put out on a daily basis. Maybe we predict the cells are going to be this, or maybe weekly. So you kind of get you kind of flatten the data coming out, and you say, hey, this is what we're looking at. The big takeaway from this is that we're working with, let me go back up here. Whoops, oh, too far. There we go. Is this model here. This is what this is all about. We worked through all of those pieces, all the TensorFlows, and that is to build this sequential model. And we're only putting in the 2 layers. This can get pretty complicated. If you get too complicated, it never, never verges into a usable model. So if you have like 30 different layers in here, there's a good chance you might crash it, kind of thing. So don't go too haywire on that. And that you kind of learn as you go. Again, it's domain knowledge, and also starting to understand all these different layers and what they mean. The data analytics behind those layers is something that your data analysis professional would come in and say, this is what we want to try. But I tell you, as a data scientist, a lot of these basic setups are common. And I don't know how many times working with somebody and they're like, oh my gosh, if I only did a tangent H instead of a ReLU activation, I worked for 2 weeks to figure that out. Well, as a data science, I can run it through the model in 5 minutes instead of spending 2 weeks doing the math behind it. So that's one of the advantages of data scientists, is we do it from programming side, and a data analytics is going to look for it. How does it work in math? And this is really the core right here of TensorFlow and Keras, is being able to build your data model quickly and efficiently. And of course, with any data science, putting out a pretty graph so that your shareholders, again, we want to take and reduce the information down to something people can look at and say, oh, that's what's going on. They can see what's going on as far as the dates and the change in the ISPU.
In this video, I will walk you through the TensorFlow code to perform object detection in a video. So let's get started. This part is basically you're importing all the libraries. We need a lot of these libraries. For example, NumPy, we need image IO, datetime, and pill, and so on and so forth. And of course, matplotlib. So we import all these libraries. And then there are a bunch of variables which have some paths for the files and folders. So this is regular stuff. Let's keep moving. Then we import the matplotlib and make it inline, and a few more imports. All right. And then these are some warnings. We can just ignore them. So if I run this code once again, it will go away. All right. And then here onwards, we do the model preparation. Now what we're going to do is we are going to use an existing neural network model. So we are not going to train a new one, because that really will take a long time, and it needs a lot of computation resources and so on, and it is really not required. There are already models that have been trained, and in this case it is the SSD with MobileNet. That's the model that we are going to use, and this model is trained to detect objects, and it is readily available as open source, so we can actually use this. And if you want to use other models, there are a few more models available, so you can click on this link here, and let me just take you there. There are a few more models, but we have chosen this particular one because this is faster. It may not be very accurate, but that is one of the faster models. But on this link you will see a lot of other models that are readily available. These are trained models. Some of them would take a little longer, but they may be more accurate and so on, so you can probably play around with these other models. Okay, so we will be using that model. So this piece of code, this line, is basically importing that model, and this is also known as frozen model. The term we use is frozen model. So we import, download and import that, and then we will actually use that model in our code. Alright, so these two cells, we have downloaded and imported the model, and then once it is available locally, we will then load this into our program. Alright, so we are loading this into memory, and you need to perform a couple of additional steps, which is basically we need to map the numbers to text. As you may be aware, when we actually build the model and when we run predictions, the model will not give a text. The output of the model is usually a number. So we need to map that to a text. So for example, if the network predicts that the output is 5, we know that 5 means it is an aeroplane. Things like that. So this mapping is done in this next cell. Alright, so let's keep moving. And then we have a helper code which will basically load the data or load the images and transform into NumPy arrays. This is also used in doing object detection in images. So we are actually going to reuse, because video is nothing but it consists of frames, which in turn are images. So we are going to pretty much reuse the same code which we used for doing object detection in images. So this is where the actual detection starts. So here, this is the path for where the images are stored. So this is, here once again we are reusing the code which we wrote for detecting objects in an image. So this is the path where the images were stored, and this is the extension, and this was done for about 2 or 3 images. So we will continue to use this, and if we go down, I'll skip this section. So this is the cell where we are actually loading the video and converting it into frames, and then using frame by frame we are detecting the objects in the image. So in this code, what we are doing basically is, there are a few lines of code. What they do is basically, once they find an object, a box will be drawn around those each of those objects, and the input file, the name of the input video file is traffic. It is the extension is MP4, and we have this video reader. It's an excellent object which is basically part of this class called image.io. So we can read and write videos using that, and the video that we are going to use is traffic.mp4. You can use any MP4 file, but in our case I picked up video which has like cars. So let me just show you. So this is in this object detection folder. I have this MP4 file. I'll just quickly play this video. It's a little slow. Yeah, okay. So here we go. This is the video. It's a short one, relatively small video, so that for this particular demo. And what it will do is, once we run our code, it will detect each of these cars and it will annotate them as cars. So in this particular video, we only have cars. We can later on see with another video. I think I have cat here, so we can also try with that. But let's first check with this traffic video. So let me go back. So we will be reading this frame by frame, and no, actually we will be reading the video file, but then we will be analyzing it frame by frame, and we will be reading them at 10 frames per second. That is the rate we are mentioning here, and analyzing it and then annotating and then writing it back. So you will see that we will have a video file named something like this, traffic_annotated, and we will see the annotated video. So let's go back and run through this piece of code, and then we will come back and see the annotated video. This might take a little while, so I will pause the video after running this particular cell and then come back to show you the results. Alright, so let's go ahead and run it. So it is running now, and it is also important that at the end you close the video writer, so that it is similar to a file pointer. When you open a file, you should also make sure you close it so that it doesn't hog the resources. So it's very similar. So at the end of it, the last piece or last line of code should be video_writer.close. Alright, so I'll pause and then I'll come back. Okay, so I will see you in a little bit. Alright, so now as you can see here, the processing is done. The hourglass has disappeared. That means the video has been processed. So let's go back and check the annotated video. I'll go back to my file manager. So this was the original traffic.mp4, and now you have here traffic_annotated mp4. So let's go and run this and see how it looks. You see here, it has got each of these cars are getting detected. Let me pause and show you. So we pause here. It says car 70%. Let us allow it to go a little further. It detects something on top. What is that? Truck. Okay. So I think because of the board on top, it somehow thinks there is a truck. Let's play it some more and see if it detects anything else. So this is again a car, looks like. So let us, yeah. So this is a car, and it has confidence level of 69%. Okay, this is again a car. Alright, so basically till the end it goes and detects each and every car that is passing by. Now we can quickly quickly repeat this process for another video. Let me just show you the other video, which is a cat. Again, there is this cat is not really moving or anything, but it is just standing there staring and moving a little slowly, and our network will detect that this is a cat, and even when the cat moves a little bit in the other direction, it will continue to detect and show that it is a cat. Okay, so yeah, so this is how the original video is. Let's go ahead and change our code to analyze this one and see if it detects, our network detects this cat. Close this, here we go, and I'll go back to my code. All we need to do is change this traffic to cat. The extension, it will automatically up because it is given here, and then it will run through. So very quickly, once again, what it is doing is this video underscore reader has a neat little feature or interface whereby you can say for frame in video underscore reader. So it will basically provide frame by frame. So you're in a loop frame by frame, and then you take that each frame that is given to you, you take it and analyze it as if it is an image, individual image. So that's the way it works. So it is very easy to handle this. Alright, so now let's once again run just this cell. The rest of the stuff remains the same. So I will run this cell. Again, it will take a little while, so the hourglasses come back. I will pause and then come back in a little while. Alright, so the processing is done. Let's go and check the annotated video. Go here. So we have cat annotated.mp4. Let's play this. Alright, so you can see here it is detecting the cat, and in the beginning you also saw it detected something else here. There looks like it detected one more object. So let's just go back and see what it has detected here. Let's see. Yes. So what is it trying to show here? It's too small, not able to see, but it is trying to detect something. I think it is saying it is a car. I don't know. Alright, okay, so in this video there's pretty much only one object, which is a cat, and let's wait for some time and see if it continues to detect it when the cat turns around and moves as well. Just in a little bit that's going to happen, and we will see. There we go. And in spite of turning the other way, I think our network is able to detect that it is a cat. So let me freeze and then show here it is actually still continues to detect it as a cat. Alright, so that's pretty much it. I think that's the only object that it detects in this particular video.
Convolution neural network tutorial. Do you know how deep learning recognizes the objects in an image? And really, this particular neural network is how image recognition works. It's very central, one of the biggest building blocks for image recognition. It does it using convolution neural network. And over here we have the basic picture of a hummingbird. Pixels of an image fed as input. You have your input layer coming in, so it takes that graphic and puts it into the input layer. You have all your hidden layers. And then you have your output layer, and your output layer, one of those is going to light up and say, oh, it's a bird. We're going to go into depth. We're going to actually go back and forth on this a number of times today. So if you're not catching all the image, don't worry, we're going to get into the details. So we have our input layer accepts the pixels of the image as input in the form of arrays. And you can see up here where they've actually labeled each block of the bird in different arrays. So we'll dive into deep as to how that looks like and how those matrices are set up. Your hidden layer carry out feature extraction by performing certain calculations and manipulations. So this is the part that kind of reorganizes that picture multiple ways until we get some data that's easy to read for the neural network. This layer uses a matrix filter and performs convolution operation to detect patterns in the image. And if you remember that convolution means to coil or to twist. So we're going to twist the data around and alter it and use that operation to detect a new pattern. There are multiple hidden layers like convolution layer. ReLU is how that is pronounced. And that's the rectified linear unit. That has to do with the activation function that's used. Pooling layer also uses multiple filters to detect edges, corners, eyes, feathers, beak, etc. And just like the term says, pooling is pooling information together. And we'll look into that a lot closer here. So if it's a little confusing now, we'll dig in deep and try to get you squared away with that. And then finally, there is a fully connected layer that identifies the object in the image. So we have these different layers coming through in the hidden layers, and they come into the final area, and that's where we have, say, one node or one neural network entity that lights up that says it's a bird. What's in it for you? We're going to cover an introduction to the CNN, what is convolution neural network, how CNN recognizes images. We're going to dig deeper into that and really look at the individual layers in the convolutional neural network. And finally, we do a use case implementation using the CNN. We'll begin our introduction to the CNN by introducing the pioneer of convolutional neural network, Yann LeCun. He was the director of Facebook AI Research Group. Built the first convolutional neural network called LeNet in 1988. So these have been around for a while and have had a chance to mature over the years. It was used for character recognition tasks like reading zip code digits. Imagine processing mail and automating that process. CNN is a feed-forward neural network that is generally used to analyze visual images by producing data with a grid-like topology. A CNN is also known as a convnet. And very key to this is we are looking at images. That was what this was designed for, and you'll see the different layers as we dig in mirror some of them are actually now used since we're using TensorFlow and Keras in our code later on. You'll see that some of those layers appear in a lot of your other neural network frameworks. But in this case, this is very central to processing images and doing so in a variety that captures multiple images and really drills down into their different features. In this example here you see flowers of two varieties, orchid and a rose. I think the orchid is much more dainty and beautiful, and the rose smells quite beautiful. I have a couple rose bushes in my yard. They go into the input layer. That data is then sent to all the different nodes in the next layer, one of the hidden layers, based on its different weights and its setup. It then comes out and gives those a new value. Those values then are multiplied by their weights and go to the next hidden layer, and so on. And then you have the output layer, and one of those nodes comes out and says it's an orchid, and the other one comes out and says it's a rose, depending on how well it was trained. What separates the CNN, or the convolutional neural network, from other neural networks is a convolutional operation. Forms the basis of any convolutional neural network. In a CNN, every image is represented in the form of arrays of pixel values. So here we have a real image of the digit 8. That then gets put onto its pixel values, represented in the form of an array. In this case, you have a two-dimensional array. And then you can see in the final end form, we transform the digit 8 into its representational form of pixels of zeros and ones, where the ones represent, in this case, the black part of the 8, and the zeros represent the white background. To understand the convolution neural network, or how that convolutional operation works, we're going to take a sidestep and look at matrices. In this case, we're going to simplify it. We're going to take two matrices, A and B, of one dimension. Now, kind of separate this from your thinking as we learn that you want to focus just on the matrix aspect of this. And then we'll bring that back together and see what that looks like when we put the pieces for the convolutional operation. Here we've set up two arrays. We have, in this case, they're a single dimension matrix. And we have A equals 5, 3, 7, 5, 9, 7. And we have B equals 1, 2, 3. So in the convolution, as it comes in there, it's going to look at these two, and we're going to start by multiplying them, A times B. And so we multiply the arrays element-wise, and we get 5, 6, 6, where 5 is the 5 times 1, 6 is 3 times 2, and then the other 6 is 2 times 3. And since the two arrays aren't the same size, they're not the same setup, we're going to just truncate the first one, and we're going to look at the second array multiplied just by the first three elements of the first array. Now that's going to be a little confusing. Remember, a computer gets to repeat these processes hundreds of times, so we're not going to just forget those other numbers later on. We'll bring those back in. And then we have the sum of the product. In this case, 5 plus 6 plus 6 equals 17. So in our A times B, our very first digit in that matrix of A times B is 17. And if you remember, I said we're not going to forget the other digits. So we now have 3, 2, 5. We move one set over, and we take 3, 2, 5, and we multiply that times B. And you'll see that 3 times 1 is 3, 2 times 2 is 4, and so on and so on. We sum it up, so now we have the second digit of our A times B product in the matrix. And we continue on with that same thing, so on and so on. So then we would go from 375 to 759 to 597. This short matrix that we have for A, we've now covered all the different entities in A that match 3 different levels of B. Now, in a little bit, we're going to cover where we use this math at, this multiplying of matrices and how that works. But it's important to understand that we're going through the matrix and multiplying the different parts to it to match the smaller matrix with the larger matrix. I know a lot of people get lost at is, what's going on here with these matrices? Ooh, scary math. Not really that scary when you break it down. We're looking at a section of A and we're comparing it to B. So when you break that down in your mind like that, you realize, okay, so I'm just taking these two matrices and comparing them, and I'm bringing the value down into one matrix, A times B. We're reducing that information in a way that will help the computer see different aspects. Let's go ahead and flip over again back to our images. Here we are back to our images. Talking about going to the most basic two-dimensional image you can get to. Consider the following two images. The image for the symbol backslash. When you press the backslash, the above image is processed. And you can see there for the image for the forward slash is the opposite. So when we click the forward slash button, that flips. Very basic. We have 4 pixels going in. Can't get any more basic than that. Here we have a little bit more complicated picture. We take a real image of a smiley face. Then we represent that in the form of black and white pixels. So if this was an image in the computer, it's black and white. And like we saw before, we convert this into the zeros and ones. So where the other one would have just been a matrix of just 4 dots, now we have a significantly larger image coming in. So don't worry, we're going to bring this all together here in just a little bit. Layers in convolutional neural network. When we're looking at this, we have our convolution layer. And that really is the central aspect of processing images in the convolutional neural network. That's why we have it. And then that's going to be feeding in. And you have your ReLU layer, which is, as we talked about, the rectified linear unit. We'll talk about that a little bit later. The ReLU is how that layer is activated, is the math behind it, what makes the neurons fire. You'll see that in a lot of other neural networks. When you're using it just by itself, it's for processing smaller amounts of data, where you use the atom activation feature for large data coming in. Now, because we're processing small amounts of data in each image, the ReLU layer works great. You have your pooling layer. That's where you're pooling the data together. Pooling is a neural network term. It's very commonly used. I like to use the term reduce. So if you're coming from the map and reduce side, you'll see that we're mapping all this data through all these networks, and then we're going to reduce it. We're going to pool it together. And then finally we have the fully connected layer. That's where our output's going to come out. So we have started to look at matrices. We've started to look at the convolutional layer and where it fits in and everything. We've taken a look at images. So we're going to focus more on the convolution layer, since this is a convolutional neural network. A convolution layer has a number of filters and perform convolution operation. Every image is considered as a matrix of pixel values. Consider the following 5x5 image whose pixel values are only 0 and 1. Now obviously when we're dealing with color, there's all kinds of things that come in on color processing, but we want to keep it simple and just keep it black and white. And so we have our image pixels, so we're sliding the filter matrix over the image and computing the dot product to detect the patterns. And right here, you're going to ask, where does this filter come from? This is a bit confusing because the filter is going to be derived later on. We build the filters when we program or train our model. So you don't need to worry what the filter actually is, but you do need to understand how a convolution layer works, is what is the filter doing. Filter, and you'll have many filters. You don't have just one filter. You'll have lots of filters that are going to look for different aspects. And so the filter might be looking for just edges. It might be looking for different parts. We'll cover that in a little bit more detail in a minute. Right now, we're just focusing on how the filter works as a matrix. Remember earlier we talked about multiplying matrices together? And here we have our two-dimensional matrix. And you can see we take the filter and we multiply it in the upper left image, and you can see right here 1 times 1, 1 times 0, 1 times 1. We multiply those all together, then sum them, and we end up with a convolved feature of 4. We're going to take that and sliding the filter matrix over the image and computing the dot product to detect patterns. So we're just going to slide this over. We're going to predict the first one and slide it over 1 notch, predict the second one, and so on all the way through until we have a new matrix. And this matrix, which is the same size as the filter, has reduced the image, and whatever filter, whatever that's filtering out, it's going to be looking at just those features reduced down to a smaller matrix. So once the feature maps are extracted, the next step is to move them to the ReLU layer. So the ReLU layer, the next step, first is going to perform an element-wise operation. So each of those maps coming in, if there's negative pixels, so it sets all the negative pixels to 0. And you can see this nice graph where it just zeroes out the negatives, and then you have a value that goes from 0 up to whatever value is coming out of the matrix. This introduces nonlinearity to the network. So up until now, we say linearity. We're talking about the fact that the feature has a value. So it's a linear feature. This feature came up and it has, let's say the feature is the edge of the beak. It's like, or that backslash that we saw. It'll look at that and say, okay, this feature has a value from -10 to 10 in this case. If it was 1, it'd say, yeah, this might be a beak. It might not. It might be an edge right there. A -5 means, no, we're not even going to look at it. It's a 0. And so we end up with an output, and the output takes all these filtered features. Remember, we're not just running one filter on this, we're running a number of filters on this image. And so we end up with a rectified feature map that is looking at just the features coming through and how they weigh in from our filters. So here we have an input of it looks like a toucan bird. Very exotic looking. Real image is scanned in multiple convolution and the ReLU layers for locating features. And you can see up here, it's turned it into a black and white image. And in this case, we're looking in the upper right-hand corner for a feature, and that box scans over. A lot of times it doesn't scan 1 pixel at a time. A lot of times it will skip by 2 or 3 or 4 pixels to speed up the process. That's one of the ways you can compensate if you don't have enough resources on your computation for large images. And it's not just one filter that slowly goes across the image. You have multiple filters that have been programmed in there. So you're looking at a lot of different filters going over the different aspects of the image and just sliding across there and forming a new matrix. One more aspect to note about the ReLU layer is we're not just having one ReLU coming in. So not only do we have multiple features going through, but we're generating multiple ReLU layers for locating the features. That's very important to note. So we have quite a bundle. We have multiple filters, multiple ReLU, which brings us to the next step, forward propagation. Now we're going to look at the pooling layer. The rectified feature map now goes through a pooling layer. Pooling is a downsampling operation that reduces the dimensionality of the feature map. That's all we're trying to do. We're trying to take a huge amount of information and reduce it down to a single answer. This is a specific kind of bird. This is an iris. This is a rose. So you have a rectified feature map. And you see here we have our rectified feature map coming in. We set the max pooling with a 2x2 filters and a stride of 2. And if you remember correctly, I talked about not going 1 pixel at a time. Well, that's where the stride comes in. We end up with a 2x2 pooled feature map, but instead of moving 1 over each time and looking at every possible combination, we skip a few there. We go by 2. We skip every other pixel. We just do every other one. And this reduces our rectified feature map, which as you can see over here, 16 by 16 to a 4 by 4. So we're continually trying to filter and reduce our data so that we can get to something we can manage. And over here you see that we have the max 3, 4, 1, and 2. And in the max pooling, we're looking for the max value. A little bit different than what we were looking at before. So coming from the rectified feature, we're now finding the max value and then we're pooling those features together. So instead of think of this as image of the map, think of this as how valuable is a feature in that area? How much of a feature value do we have? And we just want to find the best or the maximum feature for that area. They might have that one piece of the filter of the beak said, oh, I see a 1 in this beak in this image. And then it skips over and says, I see a 3 in this image. And it says, oh, this one is rated as a 4. We don't want to sum it together because then, you might have like 5 1s and it'll say 5, but you might have 4 zeros and 1 10, and that 10 says, well, this is definitely a beak, where the 1s will say probably not a beak. A little strange analogy since we're looking at a bird, but you can see how that pooled feature map comes down, and we're just looking for the max value in each one of those matrices. Pooling layer uses different filters to identify different parts of the image, like edges, corners, body, feathers, eyes, beak, etc. I know I focus mainly on the beak, but obviously each feature could be a different part of the bird coming in. So let's take a look at what that looks like. Structure of a convolution neural network so far. This is where we're at right now. we have our input image coming in, and then we use our filters, and there's multiple filters on there that are being developed to kind of twist and change that data. And so we multiply the matrices. We take that little filter, maybe it's a 2 by 2, we multiply it by each piece of the image. And if we step 2, then it's every other piece of the image. That generates multiple convolution layers. So we have a number of convolution layers we have set up in there that is looking at that data. We then take those convolution layers, we run them through the ReLU setup, and then once we've done through the ReLU setup, and we have multiple ReLUs going on, multiple layers that are ReLU, then we're going to take those multiple layers and we're going to be pooling them. So now we have the pooling layers, or multiple poolings going on. Up until this point, we're dealing with, sometimes it's multiple dimensions. You can have 3 dimensions. Some strange data setups that aren't doing images but looking at other things, they can have 4, 5, 6, 7 dimensions. So right now we're looking at 2D image dimensions coming into the pooling layer. So the next step is we want to reduce those dimensions, or flatten them. So flattening. Flattening is a process of converting all of the resultant 2-dimensional arrays from pooled feature map into a single long continuous linear vector. So over here you see where we have a pooled feature map. Maybe that's the bird wing, and it has values 6, 8, 4, 7. And we want to just flatten this out and turn it into 6, 8, 4, 7, or a single linear vector. And we find out that not only do we do each of the pooled feature maps, we do all of them into one long linear vector. So now we've gone through our convolutional neural network part, and we have the input layer into the next setup. All we've done is taken all those different pooling layers and we've flattened them out and combined them into a single linear vector going in. So after we've done the flattening, we have just a quick recap because we've covered so much, so it's important to go back and take a look at each of the steps we've gone through. The structure of the network so far is we have our convolution where we twist it and we filter it and multiply the matrices. We end up with our convolutional layer, which uses the ReLU to figure out the values going out into the pooling. As you have numerous convolution layers that then create numerous pooling layers, pooling that data together, which is the max value, which one we want to send forward. We want to send the best value. And then we're going to take all of that from each of the pooling layers and we're going to flatten it. And we're going to combine them into a single input going into the final layer. Once you get to that step, you might be looking at that going, boy, that looks like the normal input to most neural network. And you're correct, it is. So once we have the flattened matrix from the pooling layer, that becomes our input. So the pooling layer is fed as an input to the fully connected layer to classify the image. And so you can see as our flattened matrix comes in this case we have the pixels from the flattened matrix fed as an input back to our toucan, or whatever that kind of bird that is. I need one of these to identify what kind of bird that is. It comes into our forward propagation network. And that will then have the different weights coming down across. And then finally it selects that that's a bird and that it's not a dog or a cat in this case. Even though it's not labeled, the final layer there in red is our output layer, our final output layer that says bird, cat, or dog. So, quick recap of everything we've covered so far. We have our input image, which is twisted and multiplied. The filters are multiplied times the two matrices multiplied all the filters to create our convolution layer. Our convolution layers, there's multiple layers in there because it's all building multiple layers off the different filters. Then goes through the ReLU as its activation, and that creates our pooling. And so once we get into the pooling layer, we then on the pooling look for who's the best, what's the max value coming in from our convolution. And then we take that layer and we flatten it. And then it goes into a fully connected layer, our fully connected neural network, and then to the output. And here we can see the entire process, how the CNN recognizes a bird. This is kind of nice because it's showing the little pixels and where they're going. You can see the filter is generating this convolution network, and that filter shows up in the bottom part of the convolution network. And then based on that, it uses the ReLU for the pooling. The pooling then find out which one's the best, and so on, all the way to the fully connected layer at the end, or the classification in the output layer. So that'd be a classification neural network at the end. So we covered a lot of theory up till now, and you can imagine each one of these steps has to be broken down in code. So putting that together can be a little complicated. Not that each step of the process is overly complicated, but because we have so many steps. We have 1, 2, 3, 4, 5 different steps going on here with sub-steps in there. We're going to break that down and walk through that in code. So in our use case implementation using the CNN, we'll be using the CFAR10 dataset from Canadian Institute for Advanced Research for classifying images across 10 categories. Unfortunately, they don't let me know whether it's going to be a toucan or some other kind of bird, but we do get to find out whether it can categorize between a ship, a frog, deer, bird, airplane, automobile, cat, dog, horse, truck. So that's a lot of fun. And if you're looking anything in the news at all of our automated cars and everything else, you can see where this kind of processing is so important in today's world and very cutting edge as far as what's coming out in the commercial deployment. I mean, this is really cool stuff. We're starting to see this just about everywhere in industry. So a great time to be playing with this and figuring it all out. Let's go ahead and dive into the code and see what that looks like when we're actually writing our script. Before we go on, let's do one more quick look at what we have here. Let's just take a look at data batch 1 keys. And remember, in Jupyter Notebook, I can get by with not doing the print statement. If I put a variable down there, it'll just display the variable. And you can see under data batch 1 for the keys, since this is a dictionary, we have the batch 1 label, data, and file names. So you can actually see how it's broken up in our data set. So for the next step, or step 4 as we're calling it, we want to display the image using matplotlib. There's many ways to display the images. You could even, well, there's other ways to drill into it, but matplotlib is really good for this. And we'll also look at our first reshape setup, or shaping the data, so you can have a little glimpse into what that means. So we're going to start by importing our matplot, and of course, since I am doing Jupyter Notebook, I need to do the matplot inline command, so it shows up on my page. So here we go. We're going to import matplotlib.pyplot as PLT. And if you remember matplotlib, the pyplot is like a canvas that we paint stuff onto. And there's my %sign matplotlib inline, so it's going to show up in my notebook. And then of course we're going to import numpy as np for our numbers Python array setup. And let's go ahead and set x equals to data batch 1. So this will pull in all the data going into the x value. And then, because this is just a long stream of binary data, we need to go a little bit of reshaping. So in here we have to go ahead and reshape the data. We have 10,000 images. Okay, that looks correct. And this is kind of an interesting thing. It took me a little bit I had to go research this myself to figure out what's going on with this data. And what it is it's a 32 by 32 picture. And let me do this. Let me go ahead and do a drawing pad on here. So we have 32 bits by 32 bits, and it's in color. So there's 3 bits of color. Now, I don't know why the data is particularly like this. It probably has to do with how they originally encoded it. But most pictures put the 3 afterward. So what we're doing here is we're going to take the shape, we're going to take the data, which is just a long stream of information, and we're going to break it up into 10,000 pieces, and those 10,000 pieces then are broken into 3 pieces each, and those 3 pieces then are 32 by 32. You can look at this like an old-fashioned projector where they have the red screen, or the red projector, the blue projector, and the green projector, and they add them all together, and each one of those is a 32 by 32 bit. So that's probably how this was originally formatted, was in that kind of ideal. Things have changed, so we're going to transpose it, and we're going to take the 3, which was here, and we're going to put it at the end. So the first part is reshaping the data from a single line of bit data, or whatever format it is, into 10,000 by 3 by 32 by 32, and then we're going to transpose the color factor to the last place. So it's the image, then the 32 by 32 in the middle, that's this part right here, and then finally we're going to take this, which is 3 bits of data, and put it at the end. So it's more like we process images now. And then as type, this is really important that we're going to use an integer 8. You can come in here and you'll see a lot of these, they'll try to do this with a float or a float 64. What you got to remember though is a float uses a lot of memory. So once you switch this into something that's not integer 8, which goes up to 128, you are just going to, the amount of RAM, let me just put that in here, is going to go way up. The amount of RAM that it loads. So you want to go ahead and use this. You can try the other ones and see what happens if you have a lot of RAM on your computer. But for this exercise, this will work just fine. And let's go ahead and take that and run this. So now our X variable is all loaded and it has all the images in it from the batch 1, data batch 1. And just to show what we were talking about with the as type on there, if we go ahead and take X0 and just look for its max value, let me go ahead and run that. you'll see it doesn't, oops, I said 128, it's 255. You'll see it doesn't go over 255 because it's basically an ASCII character is what we're keeping that down to. We're keeping those values down. So they're only 255, 0 to 255 versus a float value, which would bring this up exponentially in size. And since we're using the matplot library, we can do, oops, that's not what I wanted. Since we're using the matplot library, we can take our canvas and just do a plt.im for image show, and let's just take a look at what x0 looks like. And it comes in, I'm not sure what that is, but you can see it's a very low grade image broken down to the minimal pixels on there. And if we did the same thing, let's see what 1 looks like. Hopefully it's a little easier to see. Run on there, not enter. Let's hit the run on that. And we can see this is probably a semi-truck. That's a good guess on there. And I can just go back up here instead of typing the same line in over and over. And we'll look at 3. That looks like a dump truck unloading, and so on. You can do any of the 10,000 images. We can just jump to 55. Looks like some kind of animal looking at us there, probably a dog. And just for fun, let's do just one more run on there, and we can see a nice car for our image number 4. So you can see we paste through all the different images, and it's very easy to look at them. And they've been reshaped to fit our view and what the matplot library uses for its format. So the next step is we're going to start creating some helper functions. We'll start by a one-hot encoder to help us when we're processing the data. Remember that your labels, they can't just be words. They have to switch it, and we use the one-hot encoder to do that. And then we'll also create a class CFAR helper, so it's going to have an init and a setup for the images. And then finally we'll go ahead and run that code so you can see what that looks like. And then we get into the fun part where we're actually going to start creating our model, our actual neural network model. So let's start by creating our one-hot encoder. We're going to create our own here, and it's going to return an out. And we'll have our vector coming in and our values equal 10. What this means is that we have the 10 values, the 10 possible labels. And remember, we don't look at the labels as a number, because a car isn't one more than a horse. That'd be just kind of bizarre to have horse equals 0, car equals 1, plane equals 2, cat equals 3. So a cat plus a car equals what? So instead, we create a numpy array of zeros. And there's going to be 10 values, so we have 10 different values in there. So you have 0 or 1. 1 means it's a cat, 0 means it's not a cat. In the next line it might be that 1 means it's a car, 0 means it's not a car. So instead of having one output with a value of 0 to 10, you have 10 outputs with the values of 0 to 1. That's what the one-hot encoder is doing here. And we're going to utilize this in code in just a minute. So let's go ahead and take a look at the next helpers. We have a few of these helper functions we're going to build. And when you're working with a very complicated Python project, dividing it up into separate definitions and classes is very important. Otherwise, it just becomes really ungainly to work with. So let's go ahead and put in our next helper, which is a class. And there's a lot in this class, so we'll break it down here. And let's just start, oops, we can put a space right in there. There we go. Now this is a little bit more readable. Add a second space. So we're going to create our class, the Cipher Helper. And we'll start by initializing it. Now, there's a lot going on in here. So let's start with the init part. Self.I equals 0. That'll come in a little bit. We'll come back to that in the lower part. We want to initialize our training batches. So when we went through this, there was like a meta batch. We don't need the meta batch, but we do need the data batch 1, 2, 3, 4, 5, and we do not want the testing batch in here. This is just the self-all train batches. So we're going to make an array of all those different images. And then, of course, we left the test batch out, so we have our self.test batch. We're going to initialize the training images and the training labels, and also the test images and the test labels. So this is just to initialize these variables in here. Then we create another definition down here, and this is going to set up the images. And let's just take a look and see what's going on in there. Now we could have all just put this as part of the init part, since this is all just helper stuff, but breaking it up again makes it easier to read. It also makes it easier when we start executing the different pieces to see what's going on. So that way we have a nice print statement to say, hey, we're now running this and this is what's going on in here. We're going to set up the self-training images at this point, and that's going to go to a numpy array vstack. And in there we're going to load up, in this case, the data for D and self all train batches. Again, that points right up to here. So we're going to go through each one of these files, or each one of these data sets, because they're not a file anymore. We've brought them in. Data batch 1 points to the actual data. And so our self-training images is going to stack them all into a NumPy array. And then it's always nice to get the training length, and that's just a total number of self-training images in there. And then we're going to take the self-training images. And let me switch marker colors, because I am getting a little too much on the markers up here. Oops, there we go. Bring down our marker change so we can see it a little better. And at this point, this should look familiar. Where did we see this? Well, when we wanted to look at this above, and we wanted to look at the images in the Matplot library, we had to reshape it. So we're doing the same thing here. We're taking our self-training images, and based on the training length, total number of images, because we stacked them all together, so now it's just one large file of images, we're going to take and look at it as our 3 video cameras that are each displaying 32 by 32, and we're going to switch that around so that now we have each of our images, that stays the same place, and then we have our 32 by 32, and then by our 3. Our 3 different values for the color. And of course, we want to go ahead and they run this where we say divide by 255. That was from earlier. It just brings all the data into 0 to 1. That's what this is doing. So we're turning this into a 0 to 1 array, which is all the pictures 32 by 32 by 3. And then we're going to take the self-training labels, and we're going to pump those through our one-hot encoder we just made, and we're going to stack them together. And again, we're converting this into an array that goes from, instead of having horse equals 1, dog equals 2, and then horse plus dog would equal 3, which would be cat. No, it's going to be an array of 10 where each one is 0 to 1. Then we want to go ahead and set up our test images and labels. And when we're doing this, you're going to see it's the same thing we just did with the rest of them. We just changed colors right here. This is no different than what we were doing up here with our training set. We're going to stack the different images. We're going to get the length of them so we know how many images are in there. You certainly could add them by hand, but it's nice to let the computer do it, especially if it ever changes on the other end and you're using other data. And again, we reshape them and transpose them, and we also do the one-hot encoder. Same thing we just did on our training images. So now our test images are in the same format. So now we have a definition which sets up all our images in there. And then the next step is to go ahead and batch them, or next batch. And let's do another breakout here for batches, because this is really important to understand. It tends to throw me for a little loop when I'm working with TensorFlow or Keras or a lot of these. We have our data coming in. If you remember, we had like 10,000 photos. Let me just put 10,000 down here. We don't want to run all 10,000 at once, so we want to break this up into batch sizes. And you also remember that we had the number of photos, in this case length of test or whatever number is in there. We also have 32 by 32 by 3. So when we're looking at the batch size, we want to change this from 10,000 to a batch of, in this case I think we're going to do batches of 100. So we want to look at just 100, the first 100 of the photos. And if you remember, we set self-I equal to 0. So what we're looking at here is we're going to create X. We're going to get the next batch from the very initialized. We've already initialized it for 0. So we're going to look at X from 0 to batch size, which we've set to 100. So just the first 100 images. And then we're going to reshape that into, and this is important to let the data know, that we're looking at 100 by 32 by 32 by 3. Now, we've already formatted it to the 32 by 32 by 3. This just sets everything up correctly so that X has the data in there in the correct order and the correct shape. And then the Y, just like the X, is our labels. So our training labels, again, they go from 0 to batch size. In this case, they do self-I plus batch size because the self-I is going to keep changing. And then finally, we increment the self-I because we have 0. So the next time we call it, we're going to get the next batch size. And so basically, we have X and Y. X being the photograph data coming in, and Y being the label. And that, of course, is labeled through one hot encoder. So if you remember correctly, if it was, say, horse is equal to 0, it would be 1 for the 0 position, since this is the horse, and then everything else would be 0 in here. Let me just put lines through there. There we go. There's our array. Hard to see that array. So let's go ahead and take that, and we're going to finish loading it, since this is our class. And now we're armed with all this, our setup over here. Let's go ahead and load that up. And so we're going to create a variable ch with the CFAR helper in it. And then we're going to do ch.setupImages. Now we could have just put all of the setup images under the init, but by breaking this up into two parts, it makes it much more readable. And also, if you're doing other work, there's reasons to do that as far as the setup. Let's go ahead and run that. And you can see where it says setting up training images and labels, setting up test images. And that's one of the reasons we broke it up, is so that if you're testing this out, you can actually have print statements in there telling you what's going on, which is really nice. They did a good job with this setup. I like the way that it was broken up in the back. And then one quick note, you want to remember that batch, to set up the next batch, says we have to run batch equals ch next batch of 100, because we're going to use the 100 size. But we'll come back to that. We're going to use that. Just remember that that's part of our code we're going to be using in a minute from the definition we just made. So now we're ready to create our model. First thing we want to do is we want to import our TensorFlow as TF. I'll just go ahead and run that so it's loaded up. And you can see we got a warning here. That's because they're making some changes. It's always growing, and they're going to be depreciating one of the values from float 64 to float type, or is treated as an NP float 64. Nothing to really worry about, because this doesn't even affect what we're working on, because we've set all of our stuff to a 255 value, or 0 to 1. And do keep in mind that 0 to 1 value that we converted to 255 is still a float value, but it'll easily work with either the NumPy float 64 or the NumPy D-type float. It doesn't matter which one it goes through, so the depreciation would not affect our code as we have it. And in our TensorFlow, we'll go ahead, let me just increase the size in there just a moment so you can get a better view of the what we're typing in. We're going to set a couple placeholders here. And so we're going to set x equals TF placeholder TF float 32. We just talked about the float 64 versus the NumPy float. We're actually just going to keep this at float 32. More than significant number of decimals for what we're working with. And since it's a placeholder, we're going to set the shape equal to, and we've set it equal to none, because at this point we're just holding the place on there. We'll be setting up as we run the batches, that's what that first value is. And then 32 by 32 by 3, that's what we reshaped our data to fit in. And then we have our y true equals placeholder TF float 32, and the shape equals none, comma 10. 10 is the 10 different labels we have, so it's an array of 10. And then let's create one more placeholder. We'll call this hold prob, or hold probability. And we're going to use this, we don't have to have a shape or anything for this. This placeholder is for what we call dropout. If you remember from our theory before, we drop out so many nodes it's looking at, or the different values going through, which helps decrease bias. So we need to go ahead and put a placeholder for that also. And we'll run this, so it's all loaded up in there. So we have our 3 different placeholders. And since we're in TensorFlow, when you use Keras, it does some of this automatically, but we're in TensorFlow direct. Keras sits on TensorFlow. We're going to go ahead and create some more helper functions. We're going to create something to help us initialize the weights, initialize our bias. If you remember that each layer has to have a bias going in. We're going to go ahead and work on our convolutional 2D, our max pool, so we have our pooling layer, our convolutional layer, and then our normal full layer. So we're going to go ahead and put those all into definitions, and let's see what that looks like in code. And you can also grab some of these helper functions from the MNIST, the NIST setup. We just put that in there if you're under the TensorFlow. So a lot of these are already in there, but we're going to go ahead and do our own. And we're going to create our init weights. And one of the reasons we're doing this is so that you can actually start thinking about what's going on in the back end. So even though there's ways to do this with an automation, sometimes these have to be tweaked and you have to put in your own setup in here. Now we're not going to be doing that. We're just going to recreate them for our code. And let's take a look at this. We have our weights, and so what comes in is going to be the shape, and what comes out is going to be random numbers. So we're going to go ahead and just init some random numbers based on the shape with a standard deviation of 0.1. Kind of a fun way to do that. And then the TF variable, init random distribution. So we're just creating a random distribution on there. That's all that is for the weights. Now, you might change that. You might have a higher standard deviation. In some cases, you actually load preset weights. That's pretty rare. usually you're testing that against another model or something like that, and you want to see how those weights configure with each other. Now remember, we have our bias, so we need to go ahead and initialize the bias with a constant. In this case, we're using 0.1. A lot of times the bias is just put in as 1, and then you have your weights to add on to that. But we're going to set this as 0.1. So we want to return a convolutional 2D, in this case a neural network. This is would be a layer on here. What's going on with the conv2D is we're taking our data coming in, we're going to filter it. Strides, if you remember correctly, strides came from, here's our image, and then we only look at this picture here, and then maybe we have a stride of 1, so we look at this picture here, and we continue to look at the different filters going on there. The other thing this does is that we have our data coming in as 32 by 32 by 3. And we want to change this so that it's just, this is 3 dimensions, and it's going to reformat this as just 2 dimensions. So it's going to take this number here and combine it with the 32 by 32. So this is a very important layer here because it's reducing our data down using different means. And it connects down, I'm just going to jump down one here. It goes with the convolutional layer. So you have your kind of your pre-formatting and the setup, and then you have your actual convolution layer that goes through on there. And you can see here we have init weights by the shape, init bias shape of 3, because we have the 3 different, here's our 3 again. And then we return the TFNN ReLU with the convention 2D, so this convolutional has this feeding into it. Right there, it's using that as part of it. And of course the input is the XY plus B, the bias. So that's quite a mouthful, but these two are the keys here to creating the convolutional layers there. The convolutional 2D coming in, and then the convolutional layer, which then steps through and creates all those filters we saw. Then of course we have our pooling. So after each time we run it through the conventional layer, we want to pool the data. If you remember correctly on the pool side, and let me just get rid of all my marks, it's getting a little crazy there. And in fact, let's go ahead and jump back to that slide. Let's just take a look at that slide over here. So we have our image coming in. We create our convolutional layer with all the filters. Remember, the filters go, the filters coming in here, and it looks at these 4 boxes, and then if it's a step, let's say step 2, it then goes to these 4 boxes, and then the next step, and so on. So we have our convolutional layer that we generate, or convolutional layers. They use the ReLU function. There's other functions out there. For this, though, the ReLU is the the one that works the best, at least so far. I'm sure that will change. And then we have our pooling. Now, if you remember correctly, the pooling was max. So if we had the filter coming in, and they did the multiplication on there, and we have a 1, and maybe a 2 here, and another 1 here, and a 3 here, 3 is the max. And so out of all of these, you then create an array that would be 3, and if the max is over here 2 or whatever it is, that's what goes into the pooling, and what's going on in our pooling. So again, we're reducing that data down. We're reducing it down as small as we can, and then finally we're going to flatten it out into a single array, and that goes into our fully connected layer. And you can see that here in the code. Right here we're going to create our normal full layer. So at some point we're going to take from our pooling layer, this will go into some kind of flattening process, and then that will be fed into the different layers going in down here. And so we have our input size. You'll see our input layer get shape, which is just going to get the shape for whatever's coming in. And then input size, initial weights is also based on the input layer coming in. And the input size down here is based on the input layer shape. So we're just going to already use the shape and already have our size coming in. And of course, you have to make sure you init the bias. Always put your bias on there. And we'll do that based on the size. So this will return tf.matmul input layer W plus B. This is just a normal full layer. That's what this means right down here. That's what we're going to return. So that was a lot of steps we went through. Let's go ahead and run that. So those are all loaded in there. And let's go ahead and create the layers. Let's see what that looks like. Now that we've done all the heavy lifting and everything, we get to do all the easy part. Let's go ahead and create our layers. We'll create a convolution layer 1 and 2 different convolutional layers, and then we'll take that and we'll flatten that out, create a reshape pooling in there for our reshape, and then we'll have our full layer at the end. So let's start by creating our first convolutional layer. Then we come in here, and let me just run that real quick. And I want you to notice on here the 3 and the 32. This is important because coming into this convolutional layer, we have 3 different channels and 32 pixels each. So that has to be in there. The 4 and 4 you can play with. This is your filter size. So if you remember, you have a filter and you have your image, and the filter slowly steps over and filters out this image depending on what your step is. For this particular setup, 4 is just fine. That should work pretty good for what we're doing and for the size of the image. And then of course at the end, once you have your convolutional layer set up, you also need to pool it, and you'll see that the pooling is automatically set up so that it would see the different shape based on what's coming in. So here we have max 2 by 2, and we put in the convolutional one that we just created. The convolutional layer we just created goes right back into it. And that right up here, as you can see, is the X. It's coming in from here, so it knows to look at the first model and set the data accordingly. Set that up so it matches. And we went ahead and ran this already. I think I ran it. Let me go and run it again. And if we're going to do one layer, let's go ahead and do a second layer down here. And it's we'll call it Convo 2. It's also a convolutional layer on this. And you'll see that we're feeding convolutional 1 in, the pooling. So it goes from convolutional 1 into convolutional 1 pooling, from convolutional 1 pooling into convolutional 2, and then from convolutional 2 into convolutional 2 pooling. And we'll go ahead and take this and run this. So these variables are all loaded into memory. And for our flattened layer, let's go ahead and we'll do, since we have 64 coming out of here and we have 4 by 4 going in, let's do 8 by 8 by 64. So let's do 4096. This is going to be the flat layer. So that's how many bits are coming through on the flat layer. And we'll reshape this. So we'll reshape our Convo 2 pooling, and that will feed into here, the Convo 2 pooling, and then we're going to set it up as a single layer that's 4096 in size. That's what that means there. We'll go ahead and run this. So we've now created this variable, the Convo 2 flat, and then we have our first full layer. This is the final neural network where we have the flat layer going in. And we're going to again use the ReLU for our setup on there in a neural network for evaluation. And you'll notice that we're going to create our first full layer. Our normal full layer, that's our definition. So we created that. That's creating the normal full layer. And our input for the data comes right here from this goes right into it. The Convo 2 flat. So this tells it how big the data is. And we're going to have it come out. It's going to have 1024. That's how big the layer is coming out. We'll go ahead and run this. So now we have our full layer 1. And with the full layer 1, we want to also define the full 1 dropout to go with that. So our full layer 1 comes in, keep probability equals hold probability. Remember we created that earlier. And the full layer 1 is what's coming into it. And this is going backwards and training the data. We're not training every weight. We're only training a percentage of them each time, which helps get rid of the bias. So let me go ahead and run that. And finally, we'll go ahead and create a Y-predict, which is going to equal the normal full 1 dropout and 10, because we have 10 labels in there. Now, in this neural network, we could have added additional layers. That would be another option to play with. You can also play with, instead of 1024, you can use other numbers for the way that sets up and what's coming out and going into the next one. We're only going to do just the 1 layer and the 1 layer dropout. And you can see if we did another layer, it'd be real easy just to feed in the full 1 dropout into full layer 2. And then full layer 2 dropout would have full layer 2 feed into it. And then you'd switch that here for the Y prediction. For right now, this is great. This particular data set is tried and true, and we know that this will work on it. And if we just type in Y predict and we run that, we'll see that this is a tensor object, shape $10, D-type 32. A quick way to double check what we're working on. So now we've got all of our, we've done a setup all the way to the Y predict, which we just did. We want to go ahead and apply the loss function and make sure that's set up in there. Create the optimizer. And then train our optimizer and create a variable to initialize all the global TF variables. So before we dive into the loss function, let me point out one quick thing, or just kind of a rehab over a couple things. And that is, when we're playing with these setups, we pointed out up here we can change the 4-4 and use different numbers there, they change your outcome. So depending on what numbers you use here will have a huge impact on how well your model fits. And that's the same here with the 1024 also. This is also another number that if you continue to raise that number, you'll get possibly a better fit. You might overfit. And if you lower that number, you'll use less resources. And generally, you want to use this in the exponential growth. An exponential being 2, 4, 8, 16. And in this case, the next one down would be 5, 12. You can use any number there, but those would be the ideal numbers when you look at this data. So the next step in all this is we need to also create a way of tracking how good our model is. And we're going to call this a loss function. And so we're going to create a cross-entropy loss function. And so before we discuss exactly what that is, let's take a look and see what we're feeding it. We're going to feed it our labels, and we have our true labels and our prediction labels. So coming in here is the two different variables we're sending in, or the two different probability distributions, is one that we know is true and what we think it's going to be. Now this function right here, when they talk about cross-entropy, in information theory, the cross-entropy between two probability distributions over the same underlying set of events measures the average number of bits needed to identify an event drawn from the set. That's a mouthful. Really, we're just looking at the amount of error in here. How many of these are correct and how many of these are incorrect? So how much of it matches? And we're going to look at that. We're just going to look at the average. That's what the mean, the reduced to the mean means here. So we're looking at the average error on this. And so the next step is we're going to take the error. We want to know our cross entropy, or our loss function, how much loss we have. That's going to be part of how we train the model. So when you know what the loss is and we're training it, you feed that back into the back propagation setup. And so we want to go ahead and optimize that. Here's our optimizer. We're going to create the optimizer using an atom optimizer. Remember, there's a lot of different ways of optimizing the data. Atom's the most popular used. So our optimizer is going to equal the TF train atom optimizer. If you don't remember what the learning rate is, let me just pop this back into here. Here's our learning rate. When you have your weights, you have all your weights in your different nodes that are coming out. Here's our node coming out, and it has all its weights. And then the error is being sent back through in reverse on our neural network. So we take this error and we adjust these weights based on the different formulas. In this case, the atom formula is what we're using. We don't want to just adjust them completely. We don't want to change this weight so it exactly fits the data coming through. Because if we made that kind of adjustment, it's going to be biased to whatever the last data we sent through is. Instead, we're going to multiply that by 0.001 and make a very small shift in this weight. So our delta W is only 0.001 of the actual delta W of the full change we're going to compute from the atom. And then we want to go ahead and train it. So our training, or set up a training variable or function. And this is going to equal our optimizer minimize cross entropy. And we make sure we go ahead and run this. So it's loaded in there. And then we're almost ready to train our model. But before we do that, we need to create one more variable in here. And we're going to create a variable to initialize all the global TF variables. And when we look at this, the TF global variable initializer, this is a TensorFlow object. It goes through there and it looks at all our different setup that we have going under our TensorFlow and then initializes those variables. So it's kind of like a magic wand because it's all hidden in the back end of TensorFlow. All you need to know about this is that you have to have the initialization on there, which is an operation, and you have to run that once you have your setup going. So we'll go ahead and run this piece of code, and then we're going to go ahead and train our data. So let me run this so it's loaded up there. And so now we're going to go ahead and run the model by creating a graph session. Graph session is a TensorFlow term. So you'll see that coming up. It's one of the things that throws me because I always think of GraphX and Spark and graph as just general graphing. But they talk about a graph session. So we're going to go ahead and run the model. And let's go ahead and walk through this, what's going on here. And let's paste this data in here. And here we go. So we're going to start off with a TF session as ses. So that's our actual TF session that we've created. So we're right here with the TF session. Our session we're creating, we're going to run TF global variable initializer. So right off the bat, we're initializing our variables here. And then we have for I in range 500. So what's going on here, remember 500, we're going to break the data up and we're going to batch it in at 500 points each. We've created our session run. So we're going to do with TF session as session right here. We've created our variable session. And then we're going to run and we're going to go ahead and initialize it. So we have our TF global variables initializer that we created. That initializes our session in here. The next thing we're going to do is we're going to go for I in range of 500, batch equals ch.next batch. So if you remember correctly, this is loading up 100 pictures at a time. And this is going to loop through that 500 times. So we are literally doing, what is that? 500 times 100 is 50,000. So that's 50,000 pictures we're going to process right there. In the first process is we're going to do a session run. We're going to take our train. We created our train variable or our optimizer in there. We're going to feed it the dictionary. We had our feed dictionary that we created. And we have x equals batch 0 coming in, y true, batch 1, hold the probability, 0.5. And then just so that we can keep track of what's going on, we're going to, every 100 steps, we're going to run a print. So currently on step, format, accuracy is, and we're going to look at matches equals tf.equal tf argument y prediction 1, tf.arg max y true, comma 1. So we're going to look at this as how many matches it has. And here our ACC, all we're doing here is we're going to take the matches, how many matches they have, it generates a chart. We're going to convert that to float. That's what the tfcast does. And then we just want to know the average. We just want to know the average of the accuracy. And then we'll go ahead and print that out, print session run accuracy feed dictionary. So it takes all this and it prints out our accuracy on there. So let's go ahead and take this. Oops, flip screens there. Let's go ahead and take this and let's run it. And this is going to take a little bit to run. So let's see what happens on my old laptop. And we'll see here that we have our current, we're currently on step 0. It takes a little bit to get through the accuracy. And this will take just a moment to run. We can see that on our step 0 it has an accuracy of 0.1 or 0.1028. And as it's running, we'll go ahead, you don't need to watch it run all the way, but this accuracy is going to change a little bit up and down. So we've actually lost some accuracy during our step 2. But we'll see how that comes out. Let's come back after we run it all the way through and see how the different steps come out. I was actually reading that backwards. The way this works is the closer we get to 1, the more accuracy we have. So you can see here we've gone from a 0.1 to a 0.39, and we'll go ahead and pause this and come back and see what happens when we're done with the full run. Alright, now that we've prepared the meal, got it in the oven, and pulled out my finished dish here, if you've ever watched any of the old cooking shows, let's discuss a little bit about this accuracy going on here, and how do you interpret that? We've done a couple things. First, we've defined accuracy. The reason I got it backwards before is you have loss or accuracy. And with loss, you'll get a graph that looks like this. It goes, oops, that's an S, by the way. There we go. You get a graph that curves down like this. And with accuracy, you get a graph that curves up. This is how good it's doing. Now, in this case, 1 is supposed to be really good accuracy. That means it gets close to 1, but it never crosses 1. So if you have an accuracy of 1, that is phenomenal. In fact, that's pretty much unheard of. And the same thing with loss. If you have a loss of 0, that's also unheard of. And the 0 is actually on this axis right here as we go in there. So how do we interpret that? Because, if I was looking at this and I go, oh, 0.51, that's 51%. You're doing 50-50. No, this is not percentage. Let me just put that in there. It is not percentage. This is logarithmic. What that means is that 0.2 is twice as good as 0.1. And when we see 0.4, that's twice as good as 0.2. Real way to convert this into a percentage. You really can't say this is a direct percentage conversion. What you can do, though, is in your head, if we were to give this a percentage, we might look at this as 50%, we're just guessing, equals 0.1. And if 50% roughly equals 0.1, that's where we started up here at the top. Remember at the top here, here's our 0.1028. The accuracy of 50%, then 75% is about 0.2, and so on and so on. Don't quote those numbers because that doesn't work that way. They say that if you have 0.95, that's pretty much saying 100%. And if you have anywhere between, you'd have to go look this up. Let me go ahead and remove all my drawings there. So the magic number is 0.5. We really want to be over a 0.5 in this whole thing. And we have both 0.5004. Remember, this is accuracy. If we were looking at loss, then we would be looking the other way. But 0.05, instead of how high it is, we want how low it is. But with accuracy, being over a 0.5 is pretty valid. That means this is pretty solid. And if you get to a 0.95, then it's a direct correlation. That's what we're looking for here in these numbers. And you can see we finished with this model at 0.5135, so still good. And if we look at when they ran this in the other end, remember there's a lot of randomness that goes into it when we seed the weights. They got 0.5251, so a little better than ours. But that's fine. You'll find your own comes up a little bit better or worse depending on just that randomness. And so we've gone through the whole model. We trained the model, and we've also gone through on every 100th run to test the model to see how accurate it is. Welcome to the RNN tutorial. That's the recurrent neural network. So we talk about a feed-forward neural network. In a feed-forward neural network, information flows only in the forward direction, from the input nodes through the hidden layers, if any, and to the output nodes. There are no cycles or loops in the network. And so you can see here we have our input layer. I was talking about how it just goes straight forward into the hidden layers. So each one of those connects and then connects to the next hidden layer, connects to the output layer. And of course we have a nice simplified version where it has a predicted output, and they refer to the input as X a lot of times and the output as Y. Decisions are based on current input, no memory about the past, no future scope. Why recurrent neural network? Issues in feed-forward neural network. So one of the biggest issues is because it doesn't have a scope of memory or time, a feed-forward neural network doesn't know how to handle sequential data. It only considers the current input. So if you have a series of things, and because 3 points back affects what's happening now, and what your output affects what's happening, that's very important. So whatever I put as an output is going to affect the next one. A feed-forward doesn't look at any of that. It just looks at this is what's coming in. And it cannot memorize previous inputs. So it doesn't have that list of inputs coming in. Solution to feed-forward neural network. You'll see here where it says recurrent neural network, and we have our X on the bottom going to H, going to Y. That's your feed forward. But right in the middle it has a value C, so there's a whole other process. So it's memorizing what's going on in the hidden layers, and the hidden layers, as they produce data, feed into the next one. So your hidden layer might have an output that goes off to Y, but that output goes back into the next prediction coming in. What this does is this allows it to handle sequential data. It considers the current input and also the previously received inputs. And if we're going to look at general drawings and solutions, we should also look at applications of the RNN. Image captioning. RNN is used to caption an image by analyzing the activities present in it. A dog catching a ball in midair. That's very tough. I mean, we have a lot of stuff that analyzes images of a dog and the image of a ball, but it's able to add one more feature in there that's actually catching the ball in midair. Time series prediction. Any time series problem like predicting the prices of stocks in a particular month can be solved using RNN. And we'll dive into that in our use case and actually take a look at some stock. One of the things you should know about analyzing stock today is that it is very difficult. And if you're analyzing the whole stock, the stock market at the New York Stock Exchange in the U.S. produces somewhere in the neighborhood, if you count all the individual trades and fluctuations by the second, it's like 3 terabytes a day of data. So we're only going to look at one stock. Just analyzing one stock is really tricky. In here, we'll give you a little jump on that, so that's exciting, but don't expect to get rich off of it immediately. Another application of the RNN is natural language processing. Text mining and sentiment analysis can be carried out using RNN for natural language processing. And you can see right here the term natural language processing, when you stream those 3 words together, is very different than if I said processing language naturally. So the time series is very important when we're analyzing sentiments. It can change the whole value of a sentence just by switching the words around. Or if you're just counting the words, you might get one sentiment where if you actually look at the order they're in, you get a completely different sentiment. When it rains, look for rainbows. When it's dark, look for stars. Both of these are positive sentiments, and they're based upon the order of which the sentence is going in. Machine translation. Given an input in one language, RNN can be used to translate the input into a different languages as output. I myself am very linguistically challenged. But if you study languages and you're good with languages, you know right away that if you're speaking English, you would say big cat. And if you're speaking Spanish, you would say cat big. So that translation is really important to get the right order, to get, there's all kinds of parts of speech that are important to know by the order of the words. Here this person is speaking in English and getting translated. And you can see here a person is speaking in English in this little diagram. I guess that's denoted by the flags. I have a flag. I own it. No. But they're speaking in English and it's getting translated into Chinese, Italian, French, German, and Spanish languages. Some of the tools coming out are just so cool. So somebody like myself who's very linguistically challenged, I can now travel into worlds I would never think of, because I can have something translate my English back and forth readily, and I'm not stuck with a communication gap. So let's dive into what is a recurrent neural network. Recurrent neural network works on the principle of saving the output of a layer and feeding this back to the input in order to predict the output of the layer. Sounds a little confusing. When we start breaking it down, it'll make more sense. And usually we have a propagation forward neural network with the input layers, the hidden layers, the output layer. With the recurrent neural network, we turn that on its side. So here it is, and now our X comes up from the bottom into the hidden layers into Y, and they usually draw it very simplified, X to H, with C as a loop, A to Y, where A, B, and C are the perimeters. A lot of times you'll see this kind of drawing in here, digging closer and closer into the H and how it works. Going from left to right, you'll see that the C goes in, and then the X goes in. So the X is going upward bound, and C is going to the right. A is going out. And C is also going out. That's where it gets a little confusing. So here we have X in, C in, and then we have Y out and C out. And C is based on HT minus 1. So our value is based on the Y and the H value are connected to each other. They're not necessarily the same value because H can be its own thing. And usually we draw this, or we represent it as a function. H of T equals a function of C, where H of T minus 1, that's the last H output, and X of T going in. So it's the last output of H combined with the new input of X, where HT is the new state, FC is a function with the parameters C, that's a common way of denoting it, HT minus 1 is the old state coming out, and then X of T is an input vector at time of step T. Well, we need to cover types of recurrent neural networks. And so the first one is the most common one, which is a one-to-one single output. One-to-one neural network is usually known as a vanilla neural network, used for regular machine learning problems. Why? Because vanilla is usually considered kind of just a real basic flavor. But because it's very basic, a lot of times they'll call it the vanilla neural network, which is not the common term, but it is, like kind of a slang term. People will know what you're talking about usually if you say that. Then we run one to many, so you have a single input, and you might have multiple outputs. In this case, image captioning, as we looked at earlier, where we have not just looking at it as a dog, but a dog catching a ball in the air. And then you have many-to-one network, takes in a sequence of inputs. Examples, sentiment analysis, where a given sentence can be classified as expressing positive or negative sentiments. And we looked at that as we were discussing, if it rains, look for a rainbow. So positive sentiment, where rain might be a negative sentiment if you were just adding up the words in there. And then, of course, if you're going to do a one-to-one, many-to-one, one-to-many, there's many-to-many networks, takes in a sequence of inputs and generates a sequence of outputs. Example, machine translation. So we have a lengthy sentence coming in English and then going out in all the different languages. Just a wonderful tool. Very complicated set of computations. If you're a translator, you realize just how difficult it is to translate into different languages. One of the biggest things you need to understand when we're working with this neural network is what's called the vanishing gradient problem. While training an RNN, your slope can be either too small or very large, and this makes training difficult. When the slope is too small, the problem is known as vanishing gradient. And you'll see here they have a nice image, loss of information through time. So if you're pushing not enough information forward, that information is lost, and then when you go to train it, you start losing the third word in the sentence or something like that, or it doesn't quite follow the full logic of what you're working on. Exploding gradient problem. Oh, this is one that runs into everybody. When you're working with this particular neural network, when the slope tends to grow exponentially instead of decaying, this problem is called exploding gradient. Issues in gradient problem: long training time, poor performance, bad accuracy. And I'll add one more in there. Your computer, if you're on a lower end computer testing out a model, will lock up and give you the memory error. Explaining gradient problem. Consider the following two examples to understand what should be the next word in the sequence. The person who took my bike and blank, a thief. The students who got into engineering with blank from Asia. And you can see in here we have our x value going in, we have the previous value going forward, and then you back propagate the error like you do with any neural network. And as we're looking for that missing word, maybe we'll have the person took my bike and blank was a thief, and the student who got into engineering with a blank were from Asia. Consider the following example, the person who took the bike, so we'll go back to the person who took the bike was blank a thief. In order to understand what would be the next word in the sequence, the RNN must memorize the previous context, whether the subject was singular noun or a plural noun. So, was a thief is singular. The student who got into engineering, well, in order to understand what would be the next word in the sequence, the RNN must memorize the previous context, whether the subject was singular noun or a plural noun. And so you can see here the students who got into engineering with blank were from Asia. It might be sometimes difficult for the error to back propagate to the beginning of the sequence to predict what should be the output. So when you run into the gradient problem, we need a solution, the solution to the gradient problem. First, we're going to look at exploding gradient, where we have three different solutions depending on what's going on. One is identity initialization. So the first thing we want to do is see if we can find a way to minimize the identities coming in instead of having it identify everything, just the important information we're looking at. Next is to truncate the back propagation. So instead of having whatever information it's sending to the next series, we can truncate what it's sending. We can lower that particular set of layers, make those smaller. And finally is a gradient clipping. So when we're training it, we can clip what that gradient looks like and narrow the training model that we're using. When you have a vanishing gradient, the option problem, we can take a look at weight initialization, very similar to the identity, but we're going to add more weights in there so it can identify different aspects of what's coming in better. Choosing the right activation function. That's huge. So we might be activating based on one thing and we need to limit that. We haven't talked too much about activation functions, so we'll look at that just minimally. There's a lot of choices out there. And then finally there's long short-term memory networks, the LSTMS. And we can make adjustments to that. So just like we can clip the gradient as it comes out, we can also expand on that. We can increase the memory network, the size of it, so it handles more information. And one of the most common problems in today's setup is what they call long-term dependencies. Suppose we try to predict the last word in the text. The clouds are in the, and you probably said sky. Here we do not need any further context. It's pretty clear that the last word is going to be sky. Suppose we try to predict the last word in the text. I have been staying in Spain for the last 10 years. I can speak fluent. Maybe you said Portuguese or French. No, you probably said Spanish. The word we predict will depend on the previous few words in context. Here we need the context of Spain to predict the last word in the text. It's possible that the gap between the relevant information and the point where it is needed to become very large. LSTMs help us solve this problem. So the LSTMs are a special kind of recurrent neural network capable of learning long-term dependencies. Remembering information for long periods of time is their default behavior. All recurrent neural networks have the form of a chain of repeating modules, of neural network connections. In standard RNNs, this repeating module will have a very simple structure such as a single tangent H layer. LSTMSs also have a chain-like structure, but the repeating module has a different structure. Instead of having a single neural network layer, there are 4 interacting layers communicating in a very special way. LSTMS are a special kind of recurrent neural network, capable of learning long-term dependencies. Remembering information for long periods of time is their default behavior. LSTMSs also have a chain-like structure, but the repeating module has a different structure. Instead of having a single neural network layer, there are 4 interacting layers communicating in a very special way. As you can see, the deeper we dig into this, the more complicated the graphs get. In here, I want you to note that you have x at t minus 1 coming in, you have x at t coming in, and you have x at t plus 1. And you have h at t minus 1, and h at t coming in, and h at t plus 1 going out. And of course, on the other side is the output A. In the middle, we have our tangent H, but it occurs in 2 different places. So not only when we're computing the x at t plus 1 are we getting the tangent H from x at t, but we're also getting that value coming in from the x at t minus 1. So the short of it is that as you look at these layers, not only does the propagate through the first layer goes into the second layer and back into itself, but it's also going into the third layer. So now we're kind of stacking those up. And this can get very complicated as you grow that in size. It also grows in memory too, and in the amount of resources it takes. But it's a very powerful tool to help us address the problem of complicated, long sequential information coming in, like we were just looking at in the sentence. And when we're looking at our long, short-term memory network, there's 3 steps of processing in the LSTMS that we look at. The first one is we want to forget irrelevant parts of the previous state. A lot of times, like, is, as, in, a, unless we're trying to look at whether it's a plural noun or not, they don't really play a huge part in the language, so we want to get rid of them. Then selectively update cell state values. So we only want to update the cell state values that reflect what we're working on. And finally, we want to only output certain parts of the cell state. So whatever's coming out, we want to limit what's going out too. And let's dig a little deeper into this. Let's just see what this really looks like. So step 1 decides how much of the past it should remember. First step in the LSTM is to decide which information to be omitted from the cell in that particular time step. It is decided by the sigmoid function. It looks at the previous state, h at t minus 1, and the current input, x at t, and computes the function. So you can see over here we have a function of t equals the sigmoid function of the weight of f, the h at t minus 1, and then x at t, plus, of course, you have a bias in there with any of our neural networks, so we have a bias function. So f at t equals forget gate, decides which information to delete that is not important from the previous time step. Considering an LSTM is fed with the following inputs from the previous and present time step. Alice is good in physics. John, on the other hand, is good in chemistry. So, previous output. John plays football well. He told me yesterday over the phone that he had served as a captain of his college football team. That's our current input. So as we look at this, the first step is the forget gate realizes there might be a change in context after encountering the first full stop. Compares with the current input sentence of x at t. So we're looking at that full stop and then compares it with the input of the new sentence. The next sentence talks about John, so the information on Alice is deleted. Okay, that's important to know. So we have this input coming in, and if we're going to continue on with John, then that's going to be the primary information we're looking at. The position of the subject is vacated and is assigned to John. And so in this one, we've seen that we've weeded out a whole bunch of information, and we're only passing information on John, since that's now the new topic. So step 2 is then to decide how much should this unit add to the current state. In the second layer, there are 2 parts. One is the sigmoid function, and the other is the tangent h. In the sigmoid function, it decides which values to let through, 0 or 1. Tangent h function gives the weightage to the values which are passed, deciding their level of importance, -1 to 1. And you can see the 2 formulas that come up. The I of t equals the sigmoid of the weight of I, h at t minus 1, x at t plus the bias of I. And the c of t equals the tangent of h of the weight of c of h at t minus 1, x at t plus the bias of c. So our I of t equals the input gate, determines which information to let through based on its significance in the current time step. If this seems a little complicated, don't worry, because a lot of the programming is already done when we get to the case study. Understanding, though, that this is part of the program is important when you're trying to figure out what to set your settings at. You should also note when you're looking at this, it should have some semblance to your forward propagation neural networks, where we have a value assigned to a weight plus a bias. Very important steps in any of the neural network layers, whether we're propagating into the information from one to the next, or we're just doing a straightforward neural network propagation. Let's take a quick look at this, what it looks like from the human standpoint, as I step out of my suit again. Consider the current input at x of t. John plays football well. He told me yesterday over the phone that he had served as a captain of his college football team. That's our input. Input gate analyzes the important information. John plays football and he was a captain of his college team is important. He told me over the phone yesterday is less important, hence it is forgotten. This process of adding some new information can be done via the input gate. Now this example is as a human form, and we'll look at training this stuff in just a minute. But as a human being, if I wanted to get this information from a conversation, maybe it's a Google Voice listening in on you or something like that, how do we weed out the information that he was talking to me on the phone yesterday? Well, I don't want to memorize that he talked to me on the phone yesterday, or maybe that is important. But in this case, it's not. I want to know that he was the captain of the football team. I want to know that he served. I want to know that John plays football and he was the captain of the college football team. Those are the two things that I want to take away as a human being. Again, we measure a lot of this from the human viewpoint, and that's also how we try to train them so we can understand these neural networks. Finally, we get to step 3, decides what part of the current cell state makes it to the output. The third step is to decide what will be our output. First, we run a sigmoid layer, which decides what parts of the cell state make it to the output. Then we put the cell state through the tangent h to push the values to be between -1 and 1, and multiply it by the output of the sigmoid gate. So when we talk about the output of t, we set that equal to the sigmoid of the weight of 0 of the h of t minus 1, back one step in time, by the x of t, plus of course the bias. The h of t equals the out of t times the tangent h of c of t. So our O of t equals the output gate, allows the passed in information to impact the output in the current time step. Let's consider the example to predicting the next word in the sentence. John played tremendously well against the opponent and won for his team. For his contributions, Brave blank was awarded player of the match. There are going to be a lot of choices for the empty space. Current input, Brave, is an adjective. Adjectives describe a noun. John could be the best output after Brave. Thumbs up for John, awarded player of the match. And if you were to pull just the nouns out of the sentence, team doesn't look right because that's not really the subject we're talking about. Contributions, brave contributions, or brave team, brave player, brave match, size in there. This, and you can start to train this neural network so it starts looking at it and goes, oh no, John is what we're talking about. So brave is an adjective, John's going to be the best output. And we give John a big thumbs up. And then of course we jump into my favorite part, a case study. Use case implementation of LSTM. Let's predict the prices of stocks using the LSTM network based on the stock price data between 2012 and 2016. We're going to try to predict the stock prices of 2017. And this will be a narrow set of data. We're not going to do the whole stock market. It turns out that the New York Stock Exchange generates roughly 3 terabytes of data per day. That's all the different trades up and down of all the different stocks going on. And each individual one second to second or nanosecond to nanosecond. But we're going to limit that to just some very basic fundamental information. So don't think you're going to get rich off this today. But at least you can give a step forward in how to start processing something like stock prices, a very valid use for machine learning in today's markets. Use case implementation of LSTM. Let's dive in. We're going to import our libraries, we're going to import the training set, and get the scaling going. Now, if you watch any of our other tutorials, a lot of these pieces just start to look very familiar because it's a very similar setup. But let's take a look at that. And just a reminder, we're going to be using Anaconda, the Jupyter Notebook. So here I have my Anaconda navigator. When we go under environments, I've actually set up a Keras Python 3.6. I'm in our Comp 6. And nice thing about Anaconda, especially the newer version, I remember a year ago messing with Anaconda in different versions of Python in different environments. Anaconda now has a nice interface. And I have this installed both on a Ubuntu Linux machine and on Windows, so it works fine on there. You can go in here and open a terminal window, and then in here, once you're in the terminal window, this is where you're going to start installing using pip to install your different modules and everything. Now we've already pre-installed them, so we don't need to do that in here. But if you don't have them installed in your particular environment, you'll need to do that. And of course, you don't need to use the Anaconda or the Jupyter. You can use whatever favorite Python IDE you like. I'm just a big fan of this because it keeps all my stuff separate. You can see on this machine I have specifically installed one for Keras, since we're going to be working with Keras under TensorFlow. When we go back to home, I've gone up here to application, and that's the environment I've loaded on here, and then we'll click on the Launch Jupyter Notebook. Now I've already, in my Jupyter Notebook, have set up a lot of stuff so that we're ready to go. Kind of like Martha Stewart's in the old cooking shows. We want to make sure we have all our tools for you so you're not waiting for them to load. And if we go up here to where it says New, you can see where you can create a new Python 3. That's what we did here underneath the setup, so it already has all the modules installed on it. And I'm actually renamed this. If you go under File, you can rename it. I'm calling it RNN Stock. And let's just take a look at start diving into the code. Let's get into the exciting part. Now we've looked at the tool, and of course you might be using a different tool, which is fine. Let's start putting that code in there and seeing what those imports and uploading everything looks like. Now, the first half is kind of boring when we hit the Run button, because we're going to be importing NumPy as NP. That's the number Python, which is your NumPy array, and the matplot library, because we're going to do some plotting at the end, and our pandas for our data set. Our pandas is PD. And when I hit run, it really doesn't do anything except for load those modules. Just a quick note, let me just do a quick draw here. Oops, Shift-Alt, there we go. You'll notice when we're doing this setup, if I was to divide this up, oops, I'm going to actually, let's overlap these, here we go. This first part that we're going to do is our data prep. A lot of prepping involved. In fact, depending on what your system is, since we're using Keras, I put an overlap here, but you'll find that almost maybe even half of the code we do is all about the data prep. And the reason I overlap this with Keras, let me just put that down because that's what we're working in, is because Keras has like their own preset stuff, so it's already pre-built in, which is really nice. So there's a couple steps a lot of times that are in the Keras setup. We'll take a look at that to see what comes up in our code as we go through and look at stock. And then the last part is to evaluate. And if you're working with shareholders or classroom, whatever it is you're working with, the evaluate is the next biggest piece. So the actual code here, Keras is a little bit more, but when you're working with some of the other packages, you might have like 3 lines. That might be it. All your stuff is in your pre-processing and your data. Since Keras is cutting edge and you load the individual layers, you'll see that there's a few more lines here and Keras is a little bit more robust. And then you spend a lot of times, like I said, with the evaluate, you want to have something you present to everybody else and say, hey, this is what I did, this is what it looks like. So let's go through those steps. This is like a kind of just general overview. And let's just take a look and see what the next set of code looks like. And in here we have a dataset train, and it's going to be read using the PD, or pandas, .readcsv, and it's the Google stock price train.csv. And so under this we have training set equals dataset train.ilocation, and we've kind of sorted out part of that. So what's going on here? Let's just take a look at let's look at the actual file and see what's going on there. Now if we look at this, ignore all the extra files on this, I already have a train and a test set where it's sorted out. This is important to notice because a lot of times we do that as part of the pre-processing of the data. We take 20% of the data out so we can test it, and then we train the rest of it. That's what we use to create our neural network. That way we can find out how good it is. But let's go ahead and just take a look and see what that looks like as far as the file itself. And I went ahead and just opened this up in a basic WordPad and text editor just so we can take a look at it. Certainly you can open up an Excel or any other kind of spreadsheet. And we note that this is a comma-separated variables. We have a date, open, high, low, close, volume. This is the standard stuff that we import into our stock, or the most basic set of information you can look at in stock. It's all free to download. In this case, we downloaded it from Google. That's why we call it the Google stock price. And it specifically is Google. This is the Google stock values from, as you can see here, we started off at 1/3/2012. So when we look at this first setup up here, we have a dataset train equals PD_CSV. And if you noticed on the original frame, let me just go back there, they had it set to home Ubuntu downloads Google stock price train. I went ahead and changed that because we're in the same file where I'm running the code. So I've saved this particular Python code, and I don't need to go through any special paths or have the full path on there. And then of course we want to take out certain values in here. And you're going to notice that we're using our data set, and we're now in pandas. So pandas, basically it looks like a spreadsheet. And in this case we're going to do iLocation, which is going to get specific locations. The first value is going to show us that we're pulling all the rows in the data. And the second one is we're only going to look at columns 1 and 2. And if you remember here from our data, as we switch back on over, columns, we always start with 0, which is the date. And we're going to be looking at open and high, which would be 1 and 2. We'll just label that right there so you can see. Now, when you go back and do this, you certainly can extrapolate and do this on all the columns. But for the example, let's just limit a little bit here so that we can focus on just some key aspects of stock. And then we'll go up here and run the code. And again, I said the first half is very boring. Whenever you hit the run button, it doesn't do anything because we're still just loading the data and setting it up. Now that we've loaded our data, we want to go ahead and scale it. We want to do what they call feature scaling. And in here, we're going to pull it up from the sklearn or the skKit pre-processing import min-max scaler. And when you look at this, you got to remember that biases in our data, we want to get rid of that. So if you have something that's like a really high value, let's just draw a quick graph. And I have something here like maybe the stock has a value, one stock has a value of 100, and another stock has a value of 5. You start to get a bias between different stocks. And so when we do this, we go ahead and say, okay, 100 is going to be the max, and 5 is going to be the min, and then everything else goes, and then we change this, so we just squish it down. I like the word squish. So it's between 1 and 0. So 100 equals 1, or 1 equals 100, and 0 equals 5. And you can just multiply. It's usually just a simple multiplication we're using. Multiplication. So it's going to be minus 5 and then 100 divided, or 95 divided by 1. So, or whatever value is divided by 95. And once we've actually created our scale, we've telling it's going to be from 0 to 1. We want to take our training set and we're going to create a training set scaled. And we're going to use our scaler, SC, and we're going to fit. We're going to fit and transform the training set. So we can now use the SC, this particular object. We'll use it later on our testing set. Because remember, we have to also scale that when we go to test our model and see how it works. And we'll go ahead and click on the run. Again, it's not going to have any output yet because we're just setting up all the variables. Okay, so we paste the data in here, and we're going to create the data structure with the 60 time steps and output. First note, we're running 60 time steps, and that is where this value here also comes in. So the first thing we do is we create our xtrain and ytrain variables, and we set them to an empty Python array. Very important to remember what kind of array we're in and what we're working with. And then we're going to come in here, we're going to go for I in range 60 to 1258. There's our 60 time steps. And the reason we want to do this is as we're adding the data in, there's nothing below the 60. So if we're going to use 60 time steps, we have to start at point 60 because it includes everything underneath of it. Otherwise, you'll get a pointer error. And then we're going to take our xtrain and we're going to append training set scaled. This is a scaled value between 0 and 1. And then as I is equal to 60, this value is going to be 60 minus 60 is 0. So this actually is 0 to I. So it's going to be 0 to 60, 1 to 61. Let me just circle this part right here. 1 to 61, 2 to 62, and so on and so on. And if you remember, I said 0 to 60. That's incorrect because it does not count. Remember, it starts at 0, so this is a count of 60. So it's actually 59. Important to remember that as we're looking at this. And then the second part of this that we're looking at, so if you remember correctly, here we go. We go from 0 to 59 of I, and then we have a comma, a 0 right here. And so finally, we're just going to look at the open value. Now, I know we did put it in there for 1 to 2. If you remember correctly, it doesn't count the second one, so it's just the open value we're looking at, just open. And then finally, we have ytrain.append training set I to 0. And if you remember correctly, I to, or I comma 0. If you remember correctly, this is 0 to 59, so there's 60 values in it. So when we do I down here, this is number 60. So we're going to do this is we're creating an array, and we have 0 to 59. And over here we have number 60, which is going into the ytrain. It's being appended on there. And then this just goes all the way up. So this is down here is 0 to 59, and we'll call it 60, since that's the value over here. And it goes all the way up to 1258. That's where this value here comes in. That's the length of the data we're loading. So we've loaded 2 arrays. We've loaded one array that has, which is filled with arrays from 0 to 59, and we loaded one array which is just the value. And what we're looking at, you want to think about this as a time sequence. Here's my open. What's the next one in the series? So we're looking at the Google stock, and each time it opens, we want to know what the next one, 0 through 59, what's 60? 1 through 60, what's 61? 2 through 62, what's 62? And so on going up. And then once we've loaded those in our for loop, we go ahead and take xtrain and ytrain equals np.array xtrain.nparray ytrain. We're just converting this back into a numpy array. That way we can use all the cool tools that we get with numpy array, including reshaping. So if we take a look and see what's going on here, we're going to take our xtrain, we're going to reshape it. Wow, what the heck does reshape mean? That means we have an array, if you remember correctly, so many numbers by 60. That's how wide it is. And so when you do xtrain.shape, that gets one of the shapes. And you get xtrain.shape of 1 gets the other shape. And we're just making sure the data is formatted correctly. And so you use this to pull the fact that it's 60 by, in this case, where's that value? 60 by 1199, 1258 minus 60, 1199, and we're making sure that that is shaped correctly. So the data is grouped into 1199 by 60 different arrays. And then the 1 on the end just means at the end, because when you're dealing with shapes and NumPy, they look at this as layers. And so the end layer needs to be 1 value. That's like the leaf of a tree, where this is the branch, and then it branches out some more, and then you get the leaf. np.reshape comes from and using the existing shapes to form it. We'll go ahead and run this piece of code. Again, there's no real output. And then we'll import our different Keras modules that we need. So from Keras models, we're going to import the sequential model. We're dealing with sequential data. We have our dense layers. We have actually 3 layers we're going to bring in. Our dense, our LSTM, which is what we're focusing on, and our dropout. And we'll discuss these 3 layers more in just a moment. But you do need with the LSTM, you do need the dropout, and then the final layer will be the dense. But let's go ahead and run this, and that'll import our modules. And you'll see we get an error on here. And if you read it closer, it's not actually an error, it's a warning. What does this warning mean? These things come up all the time when you're working with such cutting-edge modules that are completely being updated all the time. We're not going to worry too much about the warning. All it's saying is that the H5PY module, which is part of Keras, is going to be updated at some point. And if you're running new stuff on Keras and you start updating your Keras system, you better make sure that your H5Pi is updated too, otherwise you're going to have an error later on. And you can actually just run an update on the H5Pi now if you wanted to. Not a big deal, we're not going to worry about that today. And I said we were going to jump in and start looking at what those layers mean. I meant that. And we're going to start off with initializing the RNN, and then we'll start adding those layers in. And you'll see that we have the LSTM and then the dropout. LSTM, then dropout. LSTM, then dropout. What the heck is that doing? So let's explore that. We'll start by initializing the RNN, regressor equals sequential, because we're using the sequential model, and we'll run that and load that up. And then we're going to start adding our LSTM layer and some dropout regularization. And right there should be the cue, dropout regularization. And if we go back here and remember our exploding gradient, well, that's what we're talking about. The dropout drops out unnecessary data, so we're not just shifting huge amounts of data through the network. So we go in here, let's just go ahead and add this in. I'll go ahead and run this. And we had 3 of them, so let me go ahead and put all 3 of them in, and then we can go back over them. There's the second one, and let's put 1 more in. Let's put that in, and we'll go ahead and put 2 more in. I said 1 more in, but it's actually 2 more in. And then let's add 1 more after that. And as you can see, each time I run these, they don't actually have an output. So let's take a closer look and see what's going on here. So we're going to add our first LSTM layer in here. We're going to have units 50. The units is the positive integer, and it's the dimensionality of the output space. This is what's going out into the next layer. So we might have 60 coming in, but we have 50 going out. We have a return sequence, because it is a sequence data, so we want to keep that true. And then you have to tell it what shape it's in. Well, we already know the shape by just going in here and looking at xtrain shape. So input shape equals the xtrain shape of 1, 1. It makes it real easy. You don't have to remember all the numbers that put in 60 or whatever else is in there. You just let it tell the regressor what model to use. And so we follow our STM with a dropout layer. Now, understanding the dropout layer is kind of exciting because one of the things that happens is we can overtrain our network. That means that our neural network will memorize such specific data that it has trouble predicting anything that's not in that specific realm. To fix for that, each time we run through the training mode, we're going to take 0.2 or 20% of our neurons and just turn them off. So we're only going to train on the other ones. And it's going to be random. That way, each time we pass through this, we don't overtrain. These nodes come back in the next training cycle. We randomly pick a different 20. And finally, I see a big difference as we go from the first to the second and third and fourth. The first thing is we don't have to input the shape. Because the shape's already, the output units is 50 here, the next step automatically knows this layer is putting out 50, and because it's the next layer, it automatically sets that and says, oh, 50 is coming out from our last layer. It's coming out, goes into the regressor, and of course we have our dropout. And that's what's coming into this one, and so on, and so on. And so the next 3 layers, we don't have to let it know what the shape is. It automatically understands that. And we're going to keep the units the same. We're still going to do 50 units. It's still a sequence coming through, 50 units and a sequence. Now, the next piece of code is what brings it all together. Let's go ahead and take a look at that. And we come in here, we put the output layer, the dense layer. And if you remember up here, we had the 3 layers. We had LSTM, dropout, and dense. Dense just says we're going to bring this all down into one output. Instead of putting out a sequence, we just want to know the answer at this point. And let's go ahead and run that. And so in here, you notice all we're doing is setting things up, one step at a time. So far, we've brought in our, way up here, we brought in our data, we brought in our different modules, we formatted the data for training it, we set it up, we have our X train and our Y train. We have our source of data and the answers we know so far that we're going to put in there. We've reshaped that. We've come in and built our Horus. We've imported our different layers. And we have in here, if you look, we have 5 total layers. Now, Horus is a little different than a lot of other systems because a lot of other systems put this all in one line and do it automatic, but they don't give you the options of how those layers interface, and they don't give you the options of how the data comes in. Horus is cutting edge for this reason. So even though there's a lot of extra steps in building the model, this has a huge impact on the output and what we can do with these new models from Horus. So we brought in our dense, we have our full model put together, our regressor. So we need to go ahead and compile it, and then we're going to go ahead and fit the data. We're going to compile the pieces so they all come together, and then we're going to run our training data on there and actually recreate our regressor so it's ready to be used. So let's go ahead and compile that, and I can go ahead and run that. And if you've been looking at any of our other tutorials on neural networks, you'll see we're going to use the optimizer Atom. Atom is optimized for big data. There's a couple other optimizers out there beyond the scope of this tutorial, but certainly Atom will work pretty good for this. And loss equals mean squared value. So when we're training it, this is what we want to base the loss on. How bad is our error? Well, we're going to use the mean squared value for our error and the Atom optimizer for its differential equations. You don't have to know the math behind them, but certainly it helps to know what they're doing and where they fit into the bigger models. And then finally we're going to do our fit, fitting the RN into the training set. We have the regressor.fit, X-train, Y-train, epochs, and batch size. So we know where this is. This is our data coming in. For the X-train, our Y-train is the answer we're looking for of our data, our sequential input. Epochs is how many times we're going to go over the whole data set. We created a whole data set of X-train. So this is each of those rows, which includes a time sequence of 60. And batch size, another one of those things where Horus really shines, is if you were pulling this, say, from a large file, instead of trying to load it all into RAM, it can now pick smaller batches up and load those indirectly. We're not worried about pulling them off a file today because this isn't big enough to cause the computer too much of a problem to run, not too straining on the resources. But as we run this, you can imagine what would happen if I was doing a lot more than just one column in one set of stock, in this case Google stock. Imagine if I was doing this across all the stocks and I had, instead of just the open, I had open, close, high, low, and you can actually find yourself with about 13 different variables times 60 because there's a time sequence. Suddenly you find yourself with a gig of memory you're loading into your RAM, which will just completely, if you're not on multiple computers or cluster, you're going to start running into resource problems. But for this, we don't have to worry about that. So let's go ahead and run this, and this will actually take a little bit on my computer because it's an older laptop. And give it a second to kick in there. There we go. All right, so we have epoch. So this is going to tell me it's running the first run through all the data. And as it's going through, it's batching them in 32 pieces, so 32 lines each time. And there's 1198. I think I said 1199 earlier, but it's 1198. I was off by 1. And each one of these is 13 seconds. So you can imagine this is roughly 20 to 30 minutes runtime on this computer. Like I said, it's an older laptop running at 0.9 gigahertz on a dual processor. And that's fine. What we'll do is I'll go ahead and stop, go get a drink of coffee, and come back, and let's see what happens at the end and where this takes us. And like any good cooking show, I've kind of gotten my latte. I also had some other stuff running in the background, so you'll see these numbers jumped up to like 19 seconds, 15 seconds. But you can scroll through and you can see we've run it through 100 steps, or 100 epochs. So the question is, what does all this mean? One of the first things you'll notice is that our loss is over here. It kind of stopped at 0.0014, but you can see it kind of goes down until we hit about 0.014 3 times in a row. So we guessed our epoch pretty close, since our loss has remained the same on there. So to find out what we're looking at, we're going to go ahead and load up our test data, the test data that we didn't process yet. And a real stock price, dataset test allocation. This is the same thing we did when we prepped the data in the first place. So let's go ahead and go through this code. And we can see we've labeled it Part 3, Making the Predictions and Visualizing the Results. So the first thing we need to do is go ahead and read the data in from our test CSV. You see I've changed the path on it for my computer. And then we'll call it the real stock price. And again, we're doing just the one column here and the values from iLocation. So it's all the rows and just the values from that one location. That's the open. Stock open. And let's go ahead and run that. So that's loaded in there. And then let's go ahead and we have our inputs. We're going to create inputs here. And this should all look familiar because this is the same thing we did before. We're going to take our data set total. We're going to do a little pandas concat from the data set train. Now remember, the end of the data set train is part of the data going in. And let's just visualize that just a little bit. Here's our train data. Let me just put TR for train. And it went up to this value here. But each one of these values generated a bunch of columns. It was 60 across, and this value here equals this one, and this value here equals this one, and this value here equals this one. And so we need these top 60 to go into our new data. So to find out what we're looking at, we're going to go ahead and load up our test data, the test data that we didn't process yet. And a real stock price, dataset test allocation. This is the same thing we did when we prepped the data in the first place. So let's go ahead and go through this code. And we can see we've labeled it Part 3, Making the Predictions and Visualizing the Results. So the first thing we need to do is go ahead and read the data in from our test CSV. You see I've changed the path on it for my computer. And then we'll call it the real stock price. And again, we're doing just the one column here and the values from iLocation. So it's all the rows and just the values from that one location. That's the open. Stock open. And let's go ahead and run that. So that's loaded in there. And then let's go ahead and we have our inputs. We're going to create inputs here. And this should all look familiar because this is the same thing we did before. We're going to take our data set total. We're going to do a little pandas concat from the data set train. Now remember, the end of the data set train is part of the data going in. And let's just visualize that just a little bit. Here's our train data. Let me just put TR for train. And it went up to this value here. But each one of these values generated a bunch of columns. So it was 60 across, and this value here equals this one, and this value here equals this one, and this value here equals this one. And so we need these top 60 to go into our new data, because that's part of the next data, or it's actually the top 59. So that's what this first setup is over here, is where we're going in, we're doing the real stock price, and we're going to just take the data set test, and we're going to load that in, and then the real stock price is our data test location. So we're just looking at that first column, the open price. And then our data set total, we're going to take pandas and we're going to concat, and we're going to take our data set train for the open and our data set test open. And this is one way you can reference these columns. We've referenced them a couple different ways. We've referenced them up here with the 1, 2, but we know it's labeled as a panda set as open. So pandas is great that way. Lots of versatility there. And we'll go ahead and go back up here and run this. There we go. And you'll notice this is the same as what we did before. We have our open data set. We appended our concatenated our two data sets together. We have our inputs equals data set total length, data set total minus length of data set minus test minus 60 values. So we're going to run this over all of them. And you'll see why this works. Because normally when you're running your test set versus your training set, you run them completely separate. But when we graph this, you'll see that we'll be looking at the part that we didn't train it with to see how well it graphs. And we have our inputs equals inputs dot reshape, so reshaping like we did before. We're transforming our inputs. So if you remember from the transform between 0 and 1. And finally, we want to go ahead and take our x test, and we're going to create that x test, and for I in range 60 to 80. So here's our x test, and we're appending our inputs I to 60, which remember is 0 to 59, and I comma 0 on the other side. So it's just the first column, which is our open column. And once again, we take our x test, we convert it to a numpy array. We do the same reshape we did before, and then we get down to the final 2 lines, and here we have something new. Right here on these last 2 lines, let me just highlight those or mark them. Predicted stock price equals regressor.predicts x test. So we're predicting all the stock, including both the training and the testing model here. And then we want to take this prediction and we want to inverse the transform. So remember, we put them between 0 and 1. Well, that's not going to mean very much to me to look at a float number between 0 and 1. I want the dollar amounts. I want to know what the cash value is. And we'll go ahead and run this, and you'll see it runs much quicker than the training. That's what's so wonderful about these neural networks. Once you put them together, it takes just a second to run the same neural network that took us, what, a half hour to train? Head and plot the data. We're going to plot what we think it's going to be, and we're going to plot it against the real data, what the Google stock actually did. So let's go ahead and take a look at that in code. And let's pull this code up. So we have our PLT. That's our, if you remember from the very beginning, let me just go back up to the top. We have our matplotlibary.pyplot as PLT. That's where that comes in. And we come down here, we're going to plot, and let me get my drawing thing out again. We're going to go ahead, and PLT is basically kind of like an object. It's one of the things that always threw me when I'm doing graphs in Python, because I always think you have to create an object, and then it loads that class in there. Well, in this case, PLT is like a canvas you're putting stuff on. So if you've done HTML5, you'll have the canvas object. This is the canvas. So we're going to plot the real stock price. That's what it actually is. And we're going to give that color red. So it's going to be in bright red, and we're going to label it real Google stock price. And then we're going to do our predicted stock, and we're going to do it in blue, and it's going to be labeled predicted. And we'll give it a title, because it's always nice to give a title to your graph, especially if you're going to present this to somebody, to your shareholders in the office. And the X label is going to be time, because it's a time series. And we didn't actually put the actual date and times on here, but that's fine. We just know they're incremented by time. And then, of course, the Y label is the actual stock price. PLT.legend tells us to build the legend on here so that the color red and real Google stock price show up on there. And then the plot shows us that actual graph. So let's go ahead and run this and see what that looks like. And you can see here we have a nice graph, and let's talk just a little bit about this graph before we wrap it up. Here's our legend I was telling you about. That's why we have the legend to show the prices. We have our title and everything. And you'll notice on the bottom we have a time sequence. We didn't put the actual time in here. Now we could have. We could have gone ahead and plotted the X, since we know what the dates are, and plotted this to dates. But we also know that it's only the last piece of data that we're looking at. So last piece of data, which ends somewhere probably around here on the graph. I think it's like about 20% of the data, probably less than that. We have the Google price, and the Google price has this little up jump and then down, and you'll see that the actual Google, instead of a turn down here, just didn't go up as high and didn't go down. So our prediction has the same pattern, but the overall value is pretty far off as far as stock. But then again, we're only looking at one column. We're only looking at the open price. We're not looking at how many volumes were traded. And like I was pointing out earlier, when we talk about stock, just right off the bat, there's 6 columns. There's open, high, low, close, volume. Then there's whether how many volume shares. Then there's the adjusted open, adjusted high, adjusted low, adjusted close. They have a special formula to predict exactly what it would really be worth based on the value of the stock. And then from there, there's all kinds of other stuff you can put in here. So we're only looking at one small aspect, the opening price of the stock. And as you can see here, we did a pretty good job. This curve follows the curve pretty well. It has like little jumps on it, bends. They don't quite match up. So this bin here does not quite match up with that bin there, but it's pretty darn close. We have the basic shape of it, and the prediction isn't too far off. And you can imagine that as we add more data in and look at different aspects in the specific domain of stock, we should be able to get a better representation each time we drill in deeper. Of course, this took a half hour for my computer to train, so you can imagine that if I was running it across all those different variables, it might take a little bit longer to train the data. Not so good for doing a quick tutorial like this.
In this video, we will learn about an important popular deep learning neural network called generative adversarial networks. Yann LeCun, one of the pioneers in the field of machine learning and deep learning, described it as the most interesting idea in the last 10 years in machine learning. In this video, you will learn about what are generative adversarial networks and look in brief at generator and discriminator. Then, we'll understand how GANs work and the different types of GANs. Finally, we'll look at some of the applications of GANs. So let's begin. So what are generative adversarial networks? Generative adversarial networks, or GANs, introduced in 2014 by Ian J. Goodfellow and co-authors, became very popular in the field of machine learning. GAN is an unsupervised learning task in machine learning. It consists of two models that automatically discover and learn the patterns in input data. The two models, called generator and discriminator, compete with each other to analyze, capture and copy the variations within a dataset. GANs can be used to generate new examples that possibly could have been drawn from the original dataset. In the image below, you can see that there is a database that has real 100 rupee notes. The generator, which is basically a neural network, generates fake 100 rupees notes. The discriminator network will identify if the notes are real or fake. Let us now understand in brief about what is a generator. A generator in GANs is a neural network that creates fake data to be trained on the discriminator. It learns to generate plausible data. The generated instances become negative training examples for the discriminator. It takes a fixed length random vector carrying noise as input and generates a sample. Now the main aim of the generator is to make the discriminator classify its output as real. The portion of the GAN that trains the generator includes a noisy input vector, the generator network, which transforms the random input into a data instance, a discriminator network which classifies the generated data, and a generator loss, which penalizes the generator for failing to dolt the discriminator. The backpropagation method is used to adjust each weight in the right direction by calculating the weight's impact on the output. The backpropagation method is used to obtain gradients, and these gradients can help change the generator weights. Now, let us understand in brief what a discriminator is. A discriminator is a neural network model that identifies real data from the fake data generated by the generator. The discriminator's training data comes from two sources. The real data instances, such as real pictures of birds, humans, currency notes, etc., are used by the discriminator as positive samples during the training. The fake data instances created by the generator are used as negative examples during the training process. While training the discriminator, it connects with two loss functions. During discriminator training, the discriminator ignores the generator loss and just uses the discriminator loss. In the process of training the discriminator classifies both real data and fake data from the generator. The discriminator loss penalizes the discriminator for misclassifying a real data instance as fake or a fake data instance as real. Now moving ahead, let's understand how GANs work. Now GANs consists of two networks, a generator which is represented as G of x and a discriminator which is represented as D of x. They both play an adversarial game where the generator tries to fool the discriminator by generating data similar to those in the training set. The discriminator tries not to be fooled by identifying fake data from the real data. They both work simultaneously to learn and train complex data like audio, video or image files. Now you are aware that GANs consists of two networks, a generator G of x and discriminator D of x. Now the generator network takes a sample and generates a fake sample of data. The generator is trained to increase the probability of the discriminator network to make mistakes. On the other hand, the discriminator network decides whether the data is generated or taken from the real sample using a binary classification problem with the help of a sigmoid function that gives the output in the range 0 and 1. Here is an example of a generative adversarial network trying to identify if the 100 rupee notes are real or fake. So first, a noise vector or the input vector is fed to the generator network. The generator creates fake 100 rupee notes. The real images of 100 rupee notes stored in a database are passed to the discriminator along with the fake notes. The discriminator then identifies the notes and classifies them as real or fake. We train the model, calculate the loss function at the end of the discriminator network, and backpropagate the loss into both discriminator and generator. Now the mathematical equation of training a GAN can be represented as, you can see here. Now this is the equation and these are the parameters. Here G represents generator, D represents the discriminator. Now P data of X is the probability distribution of real data. P of Z is the distribution of generator. X is the sample of probability data of X. Z is the sample size from P of Z. D of X is the discriminator network and G of Z is the generator network. Now the discriminator focuses to maximize the objective function such that D of X is close to 1 and Z of Z is close to 0. It simply means that the discriminator should identify all the images from the training set as real, that is 1, and all the generated images as fake, that is 0. The generator wants to minimize the objective function such that D of Z of Z is 1. This means that the generator tries to generate images that are classified as real, that is 1, by the discriminator network. Next, let's see the steps for training a neural network. So we have to first define the problem and collect the data. Then we'll choose the architecture of GAN. Now depending on your problem, choose how your GAN should look like. Then we need to train the discriminator on real data. Now that will help us predict them as real for n number of times. Next, you need to generate fake inputs for the generator. After that, you need to train the discriminator on fake data to predict the generated data as fake. Finally, train the generator on the output of discriminator. With the discriminator predictions available, train the generator to fool the discriminator. Let us now look at the different types of GANs. So first we have vanilla GANs. Now vanilla GANs have min-max optimization formula that we saw earlier, where the discriminator is a binary classifier and is using sigmoid cross entropy loss during optimization. In vanilla GANs, the generator and the discriminator are simple multi-layer perceptrons. The algorithm tries to optimize the mathematical equation using stochastic gradient descent. Up next, we have deep convolutional GANs or DC GANs. Now DC GANs support convolutional neural networks instead of vanilla neural networks at both discriminator and generator. They are more stable and generate higher quality images. The generator is a set of convolutional layers with fractional strided convolutions or transpose convolutions, so it unsamples the input image at every convolutional layer. The discriminator is a set of convolutional layers with strided convolutions, so it downsamples the input image at every convolutional layer. Moving ahead, the third type we have is conditional GANs or CGANs. Vanilla GANs can be extended into conditional models by using an extra label information to generate better results. In CGAN, an additional parameter called Y is added to the generator for generating the corresponding data. Labels are fed as input to the discriminator to help distinguish the real data from fake data generated. Finally, we have super resolution GANs. Now SR GANs use deep neural networks along with adversarial neural network to produce higher resolution images. Super resolution GANs generate a photorealistic high resolution image when given a low resolution image. Let's look at some of the important applications of GANs. So with the help of DC GANs, you can train images of cartoon characters for generating faces of anime characters and Pokemon characters as well. Next, GANs can be used on the images of humans to generate realistic faces. The faces that you see on your screens have been generated using GANs and do not exist in reality. Third application we have is GANs can be used to build realistic images from textual descriptions of objects like birds, humans and other animals. We input a sentence and generate multiple images fitting the description. Here is an example of a text-to-image translation using GANs for a bird with a black head, yellow body and a short beak. The final application we have is creating 3D objects. So GANs can generate 3D models using 2D pictures of objects from multiple perspectives. GANs are very popular in the gaming industry. GANs can help automate the task of creating 3D characters and backgrounds to give them a realistic feel.
So we're going to dive right into what is Keras. We'll also go all the way through this into a couple of tutorials, because that's where you really learn a lot, is when you roll up your sleeves. So when we talk about what is Keras, Keras is a high-level deep learning API written in Python for easy implementation of neural networks. It uses deep learning frameworks such as TensorFlow, PyTorch, etc. as backend to make computation faster. And this is really nice because as a programmer, there is so much stuff out there and it's evolving so fast, it can get confusing. And having some kind of high-level order in there where you can actually view it and easily program these different neural networks is really powerful. It's really powerful to have something out really quick and also be able to start testing your models and seeing where you're going. So Keras works by using complex deep learning frameworks such as TensorFlow, PyTorch, MLPlaid, etc. as a backend for fast computation, while providing a user-friendly and easy-to-learn front-end. And you can see here we have the Keras API specifications, and under that you'd have like TF Keras for TensorFlow, Thano Keras, and so on. And then you have your TensorFlow workflow that this is all sitting on top of. And this is, like I said, it organizes everything. The heavy lifting is still done by TensorFlow or whatever underlying package you put in there. And this is really nice because you don't have to dig as deeply into the heavy end stuff while still having a very robust package you can get up and running rather quickly. And it doesn't distract from the processing time because all the heavy lifting is done by packages like TensorFlow. This is the organization on top of it. So the working principle of Keras. The working principle of Keras is Keras uses computational graphs to express and evaluate mathematical expressions. And you can see here we put them in blue. They have the expression expressing complex problems as a combination of simple mathematical operators, where we have like the percentage, or in this case in Python that's usually your remainder, or multiplication. You might have the operator of x to the power of 0.3. And it uses useful for calculating derivatives by using backpropagation. So if we're doing with neural networks, when we send the error back up to figure out how to change it, this makes it really easy to do that without really not banging your head and having to hand write everything. It's easier to implement distributed computation, and for solving complex problems, specify input and outputs and make sure all nodes are connected. And so this is really nice as you come in through, is that as your layers are going in there, you can get some very complicated different setups nowadays, which we'll look at in just a second. And this just makes it really easy to start spinning this stuff up and trying out the different models. So when we look at Keras models, Keras model, we have a sequential model. Sequential model is a linear stack of layers where the previous layer leads into the next layer. And this, if you've done anything else, even like the sklearn with their neural networks and propagation and any of these setups, this should look familiar. You should have your input layer, it goes into your layer 1, layer 2, and then to the output layer. And it's useful for simple classifier or decoder models. And you can see down here we have the model equals a Keras sequential. And this is the actual code. You can see how easy it is. We have a layer that's dense, your layer 1. As an activation, they're using the ReLU in this particular example. And then you have your name layer 1, layer dense ReLU, name layer 2, and so forth. And they just feed right into each other. So it's really easy just to stack them, as you can see here, and it automatically takes care of everything else for you. And then there's a functional model. And this is really where things are at. This is new. Make sure you update your Keras, or you'll find yourself running this, doing the functional model. You'll run into an error code because this is a fairly new release. And it uses multi-input and multi-output model. The complex model, which forks into 2 or more branches. And you can see here we have our image inputs equals your Keras input shape equals 32 by 32 by 3. You have your dense layers, dense 64 activation ReLU. This should look similar to what you already saw before, but if you look at the graph on the right, it's going to be a lot easier to see what's going on. You have 2 different inputs. And one way you could think of this is maybe one of those is a small image and one of those is a full-sized image. And that feedback goes into, you might feed both of them into one node because it's looking for one thing, and then only into one node for the other one. And so you can start to get kind of an idea that there's a lot of use for this kind of split and this kind of setup. We have multiple information coming in, but the information's very different even though it overlaps. And you don't want it to send it through the same neural network. And they're finding that this trains faster and also has a better result depending on how you split the data up and how you fork the models coming down. And so in here we do have the two complex models coming in. We have our image inputs, which is a 32 by 32 by 3 or 3 channels, or 4 if you're having an alpha channel. You have your layers dense is 64 activation using the ReLU, very common. X equals dense inputs, X layers dense X64 activation equals ReLU, X outputs equals layers dense 10X, model equals cross, model inputs equals inputs, outputs equals outputs, name equals minced model. So we add a little name on there. And again, this is this kind of split here. This is setting us up to have the input go into different areas. So if you're already looking at Horus, you probably already have this answer. What are neural networks? But it's always good to get on the same page, and for those people who don't fully understand neural networks, to dive into them a little bit or do a quick overview. Neural networks are deep learning algorithms modeled after the human brain. They use multiple neurons, which are mathematical operations, to break down and solve complex mathematical problems. And so just like the neuron, one neuron fires in and it fires out to all these other neurons, or nodes as we call them, and eventually they all come down to your output layer. And you can see here we have the really standard graph input layer, a hidden layer, and an output layer. One of the biggest parts of any data processing is your data pre-processing. So we always have to touch base on that. With a neural network, like many of these models, they're kind of, when you first start using them, they're like a black box. You put your data in, you train it, and you test it and see how good it was. And you have to pre-process that data because bad data in is bad outputs. So in data pre-processing, we will create our own data examples set with Horus. The data consists of a clinical trial conducted on 2,100 patients, ranging from ages 13 to 100, with the patients under 65 and the other half over 65 years of age. We want to find the possibility of a patient experiencing side effects due to their age. And you can think of this in today's world with COVID, what's going to happen on there. And we're going to go ahead and do an example of that in our live hands-on. Like I said, most of this you really need to have hands-on to understand. So let's go ahead and bring up our Anaconda, and I'll open that up and open up a Jupyter Notebook for doing the Python code in. Now if you're not familiar with those, you can use pretty much any of your setups. I just like those for doing demos and showing people, especially shareholders. It really helps because it's a nice visual. So let me go ahead and flip over to our Anaconda. And the Anaconda has a lot of cool tools. They just added Data Lore and IBM Watson Studio Cloud into the Anaconda framework. But we'll be in the Jupyter Lab or Jupyter Notebook. I'm going to do Jupyter Notebook for this because I use the lab for like large projects with multiple pieces because it has multiple tabs, where the notebook will work fine for what we're doing. And this opens up in our browser window because that's how Jupyter Notebook is set to run. And we'll go under New, create a new Python 3, and it creates an untitled Python. We'll go ahead and give this a title, and we'll just call this Horus Tutorial. And let's change that to capital. There we go. We'll go ahead and just rename that. And the first thing we want to go ahead and do is get some pre-processing tools involved. And so we need to go ahead and import some stuff for that, like our NumPy, do some random number generation. I mentioned sklearn or your scikit. If you're installing sklearn, the sklearn stuff, it's scikit you want to look up. That should be a tool of anybody who is doing data science. If you're not familiar with the sklearn toolkit, it's huge, but there's so many things in there that we always go back to. And we want to go ahead and create some train labels and train samples for training our data. And then just a note of what we're actually doing in here. Let me go ahead and change this. This is kind of a fun thing you can do. We can change the code to Markdown. And then Markdown code is nice for doing examples once you've already built this. Our example data, we're going to do experimental. There we go. Experimental drug was tested on 2,100 individuals between 13 to 100 years of age. Half the participants are under 65, and 95% of participants are under 65. Experienced no side effects, while 95% of participants over 65 experienced side effects. So that's kind of where we're starting at. And this is just a real quick example, because we're going to do another one with a little bit more complicated information. And so we want to go ahead and generate our setup. So we want to do for I in range, and we want to go ahead and create, if you look here, we have random integers, train the labels, append. So we're just creating some random data. And let me go ahead and just run that. And so once we've created our random data, and I mean, you can certainly ask for a copy of the code from Simplilearn. They'll send you a copy of this, or you can zoom in on the video and see how we went ahead and did our train samples, append. And we're just using this. I do this kind of stuff all the time. I was running a thing on that had to do with errors following a bell-shaped curve on a standard distribution error. And so what do? I generate the data on a standard distribution error to see what it looks like and how my code processes it, since that was the baseline I was looking for. In this, we're just doing generating random data for our setup on here. And we could actually go in, print some of the data up. Let's just do this, print. We'll do train samples, and we'll just do the first 5 pieces of data in there to see what that looks like. And you can see the first 5 pieces of data in our train samples is 49, 85, 41, 68, 19. Just random numbers generated in there. That's all that is. And we generated significantly more than that. Let's see, 50 up here, 1,000. Yeah, so there's 1,000 here. 1,000 numbers we generated. And we could also, if we wanted to find that out, we can do a quick print the length of it. And so, or you could do a shape kind of thing, and if you're using NumPy, although the link for this is just fine. And there we go, it's actually 2,100, like we said in the demo setup in there. And then we want to go ahead and take our labels. Oh, that was our train labels. We also did samples, didn't we? So we could also print, do the same thing. Oh, labels. And let's change this to labels. And labels. And run that just to double check, and sure enough we have 2,100, and they're labeled 10, 10, 10. I guess that's if they have symptoms or not. 1 symptoms, 0 none. And so we want to go ahead and take our train labels and we'll convert it into a NumPy array, and the same thing with our samples. And let's go ahead and run that. And we also shuffle. This is just a neat feature you can do in NumPy right here. Put my drawing thing on, which I didn't have on earlier. I can take the data and I can shuffle it. So we have our, so it just randomizes it. That's all that's doing. We've already randomized it, so it's kind of an overkill. It's not really necessary. But if you're doing a larger package where the data is coming in, and a lot of times it's organized somehow, and you want to randomize it just to make sure that you know, the input doesn't follow a certain pattern that might create a bias in your model. And we go ahead and create a scalar. The scalar range, minimum max scalar, feature range 0 to 1. And then we go ahead and scale the scaled train samples. So we're going to go ahead and fit and transform the data so it's nice and scaled. And that is the age. So you can see up here we have 49, 85, 41. We're just moving that, so it's going to be between 0 and 1. And so this is true with any of your neural networks. You really want to convert the data to 0 and 1, otherwise you create a bias. So if you have like 100 creates a bias versus the math behind it gets really complicated. If you actually start multiplying stuff, there's a lot of multiplication and addition going on in there, that higher end value will eventually multiply down, and it will have a huge bias as to how the model fits it, and then it will not fit as well. And then one of the fun things we can do in Jupyter Notebook is that if you have a variable and you're not doing anything with it, and it's the last one on the line, it will automatically print. And we're just going to look at the first 5 samples on here. And so it's going to print the first 5 samples. And you can see, here we go, 0.9195, 0.791. So everything's between 0 and 1. And that just shows us that we scaled it properly and it looks good. It really helps a lot to do these kind of print-ups halfway through. You never know what's going to go on there. I don't know how many times I've gotten down and found out that the data sent to me that I thought was scaled was not. And then I have to go back and track it down and figure it out on there. So let's go ahead and create our artificial neural network. And for doing that, this is where we start diving into TensorFlow and Keras. TensorFlow, if you don't know the history of TensorFlow, it helps to jump into, we'll just use Wikipedia. Be careful, don't quote Wikipedia on these things because you get in trouble. But it's a good place to start. Back in 2011, Google Brain built Disbelief as a proprietary machine learning setup. TensorFlow became the open source for it. So TensorFlow was a Google product, and then it became open sourced, and now it's just become probably one of the de factos when it comes for neural networks as far as where we're at. So when you see the TensorFlow setup, it's got like a huge following. There are some other setups like the Scikit under the sklearn has their own little neural network, but the TensorFlow is the most robust one out there right now. And Keras sitting on top of it makes it a very powerful tool, so we can leverage both the Keras easiness in which we can build a sequential setup on top of TensorFlow. And so in here we're going to go ahead and do our input of TensorFlow, and then we have the rest of this is all Keras here from number 2 down. We're going to import from TensorFlow the Keras connection. And then you have your TensorFlow Keras models, import sequential. It's a specific kind of model. We'll look at that in just a second. If you remember from the files, that means it goes from one layer to the next layer to the next layer. There's no funky splits or anything like that. And then we have from TensorFlow Keras layers, we're going to import our activation and our dense layer. And we have our optimizer Atom. This is a big thing to be aware of, how you optimize your data. When you first do it, Atom's as good as any. Atom is usually, there's a number of optimizer out there. There's a couple of main ones, but Atom is usually assigned to bigger data. It works fine. Usually the lower data does it just fine, but Atom is probably the mostly used. But there are some more out there, and depending on what you're doing with your layers, your different layers might have different activations on them. And then finally down here you'll see our setup where we want to go ahead and use the metrics. And we're going to use the TensorFlow Keras metrics for categorical cross entropy. So we can see how everything performs when we're done. That's all that is. A lot of times you'll see us go back and forth between TensorFlow, and then Scikit has a lot of really good metrics also for measuring these things. Again, it's the end of the at the end of the story. How good does your model do? And we'll go ahead and load all that. And then comes the fun part. I actually like to spend hours messing with these things. And 4 lines of code. You're like, you're going to spend hours on 4 lines of code? No, we don't spend hours on 4 lines of code. That's not what we're talking about when I say spend hours on 4 lines of code. What we have here, and I'm going to explain that in just a second, we have a model. And it's a sequential model. If you remember correctly, we mentioned the sequential up here where it goes from one layer to the next. And our first layer is going to be your input. It's going to be what they call dense, which is usually it's just dense, and then you have your input and your activation. How many units are coming in? We have 16. What's the shape? What's the activation? And this is where it gets interesting, because we have in here ReLU on 2 of these and softmax activation on 1 of these. There are so many different options for what these mean and how they function. How does the ReLU, how does the softmax function? And they do a lot of different things. We're not going to go into the activations in here. That is what really you spend hours doing, is looking at these different activations. And just some of it is just almost like you're playing with it. Like an artist, you start getting a feel for like a inverse tangent activation, or the tan-H activation takes up a huge processing amount. So you don't see it a lot. Yet it comes up with a better solution, especially when you're doing when you're analyzing Word documents and you're tokenizing the words. And so you'll see this shift from one to the other because you're both trying to build a better model. And if you're working on a huge data set, it'll crash the system. It'll just take too long to process. And then you see things like softmax. Softmax generates an interesting setup where a lot of these, when you talk about ReLU, oops, let me do this. ReLU, there we go. ReLU has a setup where if it's less than 0, it's 0, and then it goes up. And then you might have what they call lazy setup, where it has a slight negative to it so that the errors can translate better. Same thing with softmax. It has a slight laziness to it so that errors translate better. All these little details make a huge difference on your model. So one of the really cool things about data science that I like is you build your what they call you build to fail. And it's an interesting design setup. Oops, I forgot the end of my code here. The concept of build to fail is you want the model as a whole to work, so you can test your model out. So that you can do, you can get to the end and you can do your, let's see, where was it? Overshot down here. You can test out the quality of your setup on there. And see, where did I do my TensorFlow? Oh, here we go. It was right above me. There we go. We start doing your cross entropy and stuff like that. Is you need a full functional set of code so that when you run it, you can then test your model out and say, hey, it's either this model works better than this model, and this is why. And then you can start swapping in these models. And so when I say I spend a huge amount of time on pre-processing data, it's probably 80% of your programming time. Well, between those two, it's like 80-20. You'll spend a lot of time on the models. Once you get the model down, once you get the whole code and the flow down set, depending on your data, your models get more and more robust as you start experimenting with different inputs, different data streams, and all kinds of things. And we can do a simple model summary here. Here's our sequential, here's our layer, our output, our parameter. This is one of the nice things about Keras is you can see right here, here's our sequential 1 model. Boom, 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 boom. Everything's set and clear and easy to read. So once we have our model built, the next thing we're going to want to do is we're going to go ahead and train that model. And so the next step is, of course, model training. And when we come in here, this a lot of times is just paired with the model because it's so straightforward. It's nice to print out the model setup so you can have a tracking. But here's our model. The keyword in Keras is compile, optimizer atom, learning rate, another term right there that we're just skipping right over that really becomes the meat of the setup is your learning rate. So whoops, I forgot that I had an arrow, but I'll just underline it. A lot of times the learning rate set to 0.01. Depending on what you're doing, this learning rate can overfit and underfit. So you'd want to look up, I know we have a number of tutorials out on overfitting and underfitting that are really worth reading once you get to that point and understanding. And we have our loss, sparse categorical cross entropy. So this is going to tell Keras how far to go until it stops. and then we're looking for metrics of accuracy. So we'll go ahead and run that. And now that we've compiled our model, we want to go ahead and run it, fit it. So here's our model fit. We have our scaled train samples, our train labels, our validation split. In this case, we're going to use 10% of the data for validation. Batch size, another number you kind of play with. Not a huge difference as far as how it works, but it does affect how long it takes to run, and it can also affect the bias a little bit. Most of the time, though, a batch size is between 10 to 100, depending on just how much data you're processing in there. We want to go ahead and shuffle it. We're going to go through 30 epochs and put a verbose of 2. Let me just go ahead and run this. And you can see right here, here's our epoch, here's our training, here's our loss. Now, if you remember correctly up here, we set the loss. Let's see, where was it? Compiled our data. There we go, loss. So it's looking at the sparse categorical cross entropy. This tells us that as it goes, how much does the error go down? Is the best way to look at that. And you can see here, the lower the number, the better. It just keeps going down. And vice versa, accuracy we want. Let's see, where's my accuracy? Value accuracy at the end. And you can see 0.619, 0.69, 0.74, it's going up. We want the accuracy, would be ideal if it made it all the way to 1. But we also, the loss is more important because it's a balance. You can have 100% accuracy and your model doesn't work because it's overfitted. Again, you want to look up overfitting and underfitting models. And we went ahead and went through 30 epochs. It's always fun to kind of watch your code going. To be honest, I usually, the first time I run it, I'm like, oh, that's cool, I get to see what it does. And after the second time of running it, I'm like, I like to just not see that. And you can repress those, of course, in your code. Repress the warnings in the printing. And so the next step is going to be building a test set and predicting it now. So here we go. We want to go ahead and build our test set. And we have, just like we did our training set, a lot of times you just split your initial set up. But we'll go ahead and do a separate set on here. And this is just what we did above. There's no difference as far as the randomness that we're using to build this set on here. The only difference is that we already did our scalar up here. Well, that doesn't matter because the data is going to be across the same thing. But this should just be transform down here instead of fit transform. Because you don't want to refit your data on your testing data. There we go. And now we're just transforming it because you never want to transform the test data. Easy mistake to make, especially on an example like this where we're not doing, we're randomizing the data anyway, so it doesn't matter too much because we're not expecting something weird. And then we want to go ahead and do our predictions. The whole reason we built the model is we take our model, we predict, and we're going to do, here's our X-scale data, batch size 10, verbose, and now we have our predictions in here, and we could go ahead and do a, we'll print predictions, and then I guess I could just put down predictions in 5 so we can look at the first 5 of the predictions. And what we have here is we have our age and the prediction on this age versus what we think it's going to be, what we think is going to, they're going to have symptoms or not. And the first thing we notice is that's hard to read because we really want a yes/no answer. So we'll go ahead and just round off the predictions using the argmax, the NumPy argmax for predictions. So it just goes to a 0, 1, and if you remember, this is Jupyter Notebook, so I don't have to put the print. I can just put in rounded predictions, and we'll just do the first 5. And you can see here 0, 1, 0, 0, 0. So that's what the predictions are that we have coming out of this. Is no symptoms, symptoms, no symptoms, symptoms, no symptoms. And just as we were talking about at the beginning, we want to go ahead and take a look at this. There we go. Confusion matrices for accuracy check. Most important part, when you get down to the end of the story, how accurate is your model before you go and play with the model and see if you can get a better accuracy out of it. And for this, we'll go ahead and use the scikit, the sklearn metrics, scikit being where that comes from. Import confusion matrix, some iteration tools, and of course a nice matplot library. That makes a big difference, so it's always nice to have a nice graph to look at. Picture's worth 1,000 words. And then we'll go ahead and call it CM for confusion matrix, y true equals test labels, y predict rounded predictions. And we'll go ahead and load in our CM. And I'm not going to spend too much time on the plotting, going over the different plotting code. You can spend, we have whole tutorials on how to do your different plotting on there. But we do have here is we're going to do a plot confusion matrix. There's our CM, our classes, normalized false, title, confusion matrix. CMAP is going to be in blues. And you can see here we have to the nearest CMAP, titles, all the different pieces, whether you put tick marks or not, the marks, the classes, the color bar. So a lot of different information on here as far as how we're doing the printing of the confusion matrix. You can also just dump the confusion matrix into a Seaborn and real quick get an output. It's worth knowing how to do all this when you're doing a presentation to the shareholders. You don't want to do this on the fly. You want to take the time to make it look really nice, like our guys in the back did. And let's go ahead and do this. Forgot to put together our CM plot labels. We'll go ahead and run that. And then we'll go ahead and call the definition for our mapping. And you can see here, plot confusion matrix. That's the little script we just wrote. And we're going to dump our data into it. So our confusion matrix, our classes, title confusion matrix, and let's just go ahead and run that. And you can see here we have our basic setup. No side effects 195, had side effects 200, no side effects that had side effects. So we predicted the 10 of them who actually had side effects, and that's pretty good. I mean, I don't know about you, but you know, that's 5% error on this, and this is because there's 200 here. That's where I get 5%. Is divide these both by 2, and you get 5 out of 100. You can do the same kind of math up here. Not as quick on the fly because it's 15 and 195, not an easily rounded number. But you can see here where they have 15 people who predicted to have with the no side effects but had side effects kind of setup on there. And these confusion matrix are so important at the end of the day. This is really where you show whatever you're working on comes up, and you can actually show them, hey, this is how good we are or not, how messed up it is. So this was I spent a lot of time on some of the parts, but you can see here is really simple. We did the random generation of data, but when we actually built the model coming up here, here's our model summary, and we just have the layers on here that we built with our model on this, and then we went ahead and trained it and ran the prediction. Now we can get a lot more complicated. Let me flip back on over here because we're going to do another demo. So that was our basic introduction to it. We talked about the oops, here we go. Okay, so implementing a neural network with Keras. After creating our samples and labels, we need to create our Keras neural network model. We will be working with a sequential model which has 3 layers. And this is what we did. We had our input layer, our hidden layers, and our output layers. And you can see the input layer coming in was the age factor. We had our hidden layer, and then we had the output, are you going to have symptoms or not? So we're going to go ahead and go with something a little bit more complicated. Training our model is a 2-step process. We first compile our model, and then we train it in our training data set. So we have compiling. Compiling converts the code into a form of understandable by machine. We used the atom in the last example, a gradient descent algorithm, to optimize the model, and then we trained our model, which means it let it learn on training data. And I actually had a little backwards there, but this is what we just did. Is if you remember from our code we just had, oops, let me go back here. Here's our model that we created, summarized. We come down here and we compile it. So it tells it, hey, we're ready to build this model and use it. And then we train it. And this is the part where we go ahead and fit our model and put that information in here, and it goes through the training on there. And of course we scaled the data, which was really important to do. And then you saw we did the creating a confusion matrix with Keras. As we are performing classifications on our data, we need a confusion matrix to check the results. A confusion matrix breaks down the various misclassifications as well as correct classifications to get the accuracy. And so you can see here, this is what we did with the true positive, true negative, false negative. And that is what we went over. Let me just scroll down here. On the end, we printed it out, and you can see we have a nice printout of our confusion matrix with the true positive, false negative, true negative. And so the blue ones, we want those to be the biggest numbers because those are the better side. And then we have our false predictions on here as far as this one. So it had no side effects, but we predicted, let's see, no side effects predicting side effects and vice versa.
If getting your learning started is half the battle, what if you could do that for free? Visit Skill Up by Simplilearn. Click on the link in the description to know more.
Now, saving and loading models with Keras. We're going to dive into a more complicated demo. And you're going to say, oh, well, that was a lot of complication before. Well, if you broke it down, we randomized some data, we created the Keras setup, we compiled it, we trained it, we predicted, and we ran our matrix. So we're going to dive into something a little bit more fun. Is we're going to do a face mask detection with Keras. So we're going to build a Keras model to check if a person is wearing a mask or not in real time. And this might be important if you're at the front of a store. This is something today which is might be very useful as far as some of our, making sure people are safe. And so we're going to look at mask and no mask. And let's start with a little bit on the data. And so in my data I have with a mask. You can see they just have a number of images showing the people in masks. And again, if you want some of this information, contact Simplilearn, and they can send you some of the information as far as people with and without masks, so you can try it on your own. And this is just such a wonderful example of this setup on here. So before I dive into the mask detection, talking about being in the current with COVID and seeing if people are wearing masks, this particular example I had to go ahead and update to a Python 3.8 version. It might run in a 3.7, I'm not sure. I kind of skipped 3.7 and installed 3.8. So I'll be running in a Python 3.8, and then you also want to make sure your TensorFlow is up to date, because they call functional layers. That's where they split. If you remember correctly from back, let's take a look at this. Remember from here, the functional model and a functional layer allows us to feed in the different layers into different nodes into different layers and split them. Very powerful tool, very popular right now in the edge of where things are with neural networks and creating a better model. So I've upgraded to Python 3.8, and let's go ahead and open that up and go through our next example, which includes multiple layers, programming it to recognize whether someone wears a mask or not, and then saving that model so we can use it in real time. So we're actually almost a full end-to-end development of a product here. Of course, this is a very simplified version, and there'd be a lot more to it. You'd also have to do like recognizing whether it's someone's face or not. All kinds of other things go into this. So let's go ahead and jump into that code, and we'll open up a new Python 3. Oops, Python 3. It's working on it. There we go. And then we want to go ahead and train our mask. We'll just call this train mask. And we want to go ahead and train mask and save it. So it's save mask, train mask detection, not to be confused with masking data. A little bit different. We're actually talking about a physical mask on your face. And then from the cross standpoint, we got a lot of imports to do here. And I'm not going to dig too deep on the imports. We're just going to go ahead and notice a few of them. So we have in here, oops, let me go Alt-D, there we go. Have something to draw with a little bit here. We have our image processing, and the image processing right here, let me underline that, deals with how do we bring images in, because most images are like a square grid, and then each value in there has 3 values for the 3 different colors. Keras and TensorFlow do a really good job of working with that, so you don't have to do all the heavy listening and figuring out what's going to go on. We have the mobile net average pooling, 2D. This again is how do we deal with the images and pooling them. Dropout's a cool thing worth looking up. If you haven't, as you get more and more into Keras and TensorFlow, it'll auto drop out certain nodes. That way you'll get a better, the nodes just kind of die. They find that they actually create more of a bias than a help, and they also add processing time, so they remove them. And then we have our flatten. That's where you take that huge array with the 3 different colors and you find a way to flatten it so it's just a 1-dimensional array instead of a 2 by 2 by 3. Dense input, we did that in the other one, so that should look a little familiar. Oops, there we go. Our input, our model, again these are things we had on the last one. Here's our optimizer with our atom. We have some pre-processing on the input that goes along with bringing in the data in. More pre-processing with image to array, loading the image. This stuff is so nice. It looks like a lot of work, so you have to import all these different modules in here. But the truth is it does everything for you. You're not doing a lot of pre-processing. You're letting the software do the pre-processing. And we're going to be working with setting something to categorical. Again, that's just a conversion from a number to a category. 0, 1 doesn't really mean anything. It's like true, false. Label binarizer, the same thing. We're changing our labels around. And then there's our train, test, split, classification report. Our IM utilities, let me just go ahead and scroll down here a notch for these. This is something a little different going on down here. This is not part of the TensorFlow or the sklearn. This is the scikit setup in TensorFlow above. The path, this is part of OpenCV, and we'll actually have another tutorial going out with the OpenCV. So if you want to know more about OpenCV, you'll get a glance on it in this software, especially the second piece when we reload up the data and hook it up to a video camera. We're going to do that on this round. But this is part of the OpenCV thing, and you'll see CV2 is usually how that's referenced. But the IM utilities has to do with how do you rotate pictures around and stuff like that, and resize them. And then the matplot library for plotting, because it's nice to have a graph, tells us how good we're doing, and then of course our numpy numbers array and just a straight OS access. Wow, so that was a lot of imports. Like I said, I'm not going to spend a little time going through them, but we didn't want to go too much into them. And then I'm going to create some variables that we need to go ahead and initialize. We have the learning rate, number of epochs to train for, and the batch size. And if you remember correctly, we talked about the learning rate to the -4.00001. A lot of times it's 0.001 or 0.001. Usually it's in that variation depending on what you're doing and how many epochs, and they kind of play with the epochs. The epochs is how many times we're going to go through all the data. And now I have it as 2. The actual setup is for 20, and 20 works great. The reason I have it for 2 is it takes a long time to process. One of the downsides of Jupyter is that Jupyter isolates it to a single kernel. So even though I'm on an 8-core processor with 16 dedicated threads, only one thread is running on this, no matter what. So it doesn't matter. So it takes a lot longer to run, even though TensorFlow really scales up nicely. And the batch size is how many pictures do we load at once and process. Again, those are numbers you have to learn to play with depending on your data and what's coming in. And the last thing we want to go ahead and do is there's a directory with a data set we're going to run. And this just has images of masks and not masks.
And if we go in here, you'll see data set, and then you have pictures with masks. They're just images of people with masks on their face. And then we have the opposite. Let me go back up here. Without masks. So it's pretty straightforward. They look kind of askew because they tried to format them into very similar setup on there. So they're mostly squares. You'll see some that are slightly different on here. And that's kind of an important thing to do on a lot of these data sets. Get them as close as you can to each other. And we actually will run in this processing of images up here, and the cross layers and importing and dealing with images. It does such a wonderful job of converting these that a lot of it we don't have to do a whole lot with. So you have a couple things going on there. And so we're now going to be, this is now loading the images, and let me see. And we'll go ahead and create data and labels. Here's our here's the features going in, which is going to be our pictures, and our labels going out. And then for categories in our list directory, and if you remember, I just flashed that at you. I had face mask or no face mask. Those are the two options. And we're just going to load into that. We're going to append the image itself and the labels. So we're just going to create a huge array. And you can see right now this could be an issue if you had more data. At some point, thankfully I have a 32 gig hard drive or RAM. Even that, you could do with a lot less of that. Probably under 16 or even 8 gigs would easily load all this stuff. And there's a conversion going on in here. I told you about how we are going to convert the size of the image so it resizes all the images. And that way our data is all identical the way it comes in. And you can see here with our labels, we have without mask, without mask, without mask. The other one would be with mask. Those are the two that we have going in there. And then we need to change it to the one-hot encoding. And this is going to take our, up here we had, was it labels and data. We want the labels to be categorical. So we're going to take labels and change it to categorical, and our labels then equal a categorical list. We'll run that. And again, if we do labels and we just do the last or the first 10, let's do the last 10 just because minus 10 to the end. There we go. Just so we can see what the other side looks like. We now have 1. That means they have a mask. 1, 0, 1, 0, so on. 1 being they have a mask, and 0 no mask. And if we did this in reverse, I just realized that this might not make sense if you've never done this before. Let me run this. 0, 1. So 0 is, do they have a mask on? 0. Do they not have a mask on? 1. So this is the same as what we saw up here without mask. 1 equals, the second value is without mask. So with mask, without mask. And that's just with any of your data processing, we can't really, if you have a 0, 1 output, it causes issues as far as training and setting it up. So we always want to use a one-hot encoder if the values are not actual linear value or regression values. They're not actual numbers if they represent a thing. And so now we need to go ahead and do our train X, test X, train Y, test Y, train, split, test data. And we'll go ahead and make sure it's going to be random, and we'll take 20% of it for testing and the rest for setting it up as far as training their model. This is something that's become so cool. When they're training these sets, they realize we can augment the data. What does augment mean? Well, if I rotate the data around and I zoom in, I zoom out, I rotate it, share it a little bit, flip it horizontally, fill mode, as I do all these different things to the data, it is able to, it's kind of like increasing the number of samples I have. So if I have all these perfect samples, what happens when we only have part of the face, or the face is tilted sideways, or all those little shifts cause a problem if you're doing just a standard set of data. So we're going to create an augment in our image data generator, which is going to rotate, zoom, and do all kinds of cool things. And this is worth looking up, this image data generator and all the different features it has. A lot of times, the first time through my models, I'll leave that out because I want to make sure there's a thing what we call build to fail, which is just cool to know. You build the whole process, and then you start adding these different things in so that you can better train your model. And so we go and run this, and then we're going to load, and then we need to go ahead, and you probably would have gotten an error if you hadn't put this piece in right here. I haven't run it myself because the guys in the back did this. But we take our base model, and one of the things we want to do is we want to do a mobile net v2. And this is a big thing right here. Include the top equals false. A lot of data comes in with a label on the top row. So we want to make sure that that is not the case. And then the construction of the head of the model that will be placed on the top of the base model. We want to go ahead and set that up. And you'll see a warning here. I'm kind of ignoring the warning because it has to do with the size of the pictures and the weights for input shape. So it'll switch things to defaults, just saying, hey, we're going to auto shape some of this stuff for you. You should be aware that with this kind of imagery, we're already augmenting it by moving it around and flipping it and doing all kinds of things to it. So that's not a bad thing in this. But in other data, it might be if you're working in a different domain. And so we're going to go back here, and we have our base model. We're going to do our head model equals our base model output. And what we got here is we have an average pooling 2D, pool size 7.7 head model. Head model flatten, so we're flattening the data. So this is all processing and flattening the images. And the pooling has to do with some of the ways it can process some of the data. We'll look at that a little bit when we get down to the lower level and is processing it. And then we have our dense. We've already talked a little bit about a dense, just what you think about. And then the head model has a dropout of 0.5. What we can do with a dropout? The dropout says that we're going to drop out a certain amount of nodes while training. So when you actually use the model, it will use all the nodes. But this drops certain ones out, and it helps stop biases from forming. So it's really a cool feature in here. They discovered this a while back. We have another dense mode, and this time we're using softmax activation. Lots of different activation options here. Softmax is a real popular one for a lot of things, and so is the ReLU. And we could do a whole talk on activation formulas and what their different uses are and how they work. When you first start out, you'll use mostly the ReLU and the softmax for a lot of them, just because they're some of the basic setups. It's a good place to start. And then we have our model equals model, inputs equals base model dot input, outputs equals head model. So again, we're still building our model here. We'll go ahead and run that. And then we're going to loop over all the layers in the base model and freeze them so they will not be updated during the first training process. So for layer and base model layers, layers.trainable equals false. A lot of times when you go through your data, you want to kind of jump in partway through. I'm not sure why in the back they did this for this particular example, but I do this a lot when I'm working with series and specifically in stock data. I want it to iterate through the first set of 30 data before it does anything. I would have to look deeper to see why they froze it on this particular one. And then we're going to compile our model. So compiling the model, atom, init, layer, decay, initial learning rate over epochs. And we go ahead and compile. Our loss is going to be the binary cross entropy, which will have that print out. Optimizer for opt, metrics is accuracy. Same thing we had before. Not a huge jump as far as the previous code. And then we go ahead and we've gone through all this, and now we need to go ahead and fit our model. So train the head of the network, print info training head, run. Now I skipped a little time because you'll see the runtime here is at 80 seconds per epoch. It takes a couple minutes for it to get through on a single kernel. One of the things I want you to notice on here while it's finishing the processing is that we have up here our augment going on. So anytime the train X and train Y go in, there's some randomness going on there, and is jiggling it around what's going into our setup. Of course, we're batch sizing it, so it's going through whatever we set for the batch values, how many we process at a time. And then we have the steps per epoch, the train X, the batch size, validation data. Here's our test X and test Y, where we're sending that in. And this, again, it's validation. One of the important things to know about validation is when both our training data and our test data have about the same accuracy, that's when you want to stop. That means that our model isn't biased. If you have a higher accuracy on your testing, you've trained it, and your accuracy is higher on your actual test data, then something in there is probably has a bias and it's overfitted. So that's what this is really about right here with the validation data and validation steps. So it looks like it's, let me go ahead and see if it's done processing. It looks like we've gone ahead and gone through 2 epochs. Again, you could run this through about 20 with this amount of data, and it would give you a nice refined model at the end. We're going to stop at 2 because I really don't want to sit around all afternoon, and I'm running this on a single thread. So now that we've done this, we're going to need to evaluate our model and see how good it is, and to do that we need to go ahead and make our predictions. These are our predictions on our test X to see what it thinks are going to be. So now it's going to be evaluating the network, and then we'll go ahead and go down here, and we will need to turn the indexing, because remember it's either 0 or 1. It's 0, 1, 0, 1. So you have 2 outputs: not wearing a mask, not wearing a mask. And so we need to go ahead and take that argument at the end and change those predictions to a 0 or 1 coming out. And then to finish that off, we want to go ahead and let me just put this right in here and do it all in one shot. We want to show a nicely formatted classification report so we can see what that looks like on here. And there we have it. We have our precision. It's 97% with a mask. There's our F1 score, support without a mask, 97%. So that's pretty high setup on there. 3 people are going to sneak into this door who are without a mask and that thinks they have a mask, and there's going to be 3 people with a mask that's going to flag the person at the front to go, oh hey, look at this person, he might not have a mask. That's I guess if it's a setup in front of a store. So there you have it. And of course, one of the other cool things about this is if someone's walking into the store and you take multiple pictures of them, this is just it would be a way of flagging, and then you can take that average of those pictures and make sure they match or don't match if you're on the back end. And this is an important step because this is just cool. I love doing this stuff. So we're going to go ahead and take our model and we're going to save it. So model save massdetector.model. We're going to give it a name. We're going to save the format. In this case, we're going to use the H5 format. And so this model we just programmed has just been saved. So now I can load it up into, say, another program. What's cool about this is, let's say I want to have somebody work on the other part of the program. Well, I just saved the model. They upload the model. Now they can use it for whatever. And then if I get more information and we start working with that, at some point I might want to update this model, make a better model. And this is true of so many things, where I take this model and maybe I'm running a prediction on making money for a company, and as my model gets better, I want to keep updating it, and then it's real easy just to push that out to the actual end user. And here we have a nice graph. You can see the training loss and accuracy as we go through the epochs. We only did the, only shows just the one epoch coming in here, but you can see right here as the value loss, train accuracy, and value accuracy start switching and they start converging. And you'll hear converging. This is the convergence they're talking about when they say I know when I work in the scikit with sklearn neural networks, this is what they're talking about, a convergence, is our loss and our accuracy come together, and also up here, and this is why I'd run it more than just 2 epochs. As you can see, they still haven't converged all the way. So that would be a cue for me to keep going. But what we want to do is we want to go ahead and create a new Python 3 program. And we just did our train mask. So now we're going to go ahead and import that and use it and show you in a live action. Get a view of both myself in the afternoon along with my background of an office, which is in the middle still of reconstruction for another month. And we'll call this mask detector. And then we're going to grab a bunch of a few items coming in. We have our MobileNet v2 import preprocessing input, because we're still going to need that. We still have our TensorFlow image to array. We have our load model. That's where most of the stuff's going on. This is our CV2 or OpenCV. Again, I'm not going to dig too deep into that. We're going to flash a little OpenCV code at you, and we actually have a tutorial on that coming out. Our NumPy array, our IM utilities, which is part of the OpenCV or CV2 setup. And then we have, of course, time and just our operating system. So those are the things we're going to go ahead and set up on here. And then we're going to create, this takes just a moment. Our module here, which is going to do all the heavy lifting. So we're going to detect and predict a mask. We have frame, FaceNet, MaskNet. These are going to be generated by our OpenCV. We have our frame coming in, and then we want to go ahead and create a mask around the face. It's going to try to detect the face and then set that up so we know what we're going to be processing through our model. And then there's a frame shape here. This is just our height versus width. That's all HW stands for. They've called it blob, which is a CV2 DNN blob form image frame. So this is reformatting this frame that's going to be coming in literally from my camera. And we'll show you that in a minute, that little piece of code that shoots that in here. And we're going to pass the blob through the network and obtain the face detections. So FaceNet.setImport blob, detections FaceNet forward, print detections shape. So this is what's going on here. This is that model we just created. We're going to send that in there, and I'll show you in a second where that is, but it's going to be under FaceNet. And then we go ahead and initialize our list of faces, their corresponding locations, and the list of predictions from our face mask network. We're going to loop over the detections, and this is a little bit more work than you think as far as looking for different faces. What happens if you have a crowd of faces? So we're looping through the detections and the shapes going through here. And probability associated with the detection. Here's our confidence of detections. We're going to filter out weak detection by ensuring the confidence is greater than the minimum confidence. So we've set it, remember, 0 to 1. So 0.5 would be our minimal confidence, probably is pretty good. And then we're going to put in compute bounding boxes for the object. If I'm zipping through this, it's because we're going to do an OpenCV, and I really want to stick to just the Keras part. And so I'm just kind of jumping through all this code. You can get a copy of this code from Simplilearn and take it apart, or look for the OpenCV coming out. And we'll create a box. The box sets it around the image. Ensure the bounding boxes fall within the dimensions of the frame. So we create a box around what we hope is going to be the face. Extract the face, ROI, convert it from BGR to RGB channel. Again, this is an OpenCV issue. Not really an issue, but it has to do with the order. I don't know how many times I've forgotten to check the order colors when working with OpenCV. Causes all kinds of fun things when red becomes blue and blue becomes red. And we're going to go ahead and resize it, process it, frame it, face frame, setup. Again, the face, the CV2 color, we're going to convert it. We're going to resize it, image to array, pre-process the input, pin the face, locate face, start X, start Y, and X. Boy, that was just a huge amount, and I skipped over a ton of it, but the bottom line is we're building a box around the face, and that box, because the OpenCV does a decent job of finding the face, and that box is going to go in there and see, hey, does this person have a mask on it? And so that's what all this is doing on here. And then finally we get down to this where it says predictions equals massnet.predict faces batch size 32. So these different images of where we're guessing where the face is are then going to go through and generate an array of faces, if you will. And we're going to look through and say, does this face have a mask on it? And that's what's going right here is our prediction. That's the big thing that we're working for. And then we return the locations and the predictions. The location just tells where on the picture it is, and then the prediction tells us what it is. Is it a mask or is it not a mask? Alright, so we've loaded that all up. So we're going to load our serialized face detector model from disk. And we have the path that it was saved in. Obviously you're going to put it in a different path depending on where you have it or however you want to do it and how you saved it on the last one where we trained it. And then we have our weights path. And so finally our facenet, here it is, equals cv2.dnn.readnet prototext path weights path. And we're going to load that up on here. So let me go ahead and run that. And then we also need to, I'll just put it right down here. I always hate separating these things in there. And then we're going to load the actual mass detector model from disk. This is the model that we saved. So let's go ahead and run that on there also. So this is pulling in all the different pieces we need for our model. And then the next part is we're going to open up our video. And this is just kind of fun because it's all part of the OpenCV video setup. And let me just put this all in as one. There we go. So we're going to go ahead and open up our video. We're going to start it and we're going to run it until we're done. And this is where we get some real kind of live action stuff, which is fun. This is what I like working about with images and videos, is that when you start working with images and videos, it's all right there in front of you. It's visual and you can see what's going on. So we're going to start our video streaming. This is grabbing our video stream source 0 start. That means it's grabbing my main camera I have hooked up. And then, starting video, you're going to print it out. Here's our video source equals 0 start. Loop over the frames from the video stream. Oops, a little redundancy there. Let me close. I'll just leave it. That's how they had it in the code. So while true, we're going to grab the frame from the threaded video stream and resize it to have the maximum width of 400 pixels. So here's our frame. We're going to read it from our visual stream. We're going to resize it. And then we're returning. Remember, we returned from our procedure the location and the prediction. So detect and predict mask. We're sending it the frame. We're sending it the face net and the mask net. So we're sending all the different pieces that say this is what's going through on here. And then it returns our location and predictions, and then for our box and predictions in the location and predictions. And the box is again, this is an OpenCV set that says, hey, this is a box coming in from the location. Because you have the two different points on there. And then we're going to unpack the box and predictions, and we're going to go ahead and do mask without a mask equals prediction. We're going to create our label, no mask. We're going to create color if the label equals mask L00225. And this is going to make a lot more sense when I hit the run button here. But we have the probability of the label. We're going to display the label and bounding box rectangle on the output frame. And then we're going to go ahead and show the output from the frame, CV2 IM show frame. And then the key equals CV2 wait key 1. We're just going to wait till the next one comes through from our feed. And we're going to do this until we hit the stop button pretty much. So are you ready for this? Let's see if it works. We've distributed our model. We've loaded it up into our distributed code here. We've got it hooked into our camera. And we're going to go ahead and run it. And there it goes. It's going to be running, and we can see the data coming down here, and we're waiting for the pop-up. And there I am in my office with my funky headset on. And you can see in the background my unfinished wall, and it says up here, no mask. Oh no, I don't have a mask on. I wonder if I cover my mouth, what would happen? You can see my no mask goes down a little bit. I wish I'd brought a mask into my office. It's up at the house. But you can see here that this says, there's a 95, 98% chance that I don't have a mask on. And it's true, I don't have a mask on right now. And this could be distributed. This is actually an excellent little piece of script that you could start, you install somewhere on a video feed on a security camera or something, and then you'd have this really neat setup saying, hey, do you have a mask on when you enter a store or public transportation or whatever it is where they're required to wear a mask. Let me go ahead and stop that. Now, if you want a copy of this code, definitely give us a holler. We will be going into OpenCV in another one, so I skipped a lot of the OpenCV code in here as far as going into detail. Really focusing on the Keras, saving the model, uploading the model, and then processing a streaming video through it so you can see that the model works. We actually have this working model that hooks into the video camera, which is just pretty cool and a lot of fun. So I told you we're going to dive in and really roll up our sleeve and do a lot of coding today. We did the basic demo up above for just pulling in a Keras, and then we went into a cross model where we pulled in data to see whether someone was wearing a mask or not. So very useful in today's world as far as a fully running application.
And we're going to be going over the OpenCV tutorial. And it's going to throw in some Keras, and we're actually going to be covering a lot of ground in this tutorial, so I'll speed up for some of it and slow down as we focus on important aspects. When we talk about OpenCV, we're really talking about computer vision. So what is computer vision? And I would say OpenCV goes way beyond computer vision. It goes into graphic editors and all kinds of other things. But we're going to be focusing a little bit on computer vision, and we're going to cover the whole slew of the editors and all the other cool stuff that's in there. Computer vision is a field of machine learning whose goal is to help computers see. Its end goal is to make intelligent systems which can understand digital images. And there's all kinds of different examples, from handwriting, identification, categorizing of pictures, is that a dog or a cat in the picture, and all that different things. Those are all part of the computer vision. Cars, the new automated cars, and being able to drive down the road, they usually use aspects of computer vision to do that for our AIs. So what is OpenCV? OpenCV is a huge open source library for computer vision, machine learning, and image processing. It can be used to process images and videos, to identify objects' faces, or even handwriting of a human. And one of the cool things is the OpenCV project is outside of Python, but it has a high integration with Python. So you can use it in other programming languages. You're not set to just Python with it. And it has a huge community behind it, which is really nice. That's what makes the OpenCV project so great. We'll start with installing the OpenCV. It's pretty straightforward. In Python, you do a pip install opencv-python. You can pip install OpenCV contrib python headless. OpenCV can be installed in Windows, Mac OS, or any GNU Linux distribution by using the pip command. The first command we went over is to install the main module packages, and the second one is for the full package. And usually you want the full package. Once you start digging into it, it's so easy to use, and there's so much fun things you can play with. So the most common thing is reading in image in OpenCV. And we'll do this also in code. So if I go a little quick on the slides, it's so that we can roll up our sleeves and actually open up and do the coding on there. So when we're reading an image in an OpenCV, given an image to load it in, we can use the OpenCV function IamRead. The image can be displayed using the function IamShow. And so these are your two main categories on here. And so your basic thing is to read an image in, then you can manipulate it, and then you can display it depending on what you're using it for. And then when we talk about manipulating it, the most common thing is probably resizing images and videos. So you can read in videos, and we'll look at the command for that also and how you can process them frame by frame. Resizing is helpful in all kinds of aspects. Obviously on the display, you might want to resize it so it fits the display a certain way. A lot of times that's handled for the size of the image. If you're uploading it to the web, you might want to have a smaller image so you're not taking up a huge amount of memory. Not as big of a deal anymore, and then a lot of times the actual web page would handle the size of the image once you upload it. But what if you want to process all the images under the same neural network? Well, they're going to look for the same size, and that's also is huge, just to be able to resize your images to go into that neural network, so you're not looking at different sized images. And images read in might not be of correct size or might not fit the screen correctly. To overcome this, we can resize the image, and you can see it's a real simple command in the CV. And we're actually using what they call CV2. A lot of times people will just they'll import CV2 as, or open CV2 as CV just to make it easy, because they might have old code or something like that, and it's easy to swap things in and move forward. And you can see here we just resize, we have our image, we have our new dimensions, and then how do we resize it? The interpolation is kind of a function in there as far as how to guess the colors, because you're combining colors and different things. And we can use drawing with the OpenCV. We can draw images in OpenCV. It allows us to draw various things like a rectangle, circles, lines. You can add text into the images and that kind of thing. So there's a whole slew of different things we can do with the OpenCV. And we'll look at these commands. We'll glance through them and show you how they work in the actual software. And they have basic image functions. And this is just so cool because so much of this is built in. You go back 10 years and people are writing the code to do this stuff, and now it's all built in and people are continually optimizing it. So you can do a lot of things without having to lift the hood up and really do the heavy lifting underneath. And so OpenCV has built-in functions which allow us to perform various operations on our images, such as blurring, resizing, cascading, edge detection, and cropping. And there's also motion detection in videos. There's all kinds of things. And you can see here we have blurring, where you can take an image and blur it slightly. We can resize it. It's easy to crop it, you know, that we can do the little round head face cropping on a web page or whatever. Or identify where the object is and crop the background out, kind of thing. And then you have image transformation. We talked a little bit just a second ago on blurring. We can also do things like rotating it. We can transform the image various ways. You can see here we can shift it. So we can shift it left, shift it right, flip it, crop it. All of these are very easy to do in the OpenCV package. And then I mentioned a little bit about, we start looking at motion detection and detecting different things. There's contour detection, which is built into the OpenCV package, which is really nice. And again, this is stuff that usually was somebody in the back end programming this, and now you have OpenCV, which does almost everything for you. So a contour is a curve or a line joining all points which have the same color or intensity. Contours help us find the points which lie on the same plane and assist in edge detection. And you can see here we've taken the cat and done a contour detection, and it kind of looks, it makes it look almost like someone stenciled it in there. So it's kind of cool, little Zen art going on there. This is how the computer might, using contour detection, see the cat on the black background. And then you also can adjust the color channels. So you can play with all the colors. Any image is basically a combination of three main colors: red, green, blue, the RGB. Sometimes a quick note, which we won't cover in the programming, is when you see that RGB, it's not always in that order. There's different formats for it, and there's also sometimes the alpha channel. So you might have RGB-A, where A is how transparent it is. So you might actually have 4 channels, which I like to work with when trying to take the background out, because the edges of images actually have reflections, and light is also a curve and wraps around. So there's some cool things to note when you're messing with these things. And the OpenCV allows us to split our image into its respective color channels. And you can see here we've taken the image of a little landscape and we've sorted it out into different channels, and you can see how you have it all in the blues, the reds, and the greens. And there's also color spaces. Color spaces are a way to represent the color channels present in an image. They tell us the various color channels which are contributing to a particular hue. So again, we can pull things out based on the hue and the images and colors on there. And blurring. Blurring is very popular right now because it's easy to find someone's face and then blur out the background without having to play with alpha channels and different things for the coloring around the, you have the edging of the head and the coloring. So blurring is a method used to remove noise from an image. By applying a low pass filter over an image, we smooth out the edges and make the transition from one color to another very smooth. And you might not be able to see the difference in the cat video, but you start seeing smoothness and sharpness have always been a mainstay of editing images and things like that over the years. And so this is all built into OpenCV. And then there's bitwise operations. Bitwise operations are the and, or, zor, etc. in image processing. They are used to create a new image or for masking. And we'll glance at masking, but masking is huge. So when we get into the code, we'll talk a little bit more about masking. I'll probably maybe offshoot for a minute on that. The operation is done between each pixel of two images. And so you can see here we have the square plus the circle. So if it's an and, only where the white is. So where it's in both images, it then equals a new image with just the white parts. In masking, masking is used to bring certain parts of an image into focus by lowering the definition over other parts. This is done by reducing the pixel quality of other parts of the image. Kind of a little short on the masking of what it is. So in this case, the masking would either be the background, might be all ones, and the cat in the fence might be zeros, or vice versa. We might put the cat as 1 and the background as zeros. And then you can do a transformation on either the background or the foreground to, maybe you want to blur the background out and make the foreground sharper. Or maybe you want to make the little circle with the cat in it, take the colors out so he's one color. Masking allows you to separate your image out and do those different things, and that's where the masking comes in. And it has a lot of uses. And then there's histograms. Histograms, in an image processing, histograms typically refer to a graph of pixel intensity values. The intensity of each pixel is plotted in a histogram. Again, we start with these histograms are the beginning of doing different identifications and can be used for different things. You don't really publish a histogram onto your web page of the cats because it's just kind of silly, but you can use that data in data processing to look at different things and pull different things out of the picture. Thresholding, another important aspect of image processing. A method of image segmentation. It is used to convert an image of binary by setting a threshold intensity value and deeming all values above it as 1 converted to white and below as 0 black. And you can see here we were talking about masks. In the threshold, we're able to actually create a mask of the image. In this case, you have the cats, which are mostly white, stand out because we put whatever the value is to pull those cats out and put the background further back. Edge detection. Just like threshold, it's another tool we can use to bring out an image. So we can find different things on there. A lot of cool things we can do with that. You can see here we've taken a landscape, same one we had before, and we can find the boundaries of an image by consistency and brightness. It's used for image segmentation and data extraction. And you can see with this image of the buildings how powerful it is just to pull the whole sky out. I mean, you know where the sky is. There's no debate on it. So finding edge detection has a lot of cool things it can do when you're processing images and pulling the images apart. So with that, really the hands-on, there's so much hands-on on this. So we're going to start with a real basic OpenCV setup in Python. We'll then take a look at some motion detection. I usually don't put the video on here because my office is under construction. You can see the partially finished wall in the back. When we do the motion detection, we'll have the video up and show you how to pull this video in, just like I'm doing here, and utilize that in a program. You can actually start detecting motions. You could think of a wilderness webcam or something like that, all kinds of fun things you can do with motion detection. And then we'll get into melding a little bit with the OpenCV and write a short Keras neural network that will train and do facial identification. So we're going to cover just a slew of really cool tools that you can do with OpenCV. So here's my favorite package to work in, the Anaconda. I'm going to be in Python 3.8. And then if you haven't yet, you need to go under environments. You can either install them through Anaconda here, or you can open up, let's see, where is it, 3.8. You can open up your terminal and do the pip install like we discussed earlier in the slide. And that was this slide right here. Pip install OpenCV contrib Python headless. I would just go right for the second one because it installs everything. So it's the full package. And you would just go ahead and open up, in this case, Py38. There's my terminal window, and I can simply do my pip command in here. You can also, if you're in Anaconda, we can go in here, let's do all, search the packages for OpenCV. And you can see here's your OpenCV, library OpenCV, Python OpenCV, and I actually installed all of these. All these are installed on my Anaconda for the use of this setup. Didn't want to miss anything. And then once we open this up, we're going to go in here to New and create a new Python window, Python 3. In this case, we're in 3.8, as I told you, which is what's set up in here. And we'll start with just OpenCV general. So let's put that in here, OpenCV. That's just a general setup on there for doing our OpenCV. And of course, some people like to, I'm not big on looking at my own face the whole time during these, but we'll go ahead and put my video back up there. And when we talk about the OpenCV, we want to go ahead and import all of our different aspects of what we're going to be working on in here. And you'll see on this, we have our import CV2. And I mentioned earlier that a lot of people, when they see the import CV2, they just go ahead and automatically do it as CV. That way, if you're using older code, it doesn't bother me too much to use CV2, but a lot of people prefer to just keep that as an open. Someday they'll probably have CV3, who knows. We want our numpy for our numbers array. Sometimes that comes in. We have our matplot library, kind of by default, and we'll do our matplot library inline just because we're in Jupyter Notebook. That way, if we do any plotting, it's not really going to affect what we're working on. I just do it as a standard. Pretty straightforward. And then before we get started, let me go ahead and pull over. We have a file set up on here with some images in it and some videos. And just like any of our other setups in Simplilearn, if you need a copy of some of these images, of course, it's pretty easy to come up with your own images and your own videos nowadays. But if you wanted to rerun this and set this up, you can certainly have them send the information over there with, in this case, we have the cat, which is going to be an image. We have a dog, which is going to be an MP4 video. And then we have, when we do facial recognition, we took some of our very well-known actors out there, like Ben Affleck, Elton John, the musician, Jerry Seinfeld, and other people. So we can actually train a Keras setup on there and do a facial recognition on there. And again, all of this you can send to Simplilearn and say, hey, can I get a copy of some of this information? And so we're going to start out, the first thing we want to do is just the most basic thing, which is read in an image and display it. And then I'm going to go ahead and, let's see, I'm going to cut this in half. I used to have this in Windows 10 where I just hit a button and it dropped my background and everything. So we're going to look at the horrible blue color of the Windows default. You'll just have to ignore my icons up there. And so we're going to be reading images. And the reason I did a half screen here is because when they pop up, they don't necessarily pop up by default in front in the Jupyter Notebook. So you're not even going to see them. They'd be hidden behind there. The first thing we want to do is just a basic reading of an image. In this case, we're just going to read the file cat.jpg. There's no path in here because I went ahead and saved it in the same folder that the program's running in. But if you have it in a separate folder, you want to put that full path in there. And so it's real simple. We have image, we have cm.imread or read. I don't know which one they use. imread. And then cv imshow. Image, and that just stands for image show, and cats, and then image. Cats is the title of the window that's going to pop up. And let's go ahead and run that. And you can see here we have our window that pops up, and there's our cat. So that's really straightforward. If you're looking at that, there's nothing really difficult. And this is why I like OpenCV so much, because it's so easy to use. And if we're going to do the image, if you remember we had dog video going on. Maybe my image up a little bit. There we go. We can go ahead and play a movie, and that is really cool. And by the way, when I was messing with this, it does actually store the sound file with the MP4. So if you have the video playing and the microphone going, it will store both of those as a separate. There's like another channel that stores in the CV when it's reading these things. In this case, we're going to go ahead and capture. We need to go ahead and tell it what file we're capturing. In the next video, we'll actually do one of the next two sections. We'll show you how to capture the camera you're actually looking at. But in this one, we have capture CB video capture dog.mp4. Pretty straightforward. It just says here's the file we're going to capture. And then it says while true. And this, if you're doing a lot of programming in Python, you should recognize this. Instead of setting is true to true and then letting it switch each time, we just say, hey, if not is true, break, and that will break the loop. And so what we're doing here is we're going to read each frame of the video as it goes. Is true frame equals capture.read. If is true is false, it breaks, so we're done. We've hit the end of the video. And then we're going to show the video, in this case of the dog, cute little puppy. And it's going to be by frame. So each frame is shown. And you see we have a wait key here. This has to do with the encode in the back. So you could probably leave it out in here, but it's usually good to leave these particular things in. This particular key in there, because it does actually, there are times when that can affect the runtime. And you can see here's our little puppers, smiling and having fun. And it's playing each of those frames. So as you're watching it, it's going through, I don't know how many frames per second, probably 30 frames per second. And so it's displaying 30 frames one after another. And if you have sound with it, by default will play the soundtrack with there, just so you know. We're not doing too much in sound on this one, that we're just focusing on the OpenCV video. And then when you're done with something, you'll see me flash this up a bunch of times. We're going to have the destroy all windows from the CV, which closes everything we got going. When we're dealing with videos, one of the issues is you have a buffer in your video. And so you'll see this kind of coding where it says wait key 60. And it's just waiting an extra period of time to make sure everything's cleared out of memory. That's all that does. And so you can see we just closed all the windows that came in on there. And then one of the cool things we can do, and we're going to do a bunch of stuff with images in just a minute, but let's start with the video. We can do resizing. And so we have a rescale the frame. We're going to send it the frame, we're going to send it the scale, and it's going to compute the height, the width and the height based on what we send for a scale. We'll put it into dimensions, and this right here is our resize. CF resize the frame, and this could also be an image. You're not stuck with just a frame when you do this kind of resize. And then this is the code they use for resizing. Not a whole lot to look in there. It does come up sometimes because there are a couple different mathematical codes of how to blend the colors together and make it smaller without it becoming really chunky or really, they used to just delete, like if you cut it in half, you just delete every other pixel. And then, of course, you're deleting information instead of melding it together. And this smooths it over. That's what this is doing right here, this interpolation equals CV inter area. And then we have the change the res. We're going to be doing a live video, so when you change the resolution, again, there's not a whole lot to look in here. It's just helping us so that the resolution keeps it looking nice on there. And then we have this should look familiar from above. We do our capture. We need to set up where the video is coming from. We got to let the CV, the OpenCV, know what which file it's using. And then it says while true. This is again just like above. If not true, if not is true, break. And here's our frame resize. And then we're going to do CV IMShow frame, and then we're going to do CV IMShow framed resize. This would look just like you saw before. And then we have our this extra code here in case we need to break early. Now I'm going to run this, and we're going to get if you're looking at this, you should say, oh, we have 2 different videos going. One of them is labeled video, and it's based on frame, and one is video resized based on frame. So we're going to end up with 2 completely separate videos playing at the same time. And let's go ahead and run and see what that looks like. You'll know one of the videos is obviously going to be the dog because we saw him before, and you can see right here, there the dog is resized. And we could easily take this scale. Yeah, we'll go this way just a little bit. And instead of 0.5, maybe we want to do 0.25 because we want it to be like a little thumbnail on there. Let me run that. And you can see how it nicely rescales it down to 1/4 of the size. And then I'm going to keep the split screen. You'll see why in just a second. Let me go ahead and destroy the windows and clean up our desktop that we're working on. And we're going to go back to image editing. So we're going to go through a bunch of different editings you can do on here. Now, this next part, we're zooming through. There are so many things you can do with the OpenCV. First, we're going to just draw a blank box. We'll go ahead and run this. Here's my blank box. It's got nothing in it. And we can take, if you notice I've created blank, oops, there's my blank, we filled it with zeros. So this is a 500 by 500 by 3 channel. There's actually can be 4 channels if you have the alpha, which is a see-through. And this will handle an alpha channel, but you have the 3 channels in here, and you create a nice blank box. It's just black in there. And then if we're going to do a blank box, we can actually take, let me go back in here. There we go. We're going to take this blank box, and we're just going to fill it. I'll leave it called blank. We'll run this, and I'm putting in from 200 to 300. That's actual pixel counts. Remember, this is a 500 by 500 box. And we're going to do from 200 to 300 and 300 to 400. That's the upper left and bottom right corners of the array. And we're going to send them to 0, 0, 255, which happens to be green. And this is RBG. Be a little careful because some of the formats switch the order from red, blue, green to different colors. And if we run this, you can see here we've actually added, oh, I guess I did a red box. For some reason I thought that was a green color. I must have it switched around on there. But you can see right here that we can actually go in and we can change any pixel in here. And it works like a numpy array, which is really nice because now I can edit my blank box here and do different things in the blank box and fill it in there and draw lines. We'll go ahead and do a rectangle. Like I said, some of this is going to be quicker to pasting in here and showing you. We're going to take a rectangle and, oops, it's hard to see here. Create the shape. Let me open this up a little wider. There we go. And in the rectangle, we're going to use blank. I'm going to show it. We're going to give it a new window. That's what this is doing down here. If I left this blank, it just put the rectangle on top of everything. And we're going to use blank as our basis, starting at 0, 0. And you can see our different dimensions and thickness -1. And there's my weight key on the bottom. And let me go ahead and run that. Oops, I should have done an IMShow, which it did, but it was behind our Chrome. You can set where it appears on the window. We should probably do that on here. But you can see it opened up a new window. This window is called rectangle. This one's called blank. And so these are 2 completely different windows that we've set up on here. If I had changed this to blank, it would have just put the rectangle on top, just like it did the red square earlier. And we can do a lot with this. We can go ahead and draw, let's see, a circle, a line, and then put some text on here. And we'll take the same blank setup, since that's our basis right here is blank, and we'll go ahead and create all of those. And let me go ahead and paste that in here. And you can see here we have our CV circle. It's going in on the blank. we have our dimensions of the circle. Let me just bring these down a line so you can see a little bit better what we're looking at. There we go. And then we're going to do the color on this, the thickness -1. And this is basically a radius of the circle kind of setup. I'd have to look up to remember the exact what these different numbers represent. But you have the different sizes of the circle. We have a line here. We're going to draw a line blank. In this case, we have 300, 400, 255, and you can see a setup in here. This is again the color, the starting point, the end point, and a thickness of 3. So a lot of this is pretty straightforward, and this is going to open up a new window called line, because that's what we called it instead of putting it on the blank. And then we'll do text. Now, on each one of these, we're adding the line to blank, so it's in the original blank square that we've called blank. But on each one of these, we're opening it up in a new window. We could easily continue to put them in the same window, and you could turn it into a video or some other kind of thing. And you can see down here, hello, my name is Jason. My name isn't actually Jason. And we have our location that we're going to print Jason on there, and the font, and the size, and the color, and dimensions of it, and then we'll show text. And let's go ahead and run, so you can see how all these show up on here. And if I open up my screen a little wider, you can see that we have our code, and we did certainly add a circle on here. Here's our circle. We added a line on here. Here's our line. And we've added text on here. Hello, my name is Jason. Probably should have picked a different color instead of matching it with the square box we put on there. And just like all of this, we want to go ahead and clear the data. Keep a nice clean screen. And I'm not sure why it keeps printing this stuff underneath. I gotta go fix that. And the next section we want to cover is going to be your grayscales and blending and masking and stuff like that. And let's go ahead and clear our little palette. I don't know what else to call it. That's a good name for it, palette. And here we go. You remember this one. We're going to load our image. In this case, we're going to load the image park, and we're going to display park. We get that nice view of the park. That's what we did before. And there's so many things that are built into OpenCV on here. One, we can grayscale it. And we're just going to take, and you can see here we're converting blue, green, red. Remember I said there's 3 channels. You got to be a little careful what order they're in. I can never remember. I have to actually pull it up every time I go in here because I jump around between so many editors and software. It's just the nature of dealing with pictures sometimes. But you really have to make sure you catch that and double check it. And so we're just going to, this is just a conversion, and that's what the CVT stands for, color. And then we'll display this in grayscale it. And you can see I did a nice job. There's our park. Oops, if I can grab it. And there's the grayscale on there. And then we can do such things as blur. So I can come in here and we can go ahead and this uses CV Gaussian blur. And there's a lot of settings as far as how the blur works. And then you can see here we got border default, CV border default, 7.7. I believe that has to do with the square and the pixel range. When you do a lot of blurring, then you start messing with it. And we can see here's the park up here. We went ahead and grayscaled it. Oops, there we go. Gray not responding because I hit the wrong button on this. And blur. There's our blur on there. So we have a couple different setups on that. There's also edge cascade. Some of these you just pretty much, you really have to know you're editing on videos. I'm not a huge video editor. So when I do a lot of this stuff, I'm not really sure what it is I'm doing. Like I know what blur is obviously, but I don't know what edge cascade is. Except for now that it comes out, you can clearly see that it draws lines dealing with where the different colors meet and how they connect. That's a really neat tool. It puts a nice it literally creates a nice mask of the edging. And you could see where you could use this to pull out, in this case, the sky quite easily from the whole picture. And there's dilated. Let me go ahead and run that. We can see what that looks like. Oops, give it a second to pop up to the top. Keep in mind that the dilated used the edge as our input. So we took the canny, the blur. Oh, there we go. Yeah, canny, blur. Dilated used the canny, so we have our blurred coming in from the canny edges. Quite the terminology there if you're trying to follow it all. We have eroding. Let me just show you some of the settings on there. We have the number of iterations for doing eroding, so let's go ahead and run this one. And you can see how it changes the settings or the view on there. And this brought in the dilated and then eroded it back into, I'm guessing it kind of sharpens it from the blurriness we saw in the one before it, the dilated. And then, of course, probably one of the ones that I use the most, and I use the resize. And the reason I use this a lot is because I work in data science. And so if I have it coming in as a certain size on there, if the neural network is processing an image with a certain size, all the images coming in have to be that size. And so we have here resizing our image. And let's go ahead and run that. And you can see how we took the, in this case, we used the original image and we just resized it to a smaller view on there. And if we can resize the image, we can also crop it. Again, data science loves cropping. This is, you could literally crop pictures and resize them and rotate them and make that your new input for doing categorization. And we'll actually show you how we can automate that when we get to the facial recognition Keras part of this tutorial. But we can see here we can also crop it. And we just take the picture and crop a small piece off of it there. And just like we did before, let's go ahead and clean our palette, start it over again. And again, we're just chugging through these. These are commands that, depending on what you're doing, depends on what you need. So if we're looking at changing it to grayscale, sometimes processing something in grayscale in Keras is easier. It's able to pull out the dimensions better. Blurring, that's more of a display kind of thing, where you're going to display it with a slight blur. Finding the edges, that's kind of cool. You can actually come in there and maybe use those edges to help you find something in the foreground and in the background. Dilated, give it that little blurry look. Eroded, bring it back into sharpness. Resize it and crop it. All those are things that are just neat tools to have at your fingertips and easy to use. Some of them might be more for a website and bringing up icons and cropping the headshot or something like that, where others are kind of more general use in just about any industry. Another feature is being able to translate. Transmat float 32. Remember, a lot of these things, let me just full screen this here real quick. We have our image coming in, and then we can translate it 100 in different directions on here. There's so many different things we can do with this. So as we go through this, oh my goodness, I hit a button on here. Okay, give me just a second. There we go. Okay, so let's go to translate. It's on translate on there. And we have the cat, and you can see how we've translated it down instead of the full image of the cat that we had before. We can also rotate. Rotation, like I mentioned earlier, is a fun thing to do. And we'll actually do that when we do the Keras thing, because you can process the same image at different angles, and then you've just multiplied your input as far as doing identification. In this case, you can rotate on here. We have the angle, the rotation point, none. I believe it puts it in the center. I'd have to look that up. And then you have the image shape, height, width. Rotate point is none. Width, height. So this is actually going to put the rotate point in the middle. If we send it a none to this little routine that they put together in the back. And then we're going to warp. This is the actual command here, warp affine. And you have the image, you have your rotate map, and you have your dimensions on here. And if we go ahead and plug that in, we put the rotate in image at -45, let's see what happens. We're going to run that. And you can see how it nicely rotated the cat's head, although it's a little creepy the way it looks like it cut the cat's head off on there. Maybe move it, translate it down a notch just so you can't see the cutoff point. And we already did the resize, but we'll run that again so you can see how it gets resized on here. And be aware when you resize them. I do a lot of resizing for putting it into neural networks or into some kind of machine learning setup, but it does squish it. It squishes it and stretches it, and so if you're doing this for, say, display and re-editing, you might want to be a little careful about that. Make sure that you maintain the same ratio unless you intentionally want the cat to look taller and thinner. And then we can also go ahead and flip it. As you can see here, we just flipped it upside down. -1, you can probably flip it a couple different ways. I'm curious as to what -2 does. Shoop, same thing. Maybe if we put minus... And a 1 is not, well, 1 is just flipping it all the way to the opposite side from left to right. So you can see here we can flip it around a little bit. That's kind of a fun thing to have. One of those things you might have a hotkey for if you're doing some kind of picture editing and giving a lot of choices. And we also already did the, see, there we go, cropping. So you can see here where a cropped image equals the image, and we just pick out the pixels we want, and then we can show the cropped image over here. And it's just a cropping of the face. In this case, we grab 200 to 400 as the upper left corner and 300 to 400 as the bottom right corner. And let's clear our palette again. And then we're going to do contour detection. And there is so much that goes into all this. I mean, we're flashing through a lot of things, and you can see how you might combine them and use them for different things. So we're going to go ahead and get our cat back up as our image. And let's go ahead and do image shape. We're going to take an image shape and we're just going to create a blank screen for it. So this is just a blank screen here based on the shape of the cat. And strangely enough, this is done a lot. The reason that we would create a blank thing is or a blank image, is you might start filling in information on there and using that as your template for different things. And so it becomes a mask of sorts. There's an actual mask in the program, a little bit different, but you can imagine if this is your blank screen you start with, you might add circles or squares or whatever on there. And we can do the same thing here with, we can convert our picture to gray. We did that earlier, which is always kind of fun to see the cat comes back. And being that I'm messing with a lot of different feeds and stuff like that, it's you can see I got an auto-responding going on there. When you do a lot of this stuff, that's what you'll start seeing more of that as you mess with it. It'll eventually come in. You just got to give it some time. There it is. There comes in my gray one on there. And we have the Gaussian blur, so we can take it and blur the image. And in this case, we fed it the gray one. So you can see the very clear mouth underneath on the gray one, and then the more blurry one on top on there. If you remember, we did earlier, come back on here, canny edges. So again, we're doing detections and things like that and looking for different things. And there's another feature called CV threshold, or the CV threshold. And in this case, we're going to send it the gray picture. And let me just pull the coding down here. There we go. And you can see here we're going to do CV threshold based on binary. Let's set up on here, and we'll go ahead and just run this so you can see what this looks like. Run. There we go. That's actually really cool how it picks up on that, on the threshold. And you can see how it just turns it into almost a black and white image. That can be a lot of fun too. And we can also look at the contours in the OpenCV. So we talk about that. We have our, let me just open this up all the way so we can see the code. We're going to return the contours and the hierarchies. And we're going to pull this off of Canny, the Canny one that we sent up here earlier. And we have the retrieve list and chain approximate sample. So there's a lot of options in here that we can follow. Let's go ahead and run that. Let's go back down here. Where are you? Up there we go. And when we run this, we get a nice setup on this. It says, hey, there's 74 contours found on here. And And that's actually starts turning this into a math on, whoops, which one did we feed it? We fed it the Canny up here. So we start to look at these different setups. Let me get this out of the way. Where's Canny? There's Canny in the back. And you can see that this drew 74 different like line connections on here. So now we're starting to actually turn this into almost a mathematical formula on this. And while we're looking at these, we'll go ahead and do draw contours. And here's our contour. Let's return the contours up here. And we're going to put this on the blank. Remember how we did the blank earlier? So we are actually going to take the blank as, remember I told you could use it like a base setup on there, and we can now redraw the contours, but in this case we changed the color. So now we're drawing the contours in red. So that's just kind of a fun thing you can do on there to change the, literally change the appearance and the setup on there. And let's go, of course, clean up our setup, destroy all our windows, and move on to the next section. And we're going to look at color spaces. And let's start with, in the color spaces, we're going to read an image in. And I'm going to go ahead and show the image park. Let me just run that. Oops, I forgot to put the wait key in there. A lot of times the wait key just helps because I'm pushing all these graphics out through a single kernel because I'm working in Jupyter Notebook, and things get hung up. And so waiting that extra 60 milliseconds can sometimes really help. Sometimes as we start flashing these pictures up and down, you'll see there's no response and other things come up. That really is just because we're pushing so much out there. Now, one of the interesting things on this is we imported Matplot library. And so Matplot library can now easily be integrated with our imagery. And you can just see all we got to do is just dump the image into the Matplot library. And now I have the image here showing on my Matplot library setup. One of the things you're going to notice on this is the colors all look off. Well, again, you see that, and you see that they're supposed to be the same thing, and you should jump and say, oh, one of these is RBG, and the other is GBR or BGR or something like that. And so it's reading reading the colors in a different order. That's all that means, and you have to do a transformation at some point to fix that. So let's go ahead and take a look at, we'll go and go back and grayscale it again. We're going to take our image of the park. We'll put it into gray. Run. There we go. And in here we can convert our color, and this is what we were just talking about. We can convert the color scheme. Let me go ahead and run this. And you can see here we swapped the scheme out. And then I'm curious, because we did up here plot it. What does this look like when we plot this new color down here? This new scheme. What does that look like on our setup? Let me go ahead and just go down. There we go. And we called this HSV. So we'll go down here, and instead of image, I'm going to plot HSV. And let's run that. And still way off on color schemes. You can see we can really mess up with this. HSV is another type of color scheme. I was curious because I did not think it would come up correctly, but I wanted to see if it would. And we can also do a conversion to what's called, there we go, BGR, blue, green, red, to lab. And lab is just another color scheme on here. And so you can see when we swatch the color scheme, it has some really cool effects as far as what it looks like in their view. Lab ranges from, it's kind of luminosity, and then it has like then the channels coming in. So it's a little bit different setup on this, but really you have to just play with these to see what they look like. And we talk about all these different color schemes and all these switches on here. Now, the one that we were talking about earlier, I mentioned was the BGR to RGB, because we use the BGR. We'll just run this, and we see the color change on that. And then we'll go back up, because I'm still curious. Okay, there we go. Copy. If this is the same that Matplot library uses. And we'll just type in RGB down here, because that's what we called our figure. And we'll run this, and it will display it. Oops, it comes up there and gives us a problem because capitalization. Whoops. RGB, there we go. So let's go ahead and run that. And that looks pretty close to the original. So this is when we're converting between Matplot library and from the OpenCV, we really want the blue, green, red to red, green, blue. That's the conversion you want to use to get to the original picture on there. And then we can also convert from HSV to the lab. Like I said, these conversions, you have to look them up most of the time, but it's important to start recognizing them. So the very fact that you're in here looking at this, and we're talking about blue, green, red versus lab versus the where was it, HSV setup on there. When you're dealing with pictures, they come in all varieties, and so really being able to switch between them is important on here. So let's go ahead and take that particular setup, conversions, and we'll go ahead and clean up our palette. Hopefully that will save us some problems down the road. And we're going to start looking at the color channels. And with this, we'll go ahead and reload the park back up. We'll display that just so you can remember what the original picture looked like. And then for right now, let's go ahead and take a blank screen and create ourselves a blank zeros, basically same shape as our park image. D-type, U integer 8. Don't really, usually that's the default anyway, so you don't really need to even put that in there, but it's good to have. And this is an interesting line here that OpenCV allows you to do. CV split image. And this basically just takes the 3 channels in your NumPy image, and you could use the NumPy code and figure it out, I'm sure, and splits it into blue channel, green channel, and red channel. And what we're going to do is we're going to go ahead and, there we go. We're going to do a CV merge, blue, green, and red. And what we're doing is we're merging the blank one as far as blue, the blank, green, blank, 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 red. So these are the new channels as we combine them. That's what this merge thing does. This is kind of fun because you could merge, you could take like your cat with just the red whiskers, merge that with something, and then kind of mess with the images as far as like, you know, what sticks out and what sets back on there. You can get pretty creative with the imagery. And then we're just going to go ahead and show blue, green, red. We'll just do all these at once. And you can see here, the same image. Oops, there we go. I'll take it a second to pull it down. And we can now see it's either black or blue, red or blue, or, you know, the different colors in here, green or black. Kind of fun. I mean, you can really pull out the different colors and see how you can mess with them on there. And then if we go ahead and just do a quick print of these shapes, we go run. You can see here that, as you expected, you have the image shape, which is 427, 640 by 3. Well, it's only 640 by 640, so each one of these is just the color of just the one color. That's all we're showing on here. The fact that we used the shape on here is very similar to your NumPy, and these are actually NumPy in the back end. So if you haven't messed with NumPy, real powerful setup on there. You can dive in there and do a lot of stuff in NumPy that comes back right into this over here. And then we'll merge them back in. Shoop. There we go. And we see the original picture. Give it a second to pop to the front. And you see here we merge the colors back. We separated the colors. We merge them back. Same image. And that's what we expect on this because we didn't mess with any of the colors. Let's go ahead and destroy all that. So we have another clear setup. And let's go in and look at some more alterations we can do with blurring and altering the image in different ways. For this, we'll go back to our cat picture. Here's our image, CV, AMRed, cat JPEG. And if we run that and view it, there's our cat. I guess we got tired. I guess the guys in the back got tired of the cute puppy running around. And the first thing we'll go ahead and give a shot on here is averaging. These are different ways we can blur the image. So if we average it, it takes the average pixels based on 3x3. And if we change this to 30, just for fun, you can see how it really blurs it on there. So this is like a 30 by 30 pixel. Each pixel averages around it. We'll go back to 10. Kind of a little bit of fun stuff you can do on there. And you can see that because I'm doing the average blur, it knows to go to this frame right here. That's why I can so easily jump in here and just make some changes on that. That is a lot of fun when you're messing with videos, because you can so easily throw that into your interface setup on there and be able to mess with it. And here's our Gaussian blur. And the Gaussian blur is very similar, but the pixels that are closer are given more weight. And let's just jump this up here to 30. We'll run that. And whoops, it didn't like 30. I guess I jumped too high for it. Let's do 5. There we go. You start to see the blurring on there. And then the one, let's change that and see what that does. Doesn't make a huge difference on this until you start messing with, let's see, weighted. There we go. Run. You start to see it starting to blur more and more depending on how we do the weight and how it kind of blends outward. Gaussian's nice because it adds a little bit more blending to it, where this just blurs it, where the average just blurs it out. Again, those are the kind of things you almost have to play with them a lot to start seeing how they change. And there's also the medium blur. Let's go ahead and run that one as it comes up. There we go. And the median works almost identical to the average. It's very similar on there. There are some differences. And you really have to start looking at what is the difference between an average and a median value. Because that's what this is based on. This is based on the median value. If we do a run 10, there we go, there's our median. Oh, it didn't like the 10. I'm not sure why. I must have been too high of a value for it. Run. Oops. Let's try 0.5. There we go. Okay, so, and this has to be an integer for the median blur. And you can see it's similar to the average, but there is a difference in the way the math actually functions in the background. Sometimes it comes out a little different. And there's also a bilateral filter. A lot of these you use to smooth sharp edges. If something looks really sharp, you can smooth it. And this is literally what they're doing when they say smooth something and you're messing around with Photoshop. These are the kind of changes that are happening in the back end. And then we have our bilateral. Let me go and run that. And the bilateral, that is one that's really important to remember, because it works like the Gaussian, but it's like a Gaussian filter on top of a Gaussian filter. And one Gaussian filter smooths out like blotches, like if you want someone to have smooth skin, but keeps the sharp edges. And so when you're messing with this and you're doing a lot of work, remembering the bilateral filter is really important if you're doing images, especially if you look at my complexion, I really need it. I should be doing the bilateral on that one. That's the kind of thing that you'd be using to really bring up people's features while smoothing out all that fuzzy noise that shows up on their skin and blemishes. And again, let's go ahead and clear our palette. Run. Another cool feature, so we can do bitwise setup on here. And I'm going to create a blank setup just so you can see what it's going on there. Here's our blank box, 400, 400, 400. And it has a rectangle we're going to do from the blank copy, and then we're going to do a circle. The circle is going to be 200, 200 set up on here. So we're just building a circle and a rectangle like we did before. Let me just show you all the numbers on there so you can see what we're doing. Oops, let me maximize it. All right, there we go. Let me. Always a question, do you do it before or after the comma? It really depends on what I'm working on and who I'm working with. I do whatever they want. So if it's sometimes it looks nice to have the commas in front, and sometimes afterwards when you're splitting rows, it's purely visual on here. So we're going to go ahead and build ourselves a rectangle and a circle here, and let's just go ahead and display those so we can see what those look like. So we're just going to show our two images. These images are based on the blank, so they're the same size as far as the image goes. And that's important when you're working with bitwise. So how do you overlap two things if you don't know which parts are overlapping, so they have to be the same size? And we can see over here, let me just pull this over, we have our rectangle and our circle. And we can do just like we do with any kind of bitwise functionality. And let me pull it, I guess, see if I can pull it over here without losing information on the screen. I always wish the screen was 10 times bigger than it ever is. It doesn't matter how big my screen is. So here we have the bitwise and. This is where the two regions intersect, and it's like you expect. You can see the white circle on the square, but where they're both at, but not where the black part is. So it's the and. They have to have both white on both the square and the circle. And just like that, we can also do the or. And hopefully your mind's already jumped ahead. If we're doing the or, CV bitwise or, rectangle and circle, we have the combination of the two as if you just pasted one over the other in this particular case. And we have nor, or zor as it's called, Control V. So it's not X nor or not Y. And if you look at that, that kind of makes a pretty pattern on there. Not X, not Y. Not X and Y, not. But that's the ZOR on there. You can see how the ZOR comes up on there. And then, of course, there's just the bitwise not on there. We'll go ahead and run that one. And you can see here where the not set up on that. In this case, it just inverses the circle from black to white. And just like before, let's go ahead and clear our palette. So we start with a clean palette over here. Also keeps my computer running smooth. And we're now into masking. Oh my gosh, I use masking so much. And if you go into any program out there that does any kind of editing, masking comes up. So we want to go ahead and work with our masking on this. And for masking, let's bring the cat back. Sure is a cute cat. In this case, we have a bunch of cute kittens. In fact, a bucket of cute kittens. That's a little scary. And we'll go ahead and create a blank page on here. And this is really interesting. In fact, I'm going to stop here and actually do a draw. And I want you to notice right there, whoops, right there is the 2, the shape. And this is a numpy shape. So what are we talking about with this numpy shape? Well, this numpy shape is zeros or ones. We're really looking for a black and white image. A lot of times when we talk about masks, we're talking about true false. And that is the same as in numpy, like a true false mask, just like you have in numpy. And we'll go ahead and create the blank image over here, and it's just like you'd think. It's black. And then we can easily do both the circle and rectangle. And you can see here we did an image shape. Yeah, this isn't too important right now because we're going to create the mask separately in just a second. But you can see where we're creating our image here. There we go. So you can see all the different things in the window. And it's going to create both a circle and a rectangle mask on here. And let's go ahead and do a bitwise. We're going to create the mask out of the bitwise, out of the circle and the square. We'll go ahead and run that so you can see what the mask looks like. And in fact, let's go back to, let's clear up our things. It gets our palette here. We'll just go run that. We're going to play with the, let's see, where are the kittens? Got to have our cute kittens on our display. There we go. There's our kittens come back. Okay, our bucket of kittens. That cracks me up, a bucket of kittens. And here's our mask run. You can see we have an interesting mask showing on there. And then we're gonna take and combine these. Let's see, here we go. And we're going to do a bitwise where we have the image, and masked equals masked. So here's a bitwise setup on here. And let's see what that looks like. And it's just kind of fun. I've created this mask, adding all these things together, and you can see how easily we can actually just kind of zero in there and show just the kitten on the mask. So that's a lot of fun. And you could also reverse this and have an image without the kitten on there and just a black hole where the cat was. So those are both things that can happen on here. Let's go ahead and clear our setup. And masks can get so complicated. You can see we added two masks together, a square and a circle, and got a half circle on there. I tell you, I've gotten into so many layers of masks that I can't even track what's going on anymore. So you got to be a little careful with your masks and how you add them together and bring them together. But there's a lot of things you can do with them. You could just as easily swap the green channel in for one. So you have just certain areas where you have like just a circle or it's just green, or maybe the whole background is green and one area is actually full color. So there's a lot of cool things. Or you could mask, take the mask of a black and white image and then mask a section of it in color. I've seen that done to make some really cool photographs. Histograms, not something I normally think of when dealing with photographs, but you can do a histogram of the information on there. So let's bring back the kittens because they're just so cute. And let's grayscale it. Bring them back in our grayscaled cats. And then what we can do with this is we can go ahead and do a histogram on the grayscale. Boy, we can get so much into histograms because histograms have so much cool data that you can bring in. So a lot of times you can take images of something, you can start looking at the number of pixels, the bins that they fall in, different setups as it pulls in. But you can see we have a grayscale, the histogram of the grayscale here. And just like we do the grayscale, we can also do a histogram of the colored scale too. Boom, there we go. And the same setup, we got our plot figure, our title, we're just doing a histogram. We're just going to throw in the colors blue, green, red. And then we just go through each of the colors and we go ahead and mask them and then plot them on here. Let me just pull that over so you can easily see what's going on. And the same thing with the grayscale. All we did was come in here and just drop the grayscale right on here with the setup. And so we have our figure, our bins, and a number of pixels. And if we plot the red histogram of the colors, you can see here some really kind of fun patterns. And you could analyze these patterns on different things too. I don't know about kittens. I don't really think of kittens with histograms. Wouldn't really do a histogram of a cat. But you could see if this image was like a heartbeat image or something like that, the histogram would really be showing and telling you exactly what's going on. And we'll keep the cute kittens up there and look at thresholding. So we have the threshold, the thresh, and you can do a threshold on here. As far as, there we go. Let me just bring that down so you can see some of the numbers that go into there. And we're going to use the grayscale and just do a simple thresholding view on here. And what we're looking at is the colors that come forward. You can do different thresholds on different colors. And here we're just saying, hey, if it's, because we're dealing with grays, if the certain color is over 150 or 255, you can see we have a nice, or if it's over 150, then it just turns it black, otherwise it's white. And so we create a nice threshold. And you could actually turn around and use this as a mask back on the original picture, and it would bring the cats out and make some interesting pictures on there. But that's a basic threshold on there. There's what they call an inverse threshold. Let's go ahead and take a look and see what that looks like so you have an idea. We'll run this. And this is just, you'll see right here, up here we had threshold gray, very similar. But when we get down to, there we go, thresh binary inverse, there's the key that changes it. So it's still is thresh inverse equals the same call, the same module CV threshold. It's just how do we process it on the end. And if we run that, if you guessed it, inverse means inverse, then you are correct. Oh, give it a second to pop back up here on top. There we go. So very similar to the original thresh inverse, but opposite. And also makes for kind of a cool picture. You could imagine taking either one of these and doing some cool things with them over the original pictures. And then finally there's an adaptive threshold on here. And the adaptive threshold, let me just pull that over here. There we go. It doesn't quite show up on this. We have adaptive threshold Gaussian, so we're going to use the Gaussian. If you remember, Gaussian means that it is slow to bring it up. Slow, that's not even quite the right word. There we go. Okay, I wanted to bring that over so you could see a little bit better. Gaussian means it's adaptive, so that the weight closest to the pixel is very different than as you get further and further away as far as adaptive threshold. And then the adaptive is based more on the difference between the pixels as opposed to the grayness on there. And let's go ahead and when we run it, let's take a look on this and see what that looks like. And we can see just quite the wild imagery. Again, it almost makes it like a black and white etching or something like that. So it kind of a really cool effect. So a lot of these things are designed to help find edges, which is our next section we're going to go over is pulling out the edges and finding the edge detection. And so you can see how complicated it is. It's not an easy thing to find the edges on these pictures. What is the edge? What are the colors? How do you find that? With the histogram we saw in the color scheme, how they did a certain setup, and you might be able to pull that information and use it to find an edge. And so there's a whole thing on edge detection. And this is so central to a lot of stuff being worked on now because, well, let's face it, if you're doing like any kind of imagery, you want to know where the edges are so you can draw a box around it, whether you're trying to program it to do a facial recognition, as we'll do in the third section we're going to cover. We're in the first section. But let's go ahead and bring back our park, run that. And we're also going to do a nice gray picture on here. Oops, let me put the weight key back in there. I don't know why it does not. When I run it without giving it that extra 60 milliseconds or whatever to pull it in there, it sure gives me a lot of problems on this machine. And again, it's because I'm doing the Jupyter Notebook. When I put this into a widget or something like that and start using OpenCV or use it as a backend for code, I don't see these kind of problems. It has a lot to do with just using it in Jupyter Notebook. And so let's start with the Sobel, the Sobel X, or the Sobel line detection on here. We're going to put in our grayscale setup on here. There's a lot of different settings on the Sobel X, Sobel Y, and combining them back together. So let's go ahead and take that. And we want to go ahead and show, oops, I forgot to bring my shows over. And I'm doing Sobel first, and the reason I wanted to do Sobel first is because the other one is based on the math behind Sobel that we're going to hit, the second one, which is which happens to be the Laplacian. And so this works on the intensity from one pixel to the next. And it kind of creates a formula for it. And as you can see, as we get into the intensity from one setup to the other, let me bring this down, we can start to see some lines in here. We have from the Y direction and the X direction, and we combine them, and you can see there's an interesting kind of pattern set up in here. Now, for a scene like the park, it's not really pulling it in that good. And like I said, each one of these has a different strength to it. With this one, you might do images a little bit better, close-up shots. But let's look at the laplation. Now the laplation is very similar to how it works in the background as the Sobel as far as intensity. But you take that formula for generating the intensity on there. And, whoops. What happened there? Okay, we take the intensity for the laplation. There it is. And they use the second derivative. And you can see how it really transforms the edges on this image. And there's a lot of things we could do with this. If you remember from earlier, we talked about taking out noise, blurring. If you use some of those features on here, like the foreground would just disappear with the right blurring technique or the right transposition technique. And it really becomes an art form trying to jump between all these and figure out which one's going to work for your picture and your setup on there. And then you run the histogram to kind of maybe try to find a mathematical thing behind it. It's really a challenge to take the background out or bring the background in and sort those things out. And all these tools are slowly being built, and that's what OpenCV works so good, just to address that. And then we already did the Canny setup. We'll go ahead and run the line detection under Canny. And the Canny literally combines all of the different math functions of our laplation and the Sobel setup. And you can see here it does a really good job of drawing lines and putting in areas on there. And again, this is just a starting point. One of the cool things you can do with here is blur it and then get rid of the bumps in the beginning and clean it up and do all kinds of things to create a mask on there. And let's go ahead and clean up our screen or pictures and images. And then we're going to dive into the second stage of this, which is motion detection. Now, we covered a huge amount in all these tools that they have on there, from our Canny edge detection to bitwise mapping to masking. That's a lot of stuff to cover. Some of those tools we're going to use in the next setup, or one of the next two setups. But we're going to start with motion detection, which is kind of fun. If you have a web camera, or you have, there's all kinds of reasons you could use it. An outdoor webcam. That's what I've always wanted to put one up there because I live up in the mountains. It'd be fun to track the animals going by. But you could also use the motion detector to track somebody coming into an area and then do facial recognition on them. So you can see the motion detector has a lot of cool tools on there. And the fact that we're going to grab from the camera is really helpful also. So let's go ahead and go in here and open up a new, new Python 3. And we'll go ahead and rename this real quick. OpenCV motion detector. There we go. So let's dive into our motion detector. And there's so many. We're going to actually use a lot of the tools we looked at earlier. Let's go ahead and start by importing our OpenCV. And we went ahead and just did OpenCV2. Remember last time I said sometimes we leave it as CV or import CV2 as CV and so on. We're just going to import it as CV2 in this one. And we're going to do date time for tracking. We have this thing called static back. It's we want to be able to reset something to none, and so having it as a global variable here makes sense. And then I'm going to have current motion and motion list. And what it is a current motion is going to have a start time and an end time. That's when it detects a motion going on. And then the motion list is just going to keep tagging those on. So we have a new one and an ending one. Now we're looking at a lot of code here. So the first piece of code that's I really want to draw your attention to is this one right here. CV2.captureVideo. And then the number is, if you had multiple videos in here, you can actually capture the video off the different video cameras. And so we're looking for the main default one that's going to be set up in here. This is actually kind of cool because I always had the idea of having the front-facing camera and a side-facing camera so that you could flip between them and do different things as far as the final edit and that kind of thing. But this is the video. It's looking at this camera. We're just setting this up right now for which camera to look at. Now, when we're dealing with video, we're kind of creating an infinite loop, and so at some point we have to put a break in it, and we'll do that. We'll show you that break here in a sec. In fact, I'm going to skip between the two and skip the code in the middle so you can see the beginning and the end. And so we have an infinite while loop, and we're going to stack images as the video goes and display them. And then when we get to the end of this infinite while loop, we need a way out. In other words, you don't want it just to go on forever until you hit the escape key. You could do that if you want. But we like to actually add something in there. And we'll go ahead and do, here we go, this. We're going to tag on the end here key wait, key Q2, and then just break. Now, this won't work like this unless we're actually displaying a video and that video screen is highlighted. All this says is if we are active in the active video screen when we do the display, when we get to that, break. Now, I kind of jumped ahead because we actually have to create a display in the middle, but I wanted to put this all together so you could see it all in one shot here. We have our while loop we're working with. We're going to go ahead and initiate our frame outside of here. It says, hey, this is video. Whenever I do video, this is what we're looking at. Then we're going to read the video, and you'll have two returns on here, check and frame. And the frame is nothing more than the image coming in. That's what that is. And the check is, hey, do we have an image coming in? If you remember from earlier when we played the dog video, it came up with check would come out false when you got to the end of the video. Because this is an indefinite loop, we never do anything with the check. We don't have to worry about that too much. So here's our kind of our wrapper, and we're going to add a couple more things before the end of the break on this. And then we're going to initialize our motion. So up here I initialized the current motion as having nothing in it. So this is a current motion. There's no action going on. We haven't started an action. There's no end to the action. And then when these fill up, we'll put them into the motion list. And so we're going to go ahead and add in our motion equal to 0. So we're initializing the motion in the loop. And it starts out and says there's no motion going on. Now, we're going to go ahead and do some fun stuff here. And this stuff these next lines of code come off of what we just went over. We're going to grayscale it. Very straightforward. So whatever's coming in the camera is going to have a grayscale to it. And then we're going to do a Gaussian blur. This makes it easier to find the changes. We're looking for sharp edges that are moving. That's how we're going to do our motion detector. And if everything's a little blurry, that means the edges are going to stick out when they move because they're kind of blurring it to those edges. And then we're going to go ahead and do a if static back is none, static back equals gray. So we're going to assign our very first value to the first frame that comes in. That's all this is doing on here. And then continue on there. Now, I'm kind of zipping through these steps. I'm going to go back through them in just a second so that you'll make a little bit more understanding as we go. A difference between static background and the current frame, which is a Gaussian blur. So we want the difference between
One of the nice things.
And this is just kind of a fun, abstract way of finding, hey, what's the original frame and how much has it changed? And then if there's a change, and you're going to hopefully already have guessed that there's some problems with this piece of code right here. And I've run into this. What if your image is your outdoor cam and the grass is blowing in the wind? Or the lighting changes because the sun rises and sets. So it might work great in a room that has consistent lighting, not so good for a wilderness cam. And you've got to start thinking about these things, and there's ways around it. And And if there's a change between the static background and the current frame is greater than 30, it will show white color. So this is kind of fun. Here's our first threshold. We're looking for a threshold between the background and the foreground. So we're starting to find a little bit there on the setup, and then we're going to go ahead and take our threshold frames, the difference from the background and the foreground, and we're going to put that into a thresh frame copy into a find contours, and we're going to use the chain approximate sample for finding the contours. So this is going to find some contours for us. And then what we want to look at is on the contours, so we're counting lines. We're counting how many contours or how many lines are in here. And if there's over 10,000 of these lines that are the difference initial frame and the new frame, then the motion's going to be 1. Wow, that's a lot to unpack. So let's go back up here and just go over that real quick, because I did each line as we went in there. First thing we're doing is we're converting it to gray. Why? It's easier to see gray. You can see the differences in movements and things like that in gray a lot better than in color. Next, we're going to blur the gray. This just makes it so it's easier to see the changes going on. We've reset our static back to none, so we initialize our background to gray. So if it's none, then we want the static back to be whatever the gray value is of our first frame. So when I turn the camera on, I'm going to be outside the camera, so you can see the back wall of my office, which is still under construction. Just a wall socket and some weird stuff back there. And that's what I'm going to use for my basic setup, and then when I go back in and move around, or actually I'll just be in it and just try to hold still and move around a little bit. And then we have the difference between the static background and the gray frame. So this is the gray frame coming in versus the static background. And then we take that and we make our threshold, and we basically create a bunch of lines. We find the contours of the threshold, the difference between those. And so that's where we get our nice lines, and if we have enough lines on there, then that means we have a motion equals 1. So that's a lot of fun. Motion equals 1. So the next stage is if we have a motion equals 1, we want to track it. And so we'll go ahead and do that here. Just throw that one in. And it says, hey, if this is a motion equals 1, and our current motion that we're looking at on our 0 slot has nothing in it, and the motion equals 1, then we want to go ahead and stamp the date time in there. So now we're tracking the start of movement. We have the beginning of movement. And we can do a bunch of really fun things. And this next part we're going to use for a bounding rectangle. And this is going to come up in a display we're going to show you in a second. This one, like, you know, tracking the current motion, you know, it's kind of cool. It's either 0 or 1. Really looking at the contour area and figuring out how much value to put this at. We put it at 10,000. That's really part of the OpenCV. Another thing with the OpenCV is we're going to start looking at these contours and we're going to create a rectangle around them. And then CV2 rectangle, we're just going to take the frame and write a rectangle right on top of that frame. Now, if for some reason I stop moving, we want to know about that. So now we've created a rectangle around movements. We've detected our motions. If it didn't detect any motions and there's nothing going on, then we want to go ahead and take and append the end time. So if motion equals 0 and current motion equals of 0 is not equal to an empty set, then we've had movement going on, and the current motion of 1 needs to equal the date time. We'll go ahead and just tag the current motion right on top, and then the current motion is reset to an empty set. So that's all it is we're just creating an array of the emotions. And this is just kind of fun right now. We're going to go ahead and do displaying the images. We'll start with image gray frame. And there's our gray on there. And if you remember up here, we drew a box on it. So you're going to start seeing the rectangle on the frame coming in. And then we're going to go and start displaying the gray frame because we converted everything to frame. We want to go ahead and display the differential so you can see what's going on in there and why that looks different. And we want to display both the threshold frame and the color frame. So we're going to do all of these up here. There we go. Okay. So we basically are showing up everything that we put together so that it's going to show up on the screen in little boxes. And then we have our key weight, and I said I need to fill some more stuff in here. Well, if we're in the middle of detection of motion and I hit the Q button, it'll be nice to know that. It'd be nice to tag that on to the end. So we'll go ahead and tag that on to the end here. And if motion equals 1 and current motion of 0 is not equal to an empty set, then current motion of 1 equals date time now, and motionless append the current motion. And then break. That takes us out of the loop completely. And then once we hit the break, we'd like to see what's going on with our motion list. That's what it's all about, is the motion list. So we'll do a quick display on our motion list. I don't want to go past 30 if I do too many start and stops. This is important. Let me go ahead and highlight this right here. We want to release the video and of course destroy all our windows. Okay, and that's just cleaning up. Always good to clean up on there. And these are nothing more. Let me go back up to the top. Here we go. We've already talked a lot about the show. So we're showing the gray frame that we created. We're showing the difference frame that we created. We're showing the threshold frame. And then we're showing the actual color frame that's actually coming in, the frame that's coming in. So, wow, that's a lot to break down. Let's go ahead and run it. Hopefully I didn't miss something when I was coming over here. And we should see it coming through. It's setting up, it's accessing the window. And I have to minimize it because it's behind it, and there we are. Still moving. There we go, move back and forth. This is kind of cool because you can see as I move back and forth, look at the lines around my face. Especially on the difference frame, you can see where it's putting nice contours on there and setting it up. So I need to go ahead and click on one of these boxes because I moved the mouse on the other one, and then we'll push the Q button. And then we'll bring back up our OpenCV. And you can see here, every time I start and stop, it puts a start time and an end time. And we could have easily put the frame count. You can put just about anything you want on there. And I wanted to go ahead and run this one more time. And then move. Then hold still. And then click on, and then go ahead and hit the Q. And we can see here that instead of having, there we go, boom, that it picked up on a number of different start and stops on here. 1, 2, 3, 4, 5, 6, 7 start and stops. So not bad, you know, a little motion detector. Again, you can see up here where we're capturing the video. We're looping through and finding the video on each one. And then we do all of our fun transformations on creating the grayscale and Gaussian blur, anything to make it cleaner as far as counting up the threshold lines to see whether we should make it a motion or not. And then of course we tack the motion on there. We added these little boxes around the contours. That was kind of fun because you could see as I moved how it changed and there was still like this weird blur in the background. And then of course if we stop, it tags on an end value. And here's all of our displays. And voila, we have a motion detector. Or at least a start to one. You got to mess with it a little bit. And there's obviously you might want to do like every... one of the tricks that I use is where you have the static right here, is we revert to the gray static view. This one is if it's... you might just revert this to a new frame every so many frames. That kind of thing. So there's a little bit of lots of play in here that you can do with this.
We're going to help you prepare for interview questions dealing with deep learning. And we're going to go from the very basics of neural networks and deep learning into some of the more commonly used models so that you can have an understanding of what kind of questions are going to come up and what you need to know in interview questions. We'll start with a very general concept of what is deep learning. This is where we take large volumes of data, in this case on cats and dogs or whatever. A lot of times you use a training setup to train your model. Remember, it's kind of like a magic black box going on there. And then we use that to extract features or extract information, and in this case classify the image of a cat and a dog. So the primary takeaway when we're talking about deep learning is it learns from large volumes of structured and even unstructured data and uses complex algorithms to train neural network. It also performs complex operations to extract hidden patterns and features. And if we're going to discuss deep learning in this very simplified overview, then we also have to go over what is a neural network. This is a common image you'll see of a drawing of a forward propagation neural network. And it's a human brain inspired system which replicate the way humans learn. So this is inspired how our own neurons in our brain fire, but at a much simplified level. Obviously it's not ready to take over the human population and be our leader yet, not for many years. It's very much in its infant stage. But it's inspired by how our brains work. And they use a lot of other inspirations. You can study brains of moths and other animals that they've used to figure out how to improve these neural networks. The most common one consists of 3 layers of network, and this is generally how you view these networks, is you have an input, you have a hidden layer, and an output. And the neural network is broken up into many pieces, but when we focus just on the neural network, it's always on the hidden layers that we're making all the adjustments and figuring out how to best set up those hidden layers for their functions to both train faster and to function better. When we look at this, of course, we have our input, hidden, and output. Each layer contains neurons called as nodes that perform various operations. And you can see here we have the list of the nodes. We have both our input nodes and our output nodes, and then our hidden layer nodes. And it's used in deep learning algorithm like CNN, RNN, GAN, etc. We'll address some of these models a little closer, at least the most common models, as we go down the list and we study the deep learning and the neural network framework. Let's start with what is a multi-layer perceptron, or MLP, a lot of time is referred to. And you'll see these abbreviations. I'll be honest, I have to write them down on a piece of paper and go through them because I never remember what they all mean, even though I play with them all the time. What is a multi-layer perceptron? Well, if you look at the image on the right, it's very similar to what we just looked at. You have your input layer, your hidden layer, and your output layer. And that's exactly what this is. It has the same structure of a single layer perceptron with one or more hidden layers, except the input layer. Each node in the other layers uses a nonlinear activation function. What that means is your input layer is your data coming in, and then your activation function is based upon all those nodes and weights being added together, and then it has the output. MLP uses supervised learning method called backpropagation for training the model. Very key word there is backpropagation. Single layer perceptron can classify only linear separable classes with binary output, 0, 1, but the MLP can classify nonlinear classes. So let's break this down just a little bit. The multi-layer perceptron with an input layer and a hidden layer and an output layer. As you see that it comes in there, it adds up all the numbers and weights depending on how your setup is, that then goes to the next layer, that then goes to the next hidden layer if you have multiple hidden layers, and finally to the output layer. The backpropagation takes the error that it sees. So whatever the output is, it says, hey, this has an error to it, it's wrong. And then sends that error backwards from where it came from. And there's a lot of different functions used to train this based on that error and how that error goes backwards in the nodes. So forward is you get your answers, backward is for training. You see this every day. Even my Google Pixel phone has this. They train the neural network, which takes a lot more data to train than it does to use. And then they load up that neural network into, in this case I have a Pixel 2, which actually has a built-in neural network for processing pictures. And so it's just the forward propagation I use when it processes my photos. But when they were training it, it used the back propagation to train it with the errors they had. We'll be coming back to different models that are used. For right now, though, multi-layer perceptron, MLP. Put that down as your vocabulary word. And, of course, back propagation. What is data normalization and why do we need it? This is so important. We spend so much time in normalizing our data and getting our data clean and setting it up. So when we talk about data, there's a pre-processing step to standardize the data. So whatever we have coming in, we don't want it to be a 1 gigabyte file here, a 2 gigabyte picture here, and a 3 kilobyte text there. Even as a human, I can't process those all in the same group. I have to reformat them in some way that loops them together so that it's standardized format. We use this data normalization in pre-processing to reduce it and eliminate data redundancy. A lot of times the data comes in and you end up with two of the same images or the same information in different formats. Then we want to rescale values to fit into a particular range for achieving better convergence. What this means is with most neural networks, they form a bias. We've seen this recently in attacks on neural networks where they light up one pixel or one piece of the view and it skews the whole answer. So suddenly, because one pixel is really bright, it doesn't know what to do. Well, when we start rescaling it, we put all the values between, say, -1 and 1, and we change them and refit them to those values. It helps get rid of that bias, helps fix for some of those problems. And then finally, we restructure the data and improve the integrity. We want to make sure that we're not missing values or we don't have partial data coming in. One way to look at this is bad data in, bad data out. So you want clean data in and you want good answers coming out. One of the most basic models used is a Boltzmann machine. So let's address what is a Boltzmann machine. And if you know, we just did the MLP, multi-layer perceptron. So now we're going to come into almost a simplified version of that. And in this we have our visible input layer and we have our hidden layer. The Boltzmann machines are almost always shallow. They're usually just two-layer neural nets that make stochastic decisions whether a neuron should be on or off. True, false, yes, no. First layer is the visible layer, and second layer is the hidden layer. Nodes are connected to each other across layers, but no two nodes of the same layer are connected. Hence it is also known as restricted Boltzmann machine. Now that we've covered a basic MLP or multi-layer perceptron, and we've gone over the Boltzmann machine, also known as the restricted Boltzmann machine, let's talk a little bit about activation formulas. And this is a huge topic that can get really complicated, but it also is automated, so it's very simple. So you have both a complicated and a simple at the same time. So what is the role of activation functions in a neural network? Activation function decides whether a neuron should be fired or not. That's the most basic one. And that actually changes a little bit because it's either whether it's fired or not, in this case activation function, or what value should come out when it's fired. But in these models we're looking at just the Boltzmann restricted layers. So this is what causes them to fire. Either they don't or they do. It's a yes or no, true, false, all or nothing. It accepts the weighted sum of the inputs, the bias, as input to any activation function. So whatever our activation function is, it needs to have the sum of the weights times the input. So each input, if you remember on that model, and let's just go back to that model real quick. And then you always have to add a bias. And you can look at the bias if you remember from your Euclidean geometry. You draw a straight line. The formula for that line has a y-coordinate at the end. It's always cx plus m or something like that, where m is where it crosses the y-coordinates if you're doing a straight line. With these weights, it's very similar, but a lot of times we just add it in as its own weight. We take it as a node of a one value coming in, and then we compute its new weight, and that's how we compute that bias, just like we compute all the other weights coming in. The node which gets fired depends on the y value, and then we have a step function. And the step function, this is where, remember I said it's going to get complicated and simple all at the same time? We have a lot of different step functions. We have the sigmoid function, we have just a standard step function, we have the ReLU, it's pronounced like ray, the ray from the sun, and lu, like a name, so ReLU function. And we have the tangent h function. And if you look at these, they all have something similar. They all either force it to be one value or the other. They force it to be, in the case of the first three, a 0 or a 1, and in the last one, it's either a -1 or a 1. And you can easily convert that to a 0, 1, yes, no, true, false. And on this, one of the most common ones is the step function itself, because there is no middle value. There is no discrepancy that says, well, I'm not quite sure. But as you get into different models, probably the most commonly used, it used to be the sigmoid was most commonly used, but I see the ReLU used more often. Really, depending on what you're doing, you just have to play with these and find out which one works best, depending on the data and your output. The reason to have a non-0-1 answer or something kind of in the middle is when you're looking at this and it's coming out, you can actually process that middle ground as part of the answer into another neural network. So it might be that the ReLU function says, hey, this is only a 0.6, not a 1. And even though the 1 is what's going into the next neural network or the next hidden layer as an input, the 0.6 value might also be going in there to let you know, hey, this is not a straight up 1 or a straight up 0, it's someplace in the middle. This is a little uncertain what's coming out here. So it's a very powerful tool, but in the basic neural network, you usually just use the step function. It's yes or no. Let's take a big step back and take a kind of an overview. The next function is what is a cost function that we're going to cover. This is so important because this is your end result that you're going to do over and over again and use to decide whether the model is working or not, whether you need to try a different step function, whether you need to try a different activation, whether you need to try a fully different model used. So what is the cost function? Cost function is a measure to evaluate how good your model's performance is. It is also referred as loss or error, used to compute the error of the output layer during backpropagation. There's our backpropagation where we're training our model. That's one of our key words. Mean squared error is an example of a popular cost function. And so here we have the cost function C equals half of y minus y predicted, and then you square that. So the first thing is, real quick, if you haven't done statistics, this is not a percentage. It's not a percentage of how accurate it is. It's just a measurement of the error. And we take that error if we're training it, and we push that error backwards through the neural network, and we use that through the different training functions, depending on what model you're using, to train the neural network. So when you deploy the network, you're usually done training it because it takes a lot of computational force to train it. This is a very simple model. And so you deploy the trained one, but we want to know how your error is. And so how do we do that? Well, you split your data. Part of your data is for training and part of your data is for testing, and then we can also test the error on there. So it's very important. And then we're going to go one more step on this. We got to look at both the local and the global setup. It might work great to test your data on what you have on your computer, but that's different than in the field. So when we're talking about all these different tests in the error test, as far as your loss, you want to make sure that you're in a closed environment when you do your initial testing, but you also want to open that up and make sure you follow up with the testing on the larger scale of data, because it will change. It might not fit the larger scale. There might be something in there in the way you brought the data in specifically, or the data group you used, or any of those could cause an error. So it's very important to remember that we're looking at both the local and the global context of our error. And just one other side note on a lot of the newer models of neural networks, by comparing the error we get on the data, our training data, with a portion of the test data, we can actually figure out how good the model is, whether it's overfitted or not. We'll go into that a little bit more as we go into some of the different models. So we have our output. We're able to figure out the error on it based on the square means usually, although there's other functions used. So we want to talk about what is gradient descent, another vocabulary word. Gradient descent is an optimization algorithm to minimize the cost function or to minimize the error. Aim is to find the local or global minima of a function. Determine the direction the model should take to reduce the error. So, as we're looking at this, we have our squared error that we just figured out based on the cost function. It says, how bad is my model fitting the data I just put through it? And then we want to reduce that error. So how do you figure out what direction to do that in? Well, it could be that you're looking at just that line of data coming in, so that would be a local minima. We want to know the error of that particular setup coming in. And then you have your global minima. We want to minimize it based on the overall data we're putting through it. And with this, we can figure out the global minimum cost. We want to take all those local minimum costs of each piece of data coming in and figure out the global one. How are we going to adjust this model to fit all the data? We don't want it to be biased just on 3 or 4 lines of data coming in. We want it to kind of extrapolate a general answer for all the data coming in. But this, of course, we mentioned it briefly about backpropagation. This is where it really comes in handy, is training our model. Neural network technique to minimize the cost function helps to improve the performance of the network, backpropagates the error, and updates the weights to reduce the error. So as you can see here is a very nice depiction of a back propagation. We have our predicted y coming out, and then we have, since it's a training set, we already know the answer, and the answer comes back, and based on case of the square means was one of the functions we looked at, one of the activation functions based on cost function. That cost function then, depending on what you choose for your back propagation method, and there's a number of them, will change the weights. It will change the weight going to each of one of those nodes in the hidden layer, and then based upon the error that's still being carried back, it'll change the weights going to the next hidden layer. And then it computes an error level on that and sends that back up. And you're going to say, well, if it computes the error into the first hidden layer and fixes it, why would it stop there? Well, remember, we don't want to create a biased neural network. So we only make small adjustments on these weights. We don't make a big adjustment that changes everything right off the bat. So no matter how far back you go, you're always going to have a small amount of error, and that's still going to continue to go all the way back up the hidden layers. For right now, focus on the back propagation is taking that error and moving it backwards on the neural network to change the weights and help program it so that it'll have the correct answers. So far, we've been talking about forward propagation neural networks. Everything goes forwards, goes left to right. But let's take a little detour and let's see what is the difference between a feed-forward neural network and a recurrent neural network. Now this is in the function, not when we're training it using the back propagation. So you've got new information coming in and you want to get the answer. And there's a couple different networks out there, and we want to know, we have a feed-forward neural network and we have a new vocabulary term, recurrent neural network. A feed-forward neural network. Signals travel in one direction from input to output. No feedback loops. Considers only the current input. Cannot memorize previous inputs. One example of one of these feed-forward neural networks, and we've covered a number of them, but one of the ones that has a big highlight nowadays is the CNN, a convolutional neural network. TensorFlow, the one put out by Google, is probably most known for their CNN, where the information goes forward. It first takes a picture, splits it apart, goes through the individual pixels on the picture so it picks up a different reading, then calculates based on that, goes into a regular feed-forward neural network, and then gives your categorization on there. Now, we're not covering the CNN today, but we do have a video out that you can look up on YouTube, put out by Simplilearn, the convolutional neural network. Wonderful tutorial. Check that out and learn a lot more about the convolutional neural network. But you do need to know that the CNN is a forward propagation neural network only. So it's only moving in one direction. So we want to look at a recurrent neural network. Signals travel in both directions, making it a looped network. Considers the current input along with the previous received inputs for generating the output of a layer. Has the ability to memorize past data due to its internal memory. And you can see they have a nice image here. We have our input, and for some reason they always do the recurrent neural network in reverse from bottom up in the images. Kind of a standard, although I'm not sure why. Your X goes into your hidden layer, and your hidden layer, the answer for part of the answer from that it generates feeds back into the hidden layer. So now you have an input of both X and part of the hidden layer, and then that feeds into your output. Now, if we go back to the forward, let me just go back a slide, and we're looking at our forward propagation network. One of the tricks you can do to use just a forward propagation network is if you're in what they call a time sequence, that's a good term to remember, or a time series, meaning that it's sequential data. Each term comes after the other. You can trick this by creating your input nodes with the history. So if you know that you have values 1, 5, and 7 going in, and you know what the output is from what those outputs are, you can expand the input to include the history input. That's one of the ways to trick a forward propagation network into looking at that. But when you do it with a recurrent neural network, you let the hidden layer do that for you. It sends that data and reprocesses it back into itself. What are some of the applications of recurrent neural network? The RNN can be used for sentiment analysis and text mining. Getting up early in the morning is good for health. And it's a positive sentiment. One of the catches you really want to look at this when you're looking at the language is that I could switch this around and totally negate the meaning of what I'm doing, so it would no longer be positive. So when you're looking at a sentence, knowing the order of the words is as important as the meaning of the words. You can't just count how many good words there are versus bad words to get a positive sentiment. You now have to know what they're addressing. And there's lots of other different uses. Kids are playing football, or soccer as we call it in the US. RN can help you caption an image. So based on previous information coming in, it refeeds that back in and you have a image setter. And then time series problems like predicting the prices of stocks in a month or quarter or sale of products can be solved using an RNN. And this is a really good example. You have whatever your stocks were doing earlier this month will have a huge effect on what they're doing today if you're investing. So having an RNN model, a recurrent neural network, feeding into itself what was happening previously allows it to take that model and program in that whole series without having to put in the whole a month at a time of data. You can only put in one day at a time, but if you keep them in order, it will look back and say, oh, this is because of what happened yesterday. I need some information from that, and I'm going to use that to help predict today's, and so on and so on. We're going to go back to our activation functions. Remember I told you ReLU is one of the most common functions used? So let's talk a little bit more about ReLU and also softmax. Softmax is an activation function that generates the output between 0 and 1. It divides each output such that the total sum of the outputs is equal to 1. It is often used in the output layers. Softmax L of the n equals e to L of the n over the absolute value of e to the L. So what does this function mean? I mean, what is actually going on here? So we have our output nodes, and our output nodes are giving us, let's say they give us 1.2, 0.9, and 0.4. As a human being, I look at that and I say, well, the greatest value is 1.2, so whatever category that is, if you have 3 different categories, maybe you're not just doing if it's a cat or it's a dog or, let's say it's a cow. Maybe we had cats and dogs earlier. Why the cats and dogs are hanging out with a cow, I don't know. But we have a value, and it might say 1.2 is a cat, 0.9 is the dog, and 0.4 is a cow. For some reason it thinks that there's a chance of it being any one of these 3 items, and that's how it comes out of the output layer. Well, as a human, I can look at 1.2 and say this is definitely what it is. It's definitely a cat or whatever it is. Maybe it's looking at different kinds of cars. Might be a better, whether it's a car, truck, or a motorcycle. Maybe that'd be a better example. Well, from a computer standpoint, that might be a little confusing because they're just numbers waving at us. And so with the softmax, we want all those numbers to always add up to 1. So when I add 3 numbers together, I want the final output to be 1 on there. And so it goes through this formula, changes each of these numbers. In this case, it changes them to 0.46, 0.34, and 0.20. They all add up to 1. And that's a lot easier to register because it's very set. It's a set output. It's never going to be more than 1. It's never going to be less than 0. And so you can see here that there's probably a pretty high chance that it's the first one. So as a human being, we have no problem knowing that. But this output can then also go into, say, another input. So it might be an automated car that's picking up images, and it says that image in front of us is probably a big truck. We should deal with it like it's a big truck. It's probably not a motorcycle, or whatever those categories are. That's the softmax part of it. But now we have the ReLU. Well, where's the ReLU coming from? Well, the ReLU is what's generating the 1.2 and the 0.9 and the 0.4. And so if you remember, our ReLU stands for Rectified Linear Unit and is the most widely used activation function. We looked at a number of different activation functions, including tangent H, the step function. I remember I said the step function is really used if that's what your actual output is, because then you know it's a 0 or 1. But the ReLU, if you have that as your output, you now have a discrepancy in there, and if that's going into another neural network or another process, having that discrepancy is really important. And it gives an output of x if x is positive and 0 otherwise. So it says my x value is going to be somewhere between 0 or 1. And then the usually, unless it's really uncertain, the output's usually a 1 or 0. And then you have that little piece of uncertainty there that you can send forward to another network, or you can look at to know that there's uncertainty involved. And is often used in the hidden layers. This is what's coming out of the hidden layers into the output layer usually. Or as we referenced the convolutional neural network, the CNN, which you'd have to go to another video to review, the ReLU is the most common used for convolutional part of that network. It has a bunch of little pieces that are very simplified, looking at all the different images or different sections of the map, and the ReLU works really good for that. And like I said, there's other formulas used, but this is the most common one, and you'll see that in the hidden layers going maybe between one layer and the next layer. So just a quick recap, we have our softmax, which means that if you have numerous categories, only one of them is going to be picked, but you also want to have some value attached to it, how well it picked it. And you put that between 0 and 1, so it's very standardized. So we have our softmax. We looked at that. Let's go back one. We looked at that here, where it transforms the numbers. And then we have our ReLU function, which takes the information and the summation and puts it between a 0 and a 1, where it's either clearly a 0 or, depending on how confident our model is, it'll go between the 0 and 1 value. What are hyperparameters? Oh, this is a great interview question. Hyperparameters. When you are doing neural networks, this is what you're playing with most of the time once you've gotten the data formatted correctly. A hyperparameter is a parameter whose value is set before the learning process begins, determines how a network is trained and the structure of the network. This includes things like the number of hidden units. How many hidden layers are you going to have, and how many nodes in each layer? Learning rate. Learning rate is usually multiplied once you figured out the error and how much you want to change the weights. We talked about, or I mentioned it early just briefly, you don't want to just make a huge change, otherwise you're going to have a biased model. So you only take some little incremental changes, and that's what the learning rate is those small incremental changes. Epochs. How many times are you going to go through all the data in your training set? So one epoch is one trip through all the data. And there's a lot of other things depending on which model you're working with and which programming script you're working with. Like the Python sklearn package will have it slightly different than, say, Google's TensorFlow package, which will be a little bit different than the Spark machine learning package. So these are just some examples of the hyperparameters. And so you see in here we have a nice image of our data coming in, and we train our model, then we do a comparison to see how good our model is, and then we go back and we say, hey, this model's pretty good, but it's biased. So then we send it back and we change our hyperparameters to see if we can get an unbiased model, or we can have a better prediction on it that matches our data closer. What will happen if learning rate is set too low or too high? We have a nice couple graphs here. We have one over here that says the learning rate set too low, and you can see that it slowly works its way down the curve. And on the right, you can see a learning rate set too high. It's just bouncing back and forth. When your learning rate is too low, that's what we studied at 2 slides ago, that's what the learning rate was, training of the model will progress very slowly as we are making very tiny updates to the weights. We'll take many updates before reaching the minimum point. So I just mentioned epoch, going through all the data. You might have to go through all the data 1,000 times instead of 500 times for it to train. Learning rate too high causes undesirable divergent behavior to the loss function due to drastic updates in weights. At times it may fail to converge or even diverge. So if you have your learning rate set too high and it's training too quickly, maybe you'll get lucky and it trains after one epoch run, but a lot of times it might never be able to train because the weights are changing too fast. They flip back and forth too easy. And you see down here we've introduced 2 new terms, converge and diverge. Converge means that our model has reached a point where it's able to give a fairly good answer for all the data we put in. All those weights have adjusted and it's minimized the error. Diverge means that the data is so chaotic that it can never manage to train to that data. The data is just too chaotic for it to train. So we have 2 new words there, converge and diverge are important to know also. What is dropout and batch normalization? Dropout is a technique of dropping out hidden and visible units of a network randomly to prevent overfitting of data. It doubles the number of iterations needed to converge the network. So here we have our standard neural network, and then after applying dropout. Now it doesn't mean we actually delete the node. The node is still there, and we're still going to use that node. What it means is that we're only going to work with a few of the nodes. A lot of times, I think the most common one right now used is 20%. So you'll drop out 20% of the nodes when you do your training. You reverse propagate your data, and then you'll randomly pick another 20 nodes the next time you go through an epoch data training. So each time you go through one epoch, you will randomly pick 20 of those nodes not to mess with. And this allows for less overfitting of the data. So by randomly doing this, you create some, I guess it just kind of pulls some nodes off to the sides and says we're going to handle the data later on so we don't overfit. Batch normalization is a technique to improve the performance and stability of neural network. The idea is to normalize the inputs in every layer so that they have mean output and activation of 0 and standard deviation of 1. This question covers a lot of different things, which is great. It's a great interview question because it pulls in that you have to understand what the mean value is. So a mean output activation of 0, that means our average activation is 0. So when you normalize it, remember usually we're going between -1 and 1 on a lot of these. It's a very standard setup. So you have to be very aware that this is your mean output activation of 0. And then we have our standard deviation of 1. So we want to keep our error down to just a 1 value. The benefits of this doing a batch normalization is it provides regularization. it trains faster, higher learning rates, and weights are easier to initialize. What is the difference between batch gradient descent and stochastic gradient descent? Batch gradient descent. Batch gradient computes the gradient using the entire data set. It takes time to converge because the volume of data is huge and weights update slowly. So you can look at the batch as, a lot of times if you're using big data, batch the data in, but you still go through a full epoch. You still go through all the data on there. So batch gradient descent means you're going to use it to fit all the data and look for a convergence there. Stochastic gradient descent. Stochastic gradient computes the gradient using a single sample. It converges much faster than batch gradient because it updates weight more frequently. Explain overfitting and underfitting and how to combat them. Overfitting happens when a model learns the details and noise in the training data to the degree that it adversely impacts the execution of the model on the new information. It is more likely to occur with nonlinear models that have more flexibility when learning a target function. An example of this would be if you're looking at, say, cars and trucks and motorcycles, it might only recognize trucks that have a certain box-like shape. It might not be able to notice a flatbed truck unless it's only a specific kind of flatbed truck or only Ford trucks because that's what it saw on the training set. This means that your model performs great on your trained data and great on maybe a small test amount of data, but when you go to use it in the real world, it leaves out a lot and is not very functional outside of your small area, your small laboratory data coming in. Underfitting, doing the opposite when you underfit your data. Underfitting alludes to a model that is neither well trained on training data nor can generalize to new information. Usually happens when there is less and improper data to train a model, has a poor performance and accuracy. So if you're using underfitted data and you generate a model and you distribute that in a commercial zone, you'll have a lot of people unhappy with you because it's not going to give them very good answers. So we've explained overfitting and underfitting, so now we want to ask how to combat them. Combating overfitting and underfitting. Resampling the data to estimate the model accuracy, k-fold cross-validation. Having a validation data set to validate the model. So when we do the resampling, we're randomly going to be picking out data, and we'll run it a few times to see how that works, depending on our random data and how we sample the data to generate our model. And then we want to go ahead and validate the data set by having our training data and then keeping some data on the side, testing data to validate it. How are weights initialized in a network? Initializing all weights to 0. All the weights are set to 0. This makes your model similar to a linear model. So if you have linear data coming in, doing a basic setup like that might work. All the neurons in every layer perform the same operation given the same output and making the deep net useless. Right there is a key word. It's going to be useless if you initialize everything to 0. At that point, be looking into some other machine learning tools. Initializing all weights randomly. Here the weights are assigned randomly by initializing them very close to 0. It gives better accuracy to the model since every neuron performs different computations. And here we have the weights are set randomly. We have our input layer, the hidden layers, and the output layer. And W equals NP random, random N. Layer size L L minus 1. This is the most commonly used, is to randomly generate your weights. What are the different layers in CNN, convolutional neural network? First is the convolutional layer that performs a convolutional operation. We have our other video out if you want to explore that more, so you can go into detail exactly how the convolutional layer works in the CNN as far as creating a number of smaller picture windows that go over the data. The second step is as a ReLU layer. ReLU brings nonlinearity to the network and converts all the negative pixels to 0. Output is rectified feature map. So it goes into a mapping feature there. Pooling layer. Pooling is a downsampling operation that reduces the dimensionality of the feature map. So we have all our ReLU layer, which is pulling all these little maps out of our convolutional layer. It's taking that picture and creating little tiny neural networks to look at different parts of the picture. Then we need to pool it together. And then finally, the fully connected layer. So we flatten our pooling layer out, and we have a fully connected layer recognizes and classifies the objects in the image. And that's actually your forward propagation, reverse propagation training model, usually. I mean, there's a number of different models out there, of course. What is pooling in CNN and how does it work? Pooling, used to reduce the spatial dimensions of a CNN, performs downsampling operation to reduce the dimensionality, creates a pooled feature map by sliding a filter matrix over the input matrix. I mentioned that briefly on the previous slide. It's important to know that you have, if you see here, they have our rectified feature map. And so each one of those colors, like the yellow color, that might be one of a smaller little neural network using the ReLU. It'll just kind of go over the main picture and look at all the different areas on the main picture. So you might step 1, 2, 3, 4 spaces. And then you have another one that's also looking at features, and it has a 2, 7, 8, 5. Each one of those is a map. So it might be, the first one might be a map looking for cat ears, and the second one looking for human eyes. When it does this, you then have this rectified feature map looking at these different features. And the max pooling with a 2x2 filters and a stride of 2. Stride means instead of skipping every pixel, you're going to go every 2 pixels. You take the maximum values. And you can see over here, when we look at a pooled feature map, one of the features says, hey, I had a max value of 8, so somewhere in here we saw a human eye labeled as 8, pretty high label. And maybe 7 was a human hand, and maybe 4 was cat whiskers, or something that we thought might be cat whiskers. 4 is kind of a low number in this particular case compared to the other ones. So you have your full pooled feature map. You can see the process here as we have our stepping. We look for the max value, and then we create a pooled feature map of the maxed values. How does a LSTM network work? And that's long short-term memory. So the first thing to know is that an LSTMS are a special kind of recurrent neural network capable of learning long-term dependencies. Remembering information for long periods of time is their default behavior. We did look at the RNN briefly, talked about how the hidden layer feeds back into itself. With the LSTM, it has a much more complicated feedback, and you can see here we have the hidden layer of t-1, and the hidden layer, that's what the H stands for, hidden layer of t, and the formula is going in. As we can see here, we have the hidden layers. We have t-1 and then h of t, where t stands for time. So this is a series. Remember, we're working with series, and we want to remember the past. And you can see you have your input of t, and that might be a frame in a video. As a frame comes in, they usually use in this one the tangent H activation formula, but you also see that it goes through a couple other formulas, the omega formula. And so when it combines these, that then goes into the next layer, your next hidden layer. That then goes into the data that's submitted to the next input. So you have your x of t plus 1. So when you have that coming in, then you have your h value that's coming forward from the last process. And depending on how many of these omega structures you put in there, depends on how long-term the memory gets. So it's important to remember this is more for your long-term recurrent neural networks. The 3 steps in an LSTM. Step 1 decides what to forget and what to remember. Step 2 selectively updates cell state values. So based on what we want to remember and forget, we want to update those cell values. And then decides what part of the current state make it to the output. So now we have to also have an output on there. What are vanishing and exploding gradients? This is a great question that affects all our neural networks. While training an RNN, your slope can become either too small or too large, and this makes the training difficult. When the slope is too small, the problem is known as vanishing gradient. So our slope, we have our change in x and our change in y. When the slope decreases gradually to a very small value, sometimes negative, and makes training difficult. When the slope tends to grow exponentially instead of decaying, this problem is called exploding gradient. The slope grows exponentially. You can see a nice graph of that here. Issues in gradient problem: long training time, poor performance, and low accuracy. What is the difference between epoch, batch, and iteration in deep learning? Epoch. An epoch represents one iteration over the entire data set. So that's everything you're going to go ahead and put into that training model. Batch. We cannot pass the entire data set into the neural network at once, so we divide the data set into a number of batches. And then iteration. If we have 10,000 images as data and a batch size of 200, then the epoch should run 10,000 times over 200. So that means we have our total number over the 200 equals 50 iterations. So in each epoch, we're running over all the data set, we're going to have 50 iterations. And each of those iterations includes a batch of 200 images in this case. Why TensorFlow is the most preferred library in deep learning? Well, first, TensorFlow provides both C++ and Python APIs that makes it easier to work on. Has a faster compilation time than other deep learning libraries like Keras and Torch. TensorFlow supports both CPUs and GPUs computing devices. So right now TensorFlow is at the top of the market because it's so easy to use for both programmer side and for hardware side and for the speed of getting something up and running. What do you mean by tensor in TensorFlow? Tensor is a mathematical object represented as arrays of higher dimension. These arrays of data with different dimensions and ranks that are fed as input to the neural network are called tensors. And you can see here we have a tensor of dimensions 5, 4. So it's a two-dimensional tensor coming in. You can look at an image like this, that each one of those pixels is a different value if it's a black and white. So it might be 0 and 1s, and then each one represents a black and white image. In a color photo, you might either find a different value system, or you might have a tensor value that has the XY coordinates as we see here, plus the colors. So you might have 3 more different dimensions for the 3 different images, the red, the blue, and the yellow coming in. And even as you go from one layer or one tensor to the next, these layers might change. We might flatten them, we might bring in numerous, in the case of the convergence neural network, we have all those smaller different mappings of features that come in. So each one of those layers coming through is a tensor if it has multiple dimensions coming in and weights attached to it. What are the programming elements in TensorFlow? Well, we have our constants. Constants are parameters whose value does not change. To define a constant, we use tf.constant command. Example, a equals tf.constant 2.0 tf float 32. So it's a tensor float value of 32. B equals tf constant 3.0. Print AB. If we did a print of AB, we'd have tf.constant, and then of course B is that instance of it. Variables. Variables allow us to add new trainable parameters to graph. To define a variable, we use tf.variable command and initialize them before running the graph in session. Example, w equals tf variable 0.3 d-type tf float 32, or b equals the tf variable minus 3 comma d-type float 32. Placeholders. Placeholders allow us to feed data to a TensorFlow model from outside a model. It permits a value to be assigned later. To define a placeholder, we use tf_placeholder command. Example, a equals tf placeholder, b equals a times 2. With the tf session as SESS, result equals session run, b comma feed dictionary equals a 3.0, print result. So we have a nice example there of a placeholder. Session. A session is run to evaluate the nodes. This is called as the TensorFlow runtime. So for example, you have a equals tf constant 2.0, b equals tf constant 4.0, c equals a plus b. And at this point, you'd go ahead and create a session equals tf session, and then you could evaluate the tensor c print session run c. That would input C as an input into your session. What do you understand by a computational graph? Everything in TensorFlow is based on creating a computational graph. It has a network of nodes where each node performs an operation. Nodes represent mathematical operation and edges represent tensors. Since data flows in a form of a graph, it is also called a data flow graph. And we have a nice visual of this graph, or graphic image of a computational graph. And you can see here we have our input nodes, our add, multiply nodes, and our multiply node at the end. And then we have the edges where the data flows. So we have from A going to C, A going to D. You can see we have a 2 flowing, 4 flowing. Explain generative adversarial network along with an example. Suppose there is a wine shop that purchases wine from dealers, which they will resell later. So we have our dealer going to the wine, our shop owner that then sells it for a profit. But there are some malefactor dealers who sell fake wine. In this case, the shop owner should be able to distinguish between fake and authentic wine. The forger will try different techniques to sell fake wine and make sure certain techniques go past the shop owner's check. So here's our forger, fake wine, shop owner. The shop owner would probably get some feedback from the wine experts that some of the wine is not original. The owner would have to improve how he determines whether a wine is fake or authentic. Goal of forger, to create wines that are indistinguishable from the authentic ones. Goal of shop owner, to accurately tell if the wine is real or not. There are 2 main components of generative adversarial network. And we'll refer to it as a noise vector coming in, where we have our forger who's going to generate fake wine, and then we have our real authentic wine, and of course our shop owner who has to figure out whether it's real or fake. The generator is a CNN that keeps producing images that are closer in appearance to the real images, while the discriminator tries to determine the difference between real and fake images. The ultimate aim is to make the discriminator learn to identify real and fake images. What is an autoencoder? The network is trained to reconstruct its inputs. It is a neural network that has 3 layers. Here the input neurons are equal to the output neuron. The network's target outside is same as the input. It uses dimensionality reduction to restructure the input. Input image, comes in, we have our Latin space representation, and then it goes back out, reconstructing the image. It works by compressing the input to a Latin space representation, and then reconstructing the output from this representation. What is bagging and boosting? Bagging and boosting are ensemble techniques where the idea is to train multiple models using the same learning algorithm and then take a call. So we have in here where we're bagging, we take a data set and we split it. We're going to have our training data and our test data. Very standard thing to do. Then we're going to randomly select data into the bags and train your model separately. So we might have bag 1, model 1, bag 2, model 2, bag 3, model 3, and so on. In boosting, the emphasis is to select the data points which give wrong output in order to improve the accuracy. So in boosting, we have our data set. Again, we split it to test data and train data. And we'll take bag 1 and we'll train the model. Data points with wrong predictions then go into bag 2, and we then train that model and repeat.
So that brings us to the end of this video tutorial on AI and Deep Learning full course. I hope you enjoyed watching this video. If you have any questions, please feel free to put them in the comment section. Our team will help you. Thank you for watching and keep learning.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.